What's up, everybody? This is your boy Tech G back with another video, and I want to welcome you all to my CompTIA Network Plus N10-008 course. And this information that I will be presenting is going to give you everything that you need to know to successfully pass the CompTIA Network N10-008 examination, assuming you study properly. So the CompTIA Network Plus certification, this is an entry-level computer certification for PC computer service technicians. And the exam is designed to certify the competency of entry-level IT professionals in troubleshooting, configuring, and managing networks. All right, let's talk about some of the skills that you're going to learn in the Network Plus certification. So understand that the CompTIA Network Plus is broken into 5 domains. You have domain 1, which is the networking fundamentals domain, and this will make up 24% of the exam. This domain will focus on basic networking concepts, including network services, physical connections, topologies and architecture, and cloud connectivity. Domain 2 is called network implementations, and this is going to make up 19% of the exam. And this domain is going to focus on routing technologies and networking devices, deploying Ethernet solutions, and configuring wireless technologies. Domain 3, which is network operations, going to take up 16% of the exam, and it's going to focus on monitoring and optimizing networks to ensure business continuity. Domain 4 is network security. It's going to make up 19% of the exam, and it's going to focus on security concepts and network attacks in order to harden networks against threats. You have domain 5, which is network troubleshooting, and that's going to take up 22% of the exam, and it's going to focus on troubleshooting common cables, connectivity, and software issues related to networking. All right, so let's talk about the CompTIA Network Plus N10-008 exam details. So the Network Plus N10-008, this is the latest and greatest exam version, and it was launched September 15th, 2021. Now, at the time of this recording, CompTIA has not scheduled a retirement date for this exam, but normally 3 years after the launch of an exam is when you can expect for that exam to be officially retired, so they can begin the process of introducing the latest version. Also, this exam has a maximum of 90 questions, and the questions are presented as multiple choice and performance-based questions. You will also have 90 minutes to take this exam, and in order to pass the CompTIA Network Plus exam, you're going to need to score 720 out of a possible 900 points or get an 80% on the exam. Also, it is recommended by CompTIA that a candidate be CompTIA A+ certified and have at least 9 to 12 months of hands-on experience working in a junior network administrator or network support technician role. Now, based off of my professional experience of working in tech for over 20 years, I can tell you that you can pretty much throw that recommendation out the window, because there have been plenty of people who do not have that type of experience who have gone on to successfully pass this certification, especially those who I have taught personally. Now, moving on. The exam is available in English, German, Portuguese, and Spanish, and the company that is responsible for administering the test is Pearson VUE Testing Centers. And let's get to the most important bullet point here. At the time of this recording, the CompTIA Network Plus N10-008 exam is going to cost you $358. Now, if you want to get you a discount on vouchers, look in my description box and look for the link that says discount vouchers. Tech G sells discount vouchers, so you don't have to pay full price. All right. In this video, you're going to learn about the OSI model. The Open Systems Interconnection Model. This is a conceptual model that characterizes and standardizes the communication functions of a telecommunication or computing system without regard to its underlying internal structure and technology. Its goal is the interoperability of diverse communication systems with standard communication protocols. The model partitions the flow of data in the communication system into 7 abstraction layers, from the physical implementation of transmitting bits across a communication medium to the highest level representation of data of a distributed application. Each intermediate layer serves a class of functionality to the layer above it and is served by the layer below it. Classes of functionality are realized in software by standardized communication protocols. All right, so let's talk about the first layer, which is the physical layer. So the physical layer, this is responsible for the transmission and reception of unstructured raw data between a device and a physical transmission medium. It converts the digital bits into electrical, radio, or optical signals. Layer specifications define characteristics such as voltage levels, the timing of voltage changes, physical data rates, maximum transmission distances, modulation scheme, channel across medium, and physical connectors. This includes the layout of pins, voltage, line impedance, cable specification, signal timing, and frequency for wireless devices. Bit rate control is done at the physical layer, may define transmission mode as simplex, half duplex, or full duplex. The components of a physical layer can be described in terms of a network topology. Physical layer specifications are included in the specifications for the ubiquitous Bluetooth, Ethernet, and USB standards. All right, next let's talk about the second layer, which is the data link layer. So the data link layer, this provides node-to-node data transfer, which is a link between two directly connected nodes. It detects and possibly corrects errors that may occur in the physical layer. It defines the protocol to establish and terminate a connection between two physically connected devices. It also defines the protocol for flow control between them. IEEE 802 divides the data link layer into two sublayers. And the first sublayer is the MAC layer, or the medium access control layer. And this is responsible for controlling how devices in the network gain access to a medium and permission to transmit data. And then you have the logical link control layer, or the LLC layer. And this is responsible for identifying and encapsulating network layer protocols and controls error checking and frame synchronization. All right, let's talk about the third layer, which is the network layer. So the network layer is primarily concerned with forwarding data based on logical addresses. The network layer provides the functionality and procedural means of transferring packets from one node to another connected in different networks. A network is a medium to which many nodes can be connected, on which every node has an address, and which permits nodes connected to it to transfer messages to other nodes connected to it by merely providing the content of a message and the address of the destination node, and letting the network find the way to deliver the message to the destination node, possibly routing it through intermediate nodes. If the message is too large to be transmitted from one node to another on the data link layer between these nodes, the network may implement message delivery by splitting the message into several fragments at one node, sending the fragments independently, and reassembling the fragments at another node. It may, but does not need to, report delivery errors. And message delivery at the network layer is not necessarily guaranteed to be reliable. A network layer protocol may provide reliable message delivery, but it need not do so. And the network layer is responsible for a variety of tasks, such as logical addressing, switching, such as packet switching and circuit switching, message switching, route discovery and selection, connection services, flow control, which is also known as congestion control, and packet reordering. All right, so let's talk about the next layer, which is layer 4, and that is the transport layer. So the transport layer acts as the dividing line between the upper layers and the lower layers of the OSI model. The transport layer provides the functional and procedural means of transferring variable length data sequences from a source to a destination host while maintaining the quality of service functions. The transport layer controls the reliability of a given link through flow control, segmentation and desegmentation, and error control. Some protocols are state and connection oriented. This means that the transport layer can keep track of the segments and retransmit those that failed delivery. The transport layer also provides the acknowledgement of the successful data transmission and sends the next data if no errors occurred. The transport layer creates segments out of the message received from the application layer, and segmentation is the process of dividing a long message into smaller messages. And the two common transport layer protocols are as follows. You have Transmission Control Protocol, or TCP, and this is a connection-oriented transport protocol. You have UDP, or User Datagram Protocol, and this is a connection connectionless transport protocol. And then we have two common flow control protocols. The first one is called windowing. So TCP communication uses windowing in that one or more segments are sent at one time, and the receiver can attest to the receipt of all of the segments in a window with a single acknowledgement. And that is what you're looking at right here in this picture taking place. And then the next one is called buffering. And this is a device such as a router where it uses a chunk of memory or a buffer or a queue to store segments if bandwidth is not available to send the segments. A queue has a finite capacity, however, and can overflow or drop segments in case of sustained network congestion. So let's talk about the next layer, which is layer 5, or the session layer. So the session layer controls the dialogues or the connections between computers. It establishes, manages, and terminates the connections between the local and remote application. It provides for full duplex, half duplex, or simplex operation and establishes procedures for checkpointing, suspending, restarting, and terminating a session. In the OSI model, this layer is responsible for gracefully closing a session. This layer is also responsible for session checkpointing and recovery, which is not usually used in the Internet Protocol suite. The session layer is commonly implemented explicitly in application environments that use remote procedure calls. In the modern TCP/IP system, the session layer is non-existent and simply part of the TCP protocol. So functions of the session layer include the following. You have setting up a session, and this includes checking user credentials such as username and passwords, assigning numbers to a session's communication flow to uniquely find each one, negotiating services needed during the session, and negotiating which devices begin sending data. And then you have maintaining a session, and this includes transferring data, reestablishing a disconnected session, and acknowledging receipt of data. And then you have tearing down a session, and sessions can be disconnected based on agreements of the devices in the session, and they could be torn down because one party disconnects intentionally or unintentionally. So let's talk about the next layer, which is layer 6, and this is the presentation layer. So the presentation layer handles formatting the data being exchanged and securing that data with encryption. The presentation layer establishes context between application layer entities in which the application layer entities may use different syntax and semantics if the presentation service provides a mapping between them. If a mapping is available, presentation protocol data units are encapsulated into session protocol data units and pass down the protocol stack. This layer provides independence from data representation by translating between application and network formats. The presentation layer transforms data into the form that the application accepts. This layer formats data to be sent across a network, which is sometimes called the syntax layer, and can include compression functions. So functions of the presentation layer include the following. You have data formatting. So some applications might format text using ASCII, while other applications might format text using the EBCDIC or the extended binary coded decimal interchange code. The presentation layer handles formatting the text in a format that allows compatibility between the communicating devices. And then you have encryption. So to add a layer of security for data transmission, encryption is used to scramble data that will make it impossible for a third party to decrypt the transmission. All right, let's talk about the final layer, which is layer 7, also known as the application layer. So the application layer is the OSI layer closest to the end user, which means both the OSI application layer and the user interact directly with the software application. This layer interacts with software applications that implement a communicating component. Such application programs fall outside of the scope of the OSI model, and application layer functions typically include identifying communication partners, determining resource availability, and synchronizing communication. When identifying communication partners, the application layer determines the identity and availability of communication partners for an application with data to transmit. The most important distinction in the application layer is the distinction between the application entity and the application. So for example, a reservation website might have two application entities, one using HTTP to communicate with its users and one for a remote database protocol to record the reservations. Neither of these protocols have anything to do with reservations. The logic is in the application itself. The application layer has no means to determine the availability of resources in the network. And these are the functions of the application layer. So you got application services, and examples of these services may include file sharing and email. And then you have service advertisement. Some application services, they periodically send out advertisements such as network printers, making their availability known to other devices on the network. Now, as a simple way to remember the OSI layers, you can remember this right here. Please do not throw sausage pizza away. So that's the physical, the data link, the network, the transport, session, presentation, and application. So please do not throw sausage pizza away. That will help you to remember the 7 layers of the OSI model. In this video, you are going to learn about the TCP/IP stack. All right, so let's talk about the TCP/IP stack. So the ISO developed the OSI reference model to be generic in terms of what protocols and technologies could be categorized by the model. However, most of the traffic on the internet and the traffic on corporate networks is based on the TCP/IP protocol suite. The TCP/IP stack is a more relevant model for network designers and administrators to reference, which was developed by the United States Department of Defense. The TCP/IP stack has only 4 defined layers as opposed to 7 layers presented in the OSI model. And the TCP/IP stack, it allows for network designers and administrators to more easily categorize a given networking technology into a specific layer. Let's talk about the layers of the TCP/IP stack. So the TCP/IP stack is composed of the following layers. You have the network interface layer. So the TCP/IP stack's network interface layer, it encompasses the technologies offered by layers 1 and 2, or the physical and data link layers of the OSI model. Then you have the internet layer. And the internet layer of the TCP/IP stack, it maps to layer 3, or the network layer of the OSI model. Although multiple routed protocols live at the OSI model's network layer, the internet layer of the TCP/IP stack focuses on IP as the protocol to be routed through a network. Next, we have the transport layer. So the transport layer of the TCP/IP stack, it maps to layer 4, or the transport layer of the OSI model. The 2 primary protocols found at the TCP/IP stack's transport layer are TCP and UDP. And then we have the application layer. So the biggest difference between the TCP/IP stack and the OSI model is at the TCP/IP stack's application layer. This layer addresses concepts described by layers 5, 6, and 7, or the session, the presentation, and the application layers of the OSI model. And as a common practice, the OSI layer numbers 1, 2, and 3 are still used when referring to the physical, data link, and network layers of the TCP/IP stack, even though the TCP/IP stack does not explicitly separate the physical and data link layers. With the reduced complexity of a 4-layer model like the TCP/IP stack, network designers and administrators can more easily categorize a given networking technology into a specific layer. All right, so let's talk about the format of an IP version 4 packet. So notice that there are fields in the IP packet header for both source and destination IP addresses. The protocol field shows the transport layer protocol from which the packet was sent or to which the packet should be sent. Also of note is the time to live field. The value in this field is decremented by 1 every time this packet is routed from one IP network to another. That is, when it passes through a router. If the time to live value ever reaches 0, then the packet is discarded from the network, and this behavior helps to prevent routing loops. Let's talk about the structure of a TCP segment. So this picture right here, it details the structures of a TCP segment. Notice the fields for source and destination ports. As described later in this video, these ports identify to which upper layer protocol data should be forwarded, or from which upper layer protocol the data is being sent. Also notice the field for window size. The value in this field determines how many bytes a device can receive before expecting an acknowledgement. And as previously described, this feature offers flow control. In the header of a TCP segment, this also contains what is called a sequence sequence number for segments. With sequence numbering, if segments arrive out of order, the recipient can put them back in the proper order based on the sequence numbers. And the acknowledgement number in the header shows the next sequence number the receiver expects to receive. This is a way for the receiver to let the sender know that all segments up to and including that point have been received. And due to the sequencing and acknowledgments, TCP is considered to be a connection-oriented transport layer protocol. Next, let's talk about TCP flags. So you might have noticed that both the IP header and the TCP header make use of a flags field. Including this field is a very common technique in networking to permit the data unit to convey specific settings. So for example, the IP header uses the IP flags field, which is 3 bits, to help manage or prevent fragmentation. TCP flags are used to indicate a particular connection state or provide additional information. They are often used for troubleshooting purposes or to control how a particular connection is handled. Next, we have what is called the UDP header. So in this picture, this presents the structure of a UDP segment. UDP is a connectionless, unreliable protocol. UDP lacks the sequence numbering, the window size, and acknowledgement numbering that is present in the header of a TCP segment. The UDP segment header simply contains source and destination port numbers, a UDP checksum, which is an optional field used to detect transmission errors, and the segment length, which is measured in bytes. Because a UDP header is much smaller than a TCP header, UDP is a good candidate for the transport layer protocol for applications that need to maximize bandwidth and do not require acknowledgments, such as audio or video streams. So let's talk about common application protocols in the TCP/IP stack. So application layer protocols in the TCP/IP stack are identifiable by unique port numbers. So for example, when you enter a web address in an internet browser, you are by default communicating with that remote web address using TCP port 80, specifically Hypertext Transfer Protocol, or HTTP, which is the protocol used by web servers. Therefore, the data you send to that remote web server has a destination port number of 80. That data is encapsulated into a TCP segment at the transport layer. That segment is further encapsulated into a packet at the internet layer and sent out on the network using an underlying network interface layer technology such as Ethernet. Now, as a side note, thanks to the awareness of network security today, you do not see HTTP or port 80 actually being used on the internet very much anymore. It has been replaced with a secured version known as HTTPS, which uses TCP port 443 in its operation. So consider the example in this picture displayed on your screen. When you send traffic to the remote website, the packet you send out to the network needs not only the destination IP address, which will be 172.16.1.2 in this example of the web server, and the destination port number for HTTP, which will be port 80, but also the source IP address of your computer, which will be 10.1.1.1 in this example. Because your computer is not acting as a web server, its port is not port 80. Instead, your computer selects a source port number greater than 1023. In this example, let's imagine that the client's PC selects the source port of 1248. Now notice that when the web server sends content back, the IP addresses and port numbers have now switched, with the web server as the source and your PC as the destination. With both source and destination port numbers, along with the source and destination IP addresses, two-way communication becomes possible. And as a side note, ports that are numbered 1023 and below, these are called well-known ports, and ports that are above 1023, these are called ephemeral ports, and the maximum value of a port can be 65,535. In this video, you're going to learn about various network types and their characteristics. All right, so let's go ahead and define a network. So computer networks, they are no longer relegated to allowing a group of computers to access a common set of files stored on a computer chosen as a file server. Instead, with the building of high-speed, highly redundant networks, network architects are seeing the wisdom of placing a variety of traffic types on a single network. And examples include voice and video, in addition to data. And as you'll learn, the Internet of Things means just about everything wants to join your network, from the lights in your home to many of your household appliances. And one could argue that a network is the sum of its parts. So as you begin your study of networking, you should start to gain a basic understanding of fundamental networking components, including such entities as the client, server, hub, switch, and router, as well as the media used to interconnect these devices. So let's go ahead and talk about the purpose of networks. So the basic purpose of a network is to make connections. These connections might be between a PC and a printer, or between a laptop and the internet, as just a couple of examples. However, the true value of a network comes from the traffic flowing over those connections. So consider a sampling of applications that can travel over a network's connections, such as file sharing between two computers, video chatting between computers located in different parts of the world, surfing the web, such as using social media, watching streaming video, listening to the internet, radio, etc., instant messaging between computers with instant messaging software installed, email, and voice over IP to replace traditional telephony systems. Now, a term given to a network that's transporting multiple types of traffic, such as voice, video, and data, is called a converged network. A converged network might offer significant cost savings to organizations that previously supported separate network infrastructures for voice, data, and video traffic. This convergence also potentially reduces staffing costs because only a single network needs to be supported rather than separate networks for separate traffic types. So let's talk about network types and their characteristics. So as you might be sensing at this point, not all networks look the same. They vary in many ways, and one criterion by which networks are classified is how geographically dispersed the network components are. So for example, a network might interconnect devices within an office, or a network might interconnect the database at a corporate headquarters location with a remote sales office on the opposite side of the globe. And based on the geographic dispersion of network components, you can classify networks into various categories, including the following. You got local area networks, wide area networks, wireless local area networks, storage area networks, campus area networks, metropolitan area networks, and personal area networks. In addition to discussing these categories, this video is also going to talk about what is called a software-defined wide area network and multi-point generic routing encapsulation technologies, which help to create what are called network overlays, which permit virtualization of network topologies. And the traditional hardware and software of the network makeup is what is referred to as the underlay. All right, so let's talk about the first one, which is a LAN, or a local area network. So a LAN interconnects network components with a local area, such as an office building. An example of common LAN technologies you are likely to meet include Ethernet and wireless networks. And then we have what is called a wireless local area network. And this is a local area network made up of wireless networking devices in a wireless local area network. Next, we have what is called a WAN, or a wide area network. And a WAN, it interconnects network components that are geographically separated. So for example, a corporate headquarters might have multiple WAN connections to remote office sites. Multi-protocol label switching, which is known as MPLS, and asynchronous transfer mode, or ATMs, these are examples of wireless area network technologies. Next, we have what is called a SAN, or a storage area network, and you can construct a high-speed, highly reliable network for the purposes of transmitting stored data. And once again, this type of network is called a storage area network. All right, so let's talk about some other categories of networks. So although LAN and WAN are the most common terms used to categorize computer networks based on geography, other categories include campus area networks, metropolitan area networks, and personal area networks. Let's talk about the first one, which is called a CAN, or a campus area network. So you would typically find a CAN type of topology at a major university. Some universities can cover several square miles and have several dozen buildings. Many of these buildings are running individual LANs, and these building-centric LANs are interconnected. The interconnection of these LANs creates another type of network, which is known as the campus area network. Besides being common on university campuses, you can also find CANs in industrial parks and business parks as well. Next, we have what is called a metropolitan area network, or a MAN. So more widespread than a CAN and less widespread than a WAN, a metropolitan area network. It interconnects locations scattered throughout a metropolitan area. So imagine, for example, that a business in Chicago has a location near the O'Hare Airport, and then another location near the Navy Pier, and another location in the Willis Tower, which is formerly known as the Sears Tower. If a service provider could interconnect those locations using a high-speed network, such as a 10 gigabit per second network, the interconnection of those locations would form a metropolitan area network, or a MAN. And one example of a MAN technology is known as Metro Ethernet, which features much higher speeds than traditional wide area network technologies that were used in the past to connect such locations. And next we have what is called a PAN, or a personal area network. And this is a network whose scale is even smaller than that of a local area network. So for example, a connection between a PC and a digital camera via a USB cable could be considered a PAN. Another example is a PC connected to an external hard drive via a USB 3.0 or Thunderbolt connection. Personal area network, however, is not necessarily a wired connection. A Bluetooth connection between your cell phone and your car's audio system is considered a wireless personal area network. And the main distinction of a PAN is that its range is typically limited to just a few meters. Next, we have what is called software-defined wide area networks, or an SD-WAN. So almost every major networking vendor now offers a software-defined wide area network product. Cisco Systems, for example, currently has 2 of these solutions in its portfolio. The Cisco SD-WAN that Cisco acquired through the purchase of a company called Viptela, and the SD-WAN that is a part of Cisco's Meraki acquisition. An SD-WAN provides a simple policy and profile approach to managing a wide area network. It also provides tools that enables new levels of visibility into and control over the use of the varied wide area network circuits in the typical enterprise today. Next, let's talk about the multi-protocol label switching, or the MPLS. So MPLS is growing in popularity as a wide area network technology that is used by service providers. The growth in popularity is due in part to MPLS's capability to support multiple protocols on the same network. So for example, an MPLS network can accommodate users connecting via frame relay, or ATM, on the same MPLS backbone. And MPLS's capability to perform the traffic engineering, which allows traffic to be dynamically routed within an MPLS cloud based on current load conditions of specific links and availability of alternate paths. MPLS, it inserts a 32-bit header between layer 2 and layer 3 headers. Because this header is shimmed between layer 2 and layer 3 headers, it is sometimes referred to as a shim header. And the 32-bit header contains a 20-bit label that is used to make forwarding decisions within an MPLS cloud. And the process of routing MPLS frames through an MPLS cloud is referred to as label switching. All right, next let's talk about a multi-point generic routing encapsulation. So normally the flexibility GRE encapsulation protocol is a point-to-point type of technology. The multi-point generic routing encapsulation, known as MGRE variation of GRE, is a multi-point technology. In fact, when you create a GRE tunnel, you specify source and destination interfaces for the tunnel. When you create an MGRE tunnel interface, all you specify is the source interface. You do not specify a destination because there are multiple dynamic peers. MGRE is one of the key technologies in the dynamic multi-point VPN solution. MGRE makes the tunnels that are formed dynamically between spokes and hubs and between spokes and other spokes. The MGRE tunnels are secured with IPsec, or Internet Protocol Security, virtual private networking technology. And if all of that was confusing for you, here is a picture kind of visualizing what a GRE tunnel is in comparison to what an MGRE tunnel is. All right. So next, let's talk about networks defined based on resource location. So another way to categorize networks is based on where the network resources reside. So for example, a client server network, this is a collection of PCs all sharing files stored on a centralized server. However, if those PCs had their operating systems such as Microsoft 10 or Mac OS configured for file sharing, they could share files from one another's hard drives. And this is referred to as a peer-to-peer network because the peers, which are the PCs in this example, make resources available to other peers. So let's talk about the client server networks. So this picture on your screen here, this is an example of a client server network where a dedicated file server gives shared access to files and a network printer is available as a resource to the network's clients. Client server networks are commonly used in business because resources are found on one or more servers, and administration is simpler than the administration of network resources on multiple peer devices. And the performance of a client server network can be better than that of a peer-to-peer network because resources can be located on dedicated servers rather than on PCs running a variety of end-user applications. And you can simplify backups because fewer locations must be backed up. However, client server networks do come with the extra expense of dedicated server resources. And this table listed on your screen right here, this does list some of the benefits and drawbacks of the client server network. Now, as a side note, a server in a client server network could be a computer running a network operating system, such as Linux server or one of the Microsoft Windows server operating systems. Alternatively, a server might be a host making its file system available to remote clients via the network file system service, which was originally developed by Sun Microsystems. And as another side note, a variant of the traditional server in a client server network where the server provides shared file access. This is called network attached storage. A network attached storage device, this is a mass storage device that attaches directly to a network. Rather than running an advanced network operating system, a network attached storage device usually makes files available to network clients via a service such as network file systems. And let's talk about peer-to-peer networks. So peer-to-peer networks allow interconnected devices such as PCs to share their resources with one another. Those resources could be things like files or printers. And as an example of a peer-to-peer network, consider this picture right here on your screen where each of the peers can share files on its hard drive. And one of the peers has a directly attached printer that can be shared with the other peers in the network. Now, peer-to-peer networks, they tend to be used in smaller businesses and in homes, and the popularity of peer-to-peer networks is fueled in part by client operating systems that support file and print sharing. Scalability for peer-to-peer networks is a concern, however, specifically as the number of devices or peers increase, the administration does become a burden. So, for example, a network administrator might have to manage file permissions on multiple devices as opposed to on a single server. And as a side note, some networks have characteristics of both peer-to-peer and client-server networks. So, for example, all PCs in a company might point to a centralized server for accessing a shared database in a client-server topology. However, these PCs might simultaneously share files and printers with one another in a peer-to-peer topology. In such a network, which has a mixture of client-server and peer-to-peer characteristics, this is what is known as a hybrid network. In this chart right here, this outlines some of the benefits and the drawbacks of dealing with a peer-to-peer network. In this video, you're going to learn about network topologies and service-related entry points. All right, so let's talk about network topology. So a network topology, this refers to the physical or logical layout of a network. It defines the way different nodes are placed and interconnected with each other. Alternatively, a network topology may describe how the data is transferred between these nodes. All right, so let's talk about a logical topology. So a logical topology, this is a concept in networking that defines the architecture of the communication mechanism for all nodes in the network. That is the actual flow of traffic through the network. Using network equipment such as routers and switches, the logical topology of a network can be dynamically maintained and reconfigured. Next, we have the physical topology. So this refers to the interconnected structure of a local local area network. The method employed to connect the physical devices on the network with the cables and the type of cabling that's being used all constitute the physical topology. Our next topology is the bus topology, and this is also referred to as a line topology. And this is a network setup where each computer and network device is connected to a single cable or backbone. Depending on the type of computer network card, a coaxial cable or an RJ45 network cable is used to connect them together. And so let's talk about the advantages and disadvantages of a bus topology. So the advantages are it works well when you have a small network. It's the easiest network topology for connecting computers or peripherals in a linear fashion, and it requires less cable length than a star topology. Its disadvantages, it can be difficult to identify the problems if the whole network goes down. It can be hard to troubleshoot individual device issues. Bus topologies are not great for large networks. Terminators are required for both ends of the main cable. Additional devices will slow the network down, and if the main cable is damaged, the network will fail or split into two. Let's talk about our next topology, which is the ring topology. And this is a network configuration where device connections create a circular data path. Each network device is connected to two others like points on a circle. Together, devices in a ring topology are referred to as a ring network. In a ring network, packets of data travel from one device to the next until they reach their destination. Most ring topologies allow packets to travel only in one direction, and this is called a unidirectional ring network. Others permit data to move in either direction, and this is called a bidirectional network. Ring topologies may be used in either local area networks or wide area networks, and depending on the network card used in each computer of the ring topology, a coaxial cable or an RJ45 network cable is used to connect the computers together. And here are the advantages and disadvantages of a ring topology. So the advantages are all data flows in one direction, reducing the chance of packet collisions. A network server is not needed to control network connectivity between each workstation. Data can transfer between workstations at high speeds, and additional workstations can be added without impacting performance at the network. Its disadvantages are all data being transferred over the network must pass through each workstation on the network, which can make it slower than a star topology. The entire network will be impacted if one workstation shuts down, and the hardware needed to connect each workstation to the network is more expensive than Ethernet cards and hubs and switches. All right, let's talk about our next one, which is a star topology, and this is also known as a star network. And this is one of the most common network setups. In this configuration, every node connects to a central network device like a hub, switch, or a computer. The central network device acts as a server, and the peripheral devices act as clients. In a star topology setup, either a coaxial or RJ45 network cable is used, depending on the type of network card installed in each computer. And the advantages of a star topology are as follows. It has centralized management of the network through the use of the central computer hub or switch. It's easy to add another computer to the network, and if one computer on the network fails, the rest of the network continues to function normally. Its disadvantages, it may have a higher cost to implement, especially when using a switch or router as the central network device. The central network device determines the performance and number of nodes the network can handle, and if the central computer hub or switch fails, the entire network goes down and all computers are disconnected from the network. All right, so our next topology is a hub and spoke topology. So when interconnecting multiple sites, such as multiple corporate locations via wide area network links, a hub and spoke topology may be used, with a wide area network link for each remote site, which is known as the spoke site, to the main site, which is known as the hub site. And this approach is similar to the star topology used in local area networks. With wide area network links, a service provider is paid a recurring fee for each link. Therefore, a hub and spoke topology helps minimize wide area network expenses by not directly connecting any two spoke locations. If two spoke locations need to communicate with each other, their communication is sent via the hub location. And here are some of the advantages and disadvantages of the hub and spoke topology. So the advantages are it offers a reduced cost due to the minimum number of links that are used, and adding one or more additional sites is easy because only one link needs to be added per site. The disadvantages, it has suboptimal routes that must be used between remote sites because all inter-site communication must travel through the main site. All remote sites converge on the main site, and the hub site is potentially a single point of failure. And each remote site is reachable by only a single wide area network link. And the hub and spoke technology, it lacks redundancy. Let's talk about our next topology, which is a mesh topology. So a mesh topology, this is a network setup where each computer and network device is interconnected with one another. This topology setup allows for most transmissions to be distributed even if one of the connections goes down. It is a topology commonly used for wireless networks. And there are two forms of a mesh topology. So the first one is called a full mesh topology. So every computer in the network has a connection to each other computer in that network. And the number of connections in this network can be calculated using the following formula, where N is the number of computers in the network. And then we have a partially meshed topology. So at least two of the computers in the network have connections to multiple other computers in that network. It is an inexpensive way to implement redundancy in a network. And if one of the primary computers or connections in the network fails, the rest of the network will continue to operate normally. So let's talk about the advantages of a mesh topology. So the advantages are it manages high amounts of traffic because multiple devices can transmit data simultaneously. A failure of one device does not cause a break in the network or transmission of data, and adding additional devices does not disrupt data transmission between other devices. Its disadvantages are the cost to implement is higher than other network topologies, making it a less desirable option. Building and maintaining the topology is difficult and time consuming, and the chance of redundant connections is high, which adds to the high costs and potential for reduced efficiency. Let's talk about service related entry points. So an important aspect of the network topology is the service related entry point. Two possibilities of which you should be aware of for the Network Plus exam are the demarcation point and what is known as the smart jack. So let's talk about the demarcation point. So a demarcation point, which is also known as a demarc or a demarc extension, this is the point in a telephone network where the maintenance responsibility passes from the telephone company to the subscriber, unless the subscriber has purchased inside wiring maintenance. This demarc is typically located in a box that is mounted to the outside of a customer's building or their home, and this box is called a network interface device. And finally, we have what is called a smart jack. And this is a type of network interface device that adds circuitry. This circuitry adds such features as converting between framing formats on a digital circuit, such as a T1 circuit. It supports remote diagnostics and regenerating a digital signal. In this video, you're going to learn about virtual network concepts. So let's talk about virtual network concepts. So a major data center paradigm shift is underway, and this shift is away from a company having its own data center with its raised flooring and large air conditioning system containing multiple physical servers, each of which offer a specific service like email, DNS services, or Microsoft Active Directory. So let's talk about virtual servers. So the computing power available in a single high-end server is often sufficient to handle the tasks of multiple independent servers. With the advent of virtualization, multiple servers, which might be running different operating systems, can run in virtual server instances on one physical device. So for example, a single high-end server might be running an instance of a Microsoft Windows server, providing Microsoft Active Directory services to an enterprise, while simultaneously running an instance of a Linux server acting as a corporate web server, and at the same time time acting as an Oracle Solaris Unix server, providing corporate DNS services. And many virtual server platforms, they can support multiple network interface cards or NICs, and having multiple NICs offers increased throughput and load balancing. In virtualization, this is possible with servers thanks to a specialized software called a hypervisor. The hypervisor takes physical hardware and abstracts it for the virtual server. The extent of virtualization can be amazing, and even the NIC of each virtual server can be represented virtually, giving you what is called a virtual network interface card. And the networks and systems supporting virtual servers also commonly have network attached storage, where this storage is delivered as a service over the network. A technology for network storage is IP-based small computer system interface, or iSCSI. And with iSCSI, a client using the storage is referred to as an initiator, and the system providing the iSCSI storage is called the iSCSI target. And the networks supporting iSCSI are often configured to support larger than normal frame sizes, and these are what are referred to as jumbo frames. All right, so let's talk about virtual routers and firewalls. So most of the vendors that create physical routers and firewalls also have an offering that includes virtualized routers and firewalls. The benefit of using a virtualized firewall or router is that the same features of routing and security can be available in the virtual environment as it is in the physical environment. As part of interfacing with virtual networks, virtual network adapters can also be used. So for connectivity between the virtual world and the physical one, physical interfaces can be used to connect to the logical virtual interfaces. And virtualization is pervasive in networking today. In fact, virtualization is now used to implement almost all network functionality. There's actually a term for this approach, and it's called network function virtualization. And network function virtualization can include security, storage, compute, and monitoring services. Next, let's talk about virtual switches. So one potential trade-off you make with the previously described virtual server scenario is that all servers belong to the same IP subnet, which could have quality of service and security implications. If these server instances ran on separate physical devices, they could be attached to different ports on an Ethernet switch. These switch ports could belong to different VLANs, which could place each server in a different broadcast domain. Fortunately, some virtual servers allow you to still have layer 2 control. So for example, VLAN separation and filtering. This layer 2 control is made possible by the virtual server, not only virtualizing instances of servers, but also virtualizing a layer 2 switch. All right, next let's talk about virtual desktops. So another emerging virtualization technology is virtual desktops. Today's users are more mobile than ever before, and they need access to information traditionally stored on their office computers' hard drives from a variety of other locations. So for example, a user might be at an airport using their smartphone and need access to a document they created on their office computer. With virtual desktops, a user's data is stored in a data center rather than on an office computer's hard drive. By providing authentication credentials, the user can establish a secure connection between the centralized repository of user data and their device, thus allowing the user to remotely access the desired document. And finally, let's talk about other virtualization solutions. So although the previously discussed virtualization technologies such as virtual servers, switches, and virtual desktops are described as residing at a corporate location, or what is known as on-site, some service providers offer off-site options. Specifically, if a service provider's customers did not want to house and maintain its own data center, these virtualization technologies could be located at a service provider's data center, and the customer could be billed based on usage patterns. Such a service provider offering, this is what is known as network as a service, implying that network features can be provided by a service provider, just as telephony service providers offer access to public switch telephone networks, and an ISP offers access to the public internet. In this video, you're going to learn about provider links such as satellite, digital subscriber line, cable, leased lines, metro optical, and Sonnet. All right, so let's first talk about satellite. So, satellite internet services, they can be used by individuals and businesses that are out of reach of wired internet services. Satellite internet services are often bundled with satellite TV services, and satellite internet services, they use oval satellite antennas, which are very similar in appearance to satellite TV antennas, to connect with geosynchronous communication satellites orbiting over the equator. These satellites relay internet from ground stations to individual users and viewers via a satellite modem, and satellite modems are proprietary to each satellite service and are usually purchased by the user. And satellite internet services offer pricing based on one or two variables. You got data bandwidth that is allowed per month and downstream or download speeds. Data bandwidth per month ranges from 10 to 50 gigabytes to 35 to 100 gigabytes. Current download speeds, they can vary from 12 to 50 megabits per second all the way to 25 megabits per second. And satellite internet vendors, they do have data caps. Now, due to the extra time involved in relaying signals from a ground base to a satellite and back to the individual user, satellite internet services are a poor choice for gaming or voice over IP services. So here are some of the satellite advantages. You have no geographical barriers. The signal can reach places where cable or fiber are not available, and satellite is faster than a traditional old school dial-up connection. Some of the disadvantages of using satellite are it can be an expensive installation. The equipment cost can be expensive because you got to get the modem and the dish. It can be unreliable due to weather conditions that can affect the connection. You have data caps, which are common with satellite providers, and you can have a slow ping rate, which is unsuitable for playing video games online, video chat, or using voice over IP. Next, let's talk about DSL, or digital subscriber line. So a provider link that used to be commonplace in many residential and small business locations is DSL. And DSL installations, they are becoming more and more rare, but they still do exist. In DSL, this is a group of technologies that provides high-speed data transmission over existing telephone wiring. In DSL, it has several variants that differ in data rates and distance limitations. And the first one is called asymmetric DSL, or ADSL. And this is a popular internet access solution for residential locations. ADSL allows an existing analog telephone to share the same line used for data for simultaneous transmission of voice and data. So essentially, you can surf the internet and talk on the phone at the same time. And the maximum distance from a DSL modem to a DSL access multiplexer, or a DSLAM, is 18,000 feet. This limitation stems from a procedure telephone companies have used for decades to change the impedance of telephone lines. And the term asymmetric in asymmetric DSL, this indicates that the upstream and downstream speeds can be different. Typically, downstream speeds are greater than upstream speeds in ADSL connections, and that's because more people download than they upload. And the theoretical maximum downstream speed for an ADSL connection is about 8 megabits per second, and the maximum upstream speed is about 1.544 megabits per second, which is the equivalent to a T1 circuit, which you'll learn about later on. All right, next we have what is called a symmetric DSL, or an SDSL. So where ADSL is asymmetric, or it has an unequal upstream and downstream speed, by definition, SDSL has symmetric or equal upstream and downstream speeds. And another distinction between ADSL and SDSL is that SDSL does not allow simultaneous voice and data on the same phone line. Therefore, SDSL is less popular in residential installations because an additional phone line is required for data. Although service providers vary, a typical maximum upstream downstream data rate for an SDL connection is about 1.168 megabits per second. Also, SDSL connections are usually limited to a maximum distance of 12,000 feet between the DSL modem and its DSLAM. And then we have what is called very high bit rate DSL, or VDSL. So VDSL, this has a much higher bandwidth capacity than ADSL or SDSL. DSL with a common downstream limit of 52 megabits per second and a limit of 12 megabits per second for upstream traffic. All right, so the next provider link is cable. So cable television companies have a well-established and wide-reaching infrastructure for television programming. This infrastructure might contain both coaxial and fiber optic cabling, and such an infrastructure is called a hybrid fiber coax or an HFC distribution network. These networks can designate specific frequency ranges for upstream and downstream data transmissions, and the device located in a residence or a small business that can receive and transmit in those data frequency ranges, that is known as a cable modem. So the frequency ranges typically given for upstream and downstream data are as follows. So you got upstream data frequencies from 5 megabits per second to 42 megabits per second, and downstream data from 50 megabits to 860 megabits per second. Although the theoretical maximum upstream downstream bandwidth limits are greater and are dependent on the HFC distribution network that's in use, most upstream speeds are limited to around 20 megabits per second, with downstream speeds limited to around 200 megabits per second. As HFC distribution networks continue to evolve, greater bandwidth capacities will be available, and the current theoretical maximums are 1 gigabit per second upstream and 10 gigabit per second downstream. And the frequencies dedicated to data transmission are specified by a Data over Cable Service Interface Specification, or a DOCSIS version. Although DOCSIS is an international standard, European countries use their own set of frequency ranges, which are known as Eurodoxis. All right, so let's talk about a leased line, and this is also referred to as a dedicated leased line. But a leased line, this is typically a point-to-point connection interconnecting two sites. All the bandwidth on the dedicated leased line is available to those sites. That means that unlike with packet switch connections, the bandwidth of a dedicated leased line connection does not need to be shared amongst multiple service provider customers. And then we have WAN technologies that are used with dedicated leased lines that include digital circuits such as a T1, E1, T3, and an E3 circuit. These circuits can use multiplexing technology to simultaneously carry multiple conversations in different 64 kilobit per second channels. A single 64 kilobit per second channel, this is called a digital signal zero, or a DS0. When one of those circuits comes into your location, it terminates on a device called a channel service unit data service, or a CSU-DS. All right, so let's talk about the T1 circuit. So T1 circuits, they were originally used in telephony networks with the intent of one voice conversation being carried in a single channel. A T1 circuit is composed of 24 DS0s, which is called a digital signal 1, or a DS1. And the bandwidth of a T1 circuit is 1.544 megabits per second. In a T1 environment, more than one frame is sent out at once. And here are two popular approaches to grouping these frames. The first one is called a super frame, and this combines 12 standard 193-bit frames into a super frame. And then you have what is called the extended super frame. This combines 24 standard 193-bit frames into an extended super frame. And also T1 circuits, they are very popular in North America and Japan. Next, we have the E1 circuit. So an E1 circuit, this contains 32 channels, in contrast to the 24 channels on a T1 circuit. Only 30 of those 32 channels, however, can transmit data or voice or video. Specifically, the first of those 32 channels is reserved for framing and synchronization, and the 17th channel is reserved for signaling. That is setting up, maintaining, and tearing down a call. Because an E1 circuit has more DS0s than a T1, it has a higher bandwidth capacity. Specifically, an E1 has a bandwidth capacity of 2.048 megabits per second. And unlike a T1 circuit, an E1 circuit does not group frames in super frames or extended super frames. Rather, an E1 circuit groups 16 frames in a multi-frame. Next, let's talk about the T3 circuit. So in the same T carrier family of standards as T1, a T3 circuit offers an increased bandwidth capacity, whereas a T1 circuit combines 24 DS0s into a single physical connection to offer 1.544 megabits per second of bandwidth. A T3 circuit combines 672 DS0s into a single physical connection delivered to the customer over coaxial cable, which is called a digital signal 3 or a DS3. A T3 circuit, this has a bandwidth capacity of 44.7 megabits per second. All right, and then we have the E3 circuit. So just as a T3 circuit provides more bandwidth than a T1 circuit, an E3 circuit's available bandwidth of 34.4 megabits per second is significantly more than the 2.048 megabits per second of bandwidth offered by an E1 circuit. A common misconception is that the bandwidth of E3 is greater than the bandwidth of T3 because E1's bandwidth is greater than T1's bandwidth. However, this is not the case. A T3 has a greater bandwidth of 44.7 megabits per second than the E3, which only has 34.4 megabits per second. Next, let's talk about the metro optical. So telecommunication networks today are often divided into a three-tier hierarchy consisting of the access section, the metropolitan section, and the long haul section. This metropolitan section clearly plays an important role and connects to both the access section and the long haul section. Typically, this portion of the telecommunication network covers an area of 10 to 100 kilometers and is based on a sonnet ring architecture. Now, while this section is described using many different terms, CompTIA likes the term metro optical for the technology used in this part of the WAN. Finally, let's talk about the synchronous optical network, or the sonnet. And this is a layer 1 technology that uses fiber optic cabling as its media. Because sonnet is a layer 1 technology, it can be used to transport various layer 2 encapsulation types such as ATM. Also, because sonnet uses fiber optic cabling, it offers high data rates, typically in the 155 megabits per second to 10 gigabits per second range, and long distance limitations, which typically fall within 20 kilometers to 250 kilometer range. Also, sonnet networks, they can vary in their physical topology. So for example, a sonnet network can connect as many as 16 other devices in a linear fashion, similar to that of a bus topology or in a ring topology. And a metropolitan area network often uses a ring topology. The ring might circumnavigate a large metropolitan area, and a site within the metropolitan area network could then connect to the nearest point on the sonnet ring. And a sonnet network that uses a single wavelength of light along with time division multiplexing to support multiple data flows on a single fiber. In this video, you're going to learn about copper media and its connectors. All right, so let's talk about copper media and the connectors. So a network, this is an interconnection of devices. Those interconnections occur over some type of media, and the media might be physical, such as a copper or fiber optic cable. Alternatively, the media might be the air through which the radio waves propagate, as is the case with wireless networking technologies. So let's go ahead and talk about coaxial cables. A coaxial cable, it consists of two conductors, as depicted in this picture right here. One of the conductors is an inner insulated conductor, and this inner conductor is surrounded by another conductor that is sometimes made of a metallic foil or woven wire. Now, because the inner conductor is shielded by the metallic outer conductor, coaxial cable is resistant to electromagnetic interference. So for example, EMI occurs when an external signal is received on a wire that might result in a corrupted data transmission. As another example, EMI occurs when a wire acts as an antenna and radiates electromagnetic waves, which might interfere with data transmissions on another cable. Coaxial cables have associated impedance that needs to be balanced with the device or the terminator with which the cable connects. And there are three common types of coaxial cables. The first one is called the RG59, and this typically is used for short distance applications such as carrying composite video between two nearby devices. This cable has loss characteristics such that it is not right for long distance applications. An RG59 cable has a characteristics impedance of 75 ohms. And then you got RG6, and this is used by local cable companies to connect individual homes to the cable company's distribution network. Like RG59 cable, RG6 cable has a characteristic impedance of 75 ohms as well. And then you got RG58. This has loss characteristics and distance limitations like those of the RG59. However, the characteristic impedance of RG58 is 50 ohms, and this type of coaxial was popular with early 10-base-2 Ethernet networks. Now, as a side note, a far less popular cabling is called twin axial, also known as twinax, and this is very similar to coaxial cable, but it uses two inner conductors instead of one. And these are the common connectors that are used on coaxial cables. You got the BNC, which is the bayonet Neil Consolman connector, also known as the British naval connector. And this can be used for a variety of applications, including as a connector in a 10-base-2 Ethernet network and a BNC coupler. This could be used to connect two coaxial cables together back to back. And then the other connector is the F connector, and an F connector is often used for cable TV, including the cable modem connections. And you might also see the F connector simply referred to as the F-type connector as well. Next, let's talk about twisted pair cable. So today's most popular LAN media type is twisted pair cable, in which individually insulated copper strands are intertwined. Two categories of twisted pair cables are shielded twisted pair, or STP, and unshielded twisted pair, or UTP. A UTP coupler could be used to connect two UTP cables back to back. Also, for adherence to fire codes, you might need to select what is called a plenum rated cable versus that of a non-plenum cable. And we'll talk about plenum versus non-plenum later on in this video. All right, so let's go ahead and talk about shielded twisted pair versus unshielded twisted pair. So twisted pair cabling, this is a type of wiring in which two conductors of a single circuit are twisted together for the purposes of improving electromagnetic compatibility. Twisted pair cabling is the most common of the major cabling types, and twisted pair cabling typically consists of four twisted pairs of wires that are surrounded by a flexible jacket or various types of metals of foil or braid. STP and UTP are shielded twisted pair and unshielded twisted pair. They use the same RJ45 connector, but shielded twisted pair includes a metal shield for electrical insulation between the wires and the outer jacket. Shielded twisted pair is also stiffer and more durable, yet more expensive and harder to loop through tight spaces than unshielded twisted pair. It is used where electromagnetic interference prevents the use of unshielded twisted pair cabling. Both cables can be purchased in pre-built assemblies or using bulk cable and connectors. And unshielded twisted pair cable types, they vary in their data carrying capacity. So these are some of the common categories of unshielded twisted pair cabling. You got what is called Category 5 or Cat5, and this is most commonly used in Ethernet 100 base TX networks, which carry data at a rate of 100 megabits per second. However, Cat5 cable can carry ATM traffic at a rate of 155 megabits per second, and most Cat5 cables consist of four pairs of 24 gauge wires. Now you got Cat5e. This is an updated version of Cat5 that is commonly used for 1000 base T networks, which carry data at a rate of 1 gigabit per second. Also, Cat5e cables, they offer reduced crosstalk compared to the Cat5 cable. Next, we got Cat6. So like Cat5e cable, Cat6 cable is commonly used for 1000 base T Ethernet networks. And some Cat6 cable is made of thicker conductors like 22 or 23 gauge wires, although some Cat6 cable is made from the same 24 gauge wire used by the Cat5 and the Cat5e. Also, Cat6 cable has thicker insulation and offers reduced crosstalk compared with the Cat5e. And then we have the Cat6a, and this supports supports twice as many frequencies as Cat6 and can be used for 10 base T networks, which can transmit data at a rate of 10 billion bits per second or 10 gigabits per second. And then we have Cat7, and this is not an IEEE standard and is not very popular as a result. This very strict specification supports 10 gigabits per second over 100 meters using copper media. And then we have what is called Cat8. And this is capable of 40 gigabits per second speeds. And as you might guess, however, the speed comes at a cost. Cat8 supports distances of only 30 to 36 meters, depending on the patch cables that are used. And these short distances and very high speeds, they are ideal for connections in data centers between high-speed multi-layer switches. And although other wiring categories exist, the ones that are presented in this list are the categories that are most commonly seen in modern networks. Next, let's talk about the T568B and the T568A standards. So the wiring standard for all types of Ethernet untwisted pair cabling is known as the T568B. And this type of cable is also known as a straight through cable, which is most commonly used to connect a host to a client or dissimilar devices, such as with the RJ45 wire connected from a PC to a home router. In the wiring order, from left to right, when looking at the top of the connector, is as follows. You got orange, white, then orange, then green, white, blue, then blue, white, green, then brown, white, and brown. And then we have the T568A standard, and this swaps the positions of the orange and green wires that are used in the T568B. And this type of cable is also known as a crossover cable, which are most commonly used to connect two hosts directly, such as a PC directly connecting to another PC or a switch connecting to another switch, or basically it connects similar devices. In the wiring order from left to right, when looking at the top, is green, white, green, orange, white, blue, blue, white, orange, and brown, white, brown. And as a side note here, a traditional port that is found in a PC's NIC is called a Media Dependent Interface, or an MDI. If a straight through cable connects a PC's MDI port to an Ethernet port to an Ethernet switch port, the Ethernet switch port needs to swap the transmit pair of wires, that is, the wires connected to pins 1 and 2, with the receive pair of wires, which are wires that are connected to pins 3 and 6. Therefore, a traditional port that's found on an Ethernet switch is called a Media Dependent Interface Crossover, or an MDIX, and it receives the transmit and receive pairs. However, if you want to interconnect two switches where both switch ports used for the interconnection are MDIX ports, the cable needs to be a crossover cable. Fortunately, most modern Ethernet switches have ports that can automatically detect whether they need to act as an MDI port or an MDIX port and make the appropriate adjustments. This eliminates the necessity of using straight through cables for some Ethernet switch connections and crossover cables for other connections. With the auto MDIX feature, you can use either a straight through cable or a crossover cable, so it doesn't really matter which one you plug in. If you plug it into an auto MDIX feature, it'll automatically adjust as necessary. Next, let's talk about some twisted pair cable connectors. So common connectors that are used on twisted pair cables are as follows. The first one is the RJ45, or the registered jack. That's what RJ stands for. And this is an 8-pin connector found in most Ethernet networks. However, most Ethernet implementations only use 4 of the 8 pins. Next, we have the RJ11, and this has the capacity to be a 6-pin connector. However, most RJ11 connectors have only 2 or 4 conductors, and an RJ11 conductor, this is found in most home telephone networks. However, most home phones use only 2 of the 6 pins. And then we have the DB9, also known as the RS232. So a 9-pin D subminiature, or the DB9 connector. This is an older connector used for low-speed asynchronous serial communication, such as a PC to a serial printer, or a PC to a console port of a router or a switch, or a PC to an external modem. But basically, this is an older connector that you really don't see around too much, but they're still floating around out there. Finally, let's talk about plenum versus non-plenum cable. So if a twisted pair cable is to be installed under RAID hallways, flooring, or in an open air return, fire codes must be considered. So for example, imagine that there is a fire in the building. If the outer insulation of the twisted pair cabling caught on fire or started to melt, it could release toxic fumes. If those fumes were released in a location such as an open air return, basically an HVAC, those fumes could be spread throughout a building, posing a huge health risk. To mitigate the concern of pumping poisonous gas throughout a building's HVAC system, plenum cabling can be used. The outer insulation of a plenum twisted pair cable is not only fire retardant. In addition, some plenum cable uses what is called fluoride ethanol polymer, or FEPs, or a low smoke polyvinyl chloride, or PVC, to minimize dangerous fumes. In this video, you're going to learn about fiber optic cabling. An alternative to copper cabling is fiber optic cabling, which sends light instead of electricity through an optical fiber, which is typically made of glass. Using light instead of electricity makes fiber optics immune to EMI. Also, depending on the layer 1 technology being used, fiber optic cables typically have a greater range, that is, a greater maximum distance between network devices and greater data carrying capacities. Lasers are often used to inject light pulses into a fiber optic cable. However, lower cost light emitting diodes, or LEDs, are also available. Fiber optic cables are generally classified according to their diameter and fall into one of two categories. They can either be multi-mode fiber or single mode fiber. And the wavelengths of light, they also vary between multi-mode fiber and single mode fiber cables. Usually wavelengths of light in an MMF cable are in the range of 850 to 1300 nanometers, which is basically 1/1000th of a meter. Conversely, the wavelengths of light in an SMF cable are usually in the range of 1310 to 1550 nanometers. And you can also use a fiber coupler to connect two fiber cables back to back. So we're going to go ahead and talk about multi-mode fiber. So when a light source, such as a laser, sends light pulses into a fiber optic cable, exactly what keeps the light from simply passing through the glass and being dispersed into the surrounding air? The trick is that the fiber optic cable uses two different types of glass. There is an inner strand of glass known as the core, surrounded by an outer cladding of glass. And the light injected by a laser or an LED enters the core, and the light is prevented from leaving the inner strand and going into the outer cladding of glass. Specifically, the indexes of refraction of these two different types of glass are so different that if the light attempts to leave the inner strand, it hits the outer cladding and bends back on itself. So to better understand this concept, consider a straw and a glass of water. Because air and water have different indexes of refraction, that is, the light travels at slightly different speeds in air and water, the light that bounces off the straw and travels to our eyes is bent by the water's index of refraction. When a fiber optic cable is manufactured, you have what are called dopants that are injected into the two types of glasses, making up the core and cladding to give them significantly different indexes of refraction, thus causing any light attempting to escape to be bent back into the core. And the path that light takes through a fiber optic cable, this is called a mode of propagation. The diameter of the core in a multi-mode fiber is large enough to permit light to enter the core at different angles. If light enters at a steep angle, it bounces back and forth much more frequently on its way to the far end of the cable than does light that enters the cable perpendicularly. If pulses of light representing different bits travel down the cable using different modes of propagation, it is possible that the bits, which are the pulses of light representing the bits, they will arrive possibly out of order at the far end, where the pulses of light or the absence of light are interpreted as binary data by photoelectronic sensors. So for example, say that the pulse of light representing the first bit intersects the core at a steep angle and bounces back and forth many times on its way to the far end of the cable, while the light pulse representing the second bit intersects the core perpendicularly and does not bounce back and forth very much. With all of its bouncing, the first bit has to travel further than the second bit, and so the bits might arrive out of order. This condition is known as multi-mode delay distortion. And to mitigate multi-mode delay distortion, multi-mode fiber or MMF fiber, this is typically typically limited to shorter distances than single mode fiber. All right, let's talk about single mode fiber. So single mode fiber, this eliminates the issues of multi-mode delay distortion by having a core with a diameter so small that it only permits one mode or one path of propagation. With this issue of multi-mode delay distortion, single mode fiber typically can be run for longer distances than multi-mode fiber. Now, a potential downside to single mode fiber is the cost. Because SMF has to be manufactured to very exact tolerances, you usually pay more for a given length of single mode fiber optic cabling. However, for some implementations where greater distances are required, the cost is an acceptable trade-off for reaching greater distances. Let's talk about some fiber optic cable connectors. So some common connectors used in fiber optic cables are as follows. The first one is called a straight tip or an ST connector. And this is also sometimes referred to as a bayonet connector because of the long tip extending from the connector. ST connectors are most commonly used with multi-mode fiber. You can connect an ST connector to a terminating device by pushing the connector into the terminating equipment and then twisting the connector housing to lock it in place. Next, we have what is called a SC connector or a subscriber connector or a square connector. And you can connect an SC connector by pushing it into the terminating device, and then you can remove it by pulling the connector from the terminating device. This connector type has slight variance within the industry, with the major types being APC, UPC, and MTJR. And you always want to consult with the vendor or an IT staff member regarding the exact requirements. All right, next we have the local connector or the LC connector. And you can connect the local connector to a terminating device by pushing the connector into the terminating device. You can remove it by pressing the tab on the connector and pulling it out of the terminating device. And then we have the MTRJ connector or the mechanical transfer registered jack. The most unique characteristic of an MTRJ connector is that two fiber strands, where it's a transmit and a receive strand, are included in a single connector. You can connect the MTRJ connector by pushing it into the terminating device, and you can also remove it by pulling the connector from the terminating device. All right, next let's talk about fiber connector polishing styles. So fiber optic cables, they have different types of mechanical connections. The type of connection impacts the quality of the fiber optic transmission. Listed from basic to better, the options include the physical contact or the PC, the UPC or the ultra physical contact, and the APC, which is the angled physical contact. And they all refer to the polishing styles of the fiber optic connectors. The different polish of the fiber optic connectors, they result in different performance of the connector. The less back reflection, the better the transmission. So the PC back reflection is 40 decibels, the UPC back reflection is around 55 decibels, and the APC back reflection is around 70 decibels. Next, let's talk about Ethernet and fiber standards. So a popular implementation of Ethernet in the early days was called 10-base-5. The 10 in base 5 refer to the network throughput, specifically 10 megabits per second or 10 million bits per second. The base in 10-base-5, that refers to baseband and not broadband. And finally, the 5 in 10-base-5, this indicates the distance limitation of 500 meters. The cable used in the 10-base-5 network was a larger diameter than most types of media, and that cable is what you're looking at on your screen right here. In fact, this network also became known as ThickNet. Another earlier Ethernet implementation was 10-base-2. Now, from the previous analysis of 10-base-5, you might conclude that 10-base-2 was a 10 megabit per second baseband technology with a distance limitation of 200 meters. That is almost correct. However, 10-base-2's actual distance limitation was 185 meters. The cabling used in 10-base-2 networks was significantly thinner and therefore less expensive than the 10-base-5 cabling, and as a result, 10-base-2 cabling became known as ThinNet or cheaper net. And also, 10-base-5 and 10-base-2 networks are rarely, if ever, seen today. The cabling used by these legacy technologies quickly faded in popularity with the advent of unshielded twisted pair cabling. The 10 megabit per second version of Ethernet that relied on UTP cabling is known as 10-base-T. Notice that the T in 10-base-T, this refers to twisted pair cabling. All right, let's talk about distance and speed limitations. So to understand the bandwidth available on networks, you need to understand a few terms. And you should already know that a bit refers to one of two values. These values are represented using binary math, which uses only the numbers 0 and 1. On a cable such as a twisted pair cable, a bit could be represented by the absence or presence of voltage. Fiber optic cables, however, might represent a bit with the absence or presence of light. And the bandwidth of a network is measured in terms of how many bits the network can transmit during a 1 second period of time. So for example, if a network has the capacity to send 10 million bits in a 1 second period of time, the bandwidth capacity is said to be 10 megabits. In this table that you're looking at right here, this defines common bandwidths that are supported on distinct types of Ethernet networks. And also the type of cabling that is used in the Ethernet network influences the bandwidth capacity and the distance limitations of the network. So for example, fiber optic cabling has a higher bandwidth capacity and can be run longer distances than twisted pair cabling. And as mentioned earlier in this video, because of the issues of multi-mode delay distortion, single mode fiber usually has a longer distance limitation than multi-mode fiber. All right, next let's talk about transceivers. So when you want to uplink one Ethernet switch to another, you might need different connectors, for example, an MMF, SMF, or UTP for different installations. Fortunately, some Ethernet switches have one or more empty slots in which you can insert a gigabit interface converter, also known as a GBIC. And GBICs are interfaces that have a bandwidth capacity of 1 gigabit per second and are available with multi-mode fiber, single mode fiber, and unshielded twisted pair connectors. And this allows you to have flexibility in the uplink technology you use in the Ethernet switch. And a smaller variant of a regular GBIC is known as the small form factor pluggable, or the SFP, which is sometimes called a mini GBIC. And to show the variety of transceivers you might encounter today, even this SFP has many variations, including the following. You have what is called the enhanced form factor pluggable. You got the quad small form factor pluggable. And you have the enhanced quad small form factor pluggable. All right. And then finally, let's talk about multiplexing and fiber optic networks. So remember when we discussed the OSI model and encapsulation, in addition to network topologies and types, that multiplexing allows multiple communication sessions to share the same physical medium? At this point, you need to be familiar with 3 different approaches common with fiber networking. And the first one is called dense wavelength division multiplexing, or DWDM. DWDM uses as many as 32 light wavelengths on a single fiber, where each wavelength can support as many as 160 simultaneous transmissions using more than 8 active wavelengths per fiber. The next, you have what is called the coarse wavelength division multiplexing, or the CWDM. And the CWDM, this uses fewer than 8 active wavelengths per fiber. And then you have what is called the bidirectional wavelength division multiplexing, or the WDM. And this approach multiplexes a number of optical carrier signals onto a single optical fiber by using different wavelengths. Using this technique enables bidirectional communications over one strand of fiber and increases the overall capacity. In this video, you're going to learn about various aspects of cable management. All right, so let's talk about cable management. So after deciding what type of media you are going to use in your network, such as either UTP, STP, MMF, or SMF, you should install that media as part of an organized cable distribution system. And typically, cable distribution systems, they are hierarchical in nature. So consider the example in this picture that's posted. In this example, cable from end users' offices run back to common locations within the building. These locations are sometimes referred to as a wiring closet, and cables in these locations, they might terminate into a patch panel or a patch bay. The patch panel might consist of some sort of cross connect block wired into a series of ports. So for example, like an RJ45 port, which can be used to quickly interconnect cables coming from end user offices with a network device such as an Ethernet switch. And a common term for cross-connect blocks is known as a punch-down block. And this term indicates how you physically connect the media by punching the media into the appropriate slot. And the fiber connections in a wiring closet, they can terminate into a fiber distribution panel, also known as a fiber optic patch panel. And this cable management component is mainly used for accommodating fiber cable connections or terminations or patches. And the two major categories of fiber distribution panels are wall mount and rack mount types. So this one right here, this is a wall mount, and this is a rack mount type right here. And a building might have multiple patch panels. So for example, on different floors of the building, common locations where cables from nearby offices terminate, these are often called intermediate distribution frames or IDFs. And the two most popular types of cross-connect blocks that are found in the IDF are the following. You got what is called a 66 block. So 66 blocks were traditionally used in corporate environments for cross-connecting phone system cabling. As 10 megabit per second LANs grew in popularity in the late 80s and early 90s, these termination blocks were used to cross-connect Cat3 UTP cabling. The electrical characteristics are specifically the crosstalk of a 66 block. However, it does not support higher speed LAN technologies such as 100 megabit per second Ethernet networks. And then we have what is called the 110 block. So because 66 blocks are subject to a lot of crosstalk or interference between different pairs of wires for higher speed LAN connections, 110 blocks are often used to terminate cables such as Cat5e cable that is used for higher speed local area network connections. And there are two other cross-connect blocks that you need to be familiar with. First one is called Crone or Crone LSA Plus. So Crone, this is a proprietary European alternative to the 110 block and is used not only in data environments, but it's also used in television broadcasting. And then you have the BICS or the Building Industry Cross Connect. So a BICS, it terminates 25 pairs or 50 wires. The 25 pairs may be punched down to one side of a wafer that is inserted into a metal frame with the punch down side against the wall, so you only see the unused side. And then the centralized distribution frame, which connects out to the multiple IDFs, this is called the main distribution frame or the MDF. All right, and finally, let's talk about media converters. So due to the wide variety of copper and fiber cabling used by different network devices, you might need one or more media converters. And examples of media converters include the following. You got MMF to Ethernet, SMF to Ethernet, fiber to coaxial, and SMF to MMF. In this video, you are going to learn about IP version 4 addressing. All right, so let's talk about IP4 version addressing. So although IP version 6 is increasingly being adopted in corporate networks, IP version 4 is by far the most popular layer 3 addressing scheme in today's networks. So for brevity in this video, the term IP version 4 address is going to be used interchangeably with the more generic term IP address. Now, devices on an IP version 4 network, they use unique IP addresses to communicate with one another. Metaphorically, you can relate this to sending a letter through the postal service. You place a destination address on an envelope containing the letter, and in the upper left corner of the envelope, you place the return address. Similarly, when an IP version 4 network device sends data on a network, it places both a destination IP address and a source IP address in the packet's IP version 4 header. All right, let's talk about the IP version 4 address structure. So an IP version 4 address is a 32-bit address. However, rather than writing out each individual bit value, you can write the address in what is called dotted decimal notation. So consider the IP address of 192.168.1.45. Notice that this IP address is divided into 4 separate numbers that are separated by periods. Each number represents 1/4 of the IP address. Specifically, each number represents an 8-bit portion of the 32 bits in the address. Because each of these 4 divisions of an IP address represents 8 bits, these divisions are called octets. So for example, this picture that you're looking at right here, it shows the binary representation of the 192.168.1.45 IP address. All right, next let's talk about a public IP address. So a public IP address, also known as an external IP address, this is assigned to every device that connects to the internet, and each IP address is unique. This addressing scheme makes it possible for the devices to find each other online and exchange information. A user has no control over the public IP address that is assigned to the device, and the public IP address is assigned to the device by the ISP as soon as the device is connected to the internet. Also, a public IP address can be static, dynamic, or even shared. All right, next we have the private IP address. So in IP networking, a private network, this is a computer network that uses private IP address space. These addresses are commonly used for local area networks and residential, office, and enterprise environments to allow for devices to communicate with each other on the same network. Private network addresses are not allocated to any specific organization, and anyone may use these addresses without approval from regional or local internet registries. Also, an IP address is considered private if the IP number falls within one of the IP address ranges that are reserved for private networks, such as a local area network. The IANA, or the Internet Assigned Numbers Authority, they have reserved the following 3 blocks of the IP address space for private networks or local networks. And in order to communicate with the outside world, these IP addresses must be translated to a public IP address using NAT, or Network Address Translation. And as you can see, the first address space goes from 10.0.0.0 through 10.255.255.255, and it makes up a total of 16,777,216 IP addresses. Then the next one starts with 172.16. It goes all the way through 172.31, and it has just over 1 million IP addresses. And then you got the 192.168 block, and this has approximately 65,000 IP addresses. All right, next let's talk about types of IP addresses. So for the real world and for the Network Plus exam, you need to be familiar with the following categories of IP version 4 addresses, and even more, which we'll talk about later on in this class. The ones that you're going to learn about right now are called unicast, broadcast, and multicast. And the following is going to describe each of these addresses in more detail. So the first one is unicast. So most network traffic is unicast in nature, meaning that the traffic travels from a single source device to a single destination device. So you could think of this as you're on your phone looking at Amazon.com, and Amazon.com is sending you a bunch of ones and zeros back to your phone, and your phone only. Next, we have broadcast. So in computer networking, broadcasting refers to transmitting a packet that will be received by every device on the network. In practice, the scope of the broadcast is limited to a broadcast domain. Broadcasting is the most general communication method and is also the most intensive in the sense that many messages may be required and many network devices are also involved. Broadcasting may be performed as a quote-unquote all scatter, in which each sender performs its own scatter, in which the messages are distinct for each receiver, or all broadcasts in which they are the same. So basically think of this as some website that is sending ones and zeros to every single device in your house, such as your phone, your laptop, your computer, or whatever other device is capable of receiving those signals. That's kind of what broadcast is doing. It just broadcasts the signal out to everybody. All right. And then finally, we have multicast. So multicast technology, this offers an efficient mechanism for a single host to send traffic to multiple specific destinations. So for example, say that a network has 100 users and 20 of those users want to receive a video stream from a video server. With a unicast solution, the video server would have to send 20 individual streams, or one for each recipient. And such a solution could consume a significant amount of network bandwidth and put a heavy processor burden on the video server. With a broadcast solution, the video server would only have to send the video stream once. However, it would be received by every device on the local subnet, even devices not wanting to receive the video stream. Even though a lot of those devices do not want to receive the video stream, they still must pause what they are doing and take time to check each of those unwanted packets. And that leads us to multicast, which offers a compromise. And this allows the video server to send the video stream only once, and sending the video stream only to devices on the network that want to receive the stream. And multicast is possible to the use of what is called a Class D address. And a Class D address, this represents the address of a multicast group. The video server could send a single copy of each video stream packet destined for a device. And based on the device requests, switches and routers could then dynamically determine out which ports the video stream should be forwarded to. In this video, I'm going to show you guys how to convert decimal numbers into binary, binary into hexadecimal, hex into binary, and binary back into decimal so that you can look like a superstar out on these streets with these conversions. So let's get into it. First thing we need to understand, ladies and gentlemen, is what is decimal, what is hexadecimal, and what is binary. So all of you out there, you all know what decimal is. This is the base 10 numbering system that you guys learn how to count your fingers and toes when you were in preschool. And that is numbers 0 through 9. 0 through 9 or 1 through 10, but we refer to it as 0 through 9 over here in the IT world. Next, we have hexadecimal. Hexadecimal represents base 16 values, base 16 numbers, right? And how this works is you have the same numbers 0 through 9 over here, but then when you get to the number 10, instead of it becoming the number 10, it is represented by the letter A all the way through the letter F, which stands for 15. So A through F, A, B, C, D, E, F, all of those letters represents numbers 10, 11, 12, 13, 14, and 15, okay? And then we have binary. This is powers of 2 or base 2 mathematics. And this represents zeros and ones, which stand for off and on. So in binary, what happens is we're going to take what is called an IP version 4 address. You guys have seen these before. It'll be some number here, dot some number here, dot some number there, dot some number there. That represents an IP address. And if you guys aren't familiar with IP addresses, go check out my IT Fundamentals course where I explain all of this to you. But a lot of you guys are familiar with IP addresses. You're just familiar with the names that are associated with them. Like if you type in youtube.com, or youtube.com is associated with an actual IP address. So think of the IP address as the house number to the house that you currently live in. Okay. Now, how binary relates to the IP version 4 that we're looking at here, we're only going to be focusing on what is called the 4th octet. This is octet 1, octet 2, octet 3, and octet 4. We're going to be focusing on the 4th octet so that we can try to figure out which bits to turn on and off, you know, zeros and ones. And so first things first, we have to lay out the binary numbering system. So it goes like this. It goes from number 1, 2, 4, 8, 16, 32, 64, 128. This red decimal point represents the break in the 4th octet. Then we're going on to the 3rd octet. But as you can see, all of these values double themselves by a power of 2, and it just keeps going on and on and on. So we got to get this down packed first, because this is what is going to help us go through our conversion process, right? And how the actual conversion process works is if you want to go from decimal to hexadecimal, you're going to have to use binary as the middleman. If you want to go from hex back to decimal, you're going to have to use binary as the middleman. So I'm going to show you guys how to do this. It's really simple. Don't sweat it. You'll be doing this like a boss by the time I'm done with this video. All right, so let's do our first example of how to convert decimal to binary. So in this example, we're going to convert the decimal number 175 into its binary equivalent. So the first thing that you're going to want to do is you're going to want to lay out all of your powers of 2s like I just showed you, from the 4th octet, numbers 1, 2, 4, 8, 16, 32, 64, and 128. And now we're going to turn on the values that actually add up to the number 175. Because if you recall, I just stated in binary, we work off of ones and zeros. Ones represents a value or a bit is turned on, and 0 represents a value or a bit is turned off. So in order for us to get 175, we have to turn on the number 128, the number 32, the number 8, 4, 2, and 1. You add all those numbers up together, you get 175. Real simple stuff, right? I know. All right, let's take this problem one step further. So we're going to go ahead and convert the decimal number 175 into its hexadecimal equivalent. Now, if you recall, I stated that in order to go from decimal to hexadecimal, or from hex back to decimal, you have to go through binary as the middle guy. All right, so now let me go ahead and explain what all this madness on your screen means, okay? So we have the decimal number 175, and we've already figured out how to solve for its binary equivalent, and that will come out to be 1010111. Now, remember, I stated that this was basically the 4th octet, right? The last octet of an IP address. I have this blue line right here going down the middle because when we go through the process of converting it into hexadecimal, we're only going to be focusing on what is called a nibble, an N-I-B-B-L-E. This is basically half an octet that we're going to use for our conversions, okay? So we got our binary 1010111. We're going to move it down here. Now we're going to break this down into 2 groups of 4s or 2 groups of nibbles, right? We're just going to draw a line straight down the middle just like I did. Being that we're only operating off of half of an octet, we're only going to basically apply half of the powers of 2 conversion. So we have 1111. So basically the values 1, 2, 4, and 8 have all been turned on. And then we're going to apply the same 1, 2, 4, and 8 over here. So as you can see, the value 8 and the value 2 have been turned on. And now we're going to go ahead and just start adding numbers up. 8 plus 2 is what? 10. 8 plus 4 plus 2 plus 1 equals what? 15. So now we have 10 and we have 15. That is what these nibbles break down into. So now we have to go ahead and figure out what do these values mean as it relates to hexadecimal. So if you look over here, remember I told you hexadecimal numbers, they represent numbers 0 through 9 and letters A through F, where A through F represent numbers 10 through 15. So now that we have the number 10 over here, well, A equals 10. F equals 15. So the decimal number 175 equals the hexadecimal value AF. Now, if you want to go ahead and check your work real quick to verify that you know what you're doing, you can just go to Google and type in decimal to hexadecimal converter, and you just type in the number 175 and it will show you the conversions right here. Here's your hexadecimal value and here is your binary value that I was showing you earlier on this screen. All right, so now let me give you an example of how to go from hexadecimal all the way back to decimal. So in this example, we have the hexadecimal value of B2. We're trying to figure out what its decimal equivalent is. So what we're going to do with the B2, we're going to go ahead and convert it to binary, because remember, to go from hex to decimal, you got to go through binary. From decimal to hex, you got to go through binary. So we're going to go ahead and apply our middleman. So what we're going to do, we're going to take our B2 and we're going to divide it into its own little sections here of B and 2. And then we're going to come back over here and figure out what its equivalent is in its nibble notation. So remember, we're working with the number 2. So we got to come down here and do our 1, 2, 4s, and 8s that represent our nibbles so that we can figure out which value is actually turned on. So out of 8, 4, 2, and 1, the only value that is turned on is the value number 2. So that'll be 0, 0, 1, 0. Then we come over here to the letter B. If you look back up here, remember in hexadecimal notation is expressed in numbers 0 through 9 and A through F, where the letter A equals 10 and the letter F equals 15. So B would be the number 11. So 11 equals B. We go here and look at our nibble, 1, 2, 4, and 8. We add the values that are turned on. So it will be 8, 2, and 1. 8 plus 2 plus 1 equals 11. And then we just put them all together. And this is what our binary equivalent for B2 is going to look like. It's going to be 1, 0, 1, 1, 0, 0, 1, 0. Now we're going to take this and we're going to figure out what our decimal equivalent is. So now we're going to come back to the 4th octet, the entire thing. 1, 2, 4, 8, 16, 32, 64, 128. We're going to take our binary equivalent and figure out which of these values are turned on. As you can see, values 128, 32, 64, and 2 are turned on. We're going to come up here and just add those numbers together. 128 plus 32 plus 16 plus 2, and that will get you 178. So the decimal equivalent of the hexadecimal value B2 is the number 178. And like always, if you're unsure, you can just run over to Google and do a check to verify that you added your numbers up correctly. So as you can see, I put B2 up into the converter. We got our decimal equivalent of 178, and then we have our binary equivalent of 10110010. And for my last trick, ladies and gentlemen, I'm going to show you how to convert a hexadecimal number that has 3 values back into its decimal equivalent. So if we look at our screen here, we have the hexadecimal values A, B, and C. Okay, so first thing we got to do, we got to convert A, B, and C back into its binary equivalent, because binary is the middleman. And also remember, hexadecimal values are the numbers 0 through 9 and the letters A through F, where A equals 10 and F equals 15. 15. So we go through, we take ABC and we break it down into its individual groups. And then we figure out, what do these values represent? Well, A equals 10, B equals 11, and 12 equals C. We go ahead and apply our little nibbles that I was talking about here with 8421, 8421, 8421. We figure out which values are turned on that add up to this number right here. So 8 plus 4 equals 12, 8 plus 2 plus 1 equals 11, 8 plus 2 equals 10. So this is our binary equivalent of ABC, 101010111100. Now we're going to move on down to converting this into its decimal equivalent. So now we're going to apply the entire octet again. So remember, 1, 2, 4, 8, 16, 32, 64, 128. Now if you look right here, I have a little red dot right here that indicates the separation between the fourth octet and the third octet. So this value ABC is going to drag us out into the third octet. So what we're going to do, we're still going to apply the powers of 2. So 128 plus 128 is going to get us 256. 256 plus 256 is going to get us 512, then 1024, 2048, and so on and so forth. So now we're going to take our binary value and just figure out which of these numbers are turned on. As you can see, 2048's on, 512, 128, 32, 16, 8, and 4. Come up here, add up all these numbers together. 2048 plus 512 plus 128 plus 32 plus 16 plus 8 plus 4. That's going to get you the decimal equivalent of 2,748. So the hexadecimal value ABC equals 2748. And like always, you could just run over to Google and check your work if you want. So as you can see, hexadecimal number ABC, decimal value 2748, binary value down below. In this video, you're going to learn about classful IPs and classless subnetting. All right, let's talk about classful IP addresses. So classful IP addressing, this is a method that divides the IP address space for IP version 4 into 5 address classes based on the leading 4 address bits. So you got class A, B, and C. They provide unicast addresses for networks of 3 different network sizes. Then you got class D. This is for multicast networking. And the class E address range, this is for future or experimental purposes. And an IP address, this is divided into 2 fields. You got a network prefix, which is your network ID, and then you have your host ID. And what separates the network ID from the host ID depends on whether the address is a class A, B, or C address. And here's what class A, B, C, D, and E look like broken down. So class A, it ranges from 1 to 126, and it supports 16 million hosts on 127 networks. You got class B, it starts off with a number between 128 and 191, and it supports 65,000 hosts on each of 16,000 networks. Then you got class C, that starts off with the IP address of 192 all the way to 223, and this supports 254 hosts on each of 2 million networks. Then you got class D, 224 to 239, and that is reserved for multicast groups. And then you got class E, 240 to 255, and that is reserved for future use or research and development purposes. So let's talk about subnetting. So subnetting, this is the strategy used to partition a single physical network into more than one smaller logical subnetwork or a subnet. Subnetting allows for an organization to subdivide a large network into smaller, more efficient subnetworks to help minimize traffic and increase network speeds. An IP address includes a network segment and a host segment, and subnets are designed by accepting bits from the IP address's host part and using these bits to assign a number of small subnetworks inside the original network. And subnetting allows an organization to add subnetworks without the need to acquire a new network number from an internet service provider. And here are some of the benefits of subnetting. So it reduces the network traffic by reducing the volume of broadcasts. It helps to surpass the constraints in the local area network. So for example, the maximum number of permitted hosts, and it enables users to access a work network from their homes. So there is no need to open the complete network. All right, so let's talk about a subnet mask. So a subnet mask, this is a 32-bit number created by setting network bits to all ones and setting host bits to all zeros. The subnet mask splits the IP addresses into the network and host addresses, thereby defining which part of the IP address belongs to the network and which part belongs to the host. All right, so let's take a look at the subnet mask classes for A, B, C, D, and E. So as you can see here, you got class A, that's 255.0.0.0. The number 255 represents the 8 bits that identifies the network portion of an IP address. And the 3 zeros, which represents 24 bits, they represent the portion that will be assigned to identifying the host. When it comes to class B, the subnet mask will be 255.255.0.0. The first 16 bits are the 255.255. They identify the network portion of an IP address, and the 0.0 or the last 16 bits, they identify the host IPs that could be assigned to devices. And then you got class C, 255.255.255.0. And once again, the first 3 octets are 255.255.255, or those 24 bits. They identify the host, and the remaining octet, which is identified by the 0, those 8 bits identify the IP addresses that can be assigned to devices on that network. So now let's go ahead and put all of this wonderful knowledge together. So once again, class A, if you see an IP address that starts with the number 1 going all the way to the number 126, that is a class A IP address, and they support 16 million hosts, and each of them has 127 networks, and its subnet mask is going to be 255.0.0.0, where the first 8 bits identify the network portion of that IP address, and the last 24 bits, which are all those zeros, they identify the host IDs that can be assigned to devices on that network. Then you got class B. So if you see an IP address that starts with the number 128 all the way through the number 191, it can support 65,000 hosts on each of 16,000 networks. Its subnet mask is going to be 255.255.0.0. The first 16 bits represent the network portion, and the last 16 bits are the 0.0. They represent the host IDs. And then we got class C. So once again, if you see an IP address that starts with the number 192 all the way up to the number 223, that is a class C IP address, and it can support 254 hosts on each of 2 million networks, and it has a subnet mask of 255.255.255.0, with the first 24 bits identifying the network portion of that IP address, and the last octet or the last 8 bits, they identify the host ID for devices that could be assigned to that network. All right, next let's talk about classless subnetting. So earlier in the video, I talked about class-full subnetting, where I explained how to subdivide or subnet an IPv4 address, which is the strategy that is used to subdivide a large network into smaller, more efficient subnetworks to help minimize traffic and increase network speeds. The problem with class-full subnetting is that you are restricted as to how far you can subdivide a network, because class-full subnetting focuses purely on the overall class an IP address falls up under, which causes an IP address to potentially have millions of available subdivided IP addresses to utilize, which is very inefficient for most networks. Now I'm going to show you how to apply a concept called classless subnetting, which allows for you to more narrowly subdivide a network into more manageable IP addresses that can be used for a sub network. All right, so the first thing we have to talk about is this concept called CIDR notation. And CIDR, that stands for classless interdomain routing. In CIDR, this is also known as prefix notation or slash notation. And this is a method for allocating IP addresses and for IP routing. CIDR notation was introduced in 1993 to replace the previous classful network addressing architecture on the internet. And its goal was to slow the growth of routing tables on routers across the network and to help slow the rapid exhaustion of IPv4 addresses. All right, so if you guys have been in my class for a while, you have probably seen this chart once upon a time for me teaching you how to convert from decimal to binary to hexadecimal. So this is our standard binary to decimal conversion chart, where we got binary represented on the left and its decimal equivalent represented on the right. And this is going to help us out when it comes to classless subnetting, which we're going to look at on the next slide. All right, so here's our first example of classless subnetting dealing with a class A IP address. So our IP address is 101.0.0.1. And just like I told you earlier, our subnet mask for this particular IP address will be 255.0.0.0. And as you can see, it's binary equivalent. All the ones in the first octet are turned on to represent 255. And then the last 24 bits are all turned off, which represent 0. Inside our notation, we would just put a /8 to identify that the first 8 bits have been turned on. That's how simple this is, ladies and gentlemen. All right, here's example 2 of slash notation. We have a class B address, which is identified by 129.0.0.1. And like I told you earlier, our subnet mask for class B will be 255.255.0.0, where the first 16 bits are turned on to identify the network portion of the IP address, and the last 16 bits are turned off, which identify the host bits of that IP address. So when we write this out inside our notation, we could just simply write the IP address as 129.0.0.1/16. And the /16 tells us that this is a class B address, and the first 16 bits have been turned on to identify the network portion of this particular IP address. And obviously the last 16 bits are turned off, which identify the host. And next we have a class C address, 193.0.0.1, subnet mask 255.255.255.0. The first 24 bits are turned on, which identify the network portion of that IP address, and the last 8 bits are turned off. And its CIDR notation is going to be a /24. So you would simply write the IP address out as 193.0.0.1/24. And once again, that /24 lets you know that the first 24 bits of that particular IP address represents the network ID, and the last octet represents the host bits of devices that will be assigned to that network. All right, so now let's take a look at some examples that show you different numbers that don't have to deal with 8, 16, and 24. So we got this IP address of 198.0.0.1/14. So basically, when you look at this IP address with the /14, that tells you that the subnet mask is going to be 255.252.0.0. And basically what that means is the first 14 bits have been turned on to indicate that we're going to have 255 and .252 that identify the network portion of this IP address. And the last 18 bits are turned off, which identify the host bits that could be assigned to devices on this IP address. And remember, an IP version 4 address has a maximum of 32 bits. So you add 14 plus 18, that gets you a grand total of 32 bits. And this chart comes into play with helping you quickly figure out what the decimal equivalent is going to be. So you look at, we got 6 ones turned on right here and 2 zeros. You come down to your chart, 6 ones and 2 zeros, that gets you 252. That's how we ended up with a 252 right here, of the first 14 bits being turned on, which will give us 255.252 and obviously .0.0. Let's look at another example. We got IP address 201.1.0.0 with a /21. Its subnet mask is going to be 255.255.248.0, where the first 21 bits are turned on and the last 11 bits are turned off. All right, so let's look at an example where we lead off with the CIDR notation of /27. So we got /27 that tells us the first 27 bits are going to be turned on. So we got 8 bits here, 8 bits here, 8 bits here, and 3 bits here. Add that all up, that's 27 bits. That leaves us 5 bits that are turned off, which identify the host bits. And obviously all these bits turned on right here is 255, 255.255. And then we come down to our chart, find the first 3 ones that are turned on with 5 zeros following after it, and that lets us know that it is a 224. So our subnet mask for this particular / notation will be 255.255.255.224. So let's take a look at one more example with a CIDR notation of a /19. So we have a subnet mask of 255.255.224.0, where the first 19 bits are turned on and the last 13 bits are turned off, which identify the host bits. All right, next let's talk about IP version 6 CIDR notation. So an IP version 6 address is usually distributed by the Internet Assigned Numbers Authority, or the IANA. The IANA is responsible for providing address blocks to the regional internet registries, who then assign smaller blocks of IP version 6 addresses out to your ISPs or your internet service providers. From there, the ISP will then assign you, the end user, with an IP version 6 address that has a /48 subnet, which you can then further subnet down as needed. And as a side note, you want to remember that an IP version 6 address is 128 bits long, whereas consisting of 8 blocks of 16 bits. And remember that the values are hexadecimal numbers and not decimal numbers. All right, so let's look at an example of an IP version 6 address and how it is broken down. So we got IP version 6 address 2500:AAAA:3333:001: a whole bunch of zeros followed by a 1. The global routing prefixes identify the first 48 bits. So these are the first 48 bits right here. Just remember 16 times 3, they get you 48. So remember, the Internet Assigned Numbers Authority, they assign this first block right here, 2500. Your regional internet registries, they assign the second block, and your ISP, who you pay your internet bill to, they assign the third block right here. And like I say, all three of these, they make up the global routing prefixes, or the first 48 bits of an IP version 6 address. All right, so working with this same IP address, when we get down to the fourth block, this is locally assigned by the end user. And this is used for creating your network ID. So just like with IP version 4, we use subnet mask to identify which portion of the IP address represents the network ID. Well, in an IP version 6 address, this fourth block identifies the network ID of the network your IP addresses are going to reside on. And it could be a 1, 2, 3, 4, etc. And within this, you got 16 bits, and that'll give you a grand total of 65,536 total subnets you could theoretically create just off of this one block alone. All right, then finally we get down to our last 4 blocks, and these are the host IDs. So just like with the IP version 4 address, you had 255.255.255.0 or 255.0.0.0, whatever combination, right, for A, B, and C. So just like with a class A IP address where I said the subnet mask was 255.0.0.0, and I told you that the subnet mask represents the first octet, or the first 8 bits that are turned on, and the remaining 3 octets represents the network IDs that can be assigned to potential devices on that network. Well, in an IP version 6 address, this is what this represents. These last 4 blocks represents the host IDs, or IP addresses that can be assigned to various devices within a network. And under this system right here, this would get you approximately 18 million trillion hosts per subnet. So remember, we go back to the last slide when we were dealing with the actual network ID, or identifying the subnet. We can get a grand total of 65,536 total subnets. Now, out of those 65,536 total subnets, each of those subnets could potentially host as many as 18 million trillion hosts per subnet. So in case you're wondering why this is, if you go back and check out my IT fundamentals class, I explained in that series that IP version 4 only has a maximum of like 4 billion IP addresses, and we've pretty much exhausted all of them. So in order for us to continue to enjoy the internet, where we can surf our iPhones and watch YouTube videos like TechG and order random stuff off Amazon and slide into people's DMs and do all this crazy stuff we like to do, well, we need more IP addresses. And so working with an IP version 6 address where you can have 18 million trillion hosts per subnet, and then you can have a maximum of 65,000 subnets. Well, in theory, we should never, ever run out of IP addresses for at least a couple generations or so. And so continuing on with this slideshow here. So when we want to write this out in CIDR notation, we would just simply put this as a /64. So basically, when you're dealing with IP version 6 addresses, all of its CIDR notations are going to be expressed in a /64. 64. And the /64, this represents the subnet mask options of this IP version 6 address. So we got 4 blocks of zeros right here, which make up 64 bits, or 4 blocks times 16. But anyways, the whole point is IP version 6 CIDR notation. If you do the shorthand version, which I taught you guys in the A+ class of how to shorten out an IP version 6 address, but its CIDR notation is always going to be /64. And here is a graphical representation where in this picture we have 1, 2, 3, 4, 5 different networks being depicted in here, all expressed by IP version 6, and all of them have the /64 CIDR notation. In this video, we're going to talk about VLSM subnetting, or variable length subnet mask. Basically, we're going to talk about how to take an IP address and subdivide it down into smaller IPs to make a network more manageable. All right, guys, so we have been learning subnetting for the past 2 or 3 videos in this Networking Plus certification class that I'm putting together. And some of you guys are probably lost and confused and wondering why we're doing this. Well, now I'm going to show you why we are doing this, to show you that these numbers actually mean something other than weird looking numbers written in a chart. So I'm going to show you guys a concept called a router on a stick. This is something that you will learn or apply if you go for your CCNA in the future, or whatever the case may be. So the first thing you have is a router. It is represented by this circle with these lines going down the middle. It is connected to a switch, which is represented by this square with arrows going in opposite directions. And then hanging off this switch, you might have a computer over here, a computer over here, a computer over here, and a computer over here. Now, in this example, all these computers can be on the same VLAN, or we can separate them to where these guys will be representing VLAN 2, these guys will be representing VLAN 3, and the switch by default is going to represent VLAN 1. And if you don't know what a VLAN is, it stands for Virtual Local Area Network. Basically, VLANs allow for you to logically divide a switch into separate networks. So VLAN 1, 2, and 3, these would all be 3 separate networks. And in order for a computer over here in VLAN 2 to communicate with a computer over here in VLAN 3, they would have to pass their traffic through the router, come back down, and then they could receive the message. If they were all in the same VLAN, VLAN 1, if this computer wanted to communicate with this computer over here, they would only have to pass traffic through the switch to get to the other device. But being that they have been logically separated onto one physical switch, they have to use a router. Why? Because routers connect networks to networks. So if you're a little lost and confused about that, I advise you to go back and check out some of my earlier videos that explains this concept. So now what we're going to do, we're going to talk about actually subnetting an IP address. So just imagine that this router, this switch, and these computers are all in the TechG Corporation right now. And within the TechG Corporation, we have paid for some internet service from Comcast or whoever else is out there. And they said, hey, this right here is your IP address that you are going to use for your network. So basically this IP address is essentially the public IP address for this router that is communicating with the devices owned by Comcast, so that I can go out there and live my wildest fantasies surfing the internet. Okay. Now, within this network, I want to go ahead and subdivide this IP address so that I can allocate IPs for this device, this device, this device, this device, and any other device that I want. Now, within this example of the TechG Corporation, I want to have sections. Now, currently TechG doesn't make a lot of money, so all I can afford is a router and a switch, right? But I do have enough money to have a couple different departments. So let's just say that this is my marketing department over here, and this is my HR department over here, and we're all connected to the same switch, and we'll call this switch SW. VLAN. This is our router in case you need to see it. Now, I want the people in HR to only be able to access whatever devices are within the HR department, and I want the marketing people to only be able to access devices in the marketing department. So that's why these guys are in VLAN 2, these guys are in VLAN 3, but I also want them both to be able to communicate with the switch VLAN 1 as well. Like I stated earlier, in order for that to happen, you need to go through the router so you can pass traffic back and forth. Now, this IP address right here, 192.16.1.1, this is a Class C address. And if you guys recall, a Class C address is basically a classful IP address, and it ranges from 192 to 223. All right. So basically any IP address between 192.0.1.1 all the way through 223.255.255.254. That is what a Class C IP address is. So now, that is what the ISP has given me. They said, hey, this is your quote unquote street address for your router over here. Now, we all know with routers, if you've been paying attention to my class, you got a public IP address and you got your private IP address. And within the router, they perform this thing called NAT, Network Address Translation, so that basically you can quote unquote disguise all the IP addresses within your network. So when external networks are communicating with your network, the only IP address they see is this one right here. But now within this network, I want to go ahead and subdivide or subnet this network so I can allocate IP addresses to all these random devices over here in their particular VLANs. And the reason I want to do this is because it is going to make it much more easier and manageable to deal with a smaller collection of IP addresses. So we're going to go ahead and subdivide that. So before we get started, what we need to do is this. I need to first determine how many addresses do I actually need. So let's go to our marketing department over here. Let's just say our marketing department, I need 100 IP addresses for marketing. And then for my HR department, I need 50 IP addresses. And then for my switch, I need 6 addresses. And then for my router, I need 2 addresses. And this is my starting IP address right here, which once again is a /24 CIDR notation address or Class C address, right? So now we're going to go ahead and begin the construction of what is called a VLSM chart, or a variable length subnet mask chart. This is what's going to allow for us to get back over here and figure out what IP addresses we can assign to various devices within the network. So like I said earlier, we're going to need 100 IPs for the marketing department. We're going to need 50 IPs for the HR department. Our switch is going to need 6 IPs for whatever reason. And our router is going to need 2 addresses in order to make this thing work. And once again, our starting IP address is 192.16.1.1. That is our starting IP address over here. So let's go ahead and start constructing this chart. So first thing we're going to do, we're going to put what is the name column. Then we're going to have the number of hosts that we're going to need. We're going to need to know our incremental value, also known as our positional value. And I'll explain all this as we go along. We're going to need to know our network ID. We're going to need to know our gateway address. We're going to need to know our IP range. And we're going to need to know our broadcast IP address. And we're also going to need to know our custom subnet mask. And in some cases, this is more particular to CCNA, you may need to know this thing called your wildcard mask. But we're not going to worry about the wildcard mask at this present moment. So this is the chart that we are about to build, ladies and gentlemen. Now, before we go ahead and start building this chart, let me go ahead and show you a quick little way on how to go about figuring out how many hosts you may need and what the subnet mask may be and all that wonderful stuff real quick. All right, so here's a little handy dandy chart that you can put together real quick when you're out there taking your Network Plus exam, which is going to help you figure out what the hosts are and the appropriate subnet mask that goes with the host. And all you're going to be doing is using your power of twos chart. So you're going to put 2 to the 0, 2 to the first, 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, 2 to the 6th, 2 to the 7th. You can drag this thing out, 2 to the 8th, 2 to the 9th, so on and so forth. But this right here represents your 4th octet. So from there, you can calculate how many hosts you're going to need. So 2 to the 0, well, that equals 1. 2 to the 1st, 2, 4, 8, 16, 32, 64, 128. And then from there, we can go ahead and figure out what our subnet mask is going to be using slash notation. So if you got one host right here, basically that means you're going to have a slash 32 for your subnet mask. Over here, you're going to have a slash 31, slash 30, slash 29, slash 28, 27, 26, and slash 25. That's what your subnet mask is going to be. Now, if you want to know what this actually looks like in binary notation, basically this will look like this. You would just have the first 32 bits turned on, if you recall from my last video. So you have 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. So that's 24, 25, 26, 27, 28, 29, 30, 31, 32. What is that? 1, 2, 3, 4, 5, 6, 7, 8. All right, so all of them are turned on. I don't know why I didn't just put that together real quick. Slash 31, same deal. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, and a 0. So in the slash 31, basically you have 31 bits turned on. 1 bit is reserved for the actual host. Over here, you're going to need at least 2 IP addresses that are going to be used for assigning IPs to devices. And I'll explain all that as we go along. But basically, instead of you sitting around here drawing out all of your binary, you can just go ahead and remember this slash notation in conjunction with the host, and that'll help you out and expedite this process a whole lot faster. So now let's get back to our chart over here. So like I stated, this is the IP address that has been assigned to us, 192.16.1.1/24. We need 100 devices that can have IP addresses for our marketing department. We need 50 devices for our HR department that can have IPs. Our switch needs 6 IPs for some weird reason, and our router is going to need 2 IP addresses. Now, when we begin this process, we need to start figuring out how to subdivide this network or subnet this network for the one that has the highest requirements, which will be 100. So we come over here, we put marketing, and we need 100 devices over here, or 100 IPs, I should say. Now we need to figure out how many hosts do we need. So what we're going to do with each of these numbers, 100, 50, and 6, we're going to add the number 3 to all of these numbers. So 100 plus 3 is going to give me 103. 50 plus 3 is going to give me 53, and 6 plus 3 is going to give me 9. And the reason why we're adding 3 is because the 100, that actually represents the actual devices that are going to be assigned IP addresses within this little network that I set up over here. Now we're adding 3 because we also have to take into account for the IP address for the network ID, the gateway IP address, and the broadcast IP address. The network ID, this is basically the identification for this network right here. It's essentially almost the same thing as the main IP address that was assigned to us from the ISP, but now we are acting like our own quote unquote ISP, and we need to first and foremost identify the network that these devices are going to reside on. So that's how we get to the network ID. Then we also have to identify the gateway IP address. And the reason we're doing that, so when we're out here sending messages around, we need to tell these messages what is the gateway IP address that they need to go find in order for them to get out onto the wild, wild internet or communicate with somebody else in another network. And typically your gateway IP address, at least within this setup, is going to be the private IP address associated with this router for this overall network. But within this little tiny network, we're creating a separate gateway IP address, which will be programmed into this router, but we're not going to go too far into that for this video because that's more of a CCNA related topic. But basically, we need that gateway IP address. So when I start pressing 1s and 0s and sending messages, these messages know, hey, I need to go find a certain gateway IP address so I can escape my network and go communicate with somebody over here or go talk to the router so I can get out to the greater internet. And then we also need to identify what is called the broadcast IP address. The broadcast IP address is essentially the last IP address before you begin the next network. And then everything in between the gateway and the broadcast is your IP range. This is where you will pull IP addresses from to assign to these 100 devices over here. And then the custom subnet mask, this basically identifies the portion of the network that all of this stuff is going to reside on. So we'll look at my previous videos where we're talking about this and I explain that in greater detail. And the wildcard mask, we're really not going to focus on this for this particular lesson. This is something that you'll need to know when you are going for your CCNA. And I'm just trying to keep this as simple as possible so that we can make sense of why we're doing this in the first place. So like I stated, we got 100 devices that need IP addresses for our marketing department, 50 devices for our HR department, 6 IPs need to be assigned to the switch for whatever reason, and then the router is going to need 2. And with the router, we're going to add another 2 to it, and I'll explain that when we get down to it. So 100 plus the 3, remember the 3 came from, we need to set up an IP for the network ID, the gateway, and the broadcast. So we need a grand total of 103 IP addresses within this network. Now, what we're going to do next, we're going to figure out what is the positional value or the incremental value for this particular network that we are about to construct. And we come back over to this chart over here to figure that out. So when I was telling you about the hosts, I put 1, 2, 4, 8, 16, 32, 64. Then I drew a line to indicate the break between octet number 4 and octet number 3. And if you were to keep dragging this power twos thing out, you would start this positional spot all over again and just keep going down the line. But basically, these incremental values or these positional values are essentially going to tell me what spot in the octet is going to fulfill my actual host requirements so that I can have enough IP addresses to allocate to my devices. All right. So we come back over here. As I stated, I need 103 IP addresses in total for this particular network. We come back over here to our positional values, incremental values, whatever you want to call them. And we're going to figure out what number does 103 go into without going over. So does 103, does it go into 1? No. 2, no. What does it actually go into? 103 can comfortably fit inside the number 128 without going over. Now, being that we need 103 hosts, that means we're going to be just fitting comfortably inside of the 4th octet, dealing with our positional value of 128. So we're going to come down to our incremental block and we're going to put a 0.128 to indicate that we are operating out of the 4th octet because that is what 103 comfortably fits inside of, ladies and gentlemen. Now we need to figure out what is our network ID. So remember, this is our starting IP address, 192.16.1.1. With this particular network, we're operating out of the 4th octet. So that means we're just going to zero out the last octet. So our network ID for this network is going to be 192.16.1.0. That is the very first IP address for this network, which is part of the extra 3 numbers that I added here. Our gateway address is just going to be one IP address above this one. So that's going to be 192.116.1.1. And then our IP range is going to be one IP greater than the gateway. So it'll be 192.16.1.2. I'm just going to go ahead and put a .2, and we're going to stop right there. Now we're going to go ahead and start trying to figure out our requirements for the HR department that requires 50 hosts. So we come back down here, we identify HR. We said we needed 50, but we're going to add 3 to get 53 because remember, we got to create an IP address for the network ID, the gateway, and the broadcast. And then we're going to go ahead and figure out our incremental value for this particular network. So we come back over here. We said we need 53 IPs. What number does 53 go into without going over? We see it goes into the number 64. And being that we're working out of the 4th octet, our incremental value is going to be 0.64. And now we're going to go ahead and we're going to figure out the network ID. So this is what we're going to do to figure out the network ID for the HR department. We're going to take the network ID of the marketing department and add it to the incremental incremental value. So we're going to take 192.16.1.0 and add it to 0.128. Essentially, we're just going to be adding the fourth octet number. So 128 plus 0 is going to give us our starting network ID for HR department. It's going to be 192.16.1.128. That is our network ID for the HR department. Basically, this is the starting point for this network right here. And then the same thing applies with the gateway. It's going to be 192.16.1.129, just one IP address greater than the network ID. And then our IP range is going to start off with a .130. Now, we can use this number to go ahead and figure out what is the broadcast number for the marketing department, because like I told you guys, the broadcast IP address is the last IP address before you start the next network. So all we're going to do is just subtract one IP address from the network ID of the HR department, and the broadcast IP address for the marketing department is now going to be 192.16.1.127. And now we can figure out the last IP address of the IP range where we can pull IP addresses from. And in this example, it is going to be a .126. So everything between 192.16.1.2 through 192.16.1.126, this is where we can assign IP addresses to all of the devices within the marketing department. And as you can see, this is a grand total of 124 IP addresses, I believe. That is enough IP addresses to cover our requirements of 100 devices needing IP addresses. Now we can come over here and figure out our custom subnet mask, and that is real simple. All we got to do is just go back and look at our chart up here. We stated that we needed 103 hosts. 103 went into the number 128, and that gives us a /25 IP address. And if you want to write this out in this binary equivalent, it's going to look like this. It's going to be 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, then 7 zeros. 1, 2, 3, 4, 5, 6, 7, 8. Wait, 1, 2, 3, 4, 5, 6, 7, 8. All right, I put too many zeros on it. So that's what it's going to be. When written out in this binary equivalent, your subnet mask is going to be 255.255.255.128. So that is your actual subnet mask, 255.255.255.128. We just shortened it out and put /25. I mean, you can write it out if you want. It doesn't really matter. So there's another way you can figure this out for those of you who like math. So there's an actual formula for this. So basically the custom subnet mask, it equals the number 256 minus the network host. So 256 minus the network host equals the custom subnet mask. So basically you can just do 256 minus our network host, or our incremental value of 128 or 128. So 256 minus 128 is going to give you 128 over here. Since we're working out the fourth octet, it's going to be over here. So those of you who like math, that is a quick little easy formula. Custom subnet mask, 256 minus the network host, or the incremental value, I should say. And then that's going to tell you what your actual values are going to be for your custom subnet mask. Or you can do it the binary way, or you can just remember this easy little chart that I just showed you right here. Totally up to you. So now getting back to our chart over here. So we have pretty much solved all of our requirements for the marketing network. Now we're going to solve the IP address requirements for the HR department. So once again, we got 50 devices that need IP addresses. We add 3 because we got to account for the network ID, the gateway, and the broadcast. We figured out the network ID by taking the previous network ID and adding the incremental value to give us our current network ID, which then told us what our gateway IP address is going to be, which is just one IP greater than the network ID. Then it also told us our starting IP address, that we can start dishing IP addresses out to devices, and that's going to be a 130, which is just one IP greater than the gateway. So now we got that far. So now we need to go ahead and figure out the requirements for the switch. So we got our switch over here. I said we need 6 IP addresses for whatever reason. We're going to add 3. So that means we're going to have a host requirement of 9. We're going to go ahead and figure out our incremental value. So So we come back over to this chart here. What number does 9 go into without going over? And we see it goes into the number 16 without going over. So that means we're working out of the fourth octet still. So now we got a 0.16. So now we can go ahead and figure out the network ID. So we're going to take HR's network ID, add this incremental value, and that's going to give us the network ID for the switch. So 128 plus 64 equals 192. So our network ID for the switch is going to be 192.16.1.192. That's going to be our network ID. Our gateway is going to be 1 greater than the network ID. So 192.16.1.193. That is our gateway IP address. And then our IP range is going to start with 1 IP greater than the gateway. So that's going to be .194. Now we can go ahead and use this information to solve for the broadcast for the HR department. So we go to our network ID and we just subtract 1 IP address to get us 192.16.1.191. And then from there, we're just going to subtract 1 IP address from the broadcast to get our last IP address of the IP range, which is going to be 190. So right here, we're looking at 60 IP addresses that we can assign to the HR department, even though the HR department only has a requirement of 50. Well, 60 is enough to cover all to meet this requirement right here. And then also we can go ahead and figure out our custom subnet mask based off of our incremental value of .64 or our positional value. And we come back over to our chart. 64 is going to yield us a /26 custom subnet mask. So now we solved all this for the switch. So now we need to go ahead and figure out the requirements for the router. Now with the router, we got a requirement of 2, but we're going to add an additional 2 IP addresses for the router to come up with 4 total hosts. And why are we doing that? Because we need to account for the network ID of the router and the broadcast. We do not need to account for the gateway IP address. Why? Because the router is the gateway. So we come back over to our little chart over here. We need to account for 2 IP addresses for this router, the private IP address and the public IP address. That is essentially what we are accounting for in this overall network that we are constructing over here. Remember, the router by default, at least in this scenario, this is the gateway device. Everything is trying to find this gateway device so they can go out there and communicate with the internet, or this network can communicate with this network and vice versa. So that's why we don't need to account for a gateway, and we only need to add an additional 2 hosts to this. So now we need to go to our chart and figure out what does the number 4 go into without going over. So 4, it goes into the number 4 without going over. So our incremental value, since we're in octet number 4, is going to be 0.4. Now to find the network ID for the router, we're just simply going to add 192 plus 16. So our network ID for this router is going to be 192.16.1.208. That is our network ID for the router, because we simply took the network ID for the switch and added it to the incremental value 192 plus 16. We're in the 4th octet, is going to yield us a 208. Now we can figure out our IP range. It's going to be 1 IP greater than the network ID. So this is going to start with a .209. And then also we can use this number to figure out the last IP address of the switch. So we're just going to subtract 1 IP, and that's going to give us a .208. So that'll be 192.16.1.207. And then from there, we can just subtract 1 IP address, and that'll give us a .206. So all these IP addresses, that's a grand total of like 12 IP addresses. That'll meet all of our requirements over here for 6 IPs, or a grand total of 9 IPs. So we can, dish out IPs all over the place if we need to. And then we get back over here to our incremental value, .16, come back over here, 16 yields a /28 subnet mask. And now we're going to drag this thing out one more step so we can figure out this same information for the router. So we're going to take our network ID for the router, .208, and add 4 to it. And that's going to give us 192.16.1.212. We're going to subtract 1 from this miscellaneous network so we can figure out our broadcast. That's going to give us 192.16.1.211. And then we're going to subtract 1 from the broadcast of the router to figure out the last IP that's ending for this particular device. And that's going to give us a .210. So essentially 2 IP addresses, .209 and .210, that are going to be assigned to this device if we want. And then from there, we can also take our .4 and figure out what our custom subnet mask is. So we come back up to our chart. We see our positional value of 4 is going to yield a /30. And basically a /30 is a .252. So this would be 255.255.255.252 once you crunch out the binary and work its way all the way out. So in a nutshell, ladies and gentlemen, this is what a VLSM chart looks like when you are trying to subnet a network so that you can have IPs that are way more manageable to deal with when you are going through trying to subnet the network beyond just the initial IP address that you were assigned from your ISP. So in this example here, we have our marketing department. They represent VLAN 1 or VLAN 3 or whatever. It doesn't even matter. They represent VLAN 3. And we said we needed 100 devices to assign to IP. So let's just imagine that in this network, there are 100 computers hanging off this switch in VLAN 3. Well, from here, when we go through and start programming our computers to bring them to life, if we're doing this manually, these are the IP addresses that we are going to assign to these devices. So this device right here might be .2, and this one might be .3, .4. We have options all the way up to .126. For HR, we said we needed 50 devices to have IP addresses. So this is our HR department. So imagine there are 50 computers hanging off this switch in VLAN 2. We come to our IP range. We have everything from .130 all the way to .190, a grand total of 60 IP addresses. So this one could be .130 and this one could be .131 all the way up to 190 if we want. And then from so on and so forth. And then once we actually get inside of the computer, if we were to manually do this, it's going to ask you for the IP address, the gateway IP address for the network, and the subnet mask. So you would just easily come back to your chart. So let's just say we're programming up this computer. We give it the IP address of 192.16.1.130 because this is the HR department. Well, from this chart, we already know what the IP address for the gateway is going to be. And we also know what the subnet mask is going to be for this particular device in this network. And you would do the same thing for this one over here. And then you come over to VLAN 3, marketing. Like I said, we gave this one an IP address of 192.16.1.2. And then this guy will be .3. So if we go in here and manually program up these two computers, we already know what our gateway IP address is going to be. And we know what our custom subnet mask is going to be for this device so that it can properly communicate on the network. And then we also know what the information for the switch and for the router is going to be. Anyways, I just wanted to show you guys this real quick, even though it's probably been like a 30-minute long video or something like that, as to what all this madness means when we were going through subnetting, learning about classful subnetting, classless subnetting. Well, this is what these numbers actually represent when people start talking about subnetting. This basically allows for you to create networks inside of a grander network so you can easily manage this thing better, because yes, even though I have them logically separated on the switch, I might have another switch hanging off this router over here to create another little network. I can throw some firewalls up in here. I can get real funky out in these streets if I really wanted to. But this VLSM chart, this is what allows for you to create a manageable pool of IP addresses to deal with. That's why we go ahead and subnet this thing down based off of our specific requirements that we need for our network needs. So that is why we do subnetting in a nutshell, ladies and gentlemen.
In this video, you're going to learn about assigning IP version 4 addresses. So at this point in the course, you should understand that network devices need IP addresses. However, beyond just an IP address, there are extra IP address related information that needs to be provided to a device. And this video is going to discuss various parameters that might be assigned to a network device, followed by discussing various approaches to assigning IP addresses to devices. So let's talk about IP addressing components. So as discussed in previous videos, an IP address has two portions. There's a network portion and a host portion, and a subnet mask is required to delineate between these two portions. In addition, if traffic is destined for a different subnet than the subnet on which the traffic originates, a default gateway needs to be defined. The default gateway routes traffic from the sender subnet towards the destination subnet. A default gateway is a network node that serves as the forwarding host or the router to other networks, often involving not only a change of addressing, but also a different networking technology. More narrowly defined, a router merely forwards packets between networks with different network prefixes. And the networking software stack of each computer contains a routing table that specifies which interface is used for transmission and which router on the network is responsible for forwarding to a specific set of addresses. If none of these forwarding rules are appropriate for a given destination address, the default gateway is chosen as the router or last resort. In a small office, home office environment, the default gateway is a device such as a DSL router or a cable router that connects the local network to the internet. It serves as the default gateway for all network devices. Enterprise networks may require internal network segments where a device wishing to communicate with a host on a public internet would have to forward the packets to the default gateway for its network segment, which would have a default route configured to a device on an adjacent network, which would be one hop closer to the public internet. And another consideration is that end users typically do not type in the IP address of the destination device with which they want to communicate. So for example, a web server that's on the internet. Instead, end users typically type what is called a fully qualified domain name, such as technologyg.com, my website. When connecting to devices on the public internet, a domain name system or a DNS server translates a fully qualified domain name into the corresponding IP address. And also, for a very long time, in a company's internal network, which is also known as an intranet, a Microsoft Windows Internet Name Service, or WINS, was used to convert the names of network devices into their corresponding IP addresses. So for example, say that you attempted to navigate to the shared folder server1 HR docs. A WINS server could be used to resolve the network device name server1 to a corresponding IP address. The path server1 /HR docs. This is the universal naming convention, or the UNC form, where you are specifying a network device name. In this case, that will be server1, and a resource available on that device, which would be HR docs. Companies today, they use DNS even for internal network name resolutions. And to summarize, network devices like end-user PCs, they can benefit from a variety of IP address parameters, such as obviously the IP address, the subnet mask, the default gateway, and server addresses. Also, an IP address no longer needs to be assigned to a single entity or interface. A virtual IP address is commonly used and can fulfill many purposes. A virtual IP address is an IP address assigned to multiple domain names or servers that share an IP address based on a single network interface card, or a NIC card. Virtual IPs are allocated to virtual private servers, websites, or any other application residing on a single server. The host server for these applications has a network IP address assigned by a network administrator, whereas the different server applications have virtual IPs. So in layman's terms, a server IP address depends on the media access control, or the MAC address of the attached NIC, and only one logical IP address may be assigned per card. However, virtual IP addressing enables hosting for several different applications and virtual appliances on a server with only one logical IP address. The virtual IP is used for communication by all hosted applications, even though data packets are routed through actual network interfaces. And virtual IPs are primarily implemented for the following reasons. They provide key addresses used in address translation. They represent any actual IP address assigned to a network device interface. They permit the sending of traffic to multiple different network devices, all configured to respond based on the virtual IP address. They consolidate resources through the allocation of one network interface per hosted application, and they improve redundancy by providing alternative failover options on one machine. And a concept that is very similar to the virtual IP address is the sub interface. And this is a handy interface capability supported by most router and switch manufacturers that allows you to create many virtual interfaces out of a single physical interface. So if you look at this picture right here, this demonstrates the creation of a sub interface on a Cisco router and the assignment of an IP address. And this is done after enabling and providing an IP address to the physical interface. All right, next let's talk about static configurations. So a simple way of configuring a PC with IP address parameters is to statically configure that information. So for example, on a PC running Microsoft Windows as the operating system, you can navigate to the control panel, network and internet, network and sharing center, change adapter settings, network connections, properties, internet protocol version 4, TCP IP version 4, and then go to properties. And then from there, you can enter an IP address, a subnet mask, a default gateway, and DNS server information into the Internet Protocol version 4 properties window. Although DNS server information can be entered in this window, more advanced DNS options and the WINS options are available by clicking the Advanced button. And by clicking the DNS tab in the Advanced TCP/IP Settings window, this is where you can add, remove, or reorder DNS servers, and you can adjust various other DNS parameters. And also recall that a DNS server, it converts a fully qualified domain name into an IP address. And similarly, you can configure the Windows Internet Name Service or the WINS server in the WINS tab of the Advanced TCP/IP Settings window, as shown in this picture right here. And much like a DNS server, a WINS server converts a NetBIOS computer name to a corresponding IP address. All right, next let's talk about dynamic configuration. So statically assigning IP address information to individual network devices, this can be very time consuming, error prone, and it lacks in scalability. Instead of using static IP address assignments, many corporate networks dynamically assign IP address parameters to their devices. An early choice for performing this automatic assignment of IP addresses was the Bootstrap protocol. Currently, however, the most popular approach for dynamic IP address assignment is the DHCP or the Dynamic Host Configuration Protocol. In the Dynamic Host Configuration Protocol, this is a network management protocol used on IP networks whereby a DHCP server dynamically assigns an IP address and other network configuration parameters to each device, such as PCs, printers, servers, routers, etc., on a network so they can communicate with other IP networks. A DHCP server enables computers to request IP addresses and networking parameters automatically from the ISP, reducing the need for a network administrator or a user to manually assign IP addresses to all network devices. In the absence of a DHCP server, the computer or other device on the network needs to be manually assigned an IP address or to assign itself what is called an APIPA address or an automatic private IP address, the latter of which will not enable it to communicate outside of its local network. If you get your address from a DHCP server, you're getting your address assigned dynamically, and it could change periodically. Some devices on the network, they do require static addresses that do not change, such as printers and servers, which have to be assigned manually by a network administrator. And this enables these devices to be more reliable and easily accessible over time. And also DHCP, it uses ports 67 and 68, where UDP port number 67 is the destination port of a server, and UDP port number 68 is used by the client. All right, next let's talk about the Bootstrap protocol. So engineers developed the Bootstrap protocol as a method of assigning IP addresses, subnet masks, and default gateway information to diskless workstations. In the early days of Microsoft Windows, Windows did not natively support TCP/IP. To include TCP/IP support, an add-on TCP/IP application had to be run. In such an application, it would typically support the Bootstrap protocol. When a device needed to obtain IP address information, a Bootstrap protocol broadcast will be sent out from the device needing an IP address. If a BootP server, which is called a BootPS, received the broadcast, it can match the source MAC address in the receive frame, which is the MAC address from the device wanting to obtain an IP address, with a corresponding IP address in a database stored on the BootP server. The BootPS would then respond to the requesting client with IP address information. Because BootP requests were based on broadcasts, by default, a BootP request could not propagate beyond the device's local subnet. However, most enterprise class routers, they can be configured to forward selected broadcast types, including BootP broadcast. And next, let's talk about a PIPA, or the automatic private IP address. So if a router does not have enough IP addresses for the devices that need to connect to it, a PIPA IP addresses are assigned to devices arriving after the pool of addresses are used up. And a PIPA, this stands for automatic private IP addressing, which is a feature in Windows-based operating systems that enables computers to automatically self-configure an IP address and subnet mask when their DHCP server isn't reachable. The PIPA service checks regularly for the presence of the DHCP server every 3 minutes. If it detects a DHCP server on the network, the DHCP server will replace the PIPA networking address with dynamically assigned addresses. And a PIPA was designed as a solution for quickly setting up a localized network without the need to configure a DHCP server or the need to statically assign IP address information. However, there remains a need for devices on this localized network to perform name resolution and discover network services. Fortunately, these needs are covered by what's called zero configuration. And zero configuration, this is the technology supported on most modern operating systems, and it performs 3 basic functions. The first one is assigning link local IP addresses. So a link local IP address, this is a non-routable IP address usable only on a local subnet. A PIPA is an example of a technology that assigns the link local IP addresses. Then zero configuration also resolves computer names to IP addresses. So multicast domain name systems, this is an example of a technology that can resolve computer names to their corresponding IP addresses on a local subnet without the aid of a DNS server or a WIN server. And then zero configuration, it also locates network services. So examples of service discovery protocols include the standards-based service location protocol, Microsoft's simple service discovery protocol, and Apple's DNS-based service discovery. And if these devices supporting these 3 zero configuration features are interconnected on a local subnet, they can dynamically obtain link local IP addresses, resolve one another's names to IP addresses, and discover services that are available on a network. In this video, you're going to learn about IP address translation. All right, so let's talk about address translation. So as described in previous videos, some IP addresses are routable through the public internet, and other IP addresses are considered private and are intended for use within an organization. Network address translation, or NAT, this allows private IP addresses to be translated into internet routable IP addresses, also known as public IP addresses. And this video examines the operation of basic NAT and a variant called port address translation, or PAT. And address translation, this can also be done for specific ports associated with an IP address. And when this is done, it is often referred to as port forwarding. Let's talk about NAT, or network address translation. So this is a method of remapping an IP address space into another by modifying network address information in the IP header of packets while they are in transit across a traffic routing device. So in layman's terms, NAT is the process where a network device assigns a public address to a computer or a group of computers inside a private network. The main use of NAT is to limit or hide an entire IP address space on a local area network for both economic and security purposes. This functionality is typically built into a router, and when network address translation is implemented, before an IP address on a LAN can communicate with the internet, the IP address has to be converted to the public IP address of the router. This allows for the router to appear as if it is the only device making a connection to remote computers on the internet, which provides safety for the computers on the local area network. It also allows a single IP address to do the work for many other IP addresses in the LAN. And network address translation, this is performed automatically on SOHO routers when connected to an IP version 4 network. Network address translation is not necessary on an IP version 6 network because IP version 6 is much more secure and has no shortage of IP addresses. As a memory aid, when you see the word inside, it also refers to an inside device or a source device, and outside always refers to an outside device or the destination. Also, think of the word local. It's a made-up address or a private IP address that is not routable on the internet. And then finally, the word global. This refers to a global IP address that is routable on the internet. Also, NAT does not always have to be between private and public addresses. So for example, NAT could be implemented between two private address ranges or two public address ranges. Whether an inside local address is randomly assigned an inside global address from a pool of available addresses, or is assigned an address from a static configuration, this determines the type of network address translation that will be in use. And these two approaches to NAT are called DNAT and SNAT. So the first one is DNAT, and this stands for Destination Network Address Translation. And this is a technique for transparently changing the destination IP address of a routed packet and performing the inverse function for any replies. Any router situated between two endpoints can perform this translation of the packet. DNAT is commonly used to publish a service that is located in a private network on a publicly accessible IP address. And also DNAT, this is known as port forwarding. And next we have SNAT, or a static network address translation. And this is primarily used in enterprise networks where many internal servers have unregistered IP addresses and are accessed by a global audience using static public IP addresses. It provides a means to ensure network transparency, security, and privacy by hiding the details of internal network usage, architecture, and patterns from external or public users. In a static NAT, this works by creating a one-to-one relationship between the public and private IP addresses. This means that the private IP address can be mapped to only one public IP address at a time. The end user, on the other hand, has a transparent view of the remote device or network and accesses it using the mapped public IP address. And finally, we're going to talk about PAT, or port address translation. So a challenge with basic NAT is that there is a one-to-one mapping of inside local addresses to inside global addresses, meaning that a company would need as many publicly routable IP addresses as it had internal devices needing IP addresses. This does not scale well because often a service provider provides a customer with only a single IP address or a small block of IP addresses. Fortunately, many routers, they support port address translation, which allows multiple inside local addresses to share a single inside global address or a single publicly routable IP address. For this reason, port address translation is referred to as a many-to-one. Its basic function is to share a single IP public address between multiple clients who need to use the internet publicly. It is an extension of network address translation, and an example of PAT is a home network that is connected to the internet. Within this setup, the system's routers is assigned a discrete IP address. Multiple users can access the internet over the router and are each assigned a port number as they do so. In this video, you are going to learn about IP version 6 addressing. All right, so let's talk about IP version 6. So with the global proliferation of IP-based networks, available IP version 4 addresses are rapidly becoming extinct. Fortunately, IP version 6 provides enough IP addresses for many generations to come. And this video is going to introduce IP version 6 address structures and discuss some of its unique characteristics. So let's talk about the need for IP version 6. So with the worldwide depletion of IP version 4 addresses, many organizations have migrated, or they are in the process of migrating, or they are considering migrating their IP version 4 addresses to IP version 6 addresses. IP version 6 dramatically increases the number of available IP addresses. In fact, IP version 6 offers approximately 5 times 10 to the 28th power IP addresses for each person on the planet. But beyond the increased address space, IP version 6 offers many other features, such as a simplified header to where the IP version 4 header uses only 12 fields. The IP version 6 headers have 5 fields. IP version 6 has no broadcast. It has no fragmentation. It can coexist with IP version 4 during a transition. And this is known as dual stack, where you can run IP version 4 and IP version 6 simultaneously on a network interface or device. And then it also offers tunneling where you can tunnel IP version 6 over an IP version 4 network. And even if you are designing a network for IP version 4 addressing, it is a good practice to consider how readily an IP version 6 addressing scheme could be overlaid on that network at some point in the future. Using tunneling, an IP version 6 host could provide IP version 6 connectivity even when the host is directly connected to an IP version 4 only network. IP version 6, IP version 4 tunneling, this is often referred to as 6 to 4 or 4 to 6 tunneling, depending upon which protocol is being tunneled. And these are just some of the many tunneling mechanisms devised to ensure a smooth transition from IP version 4 to IP version 6. In fact, thanks to dual stack and tunneling features, it is very unlikely that you will see IP version 4 ever completely go away in your lifetime. All right, next let's talk about the IP version 6 address structure. So an IP version 6 address has the following address format, where the X is a hexadecimal digit in the range of hexadecimal values 0 to F. And a hexadecimal digit is 4 bits in size, where 4 binary bits represent 16 values. And notice that an IP version 6 address has 8 fields. Each field contains 4 hexadecimal digits. And the following formula reveals why an IP version 6 address is a 128-bit address. So you have 4 bits per digit times 4 digits per field times 8 fields. This gets you 128 bits in an IP version 6 address. Also, IP version 6 addresses can be difficult to work with because of their size. Fortunately, the following rules, often collectively referred to as shorthand notation, they exist for abbreviating these addresses. And the rules are: leading zeros in the field, they can be omitted, and contiguous fields containing all zeros can be represented with a double colon. And note that this can be done only once for a single IP version 6 address. So for example, if you look at the following IP version 6 address, you got ABCD, colon 0123, colon 4040, colon, a whole bunch of zeros. And then you got colon 00A, colon 000B. Anyways, if you use the abbreviation rules, the IP version 6 address can be shortened to look like the following. So you got ABCD, colon 123. So we took off the first 0. Then we got another colon 4040. Then we have a double colon in place to represent all of those zeros. And then we got A, then colon, and B. And you notice the 3 zeros in front of the A and in front of the B have been taken off. And another feature of IP version 6 is the extended unique identifier, or the EUI64 format. And this permits a device to automatically populate the low order 64 bits of an IP version 6 address based on the interface's MAC address. Next, let's talk about IP version 6 address types. So the following are some of the many unique aspects of IP version 6 addressing and interesting address types. So you got IP version 6 globally routable unicast addresses. They start with the first 4 hexadecimal characters in the range of 2000 to 3999. And then you have the IP version 6 link local address, which is also used on each IP version 6 interface. And the link local address, it begins with FE80. You got the multicast address that begins with FF as the first 2 hexadecimal characters. And also IP version 6, it can use auto configuration to discover the current network and select a host ID that is unique on that network. Automatic generation of a unique host ID is made possible through a process known as EUI64, which uses the first 48-bit MAC address on the device to aid in the generation of the unique 64-bit host ID. Notice that the auto configuration capabilities described here permit you to create an IP version 6 network free of DHCP type services. The ability of IP version 6 to replace the need for DHCP services like this is known as a stateless address configuration, or SLAAC, SLAAC. In IP version 6, it can also use a special version of DHCP for IP version 6, which is known as DHCP version 6. And then you have the protocol that is used for network discovery, that is to discover the network address and learn the layer 2 addresses of networks on the same network. This is called Network Discovery Protocol. And let's talk about Network Discovery Protocol because this is important in IP version 6. It defines 5 ICMP version 6 packet types for important jobs. And the first type is what what is called router solicitation. And this is where hosts inquire with router solicitation messages to locate routers on an attached link. You have router advertisement. So routers advertise their presence together with various link and internet parameters, either periodically or in response to router solicitation messages. You have neighbor solicitation. So neighbor solicitations are used by nodes to determine the link layer address of a neighbor or to verify that a neighbor is still reachable via a cached link layer address. You have neighbor advertisements. Neighbor advertisements are used by nodes to respond to a neighbor solicitation message. And you have redirect, where routers may inform hosts of a better first hop router for a destination. And finally, let's talk about IP version 6 data flows. So IP version 6 uses 3 types of data flows. You got unicast, multicast, and anycast. And just like in IP version 4, IP version 6 uses special address types for these data flows. And we're going to talk about them real quick. And the first one is called unicast. So with unicast, a single IP version 6 address is applied to a single interface, and the communication flow can be thought of as a one-to-one communication flow. Then we got multicast. So with multicast, a single IP version 6 address or a multicast group can represent multiple devices on the network, and the communication flow is called a one-to-many communication flow. And then we have anycast. So with anycast, a single IP version 6 address is assigned to multiple devices, and it is called a one-to-nearest from the perspective of the router's routing table communication flow. And as a side note, you want to remember that the broadcast frames and packets from IP version 4, they do not exist in an IP version 6 only network. IP version 6 uses only unicast, multicast, and anycast. With IP version 6, if you want to send a frame or packet to all nodes in the local network, you have to use the all nodes IP version 6 multicast address. In this video, you are going to learn about the purpose and uses of various networking ports and protocols. All right, so let's talk about the first protocol, which is FTP. So the file transfer protocol. This is a standard network protocol used for the transfer of computer files between a client and server on a computer network. FTP is also used by web browsers. To access an FTP site, you will use the prefix FTP://. Windows, Linux, and Mac, they contain a command line FTP program, and you can simply type FTP and press enter, and then type help at the FTP prompt to see the commands that you can use with FTP. Also, FTP sites with downloads available to any user, they support anonymous FTP. Anonymous FTP is a means by which archive sites allow general access to their archives of information. These sites, they create a special account called Anonymous, and user Anonymous has limited access rights to the archive host, as well as some operating restrictions. Some FTP sites require the user to log in with a specified username and password, but one drawback to FTP is that it is not considered secure due to FTP login credentials being transmitted and authenticated in the clear text. And to increase security, you can use FTP secured with SSL or TLS, which is known as FTPS, or Secure File Transfer Protocol, or SFTP. Let's talk about Secure Shell. So Secure Shell, this is a cryptographic network protocol for operating network services securely over an unsecured network. SSH is more secure than FTP and Telnet, and typical applications include remote command line, login, and remote command execution, but any network service can be secured with SSH. SSH servers housing data a client wants to retrieve uses port 22, and we need to have that port open to get access to that data. As previously mentioned, regular FTP is an insecure port, whereas Secure Shell FTP, or SFTP, is secure by way of utilizing TCP port 22, as it is run over an SSH or Secure Shell session. Next, let's talk about Telnet. So Telnet, this is an application protocol used on the internet or a local area network to provide bidirectional interactive interactive text-oriented communication facility using a virtual terminal connection. A telnet emulation enables a user to connect to a remote host or device using a telnet client over port 23. A telnet connection allows for a user to telnet into a computer that hosts their website to manage their files remotely versus simply downloading pages and files as he or she would with an HTTP or FTP connection. Before a telnet connection from a client can be established, a remote computer must already be configured to accept the telnet login on port 23, and that port must be open before a login can take place. And to utilize the telnet command prompt on a Windows or Linux computer by way of a command line telnet program, you would have to open a connection to a remote computer, followed by opening a command prompt in Windows or a terminal session in Linux, and then typing telnet and pressing enter. And for the help commands, you would just simply type help and then press the enter key. And also, telnet has been removed from recent versions of Mac due to the standard practice of using secure shell. But if telnet is still needed, it is possible to install it on a Mac operating system. All right, next let's talk about SMTP. So Simple Mail Transfer Protocol. This is a communication protocol for email transmission. SMTP utilizes port 25 to send email from a client system to an email server, which uses SMTP to relay messages to the receiving email server. To configure email settings on a client device, you would check with your ISP or organization that provides internet access for the settings, such as the server type or the ports, username and password for access to those servers, and the security settings that may be used, such as secure shell. And then also you have SMTP TLS, or sometimes it's referred to as SMTPS, and this uses TCP port 465 in its operation, and this is the secure version of SMTP. Next we have DNS. So domain name system, this is a hierarchical and decentralized naming system for computers, services, or other resources connected to the internet or a private network. It associates various information with domain names assigned to each of the participating entities. Most prominently, it translates more readily memorized domain names to numerical IP addresses, which are needed for locating and identifying computer services and devices with the underlying network protocols. So in other words, DNS can be thought of as being the phone book for the internet. Instead of memorizing IP addresses to get to a website such as YouTube, one could simply type in the URL or the Uniform Resource Locator, also known as the address bar, youtube.com, and the DNS will match the name of the IP address associated with youtube.com to take your client device to YouTube. And when manually configuring an IP address, you typically provide the IP address of a DNS server or the IP address of multiple DNS servers as part of the configuration process. In some texts, they refer to DNS as either domain name service or domain name server, which is not all the way technically correct, but it is understood in the industry with other IT professionals. Next, let's talk about DHCP. So Dynamic Host Configuration Protocol. This is a network management protocol used on IP networks whereby a DHCP server dynamically assigns an IP address and other network configuration parameters to each device, such as PCs, printers, servers, routers, etc., on a network so they can communicate with other IP networks. A DHCP server enables computers to request IP addresses and networking parameters automatically from the ISP, reducing the need for a network administrator or a user to manually assign IP addresses to all network devices. In the absence of a DHCP server, a computer or other device on the network needs to be manually assigned an IP address or to assign itself an PIPA address, the latter of which will not enable it to communicate outside of its local network. If you get your address from a DHCP server, you are getting your address assigned dynamically, and it could change periodically. In some devices on the network, they require static addresses that do not change, such as printers and servers, which have to be assigned manually by a network administrator. This enables these devices to be more reliable and easily accessible over time. In DHCP, it uses ports 67 and 68, where UDP port number 67, that is the destination port of a server, and UDP port 68 is used by the client. Next, let's talk about TFTP. So Trivial File Transfer Protocol. This is a simple lockstep file transfer protocol which allows a client to get a file from or put a file onto a remote host. One of its primary uses is in the early stages of nodes booting from a local area network. TFTP has been used for this application because it is very simple to implement. Due to its simple design, TFTP can be easily implemented by code with a small memory footprint. It is therefore the protocol of choice for the initial stages of any networking booting strategy like BootTP, PXE, or BSDP, etc., when targeting from highly resourced computers to very low resource single board computers and systems on a chip. It is also used to transfer firmware images and configuration files to network appliances like routers, firewalls, and IP phones. As of today, TFTP is virtually unused for internet transfers. All right, next let's talk about HTTP and HTTPS. So Hypertext Transfer Protocol. This is an application protocol for distributed collaborative hypermedia information systems. HTTP is the foundation of data communication for the World Wide Web, where hypertext documents include hyperlinks to other resources that the user can easily access, so for example, by a mouse click or by tapping the screen in a web browser. HTTP is used by all major web browsers such as Internet Explorer, Microsoft Edge, Firefox, and Chrome. HTTP for unsecured sites uses the prefix HTTP : // whereas sites that are secured with various forms of encryption, they use the prefix HTTPS. And HTTP uses port 80 and HTTPS uses port 443. And to check to see if a website is secure, most browsers will display a closed padlock symbol right next to the web address in the web address bar. All right, next let's talk about POP3. So Post Office Protocol version 3. This is an application layer internet standard protocol used by email clients to retrieve email from a mail server. Email is downloaded from the mail server to folders on a local system. For users who frequently switch between computers and or mobile devices, POP3 email is not a suitable solution for checking emails on multiple devices due to the email being downloaded onto only one device when the client device puts in a request. Users who utilize POP3 servers to retrieve email typically use SMTP to send messages. In POP3, this is the current version and standard, and it uses port 110. And then we also have POP3 over SSL. So POP3, this is another important networking protocol that does not feature support for built-in security. As a result, POP3 over SSL was developed, and this is the secure protocol that uses TCP port 995 in its operation. Next, let's talk about NTP. So the Network Time Protocol. This is a networking protocol for clock synchronization between computer systems over packet switch variable latency data networks. NTP is intended to synchronize all participating computers to within a few milliseconds of coordinated universal time, or UTC time. It uses the intersection algorithm to select accurate time servers and is designed to mitigate the effects of variable network latency. NTP can usually maintain time within tens of milliseconds over the public internet and can achieve better than 1 millisecond accuracy in local area networks under ideal conditions. Asymmetric routers and network congestion can cause errors of 100 milliseconds or more. The protocol is usually described in terms of a client-server model, but can also be easily used in peer-to-peer relationships where both peers consider the other to be a potential time source. In implementations, they send and receive timestamps using UDP port 23. They can also use broadcasting and multicasting, where clients passively listen to time updates after an initial round-trip calibrating exchange. And NTP supplies a warning of any impeding leap second adjustment, but no information about local time zones or daylight saving time is transmitted. Right, next we have IMAP. So Internet Message Access Protocol. This is an internet standard protocol used by email clients to retrieve email messages from a mail server over a TCP/IP connection. IMAP, it was designed with the goal of permitting complete management of an email box by multiple email clients. Therefore, clients generally leave messages on the server, which can be retrieved from multiple devices from any location until the user explicitly deletes them. IMAP IMAP forward. This is the current version of IMAP. And to configure an IMAP-based email account, you must select IMAP as the email server type, specify the name of the server, enter a username and password, and whether the server uses SSL. And also IMAP, it uses port 143. Then we have IMAP over SSL. So IMAP does not have a way to provide security for communications, and as a result, it did not take long for the more secure IMAP over SSL to be created. And this protocol uses TCP port 993 in its operation. Next, we have SNMP. So Simple Network Management Protocol. This is an internet standard protocol for collecting and organizing information about managed devices on IP networks and for modifying that information to change device behavior. Devices that typically support SNMP include cable modems, routers, switches, servers, workstations, printers, etc. They are often incorporated into software known as a network management system, or NMS. And the NMS is the main software installed on a computer known as a manager that controls everything SNMP based. And the devices to be monitored, they are known as managed devices. NMS installs a small piece of software known as an agent that allows the NMS to monitor those managed devices. In SNMP, it uses port 161. Next, we have LDAP. So Lightweight Directory Access Protocol. This is an open, vendor neutral, industry standard application protocol for accessing and maintaining distributed directory information services over an IP network. Domain directory services play an important role in developing intranet and internet applications by allowing the sharing of information about users, systems, networks, services, and applications throughout the network. As such, directory services may provide any organized set of records, often with a hierarchical structure, such as a corporate email directory. Microsoft refers to this as directory services, and LDAP uses port 389, and LDAP-S over TLS SSL, it uses port 636. Next, let's talk about SMB. So server message block, where one version of which was also known as Common Internet File System, or CIFS. This is a network communication protocol for providing shared access to files, printers, and serial ports between nodes on a network. It also provides an authenticated inter-process communication mechanism by way of using packets that authenticate remote computers. SMB uses ports 137 through 139 for SMB traffic using NetBIOS over TCP, and port 445 for SMB hosted on TCP. CIFS, this was originally used as the standard method for sharing files via corporate intranets and the internet. And also CIFS has now been widely replaced by the updated versions of SMB, which are SMB 2.0 and 3.0. All right, next we have syslog. So syslog, this is a standard used by network devices and other computer systems to report on status information and events. This data is often called machine data, and storing and analyzing this information can be very important. In syslog, it uses UDP port 514 in its operation. Next, we have structured query language, or a SQL server. So you can use the SQL language to run powerful queries against data that is stored in databases. In SQL servers, they can use TCP and UDP in its operation, and port 1443 was reserved for this Microsoft invention. And next we have SQLnet. So SQLnet is Oracle's networking software, which allows remote data access between programs and Oracle databases. Applications and databases can be distributed physically to different machines and can continue to communicate as if they were local. In SQLnet, it relies on TCP port 1521 in its operation. Next, we have MySQL. So MySQL, this is an open source relational database management system with a client server model. RDBMS is a software service used to create and manage databases based on a relational model. And MySQL uses TCP port 3306 in its operation. And next we have RDP, so Remote Desktop Protocol. This is a proprietary protocol developed by Microsoft, which provides a user with a graphical interface to connect to another computer over a network connection. The user employs RDP client software for this purpose, known as Remote Desktop Services, while the other computer must run RDP server software, known as Remote Desktop Connection. In RDP, it uses port 3389. And finally, we have SIP, so the Session Initiation Protocol.
This is a signaling protocol used for initiating, maintaining, and terminating real-time sessions that include voice, video, and messaging applications. SIP is used for signaling and controlling multimedia communication sessions and applications of internet telephony for voice and video calls, in private IP telephone systems, and instant messaging over internet protocol networks, as well as mobile phone calling over LTE. The protocol defines the specific format of messages exchanged and the sequence of communications for cooperation of the participants. SIP is a text-based protocol incorporating many elements of HTTP and SMTP. A call established with SIP may consist of multiple media streams, but no separate streams are required for applications such as text messaging that exchange data as payload in the SIP message. And SIP clients typically use TCP or UDP on port numbers 5060 or 5061 for SIP traffic to servers and other endpoints. And port 5060 is commonly used for non-encrypted signaling traffic, whereas port 5061 is typically used for traffic encrypted with transport layer security, or TLS. In this video, you're going to learn about various IP protocol types. So let's talk about exactly what is a communication protocol. So a communication protocol, this is a system of rules that allow two or more entities of a communication system to transmit information via any kind of variation of a physical quantity. The protocol defines the rules, the syntax, the semantics, and synchronization of communication and possible error recovery methods. And protocols may be implemented by hardware, software, or a combination of the two. And protocols, they are designed to allow for applications to send and receive data via predefined ports on a network adapter to make connections to another computer. Port numbers on computers, they are used to identify protocols for the purpose of sorting various processes. So for example, if you want to visit technologyg.com, you would open up a browser and type www.technologyg.com. The Hypertext Transfer Protocol, or HTTP, this is what is being used to make a connection to the web server technologyg.com. For the transmission of data, HTTP selects an unused outbound port on your computer to send and receive data to and from the web server technologyg.com. On the technologyg web server, port 80, which is the inbound port corresponding to HTTP, is open at all times to allow for a computer to make a connection to the technologyg web server. All right. And the first protocol we're going to talk about is the Internet Protocol. So the Internet Protocol, this is the principal communications protocol in the Internet Protocol suite for relaying datagrams across network boundaries. Its routing function enables internetworking and essentially establishes what we know as the Internet. IP has the task of delivering packets from the source host to the destination host solely based on the IP addresses in the packet headers. For this purpose, IP defines packet structures that encapsulate the data to be delivered. It also defines addressing methods that are used to label the datagram with source and destination information. All right, the next protocol is TCP, so Transmission Control Protocol. This is one of the main protocols of the Internet Protocol suite. It originated in the initial network implementation in which it complemented the Internet Protocol, therefore being commonly referred to as TCP/IP. In TCP, it provides reliable, ordered, and error-checked delivery of bytes between applications running on hosts communicating via an IP network. TCP is connection-oriented, and a connection between a client and a server is established before data can be sent, which requires every packet that has been sent to be checked for delivery. If packets that are transmitted to a receiving computer are not received, the receiving computer cannot assemble the message, and therefore the sending computer has to retransmit the missing packets. So for example, if a computer sends a picture of a car, but for some reason the picture is missing parts of the image that displays the tires, TCP will instruct the sending computer to retransmit the missing data for the proper assembly of that image. And the next protocol we're going to talk about is UDP, so User Datagram Protocol. This is one of the core members of the Internet Protocol suite. With UDP, computer applications can send messages, which are also known as datagrams, to other hosts on an IP network. Prior communications are not required to set up communication channels or data paths, and UDP uses a simple connectionless communication model with a minimum of protocol mechanisms.
mechanisms. UDP provides checksums for data integrity and port numbers for addressing different functions at the source and destination of the datagram. It has no handshaking dialogues like TCP and thus exposes the user's program to any unreliability of the underlying network, meaning there is no guarantee of delivery, ordering, or duplicate protection. In voice over IP and streaming media services, they use UDP in addition to simple queries and responses such as DNS. And the next protocol is ICMP. So the Internet Control Message Protocol. This is a supporting protocol in the Internet Protocol Suite. It is used by network devices, including routers, to send error messages and operational information indicating success or failure when communicating with another IP address. So for example, an error is indicated when a requested service is not available or that a host or router could not be reached. ICMP differs from transport protocols such as TCP and UDP in that it is not typically used to exchange data between systems, nor is it regularly employed by end-user network applications, with the exception of some diagnostic tools like ping and traceroute. The next protocol is IPsec, and that stands for Internet Protocol Security. So Internet Protocol Security, this is a complex suite of protocols that are used to create secure connections between network systems. In fact, IPsec is quickly becoming the de facto standard for VPN connections. And IPsec features the use of an authentication header and an encapsulating security payload. And as you would guess, the authentication header, it handles the authentication functions, and the encapsulating security payload takes care of the encryption. And our last protocol is GRE, or Generic Routing Encapsulation. So generic routing encapsulation, as its name implies, this is a multi-purpose, simple tunneling protocol that you might call on in a wide variety of circumstances. So for example, let's say you have traffic that you want to protect over an IPsec tunnel, but this traffic is multicast traffic. IPsec does not support securing this type of traffic. That is where GRE can come into play. The multicast can be encapsulated inside of GRE, and then this GRE traffic can be protected by IPsec. And this is just one example of many where GRE can come in handy. In this video, you're going to learn about various network services such as Dynamic Host Configuration Protocol, Domain Name System, and Network Time Protocol. So let's talk about network services. So while there are many network services available today, three services are so commonplace that we encounter them at every turn in the modern network. And those three services are DHCP, DNS, and NTP. And in this video, you're going to learn the important basics of these critical network components. All right, so let's talk about the first one, which is DHCP, or Dynamic Host Configuration Protocol. So statically assigning IP address information to individual network devices, this can be time-consuming, error-prone, and subject to scalability problems. Instead of using static IP address assignments, many corporate networks dynamically assign IP address parameters to their devices. This is typically referred to as dynamic address assignment, and the alternative approach is referred to as a manual assignment or a static assignment. And an early choice for performing automatic assignment of IP addresses was the Bootstrap protocol, which we discussed in previous videos. Currently, however, the most popular approach for dynamic IP address assignment is the use of the DHCP. In DHCP, it offers a more robust solution to IP address assignment than does the Bootstrap protocol. And DHCP does not require a statically configured database of MAC address to IP address mappings. Also, DHCP has a wide variety of options beyond basic IP address, subnet mask, and default gateway parameters. So for example, a DHCP server can educate a DHCP client about the IP address of a TFTP server from which a configuration file could be downloaded. And this is the process for how a DHCP client goes about obtaining IP address information from a DHCP server. So the first step is when a DHCP client initially boots, it has no IP address, default gateway, or other such configuration information. Therefore, the way a DHCP client initially communicates is by sending a broadcast message that is a DHCP discover message to the destination address of 255.255.255.255 in an attempt to discover a DHCP server. And step 2, when a DHCP server receives a DHCP discover message, it can respond with a unicast DHCP offer message. Because the DHCP discover message is sent as a broadcast, more than one DHCP server might respond to the discover request. However, the client typically selects the server that sent the first DHCP offer response that was received by the client. And then we got step 3. So the DHCP client communicates with this selected server by sending a unicast DHCP request message asking the DHCP server to provide IP configuration parameters. And then step 4, the DHCP server responds to the client with a unicast DHCP acknowledgement message. And this DHCP acknowledgement message contains a collection of IP configuration parameters. Now, notice that in step 1, the DHCP discover message is sent as a broadcast. By default, a broadcast cannot cross a router boundary. Therefore, if a client resides on a different network than the DHCP server, the client's next hop router should be configured as a DHCP relay agent, which allows a router to relay DHCP requests to either a unicast IP address or a directed broadcast address for a network. And the DHCP relay agent is often referred to as an IP helper or simply a DHCP relay. And using a DHCP relay agent allows you to centrally locate a DHCP server that can simultaneously service many different TCP/IP subnets in your enterprise infrastructure. And this is often a very desirable configuration because centralizing this information often makes it easier to manage. Now, of course, the risk in this configuration is that you must ensure that the DHCP relay agents are configured properly and that they are available. Otherwise, the client broadcasts for DHCP services, it will not be successful. And as a side note, this technology has an amazing number of different names for this technology. And once again, it includes the names IP helper, DHCP relay, DHCP relay agent, or simply relay agent, or UDP forwarder. And a DHCP server, it can be configured to assign IP addresses to devices belonging to different subnets. Specifically, a DHCP server can determine the source subnet of a DHCP request and select an appropriate address pool from which to assign an address. And one of these address pools, which typically corresponds to a single subnet, this is called a scope. And when a network device is assigned an IP address from an appropriate DHCP scope, that assignment is not permanent. Rather, it is a temporary assignment referred to as a lease. Although most client devices on the network work well with this dynamic addressing, some devices, such as servers, might need to be assigned specific IP addresses. Fortunately, you can configure a DHCP reservation where a specific MAC address is mapped to a specific IP address that will not be assigned to any other network device. This static addressing approach is referred to as a DHCP reservation. And another frequent configuration you might take in a DHCP implementation is to configure what is called an exclusion range. And this is a portion of the address pool that you never want leased out to clients in the network. Perhaps you have numbered your servers 192.168.1.1 through 192.168.1.10. Because the servers are statically configured with these addresses, you exclude these addresses from the 192.168.1.0/24 pool of addresses. Your DHCP server then leases out addresses at the first available in that range. And in this example, that will be 192.168.1.11. And as a side note, a method for remembering the 4 main steps of DHCP is to think of the acronym DORA. It stands for Discover, Offer, Request, and Acknowledge. Now, perhaps you have noticed that the DHCP dynamically assigns IP addresses and subnet masks to clients, but they need more IP addressing information than that in order to communicate properly on the network. So for example, clients need DNS server addresses, they need a default gateway assigned, and they might even need the IP addresses associated with other key services such as NTP and TFTP servers on the network. Your DHCP server can provide all this required IP addressing information. You would enable this as part of the scope options you can configure on the DHCP server. And the scope is the addresses that your DHCP server will lease out to clients. The scope options include the additional address information that must be distributed and can also include settings such as the lease time. And most DHCP TCP servers permit a client to retain IP address for 24 hours by default. If you have an environment with relatively few available addresses and therefore few available leases, you can set the lease time to a shorter duration so that clients cannot retain the address information for excessive time periods. All right, next let's talk about the DNS. So a domain name system server, this performs the task of resolving a domain name to a corresponding IP address. Because routers or multi-layer switches make their forwarding decisions based on layer 3 information such as IP addresses, an IP packet needs to contain IP address information, not DNS names. However, we humans, we recall meaningful names more readily than we recall 32-bit numbers. And as shown in this picture here on your screen, the end user who wants to navigate to google.com enters what is called the fully qualified domain name into a web browser. However, the browser cannot immediately send a packet destined to google.com. First, the end user's computer needs to resolve the fully qualified domain name to a corresponding IP address, which can be inserted as the destination IP address in an IP packet. This resolution is made possible by a DNS server, which maintains a database of local fully qualified domain names and their corresponding IP addresses, in addition to pointers to other servers that can resolve IP addresses for other domains. And a fully qualified domain name, this is a series of strings delimited by a period, such as www.google.com. The rightmost part of the fully qualified domain name is called the top level domain. And examples of top level domains include .com, .mil, and .edu. Although there are many other top level domains, these are among the most common top level domains in the United States. And then you have lower level domains where they can point upward to higher level DNS servers to resolve non-local fully qualified domain names. And DNS follows this strict hierarchy. And because public DNS is shared around the globe, we like to refer to this system as having a global hierarchy. In fact, the top level domains include country references. So for example, to enjoy a version of the Amazon.com domain tailored to India, you would simply type in www.amazon.in. In addition to the global hierarchy of the DNS name system, the organization of DNS servers throughout the world, they follow a global hierarchy. And the following DNS server types exist. So you have what is called the root DNS server. So these authoritative name servers serve the DNS root zone, and they are a network of hundreds of servers in many countries around the world. You have what is called the internal DNS servers, and these servers exist inside organizations to resolve the names of private hosts and servers within the organization. And these servers can also forward requests for outside resources to the appropriate external DNS servers when internal clients need to access external resources. You have what is called the external DNS servers. These servers reside outside an organization, typically on the public internet, and can resolve names of systems that are located outside the organization. And then you have the authoritative name servers. This DNS server is usually the last step in the journey for an IP address. The authoritative name server contains information specific to the domain name it serves. The authoritative name server is able to resolve queries thanks to the records that it contains. And a DNS server's database contains not only fully qualified domain names and corresponding IP addresses, but they also contain what are called DNS record types. And these are the various record types. So the first one you have is called an A record. And this is an address that maps a host name to an IP version 4 address. So you have an AAA record, and this is an IP version 6 record that maps a host name to an IP version 6 address. You have what is called the C name, or the canonical name, and this is an alias of an existing record, and it allows multiple DNS records to map to the same IP address. You have the MX record, or the mail exchange, and it maps a domain name to an email server for that domain. You have the NS record, or the name server, and it delegates a DNS zone to use the given authoritative name server. You got the PTR record, or the pointer record, and this points to a canonical name, and this is commonly used when performing what is called a reverse DNS lookup to determine what domain domain name is associated with a known IP address. The next record you have is called an SOA record, or a start of authority, and this provides authoritative information about DNS zones. It has email contact information for the zone's admin. It's the zone's primary name server, and the SOA also contains various refresh timers. You have the service record, or the SRV record, and the service record location is used for newer protocols instead of creating protocol-specific records such as the MX or the mail exchange records. Then you have the text record, and this is originally for arbitrary human-readable text in a DNS record, and this record contains machine-readable data, the RFC 1464, opportunistic encryption, the sender policy framework, and the DKIM, or the domain keys identified email. And here are some other DNS concepts that you need to be familiar with for the latest Network Plus exam. The first one is called a zone transfer. So because DNS servers will always need to be available to make the internet function, it is a common approach to use primary and secondary backup name servers. In order to keep the primary and secondary servers in sync with each other and updated with the same information, DNS zone transfers can be performed. There are multiple types of zone transfers, including full zone transfers and incremental zone transfers. And the next one you have is called the DNS time to live. Now, do not confuse DNS TTL with the TTL that is in an IP packet header. Whereas the TTL in an IP packet header, this is a loop prevention mechanism to ensure that a packet does not circulate endlessly on an IP network. The DNS TTL, this specifies the number of seconds a DNS server or client caches name resolution entries without having to perform a search of the DNS database. And as you might guess, there is a lot of DNS caching going on in the global DNS system, both on servers and on clients. This is why name resolution for popular destinations like Google.com appear to happen instantaneously. And as a side note, the caching of DNS resolution information, this is another reason changes in the global DNS system can take hours or even days to fully propagate. All the cached information must age out. That is, the TTL, it must expire, and then new information must be requested. And next we have what is called the forward lookup. So you might not have realized this, but when you have a DNS server resolve a name to an IP address, you are having the DNS server perform a forward lookup. And it is what DNS was essentially invented to perform. The next you have what is called the reverse lookup. And as you might have guessed, this is when the client has the IP address of the resource and needs the resolution to work in reverse. Essentially, the client is looking for the name that goes with the IP address. You have what is called a recursive lookup. In this type of DNS query, the client instructs the DNS server to respond with an answer if possible, and the client does not want to be referred to another DNS server. And then you have what is called an iterative lookup. In this type of DNS query, the client indicates that it will like the answer from the DNS server, or it will take a referral to another DNS server that might have the answer. Next, let's talk about NTP, or Network Time Protocol. And this is the final critical service that we're going to examine. And this protocol might be easy for you to overlook, or at least not think of as being very important. But for many reasons, it is actually very important that network devices possess times that are as accurate as possible. Perhaps the biggest reason is the fact that devices can then stamp syslog and other messages with the accurate time. And this can often be critical for helping you catch and prevent security attacks against your network, or for helping you troubleshoot faults that are occurring as a result of failed components or configurations. Another reason you typically need accurate time is that many services cannot properly integrate with other network services if the time is not within a certain threshold between the devices. In NTP, it does not require connection-oriented support, and as a result, NTP, it relies on UDP at the transport layer, and specifically NTP, it uses UDP port 123. And the configuration of NTP involves three main components. You have the client. So your network device is typically the NTP client and is consuming the correct time from an NTP server system. And then you have the server, and this is the network node that provides the correct time to NTP clients. And the most common servers these days, they are located regionally on the internet. And then you have what is called the stratum. So the stratum, this is an important value in NTP operations. It is like a hop count and measures how far the client is from the accurate time source. The larger the stratum value, the more chance the time on the client could be inaccurate because it is more hops away from the accurate time source. In this video, you are going to learn about corporate and data center architectures, such as the three-tiered network architecture, software-defined networking, and storage area networks. Let's talk about the three-tiered network architecture. So for a very long time now in networking, we have had the concept of building a network in tiers. Doing so allows you to separate the logical functions of the network and target the appropriate hardware and software at the correct areas. So for example, you do not want to consider a switch that is designed to permit users to access the network in the same way you would consider a switch for moving traffic through the core of the network. And we begin this video by examining one of the most classic and still used models for network architecture, which is called the classic three-tiered design. Now, perhaps the very first thing you need to understand about this model is that in addition to being called the classic or classical model, it is also referred to as the hierarchical network model. And whatever you call it, notice that it is built with three layers. You have the access layer, which is the layer closest to the end users. You have the distribution layer, and then you have the core layer. And different names are often used for these layers. So for example, the core layer might be called the backbone layer, and the distribution layer is often referred to as the aggregation layer. And finally, the access layer might be called the workstation or edge layer. And you can clearly see what is happening here. So engineers, they often use names that say more about what is happening at the various layers of the model. So let's go ahead and talk about the access or the edge layer. So the access layer, this ensures that authorized users can access the network with ease and in a high bandwidth fashion. So in addition to providing a guide for what equipment is appropriate at the access layer, the classic three-tiered model gives you a sense of what technologies are needed at certain layers. And devices that are commonly found at the access layer include the following. You have end-user devices such as laptops, desktops, tablets, and smartphones. And you have relatively inexpensive layer 2 switches, which are also called access layer switches, and then you have wireless access points. And then common technologies that are found at the access layer include the following: layer 2 switching, spanning tree protocol, power over Ethernet, VLAN technologies, quality of service functions, port security, and VLAN access control lists. And next we have the distribution or the aggregation layer. So a consistent trend in networking decade after decade has been the fact that more and more of the data that users need to access is located remotely. More and more traffic is being sent outside the local network infrastructure. And as cloud technology continues to take hold, remote data access will become even more common. The distribution layer is critical in the design of a network. This layer is responsible for connecting the access layer and the many devices inside it to the rest of the world and the valuable data that must be accessed. And at this layer, you typically find the following network devices. You'll find high-speed routers, high-speed multi-layer switches, firewalls, intrusion prevention devices, and proxy servers. Now, as a side note, network engineers often try to remove overhead from the access and core layers and add it to the distribution layer. And also, the distribution layer is famous for its use of the following technologies. It provides security, policy, routing, load balancing, redundancy, and summarization. Next, we have the core layer. So you've no doubt heard that three things are important when it comes to real estate: location, location, location. Well, when it comes to the core layer of the classic design, three things are important as well, and that is speed, speed, and more speed. So the core layer, this is responsible for moving massive amounts of data in an enterprise network, often between the data center and the main employee locations. And even in today's remote work environment, there are still core network devices that are crucial to a properly operating IT organization. And the core layer is home to very high-speed routers and multi-layer switches, or even high-speed layer 2 switches. And once again, remember that this is all about speed. So the following types of technologies are what you can find at the core layer. You'll find redundancy, bandwidth aggregation, and traffic policing and/or traffic shaping. And as a side note, most organizations are just just too small to really need a three-tiered model, and such organizations can often successfully implement a classic two-tier model, which is often referred to as a collapsed core design. And in this approach, the core and distribution layers are merged together for the sake of simplicity as well as cost savings. Next, let's talk about software-defined networking. So artificial intelligence and computers are not going to eliminate the need for humans in the network anytime soon. While software-defined networking allows you to add more and more automation and orchestration to a network, there will still be a need for you and your skills. Software-defined networking, which has been around for a very long time, is making a huge resurgence and being implemented in many parts of large and small networks today. So for example, consider your wireless LAN. Perhaps you are using lightweight access points and wireless local area network controllers. If so, you are seeing a very strict separation of the data layer from the management plane from the control layer. The wireless local area network controller, this is the primary control layer intelligence of the solution. And software-defined networking is changing the landscape of traditional networks. A well-implemented software-defined network allows the network administrator to implement features, functions, and configurations without the need to do command line configuration on the individual network devices. The front end that the administrator interfaces with can alert the administrator to what the network is currently doing, and then through the same graphical user interface, the administrator can indicate what he or she wants done. And behind the scenes, the software-defined network implements the detailed configurations across multiple network devices. And a key component in most software-defined networking solutions is a software-defined network controller. This appliance-based device is responsible for distributing control plane instructions to network devices downstream for configuration and management. So while many different approaches can be taken to software-defined networking, almost everyone agrees that the best strategy is to separate the network into different discrete planes or layers of operation. So let's talk about some of these layers. So the first one is the application layer. And this is where all the technology that involves the applications reside. Today, it is not uncommon for an application to be powered by tiny microservices running as containers in a heavily virtualized cloud environment. But of course, there are plenty of other options for powering this layer, and many of them can even be more traditional. And then we have what is called the control layer. Although this layer or plane of operation is often described as the quote-unquote brains of the operation, you are still the true brains of the operation. In fact, you are likely to use what is called a single pane of glass solution that provides the correct application programming interface, or API, that calls to the controller. And the controller turns these API commands into calls to the network devices in order to monitor or configure them properly. And the API calls to the controller, they are referred to as northbound operations, and the commands from the controller to the network devices, they are referred to as southbound operations. And the controller is always considered to be in the middle. And examples of control layer functions include routing and switching intelligence and common control layer protocols. They include Open Shortest Path First, or OSPF, Border Gateway Protocol, and Rapid Spanning Tree Protocol. And as a side note, northbound and southbound, or north to south traffic flows, are not the only descriptors for traffic flows in the software-defined networking environment. There are also eastbound and westbound traffic flows, or east-west traffic flows. Virtual machines and or containers, they communicate with each other over east-west flows, and this is the bulk of the traffic flow today. And the next layer is the infrastructure layer. So the infrastructure layer, this contains the hardware and software that powers the enterprise. In it, you'll often find legacy and dated technologies. And then we have what is called the management layer, and it is necessary to perform a lot of routine maintenance in the network. And the management plane, this is what takes care of a lot of those mundane tasks. But essentially, all the layers of operation are critically important, and each plays an important role. And the layers of operation, they work seamlessly together as one to get various jobs completed. Next, let's talk about what is called the spine and leaf. So the classic hierarchical model for building an enterprise network is excellent for building an enterprise network. But what about for different kinds of network locations in an organization, such as a data center? Certainly, different models might be more appropriate in a data center where traffic is different and traffic patterns are not always as expected. And different models are used for different network locations. And one that has become quite famous is called the spine and leaf topology or network model. And one of the reasons the spine and leaf topology has gained popularity in the data center is that vendors such as Cisco Systems, they rely on it for new technologies they are rolling out. Cisco created the application-centric infrastructure for software-defined networking in the data center. As its name directly communicates, the ACI takes a very application-centric, also known as a software as a service approach to the control and management of network design, bringing automation and orchestration to the software as a service engine of the private data center. And notice that this model consists of just two layers. You have the spine and then you have the leaf layers. And as a side note, some engineers call the spine layer the core layer or the backbone layer. So there is also no flexibility in how you connect the spine and leaf topology. Each leaf mode must connect to each spine mode, and that's it. The spine modes, they do not directly connect to each other, and the leaf nodes do not directly connect to each other as well. Rather, each leaf must connect to each spine. And this inflexibility brings several benefits. One, there is no doubt about how you should connect the equipment, so this leaves no room for doubt or experimentation. Also, there is completely predictable data pathing in the system. Virtual machines or containers are hosted on systems that connect to leaf nodes. When a virtual machine that connects to a leaf layer needs to communicate with another VM on the same leaf, it does not need to transmit to the spine layer. When a VM on one leaf needs to communicate to a VM on another leaf device, it is always one hop away, and there is exactly one spine device that must be transmitted. Another reason, the latency is predictable, due in large part to the predictability of the data patching. And then we have monitoring and expanding the topology is simple. So if you need to connect more hosts or hardware to connect more containers and VMs, you can just add a leaf device. If you need more overall bandwidth and processing power for the solution, you can just add a new spine. And as a side note, the Cisco ACI approach is actually a variation of an earlier technological approach called top-of-rack switching or end-of-rack switching. And in this design, multiple physical components act as one network device. So for example, with the end-of-rack switching design, there are physical switches in each data center rack for connectivity, but the control layer or the plane, intelligence, and the leaf switching engine are located at the end of a row of racks in the data center. This larger physical device is controlling the behavior of the distributed switches in the racks. They function logically as one big device. Specifically, the smaller switches in the racks act like line cards inserted in the chassis of a bigger and more powerful switch. And ACI functions similarly, with leaf nodes appearing to the solution as part of the spine devices. All right, next let's talk about storage area networks. So there are many approaches to storing data in networks today, including the following, such as network attached storage, directly attached storage, and storage area networks. And networks and systems supporting virtual servers, they commonly have network attached storage, where disk storage is delivered as a service over the network. As this approach evolved to include more efficiency and more features, the idea for a network dedicated to storing data was born. And so that leads us to a storage area network, which is a high-speed, very specialized network that is designed to store massive amounts of data and make that data available quickly when clients and or servers request it. Originally, fiber channel was the technology that ruled the storage area network space. Unlike Ethernet, fiber channel is designed for very low latency and guaranteed lossless connectivity. In contrast with UDP in an Ethernet environment, it is easy to contend with packet loss and delays. This is not the case in a storage area network environment. And to make storage area networks even more accessible and flexible, they began to be created to support Internet Small Computer System Interfaces, or iSCSI. And with iSCSI, which is an IP-based technology for network storage, a client using the storage is referred to as an initiator, and the system providing the iSCSI storage is called the iSCSI target. And networks that support iSCSI SCSI are often configured to support larger than normal frame sizes, and these frame sizes are referred to as jumbo frames. And overall, network convergence is often the goal today. So for example, voice and video and data networks are successfully combined today. These are very different types of communications that can all be sent over the same network. Converging different forms of traffic on a network extended to a storage area network to a local area network traffic thanks to a remarkable invention, and this is known as fiber channel over Ethernet. And just like it sounds, this technology allows Ethernet to encapsulate fiber channel frames and carry them over a high-speed Ethernet infrastructure. And modifications were made to the Ethernet standards for fiber channel over Ethernet to provide the level of service required in the storage area network for the fiber channel. And yes, fiber channel is spelled F-I-B-R-E, not F-I-B-E-R when we're talking about the other type of fiber. This fiber is spelled F-I-B-R-E. And as a side note, Ethernet needs to be truly high speed in order to have a chance at providing fiber channel over Ethernet services. In the Cisco implementations, 10 gigabits per second Ethernet is required for fiber channel over Ethernet. Now, this might sound crazy and too difficult to accommodate, but keep in mind that fiber channel over Ethernet is most commonly used in data centers when 10 gigabits per second and even 40 gigabits per second Ethernet links are becoming common. All right, finally, let's talk about deciding on an architecture. So many options are available in networking today, and this video only scratches the surface, discussing what you need to know for the Network Plus exam. And one of your first big decision points when designing modern networks has to do with the physical locations of your hardware and software. And early on, you are likely to find yourself choosing amongst the following options, such as branch office locations, hosting services, on-premise data center design, hosting services, co-location designs, where the services are hosting using your own equipment and the equipment of a provider, and cloud-based designs where you provide the data and everything else is provided by the cloud vendor. And a lot of factors are involved in this decision process, including levels of control, budgets, security, and IT staff expertise. In this video, you're going to learn about some of the most fundamental and critical topics in the vast field of cloud computing today, such as deployment models, service models, and key cloud concepts. All right, so let's go ahead and talk about deployment models. So virtualized services and solutions are often offered by service providers as cloud computing. And a company purchasing cloud computing services has several options to choose from. And the first option is called the private cloud. So private cloud services, they include systems that only have interactions and communications with other devices inside the same private cloud or system. Then you have what is called the public cloud. And public cloud services, they interact with devices on public networks, such as the internet and potentially other public clouds. And the three largest public cloud providers are Amazon Web Services, Microsoft Azure, and Google Cloud Platform. Next, we have what is called a hybrid cloud. So with hybrid cloud services, some private cloud services, they interact with public clouds. And then we have what is called a community cloud. So community cloud services, they are used by individuals, companies, or entities with similar interests. A community cloud is typically a partnership between many different cloud vendors or organizations. And an excellent example of a community cloud is cloud.gov in the United States. This community cloud provides a wide variety of services to employees of the U.S. government. And these services are offered in the community cloud by several different public cloud vendors. And when an organization requires scalability, or they want reduced costs, or they lack in-house administrative personnel trained in cloud technologies, and they have a complex network, a public cloud is the best deployment model to use. The advantages of using a public cloud include the following. You have lower infrastructure, maintenance, and administrative costs. It has greater hardware efficiency, reduced implementation times, and the availability of short-term usage. And when an organization needs to maintain strict control of business critical data, or is in a highly regulated business such as the financial industry, a private cloud is typically the best choice. A hybrid cloud environment, this is the best choice when an organization offers services that need to be configured for diverse vertical markets or has varying needs. In hybrid clouds, they are also ideal for organizations migrating to public clouds because they can ensure interoperability and efficiencies across the different environments. And then you have the community cloud option, and this is best suited for organizations that want to increase cross-organizational or collaborative processes when in-house implementation is not possible due to conditions such as geographically dispersed participants, fluctuating resource requirements, or resource limitations. All right, next let's talk about various cloud service models. So cloud services are typically offered using one of several quote-unquote as-a-service models, which are usually offered on a pay-as-you-go basis. And this is similar to the model used with utilities in the home, such as you paying your electricity or your internet bill. In the following, these are a few of the service models that are available as part of the cloud computing infrastructure. So the first one is called infrastructure as a service. So with infrastructure as a service, the company rents virtualized servers, which are hosted by a service provider and runs specific applications on those servers. Next, you have what is called software as a service. So with software as a service, the details of the server are hidden from the customer, and the customer's experience is similar to the experience of using a web-based application. And then you have what is called platform as a service. So platform as a service, it provides a development platform for companies that are developing applications and want to focus on creating the software without having to worry about the servers and infrastructure that are being used for that development. Now, as a side note, there are countless as-a-service designations that have been established. So for example, you have what is called desktop as a service, and this refers to cloud-hosted operating system desktops that are made available to cloud clients. And then you have the term called everything as a service, and this is often used to describe the vast array of cloud services available now that the use of cloud approaches has exploded in popularity. And to provide a visual representation of the various service models, you can use this diagram right here. So the first one describes enterprise, or essentially if you are managing everything in your enterprise, you will be in charge of all of this stuff right here. When you're dealing with infrastructure as a service, this is the stuff that you will be in charge of managing: the operating systems, the database security applications, and your service provider, they will be responsible for everything else. Platform as a service, all the gray is what the service provider or your cloud provider is responsible for, and you would only be responsible for the applications. Software as a service, the service provider does everything for you. And an example of this, you could think of Google Drive or Adobe Creative Cloud. Those are software as a service where essentially all you do is log in, you get access to whatever application you're using, and you don't have to worry about any of the storage or the cloud infrastructure and none of that stuff. You just log in and do what you do. And if you're still lost and confused as to how cloud service models work, hopefully this diagram, which is called pizza as a service, hopefully this will help it make more sense to you. So when the traditional, the on-premise, this is essentially you cooking pizza from scratch at the house. You're responsible for all the ingredients, the electricity, the oven, the dining room table, etc. Infrastructure as a service is equivalent to take and bake, or you going into the grocery store to get a frozen pizza, and then you bringing it back home to fire it up, cook it, and then sit down and eat it. Platform as a service, this is delivery, you ordering Papa John's or Pizza Hut or something like that. And then software as a service, this is you actually going out to a restaurant and ordering pizza and eating the pizza in the restaurant. So essentially that is pizza as a service to hopefully make this cloud service model thing make sense for you. All right, next let's go ahead and talk about some key cloud concepts. And the first one we're going to talk about is called infrastructure as code. So one of the most exciting developments in technology today is infrastructure as code. And when your infrastructure is in the cloud, is all virtualized, it can be easily created and destroyed, as well as maintained by using scripts or code. And this makes it possible for you to spin up test environments or pilot tests with ease. So think about how much easier it is to create a duplicate site for high availability needs when using infrastructure as a service and infrastructure as code than when using physical devices. And the large public cloud providers, they make it simple for you to implement infrastructure as a code. They provide tools such as CloudFormation from Amazon Web Services that permit you to easily generate the code required to script the creation of useful and even complex infrastructures. And thanks to this capability, you can easily automate and even orchestrate orchestrate common networking tasks that used to take weeks or months to carry out. So for example, say that you need to spin up 50 servers for a test project. Thanks to infrastructure as a code, you can now do this with a few clicks of a mouse instead of using massive and often expensive deployment of physical servers. And there is a difference between automation and orchestration. Automation simply refers to the automated completion of a task or task. Orchestration refers to the scheduling and monitoring of many different automations. It is basically automating the automation. And as a side note, infrastructure as a service is also known as programmable infrastructure to indicate that the infrastructure configuration can be incorporated into application code. Infrastructure as a service enables DevOps teams to test applications in product-like environments from the beginning of the development cycle. The next concept we're going to talk about is connectivity options. So as more and more technology has appeared in the cloud in both public and private, secure connectivity has become crucial. Secure protocols such as HTTPS, TLS, and SSH are necessary when accessing most cloud resources. Fortunately, massive cloud providers such as AWS, they make it simple to securely connect using a wide variety of methods, including hardware, virtual private network applications located at your corporate or home office. Although your applications and servers might be sharing physical equipment with other customers of AWS, great pains are taken to ensure that this multi-tenancy does not come at the cost of security. And AWS and large public cloud providers, they even go a step further, allowing customers to purchase AWS Direct Connect circuits. These circuits are private, dedicated lease lines directly into the AWS infrastructure. When you use AWS Direct Connect, your traffic does not commingle with that of other AWS customers or other internet users at all. Now, of course, these types of connections can be very expensive. All right. The next concept we're going to talk about is called multi-tenancy. So if you ask engineers why they are hesitant to move to the public cloud, they are likely to say that they are worried about security. When they react this way, it is almost always because they are thinking about multi-tenancy. And this is a fancy term for the fact that the physical servers in public cloud infrastructure are hosting workloads from many different customers. Your virtual machines might be located on exactly the same physical server as the virtual machines of your biggest competitor. And multi-tenancy requires you to have a great faith that the cloud provider has done an excellent setup of security to ensure that the virtual machines of one customer are completely hidden from other customers. Now, as a side note, when you have the money to spend and need the certainty, you can purchase a fully dedicated hosting solution. In such a situation, the cloud provider leases to you your own dedicated hardware in their cloud, and this hardware is not shared with other customers. All right, next concept we're going to talk about is called elasticity. So elasticity, this is another extremely compelling reason to move to the cloud. Elasticity means that a cloud solution can scale up or down or in or out as needed based on demand. And scaling up or down means adding or subtracting resources to provide larger or smaller systems. And scaling in or out, this refers to allowing systems to clone themselves or terminate themselves as needed. Now, as a side note, the National Institute of Standards and Technology, or NIST, they include rapid elasticity as one of the 5 key characteristics that define what cloud truly means. The other 4 characteristics are on-demand self-service, broad network access, resource pooling, and measured service. Now, getting back to elasticity, when your cloud offers you rapid elasticity, and it should, your network infrastructure and services offered can grow and shrink along with demand. This is incredibly exciting for many reasons, but perhaps the 2 biggest reasons are the fact that you do not have to worry as much about your infrastructure failing under a large load, and you do not have to worry about over-provisioned resources when demand is low. All right. And the final concept we're going to talk about is called cloud security. So your public cloud provider will most likely make it very clear to you that your cloud security with a public cloud is a shared responsibility model. So for example, AWS will secure your virtual machine from other customers' virtual machines, but it is up to you to properly secure the operating system inside the virtual machine, and it is your responsibility to control access to and from the virtual machine. And here are just some of the main security concerns with moving to the cloud. So some of those concerns concerns are going to be data breaches, account hijacking, insider threats, malware injection, abuse of cloud services, insecure APIs, DOS attacks, and insufficient due diligence. Now, as a side note, a lot of these concerns, they can apply to non-cloud environments as well. In this video, you are going to learn about various networking devices such as hubs, bridges, routers, wireless LAN controllers, load balancers, cable modems, DSL modems, VPN headends, proxy servers, and firewalls. All right, so let's talk about the first networking device, which is a hub. So an Ethernet hub, it lives at layer 1 of the OSI model. And as a result, a hub does not make forwarding decisions. Instead, a hub receives bits on one port and then retransmits those bits out to all other ports, that is, all ports on the hub other than the port on which the bits were received. And hubs are most often connected to other network devices via UTP cabling. However, some early versions of Ethernet hubs prior to the popularization of Ethernet switches, they supported fiber optic connections. And the three basic types of Ethernet hubs are as follows. You have what is called a passive hub, and this type of hub does not amplify or electrically regenerate received bits. You have an active hub. This type of hub regenerates incoming bits as they are sent out all the ports on a hub other than the port on which the bits were received. And then you have what is called a smart hub, and the term smart hub implies an active hub with enhanced features such as support for SNMP or Simple Network Management Protocol. And a significant downside to hubs, and this is the main reason they have largely been replaced with switches, is that all ports on a hub belong to the same collision domain. And a collision domain, this represents an area on a local area network on which there can only be one transmission at a time. Because multiple devices can reside in the same collision domain, as in the case with multiple PCs connected to a hub, if two devices transmit at the same time, those transmissions collide and have to be retransmitted. Now, because of the collision domain issue and the inefficient use of bandwidth, that is, bits being sent out all ports rather than only the port needing the bits, hubs are rarely used in modern local area networks. However, they are an important piece of history of Ethernet networks and share some of the characteristics of different areas of modern Ethernet networks. So, for example, a wireless access point is much like a hub in that all the wireless devices associated with the access point belong to the same collision domain. And in this picture right here, you will notice that the PCs depicted are interconnected using an Ethernet hub, but they are all in the same collision domain. And as a result, only one of the connected PCs can transmit at any one time. This characteristic of hubs can limit the scalability of hub-based local area networks. Now, keep in mind that all the devices on a hub belong to the same broadcast domain, which means that a broadcast sent into the hub will be propagated out all the ports on the hub other than the port on which the broadcast was received. Next networking device we have is called a bridge. So a bridge joins two or more local area network segments, typically two Ethernet LAN segments. And each LAN segment is in a separate collision domain. And as a result, an Ethernet bridge can be used to scale Ethernet networks to a larger number of attached devices. And unlike a hub, which blindly forwards received bits, a bridge, specifically an Ethernet bridge, makes intelligent forwarding decisions based on the destination MAC address in a frame. Specifically, a bridge analyzes source MAC address information on frames entering the bridge and populates an internal MAC address table based on the learned information. Then, when a frame enters the bridge destined for a MAC address known by the bridge's MAC address table to reside off a specific port, the bridge can intelligently forward the frame out the appropriate port. Because a bridge makes forwarding decisions based on layer 2 information, such as MAC addresses, a bridge is considered to be a layer 2 device. And although a bridge segments a LAN into multiple collision domains, that is one collision domain per bridge port, all ports on a bridge belong to the same broadcast domain. And to understand this concept, think about the destination MAC address in a broadcast frame. At layer 2, the destination MAC address of a broadcast frame is FFFF.FFFF.FFFF in hexadecimal notation. Also recall that a bridge filters frames, that is, it sends frames frames only out necessary ports if the bridge has previously learned the destination MAC address table. Because no device on the network will have the MAC address FFF.FFF, etc., the bridge will never enter that MAC address into its MAC address table. And as a result, broadcast frames are flooded out all bridge ports other than the port that received the frame. Also, bridges were popular in the mid to late 1980s and early 1990s, but they have largely been replaced with switches due to price, performance, and features. And from a performance perspective, a bridge makes its forwarding decisions in software, whereas a switch makes its forwarding decisions in hardware using application-specific integrated circuits. And not only do these ASICs help reduce the cost of switches, they enable switches to offer a wider array of features such as VLANs, trunks, port mirroring, power over Ethernet, power over Ethernet Plus, and 802.11 authentication. Next, let's talk about a router. So a router, this is a layer 3 device, which means it makes forwarding decisions based on logical network address information, such as an IP address. Although a router is considered to be a layer 3 device, like a multi-layer switch, it has the capability to consider higher level traffic parameters, such as quality of service settings, in making forwarding decisions. Next, let's talk about an access point. So wireless access points allow wireless clients to gain access to a wired network by communicating via radio waves with a wireless access point. And the access point can then be hardwired to a local area network. Wireless LANs include multiple standards that support various transmission speeds and security features. However, you need to understand at this point that all wireless devices connecting to the same access point are considered to be on the same shared network segment, which means that only one device can send data to and receive data from an access point at any one time. Next, we have what is called a wireless LAN controller. So access points tend to come in two major types. You got autonomous and lightweight. And lightweight access points do not have the control plane intelligence built in to perform their functions for the network. These devices are controlled by wireless local area network controllers, or WLCs. And WLCs are specialized network devices that permit the central control and management of large numbers of lightweight access points. WLCs, they simplify the administration of your access points, and they can also assist you dramatically in the monitoring and ongoing maintenance of the wireless infrastructure. Next, we have what is called a load balancer. So load balancers are important specialized network devices that can assist with performance and high availability of key network devices and services. So for example, a load balancer can sit in front of a fleet of web servers in a data center. When a large volume of requests come in from clients for the content of those web servers, the load balancer can ensure that the requests are intelligently distributed to the web servers. Often this intelligent distribution can be based on the resources available for each web server, and more requests can be sent to those web servers that have the most available resources of the group. And as you might expect, the load balancer can also check the health of the nodes periodically and intelligently prevent the forwarding of web requests to servers that are being overwhelmed. Next, we have a cable modem. So as discussed in previous videos, cable television companies have a well-established and wide-reaching infrastructure for television programming. These companies can designate specific frequency ranges from upstream and downstream data transmission, and a device located in a residence or a business that can receive and transmit in those data frequency ranges. This is known as a cable modem. In this picture right here on your screen, it shows a typical cable modem that you might find in a small SOHO environment today. Next, we have the DSL modem. So if you recall from previous videos that an alternative to cable high-speed internet is called DSL, or digital subscriber line. While this technology is getting harder and harder to find in today's WAN environments, you may discover it at a SOHO location or a remote branch. In such a case, a DSL modem is the local device that makes the data transfers possible. Next, we have what is called a VPN head-in. So companies with locations spread across multiple sites often require secure communications between those sites. One option is to purchase multiple wide area network connections to interconnect those sites. Sometimes, however, a more cost-effective option is to create source connections through an untrusted network such as the internet. In such a secure tunnel, this is called a virtual private network, or a VPN. And depending on the VPN technology that's being used, the devices that terminate the ends of a VPN tunnel might be required to perform perform heavy processing. So for example, consider a company headquarters location with VPN connections to each of 100 remote sites. The devices at the headquarters terminating these VPN tunnels might have to perform encryption and authentication for each tunnel, resulting in a heavy processor burden on that device. Now, although several router models can terminate a VPN circuit, a dedicated device called a VPN head-in or a VPN concentrator can be used instead. In the VPN head-in device, this performs the processor-intensive process required to terminate multiple VPN tunnels. And the term encryption, this refers to the capability of a device to scramble data from a sender in such a way that the data can be unscrambled by the receiver, but not by any other party that might try to intercept the data. Because a VPN concentrator is able to encrypt data, it is considered to belong to a class of devices called encryption devices, which are devices such as routers, firewalls, and VPN concentrators that are capable of participating in an encrypted session. Next, let's talk about a proxy server. So some clients are configured to forward their packets, which are seemingly destined for the internet, to a proxy server. The proxy server receives the client's requests, and on behalf of that client, which is also known as the client's proxy, the proxy server sends the request out to the internet. When a reply is received from the internet, the proxy server forwards the response onto the client. Now, what possible benefit could come from such an arrangement? Well, security is one benefit, specifically because all requests going out to the internet are sourced from the proxy server. The IP addresses of the network devices inside the trusted network, they are also hidden from the internet. Yet another benefit could come in the form of bandwidth savings because many proxy servers perform what is called content caching. So for example, without a proxy server, if multiple clients all visited the same website, the same graphics from the home page of the website will be downloaded multiple times. However, with a proxy server performing content caching, when the first client navigates to a website on the internet and the internet-based web server returns its content, the proxy server not only forwards this content to the client requesting the web page, but it also stores a copy of the content on its hard drive. Then, when a subsequent client points its web browser to the same website, after the proxy server determines that the page has not changed, the proxy server can locally serve up the content to the client without having to once again consume internet bandwidth to download all the graphic elements from the internet-based website. And as a final example of a proxy server benefit, some proxy servers can perform content filtering to restrict clients from accessing certain URLs. So for example, many companies use content filtering to prevent their employees from accessing popular social networking sites and to promote productivity. Now, as a side note, a reverse proxy, this receives requests on behalf of a server and replies back to the clients on behalf of those servers. In reverse proxies, they can also be used with load balancing and caching to better utilize a group of servers, providing scalability and high availability. Next, let's talk about a firewall. So a network firewall, this is most often implemented as a network security appliance. And as depicted in this picture right here, a firewall essentially stands guard at the door of your network, protecting it from malicious traffic. And so for example, you have what is called a stateful firewall. And this allows traffic to originate from an inside network or a trusted network and go out to the internet or the untrusted network. And likewise, return traffic coming back from the internet to the inside network is allowed by the firewall. However, if traffic originates from a device on the internet that is not returning traffic, then the firewall will block that traffic. And finally, we're going to go ahead and just kind of do a quick summary of the network devices that we discussed. So the first one we talked about is a hub, and this connects devices on an Ethernet twisted pair network. The hub does not perform any tasks besides signal regeneration. It just simply forwards data to all nodes that are connected to it. You have what is called the bridge. It connects two network segments. It operates at the data link layer, and it filters, forwards, or floods an incoming frame based on a packet's MAC address. Then you have the router. This connects networks. It uses software configured network addresses to make forwarding decisions. You have access points. They are used to create a wireless LAN and to extend a wired network. And it uses wireless infrastructure network modes to provide a connection point between wireless LANs and a wired Ethernet local area network. We also talked about a wireless LAN controller, and this is used with branch or remote office deployments deployments for wireless authentication. So when an access point boots, it authenticates with a controller before it can start working as an access point. You have a load balancer. This distributes a network's load, and load balancing, it increases redundancy and performance by distributing the load to multiple servers. We talked about modems. This modulates digital signals into analog at the sending end and then performs the reverse function at the receiving end. You have a VPN head-end. This increases remote access security and establishes secure connections or tunnels between sending and receiving network devices. And then we got a firewall. This provides controlled data access between networks. It can be hardware or software based, and this is an essential part of a network security strategy. In this video, you are going to learn about layer 2 switches and layer 3 capable switches. All right, so let's talk about the layer 2 switch. So like a bridge, a switch, in particular a layer 2 Ethernet switch, can dynamically learn the MAC addresses attached to various ports by looking at the source MAC addresses of frames coming into a port. So for example, if switch port gigabit Ethernet 11 received a frame with source MAC address DDD, D.DDD, etc., the switch could conclude that MAC address DDDD, etc. resides off port gigabit Ethernet 11. In the future, if the switch receives a frame destined for MAC address DDDD, etc., the switch would only send that frame out port gigabit Ethernet 11. Initially, however, a switch is unaware of what MAC addresses reside off which ports unless MAC addresses have been statically configured. Therefore, when a switch receives a frame destined for a MAC address not yet present in the switch's MAC address table, the switch floods that frame out all the switch ports except the port on which the frame was received. Similarly, broadcast frames or frames with destination MAC addresses FFFF, etc. are always flooded out all switch ports except the port on which the frame was received. And as discussed in previous videos where we talked about bridges, the reason broadcast frames are always flooded is that no endpoint will have the MAC address FFFF.FFFF.FFFF, which means that the FFF.etc. MAC address will never be learned in a switch's MAC address table. And to illustrate how a switch's MAC address table becomes populated, consider an endpoint named PC1 that wants to form an SSH connection with a server. Also assume that PC1 and its server both reside on the same subnet. That is, no routing is required to get traffic between PC1 and its server. Before PC1 can establish an SSH session to its server, PC1 needs to know the IP address or the layer 3 address and the MAC address, which is the layer 2 address of the server. Now, the IP address of the server is typically known or resolved via the DNS or the domain name system lookup. And in this example, we're going to assume that the server's IP address is already known. Now, to properly form an SSH segment, however, PC1 needs to know the server's layer 2 MAC address. If PC1 does not already have the server's MAC address in its address resolution protocol or the ARP cache, then PC1 can send an ARP request in an attempt to learn the server's MAC address. Now, when switch SW1 sees PC1's ARP request enter port gigaport 01, PC1's MAC address AAAA.AAA. etc. This is added to switch SW1's MAC address table. Also, because the ARP request is a broadcast, its destination MAC address is going to be FFFF.FF, etc. Now, because the MAC address FFF.FFF, etc. is not known to switch SW1's MAC address table, switch SW1 floods a copy of the incoming frame out all switch ports other than the port on which the frame was received. Now, when switch SW2 receives the ARP request over its gig01 trunk port, the source MAC address AAAA.AAA, etc. is added to the switch's SW2's MAC address table. Also, using behavior similar to that of SW1, switch SW2 floods the broadcast, and the server receives the ARP request and responds with an ARP reply. Unlike the ARP request, the ARP reply frame is not a broadcast frame. The ARP reply in this example has a destination MAC address of AAAA.AAAA, etc., which makes the ARP reply a unicast frame. And upon receiving the ARP reply from the server, switch SW2 adds the server's MAC address, bb.bb, etc., to its MAC address table. Also, the ARP reply is only sent out gigaport 01 because switch SW1 knows that the destination MAC address, AA, etc., is available off of port gigaport 01. Now, when receiving the ARP reply on this gigaport 02 port, switch SW1 adds the server's MAC address, etc., to its MAC address table. Also, like switch SW2, switch SW1 now has an entry in its MAC address table for the frame's destination MAC address, etc. Therefore, switch SW1 forwards the ARP reply out port gigaport 01 to the endpoint of PC1. Next, after receiving the server's ARP reply, PC1 knows the MAC address of the server. Therefore, PC1 can now properly construct an SSH segment destined for the server. And then switch SW1, it now has the server's MAC address, etc. in its MAC address table. Therefore, when switch SW1 receives the SSH segment from PC1, that segment is now forwarded out of switch SW1's gigaport 02 port. And with behavior similar to that of switch SW1, switch SW2 forwards the SSH segment out of its gigaport 02 port. This forwarding is possible because switch SW2 has an entry for the segment's destination MAC address, etc. in its MAC address table. And then finally, the server responds to PC1, and a bidirectional SSH session is established between PC1 and the server. Because PC1 learned the server's MAC address as a result of its early ARP requests and stored that result in its local ARP cache, the transmission to subsequent telnet segments does not require additional ARP requests. However, if unused for a period of time, entries in the PC's ARP cache can time out. Therefore, the PC would have to broadcast another ARP frame if it needed to send traffic to the same destination IP address. And the sending of the additional ARP frames, this adds a small amount of delay when reestablishing a session with that destination IP address. Next, let's talk about a layer 3 capable switch. So whereas a layer 2 switch makes forwarding decisions based on MAC address information, a multi-layer switch can make forwarding decisions based on upper layer information. So for example, a multi-layer switch could function as a router and make forwarding decisions based on destination IP address information. Now, some literature refers to a multi-layer switch as a layer 3 capable switch because of the switch's capability to make forwarding decisions like a router. And the term multi-layer switch is more accurate, however, because many multi-layer switches have policy-based routing features that allow upper layer information, such as application port numbers, to be used in making forwarding decisions. And this picture here on your screen, this makes the point that a multi-layer switch can be used to interconnect not just network segments, but entire networks. And remember that logical layer 3 IP addresses are used to assign network devices to different logical networks. For traffic to travel between two network devices that belong to different networks, that traffic must be routed. That is, a device such as a multi-layer switch has to make forwarding decisions. And as on a layer 2 switch, each port on a multi-layer switch represents a separate collision domain. However, a characteristic of a multi-layer switch and a router is that it can become a boundary of a broadcast domain. Although all ports on a layer 2 switch belong to the same broadcast domain, if configured as such, all ports on a multi-layer switch can belong to a different broadcast domain. In this video, you are going to learn about intrusion detection and prevention. All right, let's talk about intrusion detection and prevention. So when an attacker launches an attack against a network, intrusion detection system and intrusion prevention system technologies are often able to recognize the attack and respond appropriately. Attacks might be recognizable by comparing incoming data streams against a database of well-known attack signatures. Other mechanisms for detecting attacks include policy-based and anomaly-based approaches. In addition to dedicated network-based intrusion prevention system sensors, or NIPS, IPS software can be installed on a host to provide a host-based intrusion prevention system, or HIPS, or host-based intrusion detection system solution, also known as heads. All right, let's talk about intrusion detection system versus intrusion prevention systems. So both IDS and IPS devices, they can recognize network attacks, and they differ primarily in their network placement. Specifically, where an IDS device receives a copy of traffic to be analyzed, an IPS device resides in line with the traffic. And because the analyzed traffic does not flow through the IDS device is considered to be passive, and the IPS device is considered to be active. And both the IDS and IPS devices can send alerts to, for example, a management station. And although an IDS device can also communicate with a security appliance or a router to prevent subsequent attack packets, the initially offending traffic reaches its destination. Conversely, an IPS device can drop the traffic in line, thus preventing even the first malicious packet from reaching its intended target. And the previous information of IDS versus IPS devices might seem to suggest that IPS devices should always be used instead of IDS devices. However, in some network environments, these two solutions complement one another. So for example, an IDS device can add value to a network that already employs an IPS device by verifying that the IPS device is still operational. And the IDS device might also identify suspicious traffic and send alerts about that traffic without having the IPS device drop the traffic. All right, next let's talk about IDS and IPS device categories. So IDS and IPS devices, they can be categorized based on how they detect malicious traffic. Alternatively, IPS devices can be categorized based on whether they run on a network device or on a host. And the first category we're going to talk about is the signature-based detection. So the primary method used to detect and prevent attacks using IDS or IPS technologies is signature-based. And a signature could be a string of bytes that in a certain context triggers detection. So for example, attacks against a web server typically take the form of URLs. Therefore, URLs could be searched for a certain string that would identify an attack against a web server. As another example, the IDS or IPS device could search for a pattern in the MIME header of an email message. However, because signature-based IDS IPS is, as the name suggests, based on signatures, the administrator needs to routinely update the signature files. All right, the next category is called policy-based detection. So another approach to IDS IPS detection is policy-based, and with a policy-based approach, the IDS IPS device needs a specific declaration of the security policy. So for example, you could write a network access policy that identifies which networks can communicate with other networks. The IDS IPS device could then recognize an out-of-profile traffic that does not conform to the policy and report that activity. Policy-based detection could also identify unencrypted channels and plain text credentials in insecure protocols such as Telnet, SNMP version 1, HTTP, FTP, and TFTP, and secure protocols such as SSH, SNMP version 3, TLS, SSL, HTTPS, SFTP, and IPsec should be used when possible to protect the confidentiality of the data flows across that network. And then finally, we have what is called anomaly-based detection. So a third approach to detection or preventing malicious traffic is anomaly-based. This approach is prone to false positives because a normal condition is difficult to measurably define. However, there are a couple of options for detecting anomalies. The first one is called statistical anomaly detection. And this approach involves watching network traffic patterns over a period of time and dynamically building a baseline. Then if traffic patterns significantly vary from the baseline, an alarm can be triggered. The next one is called non-statistical anomaly detection. And this approach allows an administrator to define what traffic patterns are supposed to look like. However, imagine that Microsoft releases a large update for its Windows 10 operating system, and your company has hundreds of computers that are configured to automatically download that service pack. If multiple employees turn on their computers at approximately the same time tomorrow morning, and multiple copies of the service pack simultaneously start to download the service pack, the IDS IPS device might consider the traffic pattern to be significantly outside the baseline. And as a result, the non-statistical anomaly detection approach could lead to a false positive or an alarm being triggered in the absence of malicious traffic. However, anomaly-based IPSs may be able to indicate abnormal behavior compared to the baseline of normal activity, which could assist you in discovering a new type of attack that is being used against your network. And this is called a zero-day attack. And this is basically an attack that exploits a previously unknown vulnerability. In this video, you're going to learn about various network devices. All right, so let's talk about voice over IP protocols and components. So a voice over IP enabled network, it digitizes speech into packets and transmits those packets across a data network. This allows voice, data, and even video to share the same medium in a network with unified communication, such as voice, video, and data. Specialized unified communication servers, controllers, devices, and voice gateways are also likely to be used. In a cloud computing environment, they may be virtualized as well, and not only can a VoIP network provide significant cost savings over a traditional PBX solution, many VoIP networks offer enhanced services such as integration with voice video applications and calendaring software to determine availability that is not found in traditional corporate telephony environments. All right, so let's talk about some of the VoIP network elements. And the first one is the IP phone. So an IP phone, this is a telephone with an integrated Ethernet connection. Although users speak into a traditional analog handset or headset on the IP phone, the IP phone digitizes the user's speech, packetizes it, and sends it out over a data network via the IP phone's Ethernet port. And while an IP phone is a common example of a VoIP endpoint, an alternative is software running on a computer. And then we have what is called the call agent. And this is a repository for a VoIP network's dial plan. So for example, when a user dials a number from an IP phone, the call agent analyzes the dial digits and determines how to route the call towards the destination. The next element is called the gateway. So a gateway in a VoIP network, this acts as a translator between two different telephony signaling environments. And then we have what is called the PBX, and that stands for Private Branch Exchange. And this is a privately owned telephone switch traditionally used in corporate telephony systems. Although a PBX is not typically considered a VoIP device, it connects into a VoIP network through a gateway. And then we have what is called an analog phone, and this is a traditional telephone like the ones you may find in people's homes. Even though an analog phone is not typically considered a VoIP device, it can connect to a VoIP network by way of a VoIP adapter, which you're looking at on your screen right here, and that VoIP adapter is connected to the VoIP network. And the next element is called Session Initiation Protocol. And this is a signaling, setup, and management protocol used with voice and video sessions over IP networks. And SIP, in conjunction with other protocols, specifies the encoder and decoder, also known as the codec, that will be used for voice and video connections over the network. And then the final element is called RTP, and that stands for Real-Time Transport Protocol. And this is a protocol that carries voice and interactive video. All right, next, let's talk about network printers. So while network printers were once considered gems of convenience for the office environment, they were not contemplated for home or small offices for many years. Today, it is rare to find a printer that does not have networking capabilities, and printers that are used in home or small offices, they are typically wireless and are extremely easy to use on a network. Next type of network device is the physical access control devices. So in high security environments, there are typically many network devices that help control and monitor physical access. And devices that might be included in this category of physical access control devices include the following. You have an access control panel, which is also known as a controller. You have an access control vestibule or a man trap, such as a door, a turnstile, a parking gate, an elevator, or some other physical barrier. You have a reader that's installed near an entrance. You have locking hardware such as electric door strikes and electromagnetic locks. You have a magnetic door switch for monitoring door positions. And you have what are called request to exit devices for allowing egress. Next, let's talk about IP cameras. So today, many networks use cameras for monitoring and or security. And these cameras, which are called IP cameras, are digital video cameras that receive control data and send image data via an IP network. They are commonly used for surveillance, but unlike analog CCT or closed circuit television cameras, they require no local recording device, only a local area network. And most IP cameras are webcams, but the term IP camera or a net cam, they usually apply to only cameras that can be directly accessed over a network connection, and they are usually used for surveillance.
Next, let's talk about heating, ventilation, and air conditioning sensors. So HVAC, this is the technology you most likely appreciate every single day for your indoor and vehicular environmental comfort. And the goal of HVAC systems is to provide thermal comfort and acceptable indoor air quality. HVAC devices are frequently connected to networks and modern enterprise infrastructures, and providing connectivity to the HVAC system through an HVAC sensor is extremely beneficial from a maintenance and configuration standpoint. In addition, such connectivity is also of huge benefit when it comes time to carefully monitor the system and compile monitoring data in a central location for any analysis that might be required. All right, next let's talk about some of the technologies of the Internet of Things. So many wireless technologies are technologies related to wireless. They come into play to make the Internet of Things a reality. And IoT, this refers to the trend today to connect everyday objects to the internet in order to make them quote unquote smart. And smart devices, they are all over the place these days, and they include refrigerators, smart speakers, thermostats, and smart doorbells, etc. Now, you should be aware of the following key technologies to help make the modern IoT a reality. And the first one we're going to talk about is called Z-Wave. And this is a wireless communications protocol that is used primarily for home automation. It is a mesh network using low energy radio waves to communicate from appliance to appliance. And Z-Wave is used with devices such as lighting control systems, security systems, thermostats, windows, locks, swimming pools, garage door openers, and a whole bunch of other stuff. Next, we got what is called N10-008. So this is a wireless protocol for monitoring sensor data such as a person's heart rate or a car's tire pressure, as well as for controlling systems such as indoor lighting and entertainment appliances such as televisions. And N10-008 is designed and maintained by the N10 Alliance, which is owned by the company called Garmin. Next, we have Bluetooth, and this is a wireless technology that allows devices to communicate over a short distance. And Bluetooth is often used to create personal area networks, and it also enables communications for the IoT. Next, we have what is called NFC, or near field communication. And this is a set of communication protocols that enables two electronic devices to transfer information. Typically, one of these devices is a portable device such as a smartphone. And NFC devices, they must be close to each other within 4 centimeters. And NFC devices are used in contactless payment systems, such as with credit cards and electronic ticket smart cards, and allow mobile payment to replace or supplement these systems. Next one we have is called infrared, and this is another wireless technology that permits data transmission over short ranges amongst computer peripherals and personal digital assistants. These devices usually conform to standards published by the IRDA, or the Infrared Data Association. And remote controls and IRDA devices, they use infrared LEDs, or light emitting diodes, to emit infrared radiation that is focused by a plastic lens into a narrow beam. Next one we have is called RFID, or radio frequency identification. And this uses electromagnetic fields to automatically identify and track tags attached to objects. The tags contain electronically stored information. And then you have what is called a passive tag. And this collects energy from a nearby RFID readers interrogating radio waves. And then you have what is called an active tag. And this has a local power source, such as a battery, and may operate at hundreds of meters from the RFID reader. Unlike with a barcode, an RFID tag doesn't need to be in the line of sight of the reader, so it may be embedded in the tracked object. And the next we have the IEEE 802.11, and this is a set of media access control and physical layer specifications for implementing wireless local area network computer communication in the 900 megahertz, 2.4 gigahertz, 3.6, 5, 6, and 60 gigahertz frequency bands. Now, obviously, these technologies play a great role in the IoT because many appliances and common objects, they communicate over the 802.11 wireless signals to reach a main hub.
And then finally, we're going to talk about the industrial control systems and supervisory control and data acquisition, also known as ICS SCADA. So a SCADA system, this is used to control remote equipment and to monitor that equipment. It might be a part of the industrial control system or the ICS that is used to manage a power plant or a water treatment facility. And network devices like these with distributed control systems may have devices such as programmable logic controllers and remote terminal units that are proprietary and may require specialized training to learn and troubleshoot. In this video, you are going to learn about the basic routing process. So in previous videos, you learned how internet protocol networks can be divided into subnets, and each subnet is its own broadcast domain, and the device that separates broadcast domains, this is known as a router, or is also known as a multi-layer switch. And a multi-layer switch, this is a network device that can perform the layer 2 switching of frames, as well as the layer 3 routing of IP packets. And multi-layer switches, they generally use dedicated chips to perform those functions, and as a result, they may be faster than traditional routers in the forwarding of packets. Now, for traffic to flow between subnets, the traffic has to be routed. This routing is a router's primary job, and the next few videos of this section are going to discuss how routing occurs and introduce a variety of approaches for performing routing, including dynamic routing, static routing, and default routing. And this section will also break down the various categories of routing protocols and provide specific examples of each. And finally, we will conclude by discussing various bandwidth management topics such as QoS concepts and traffic shaping. All right, so let's talk about routing. So to understand the basic routing process, we're going to use this picture on your screen right here. So in this topology, PC1 needs to send traffic to server 1. Now notice that these devices are on different networks. And in this topology, these are the steps for how a packet from the source IP address of 192.168.1.2 gets routed to the destination IP address of 192.168.3.2. All right, so here are the steps for how all of this magical stuff happens. So step 1, PC1 compares its IP address and subnet mask of 192.168.1.2/24 with the destination IP address and subnet mask 192.168.3.2/24. PC1 concludes that the destination IP address resides on a remote subnet. Therefore, PC1 needs to send the packet to its default gateway, which could have been manually configured on PC1 or dynamically learned via the DHCP. Now, in this example, PC1 has the default gateway of 192.168.1.1, which is router 1. However, to construct a layer 2 frame, PC1 also needs the MAC address of its default gateway. So PC1 sends an address resolution protocol or an ARP request for router R1's MAC address. After PC1 receives an ARP reply from router R1, PC1 adds router R1's MAC address to its ARP cache, and then PC1 now sends its data in a frame that is destined for server 1. So step 2, router R1 receives the frame that was sent from PC1 and interrogates the IP header. An IP header, it contains what is called a TTL or a time to live field, which is decremented once for each router hop. Therefore, router R1 decrements the packet's TTL field. If the value in the TTL field is reduced to 0, the router discards the frame and sends what is called a time exceeded internet control message protocol or ICMP message back to the source. As long as the TTL has not been decremented to 0, router R1 checks its routing table to determine the best path to reach network 192.168.3.0/24. In this example, router R1's routing table has an entry starting that network with 192.168.3.0/24. In this example, router R1's routing table has an entry stating that network 192.168.3.0/24 is accessible via serial port 11. Now note that the ARP is not required for serial interfaces because these interface types do not have MAC addresses, and router R1 therefore forwards the frame out its serial 1/1 interface. Now, step 3, when router R2 receives the frame, it decrements the TTL in the IP header, just as router R1 did. Again, as long as the TTL has not been decremented to 0, router R2 interrogates the IP header to determine the destination network. In this case, the destination network 192.168.3.0/24 is directly attached to router R2's gigabit 0/0/0 interface, similar to the way PC1 sends out an ARP request to determine the MAC address of its default gateway. Router R2 sends an ARP request to determine the MAC address of server 1. After an ARP reply is received from server 1, router R2 forwards the frame out its gigabit 0/0/0 interface to server 1. All right, so the previous steps, we identified 2 router data structures. The first one we talked about was called the IP routing table. And so when a router needs to route an IP packet, it consults its IP routing table to find the best match. And the best match is the route that has the longest prefix. Specifically, a route entry with the longest prefix is the most specific network. So for example, imagine that a router has an entry for network 10.0.0.0/8 and for network 10.1.1.0/24. Also imagine that the router is seeking the best match for the destination address 10.1.1.1/24. The router would select the 10.1.1.0/24 route entry as the best entry because that route entry has the longest prefix, meaning /24 is longer than /8, which is a more specific entry. And the other data structure was layer 3 to layer 2 mapping. So in the previous example, router R2's ARP cache contained layer 3 to layer 2 mapping information. Specifically, the ARP cache had a mapping that said MAC address 222.222.222 corresponded to IP address 192.168.3.2. In this video, you're going to learn about various sources of routing information, such as directly connected routes, static routes, and dynamic routing protocols. All right, so let's talk about sources of routing information. So a router's routing table can be populated from various sources. And as an administrator, you could statically configure a route entry. A route could be learned via a dynamic routing protocol, such as OSPF or EIGRP, or a router could know how to get to a specific network because the router is physically attached to that network. All right, so let's talk about directly connected routes. So a router that has an interface directly participating in the network knows how to reach that specific destination network. So consider the image that's displayed on your screen right here. Router R1's routing table knows how to reach the 192.168.1.0/24 network and 192.168.2.0/30 network because router R1 has an interface physically attached to each network. Similarly, router R2 has interfaces participating in the 10.1.1.0/30 and 192.168.2.0/30 networks, and therefore knows how to reach those networks. And the entries currently shown to be in the routing tables of routers R1 and R2, these are called directly connected routes. All right, next let's talk about static routes. So it is also possible to statically configure routes in a router's routing table. So continuing to expand on the previous example, consider router R1. As shown, router R1 does not need knowledge of each route on the internet. Specifically, router R1 already knows how to reach devices on its locally attached networks. All router R1 really needs to know at this point is how to get out to the rest of the world. And as you can see in this pic, any traffic destined for a non-local network, so for example, any networks available on the public internet, can simply be sent to router R2 because R2 is the next router hop along the path to reach all of those other networks. Router R1 can be configured with a default static route, which essentially says if traffic is destined for a network not currently in the routing table, then send that traffic out interface serial 11. And as a side note, a static route does not always reference a local interface. Instead, a static route might point to what is called a next hop IP address, which is the interface's IP address on the next router to which traffic should be forwarded. And the network address of a default route that is called 0.0 0.0.0/0. And similarly, router R2 can reach the internet by sending traffic out its serial 10 interface. However, router R2 does need information about how to reach 192.168.1.0/24 network that is available off of router R1. And to educate router R2 about how this network can be reached, a network administrator can add a static route pointing to 192.168.1.0/24 to router R2's routing table. All right, and let's talk about dynamic routing protocols. So in complex networks, such as the topology that is shown here, static routing does not scale well. Fortunately, a variety of dynamic routing protocols are available that allow a router's routing table to be updated as network conditions change. So in this picture right here, router R2 is advertising a default route to its neighbors, which are routers R1, R3, and R4. So what happens if PC1 wants to send traffic to the internet? PC1's default gateway is router R3, and router R3 has received 3 different routes. So which one will it use? Well, router R3's path selection, this depends on the dynamic routing protocol that's being used. And as you will later learn, a routing protocol such as RIP or Routing Information Protocol would make the best path selection based on the number of routers that must be used to reach the internet, and that is known as a hop count. And based on the topology that's presented, router R3 would select the 128 kilobits per second link connecting to router R2 because the internet would only be 1 hop away. If router R3 instead selected a path pointing to either router R1 or R4, the internet would then be 2 hops away. However, based on the link bandwidths, you can see that the path from router R3 to R2 is suboptimal. Unfortunately, RIP does not consider available bandwidth when making its route selection. Some other protocols, such as OSPF or Open Shortest Path First, they can consider available bandwidth when making their routing decisions. And dynamic routes also allow a router to reroute around a failed link. So for example, in this picture right here, router R3 prefers to reach the internet via router R4. However, the link between routers R3 and R4 is down. So thanks to dynamic routing protocol, router R3 knows of 2 other paths to reach the internet, and it selects the next best path, which is via router R1 in this example. In this process of failing over from one route to a backup route, this is called convergence. In this video, you're going to learn about various routing protocol characteristics, such as believability of a route, metrics, interior versus exterior gateway protocols, route advertisement method, distance vector, and link state. All right, so let's talk about these routing protocol characteristics. So before examining the characteristics of routing protocols, we need to look at the important distinction between a routing protocol and a routed protocol. A routing protocol such as RIP, OSPF, or EIGRP is a protocol that advertises route information between routers. A routed protocol, this is a protocol with an addressing scheme such as an IP addressing scheme that defines different network addresses, and traffic can be routed between defined networks, perhaps with the assistance of a routing protocol. Now, this video is going to look at routing protocol characteristics such as how believable a routing protocol is compared to other routing protocols. In addition, in the presence of multiple routes, different routing protocols use different metrics to determine the best path, and a distinction is made between interior gateway protocols and exterior gateway protocols. And finally, this video will discuss different approaches to make route advertisements. So let's talk about the believability of a route. So if a network is running more than one routing protocol, which could be the result of a corporate merger or something like that, and a router receives 2 route advertisements from different routing protocols for the same network, then which route advertisement does the router believe? Interestingly, some routing protocols are considered to be more believable than others. So for example, a Cisco router would consider EIGRP to be more believable than the RIP protocol. Now, the index of believability, this is called the administrative distance, or the AD. And this table on your screen right here, this shows the AD values for various sources of routing information. And take note that the lower AD values are considered more believable than the higher AD values. Next, let's talk about metrics. So some networks might be reachable via more than one path. If a routing protocol knows of multiple paths to reach such a network, which route or routes does the routing protocol select? Actually, this varies depending on the routing protocol and what the routing protocol uses as a metric, which is a value that is assigned to a route. Lower metrics are preferred over higher metrics. In some routing protocols, they support load balancing across equal cost paths, and this is useful when a routing protocol knows of more than one route to reach a destination network and those routes have equal metrics. In EIGRP, this can be configured to do load balancing across unequal cost paths. In different routing protocols, they can use different parameters in their calculation of a metric, and these specific parameters used for a variety of routing protocols and will be presented in later lessons. All right, next let's talk about interior versus exterior gateway protocols. So routing protocols, they can also be categorized based on the scope of their operation. Interior gateway protocols, they operate within an autonomous system, where an autonomous system, this is a network under a single administrative control. Conversely, exterior gateway protocols, they operate between autonomous systems. Now consider this image on your screen right here. You have routers R1 and R2. They are in one autonomous system known as AS65002. And then you have routers R3 and R4. They're in another autonomous system known as AS65003. Within these autonomous systems, an interior gateway protocol, or an IGP, is used to exchange routing information. However, router ISP1, this is a router in a separate autonomous system known as AS65001 that is run by a service provider. An exterior gateway protocol, typically a border gateway protocol, this is used to exchange routing information between the service provider's autonomous system and each of the other autonomous systems. All right, next let's talk about route advertisement methods. So another characteristic of routing protocol is how it receives, advertises, and stores routing information. And the two fundamental approaches are called distant vector and link state protocols. So let's talk about distant vector. So a distant vector routing protocol, this sends a full copy of its routing table to its directly attached neighbors. This is a periodic advertisement, meaning that even if there have been no topological changes, a distance vector routing protocol will at regular intervals advertise again its full routing tables to its neighbors. Now, obviously, this periodic advertisement of redundant information is inefficient. Ideally, you want a full exchange of route information to occur only once, and subsequent updates to be triggered by topological changes. And another drawback to distance vector routing protocols is the time they take to converge, which is the time required for all routers to update their routing tables in response to a topological change in the network. Hold down timers, they can speed up the convergence process. And after a router makes a change to a route entry, a hold down timer prevents any subsequent updates for a specified period of time. And this approach helps stops flapping routes, which are routes that oscillate between being available and unavailable, which leads to preventing convergence. And distance vector routing protocols typically use one of two approaches for preventing routing loops. The first one is called a split horizon, and the split horizon feature prevents a route learn on one interface from being advertised back out the same interface. And then you have what is called poison reverse. The poison reverse feature causes a route received on one interface to be advertised back out the same interface with a metric that is considered to be infinite. And next, let's talk about link state. So rather than having neighboring routers exchange their full routing tables with one another, a link state routing protocol allows routers to build a topological map of the network. Then, much like the GPS device in your car, a router can execute an algorithm to calculate an optimal path to a destination network. And routers, they send what are called LSAs, or link state advertisements, to advertise to the networks that they know how to reach. And routers then use those LSAs to construct the topological map of a network. Now, unlike distance vector routing protocols, link state routing protocols, they exchange full routing information only when two routers initially form their adjacency. Then routing updates are sent in response to changes in the network, as opposed to being sent periodically. And also, link state routing protocols, they benefit from shorter convergence times compared to distance vector routing protocols.
In this video, you are going to learn about routing protocol examples such as routing information protocol, open shortest path first protocol, intermediate system to intermediate system protocol, enhanced interior gateway routing protocol, and route redistribution. All right, so let's talk about some routing protocol examples. Now that you understand some of the characteristics that distinguish one routing protocol from another, this video is going to contrast some of the most popular routing protocols used in modern networks. And the first one we're going to talk about is RIP, or Routing Information Protocol. So RIP, this is a distance vector routing protocol that uses the metric hop count. The maximum number of hops between two routers in a RIP-based network is 15. Therefore, a hop count of 16 is considered to be infinite. Also, RIP is also known as an IGP, or an interior gateway protocol. Next, we have what is called Open Shortest Path First, or OSPF. In OSPF, this is a link state routing protocol that uses the metric cost, which is based on the link speed between two routers. OSPF, this is a popular IGP because of its scalability, fast convergence, and vendor interoperability. Next, we have what is called intermediate system to intermediate system. And this link state routing protocol, this is similar in operation to OSPF. It uses a configurable yet dimensionless metric associated with an interface and runs the shortest path first algorithm. Although ISIS is an IGP that offers the scalability, fast convergence, and vendor interoperability benefits of OSPF, it has not been as widely deployed as OSPF. And then we have what is called Enhanced Interior Gateway Routing Protocol, or EIGRP. And EIGRP, this is a Cisco proprietary protocol that is popular in Cisco-only networks, but less popular in mixed vendor environments. And like OSPF, EIGRP is an IGP that offers fast convergence and scalability, and EIGRP is more challenging to classify as a distance vector or a link state routing protocol. And continuing on with EIGRP, so by default, EIGRP, it uses bandwidth and delay in its metric calculations. However, other parameters can be considered, including reliability, load, and maximum transmission unit size. And using delay as part of the metric, EIGRP can take into consideration the latency caused by the slowest links in the path. Now, some literatures will refer to EIGRP as Advanced Distance Vector Routing Protocol, and some other literatures they'll call it Hybrid Routing Protocol, which is the mixing of characteristics of both distance vector and link state routing protocols. EIGRP uses information from its neighbors to help select an optimal route, like distance vector routing protocols. However, EIGRP also maintains a database of topological information like a link state protocol. The algorithm EIGRP uses for its route selection is not the shortest path first algorithm. Instead, EIGRP uses what is called the diffusing update algorithm, or DUAL. And up under the EIGRP umbrella, you have what is called Border Gateway Protocol, or BGP. So BGP is the only EGP, or exterior gateway protocol, in widespread use today. In fact, BGP is considered to be the routing protocol that runs the internet, which is an interconnection of multiple autonomous systems. Although some literature classifies BGP as a distance vector routing protocol, it can more accurately be described as a path vector routing protocol, meaning that it can use as its metric the number of autonomous system hops that must be transited to reach a destination network, as opposed to a number of required router hops. And BGP's path selection is not solely based on autonomous system hops. However, BGP can consider a variety of other parameters, and interestingly, none of those parameters are based on link speed. In addition, although BGP is incredibly scalable, it does not quickly converge in the event of a topological change. Now, as a side note here, when studying for the Network Plus exam, you want to be sure to focus on RIP, OSPF, EIGRP, and BGP, as these are dynamic routing protocols that the exam is sure to cover. In this table right here on your screen, this compares the key characteristics of these dynamic routing protocols. And finally, let's talk about route redistribution. So a network can simultaneously support more than one routing protocol through
the process of route redistribution. So for example, a router could have one of its interfaces participating in an OSPF area of the network and have another interface participating in an EIGRP area of the network. This router could then take routes learned via OSPF and inject those routes into the EIGRP routing process. And similarly, EIGRP learned routes could be redistributed into the OSPF routing process. In this video, you're going to learn about bandwidth management as it relates to quality of service. All right, so let's talk about bandwidth management. So while the main concern with routing is ensuring that data packets as well as control plane packets reach their rightful destinations, it is the job of quality of service to ensure that packets do not suffer from long delays or latency, or even worse, drop packets. And quality of service, this is actually a suite of technologies that allows you to strategically optimize network performance for select traffic types. So for example, in today's converged networks, that is networks that simultaneously transport voice, video, and data, some applications such as voice might be more tolerant of delays or latency than other applications. So for example, an FTP file transfer is less latency sensitive than a VoIP call. Fortunately, through the use of QoS technologies, you can identify which traffic types need to be sent first, how much bandwidth to allocate to various traffic types, which traffic types should be dropped first in the event of congestion, and how to make the most efficient use of the relatively limited bandwidth of an IP WAN. And this video is going to introduce QoS and a collection of QoS mechanisms. Now, as a side note, do not get confused by the many uses we have for the word converged in networking. It all depends on the context. So for example, when speaking about the network in general and what data it can carry, a converged network is one that includes multiple forms of traffic, such as VoIP and data traffic. When we are speaking of a single routing protocol, converged means the device has learned all of the updates that have been in the routing protocol's information. All right, so here's an introduction to quality of service. So a lack of bandwidth is the overshadowing issue for most network quality problems. Specifically, when there is a lack of bandwidth, packets might suffer from one or more of the symptoms that are listed below. And the first symptom is delay. So delay, this is the time required for a packet to travel from source to destination. You might have witnessed delay on the evening news when the news anchor is talking via satellite to a foreign news correspondent. Because of the satellite delay, the conversation begins to feel unnatural. The next one we have is called jitter. And jitter, this is the uneven arrival of packets. So for example, imagine a VoIP or a voice over IP conversation where packet 1 arrives at a destination router. Then 20 milliseconds later, packet 2 arrives. After another 70 milliseconds, packet 3 arrives, and then packet 4 arrives 20 milliseconds behind packet 3. This variation in arrival times, which is known as a variable delay, is not due to drop packets, but the jitter might be interpreted by the listener as drop packets. And then we have drops. So packet drops, they occur when a link is congested and a router's interface queue overflows. Some types of traffic, such as UDP traffic carrying voice packets, are not retransmitted if the packets are dropped. Fortunately, QoS features available on many routers and switches can recognize important traffic and then treat that traffic in a special way. So for example, you might want to allocate 128 kilobits per second of bandwidth for your voice over IP traffic and give that traffic priority treatment. Now consider water flowing through a series of pipes with varying diameters. The water's flow rate through those pipes is limited to the water's flow rate through the pipe with the smallest diameter. Similarly, as a packet travels from source to destination, its effective bandwidth is the bandwidth of the slowest link along that path. So for example, in this picture right here, you will notice that the slowest link speed is 256 kilobits per second. This weakest link becomes the effective bandwidth between the client and the server. Now, because the primary challenge of QoS is a lack of bandwidth, the logical question is, how do we increase the available bandwidth? Well, a knee-jerk response to that question is often add more bandwidth. However, more bandwidth can come at a relatively high cost. So think of your network as a highway system in a large city. During rush hour, the lanes of the highway are congested. During other periods of the day, the lanes might be underutilized. Instead of just building more lanes to accommodate peak traffic rates, the highway engineers might add a carpool lane to give higher priority to cars with 2 or more occupants. Similarly, you can use QoS features to give your mission-critical applications higher priority treatment in times of network congestion. All right, next let's talk about the QoS configuration steps. So these are the three basic steps in quality of service configuration. Step one, you need to determine network performance requirements for various traffic types. So for example, consider these design recommendations for voice, video, and data traffic. So when it comes to voice, you might want no more than 150 milliseconds of a one-way delay, no more than 30 milliseconds of jitter, and no more than 1% packet loss. For video, you might not want no more than 150 milliseconds of a one-way delay for interactive voice applications such as video conferencing. You also might not want no more than 30 milliseconds of jitter and no more than a 1% of packet loss. For data applications, they have varying delay and loss requirements. Therefore, data applications, they should be categorized into predefined classes of traffic where each class is configured with specific delay and loss characteristics. All right, step two, you want to categorize traffic into specific categories. So for example, you might have a category named low delay for voice and video packets in that category. You might also have a low priority class for traffic such as music downloads from the internet. And then step three, you want to document your QoS policy and make it available to your users. So for example, if users complain that their network gaming applications are running slowly, you can point them to your corporate QoS policy, which describes how applications such as network gaming have what is called best effort treatment, while voice over IP traffic receives the priority treatment. And the actual implementation of these steps varies based on specific devices you are configuring. So in some cases, you might be using the command line interface of a router or a switch. In other cases, you might have some sort of graphical user interface through which you configure QoS on your routers and switches. All right, next let's talk about some quality of service components. So QoS features are categorized into one of the three categories that are shown on the screen right here. And the first one you have is called best effort traffic. So best effort treatment of traffic does not truly provide quality of service to that traffic because there is no reordering of the packets. Best effort uses what is called a first in, first out queuing strategy, where packets are emptied from a queue in the same order in which they entered the queue. Next, you have what is called integrated services. So integrated services is often referred to as a hard QoS because it can make strict bandwidth reservations. Integrated services uses signaling among network devices to provide bandwidth reservations. Resource reservation protocol, this is an example of an integrated services approach to QoS because the integrated services must be configured on every router along a packet's path. The main drawback of integrated services is that it lacks in scalability. And then we have what is called differentiated services. So differentiated services, as the name suggests, differentiates between multiple traffic flows. Specifically, packets are marked and routers and switches can then make decisions such as dropping or forwarding decisions based on those markings. Because differentiated services does not make explicit reservations, it is often called a soft QoS. In most modern QoS configurations, they are based on the differentiated services approach. All right, next let's talk about some quality of service mechanisms. So as previously mentioned, a differentiated service approach to QoS, it marks traffic. However, for markings to impact the behavior of traffic, a QoS tool must reference those markings and alter the packet's treatment based on them. In the following, this is a collection of commonly used QoS mechanisms. You have classification, marking, congestion management, congestion avoidance, policing and shaping, and link efficiency. Now, while all of these mechanisms can be considered important, this video focuses on the main bandwidth management tools such as policing and traffic shaping. So let's talk about policing and traffic shaping. So instead of making a minimum amount of bandwidth available for specific traffic types, you might want to limit available bandwidth. Both traffic policing and traffic shaping tools can accomplish this objective, and collectively these tools are called traffic conditioners. And policing, this can be used in either the inbound or outbound direction, and it typically discards packets that exceed the configurated rate limit, which you can think of as a speed limit for specific traffic types. Because policing drops packets resulting in retransmissions, it is recommended for higher speed interfaces. And then we have what is called shaping buffers, which are known to cause delays in traffic that exceed a configured rate. So therefore, shaping, this is recommended for slower speed interfaces. In this video, you're going to learn about the principles of Ethernet as it relates to the Ethernet's origins, carrier sense, multiple access with collision detection, and distance and speed limitations.
All right, so let's talk about the Ethernet origin. So, in the network industry, you might come upon the term IEEE 802.3, where the IEEE, this refers to the Institute of Electrical and Electronics Engineers Standards Body. So, in general, you can use the term IEEE 802.3 interchangeably with the term Ethernet. However, be aware that these technologies do have some subtle distinctions. So, for example, an Ethernet frame, this is a fixed length frame, whereas the 802.3 frame length, that can vary. And a popular implementation of Ethernet in the early days was called 10-base-5. The 10 and 10-base-5, this referred to the network throughput, specifically 10 megabits per second. The base in 10-base-5, this referred to baseband as opposed to broadband. And finally, the 5 and 10-base-5, this indicated the distance limitation of 500 meters. The cable used in 10-base-5 networks, as shown in this picture on your screen, it had a larger diameter than most types of media. In fact, this network media type, it became known as what is called ThickNet. Another early Ethernet implementation was 10-base-2. So from the previous analysis of 10-base-5, you might conclude that 10-base-2 was a 10 megabit per second baseband technology with a distance limitation of 200 meters. Well, that would be almost correct. However, 10-base-2's actual distance limitation is 185 meters, and the cabling used in 10-base-2 networks was significantly thinner and therefore less expensive than the 10-base-5 cabling. And as a result, 10-base-2 cabling, it became known as ThinNet or cheaper net. So 10-base-5 and 10-base-2 networks, they were quickly replaced with UTP cabling or unshielded twisted pair cabling. And the 10 megabit per second version of Ethernet that relied on UTP cabling is known as 10-base-T, where the T refers to twisted pair cabling. All right, next let's talk about carrier sense multiple access with collision detection, also known as CSMA-CD. So Ethernet was based on a philosophy that all network devices should be eligible at any time to transmit on a network. In contrast, Token Ring used a deterministic media access approach. Specifically, Token Ring networks passed a token around a network in a circular fashion from one network device to the next. Only when a network device was in possession of that token was it eligible to send on a network. Now, recall from previous videos the concept of a bus topology. And an example of a bus topology is a long cable, such as a thick net or a thin net, running in a length of a building with various network devices tapping into the cable to gain access to the network. In this picture right here on your left, this depicts an Ethernet network using a shared bus topology. Now, in this topology, all devices are directly connected to the network and are free to transmit at any time if they have reason to believe no other transmission currently exists on the wire. Ethernet permits only a single frame to be on the network segment at any one time. So before a device in the network transmits, it listens to the wire to see if there is currently any traffic being transmitted. If no traffic is detected, the network device transmits its data. However, what if two devices simultaneously have data to send? If they both listen to the wire at the same time, they could simultaneously and erroneously conclude that it is safe to send their data. However, when both devices simultaneously send their data, a collision occurs and data corruption results. Fortunately, Ethernet was designed with a mechanism to detect collisions and allow the devices whose transmissions collide to retransmit their data at different times. Specifically, after the devices noticed that a collision occurred, they independently set a random back-off timer. Each device waits for this random amount of time to elapse before again trying to transmit. So here's the logic. Because each device certainly picked a different amount of time to back off from transmitting, their transmissions should not collide the next time these devices transmit. As you can see, what is depicted in these pictures right here, where this computer has a back off timer of 100 milliseconds and this one has a back off timer of 200 milliseconds. So the procedure used by Ethernet to decide whether it's safe to transmit, detect collisions, and retransmit if necessary, this is called carrier sense multiple access with collision detection, or CSMA/CD. So let's break down the CSMA/CD into its constituent components. The first part is carrier sense. So a device attached
attached to an Ethernet network, it can listen to the wire prior to transmitting to make sure a frame is not being transmitted on the network segment. Then you have the multiple access component. So unlike with the deterministic method of network access, such as that used with a token ring, all Ethernet devices simultaneously have access to an Ethernet segment. And then you have collision detection. So if a collision occurs because two devices were simultaneously listening to the network and simultaneously concluded that it was safe to send, Ethernet devices can detect that collision and set random back-off timers. After each device's random timer expires, the devices again, they will try to transmit their data. Now, despite Ethernet's CSMA-CD feature, Ethernet segments still suffer from scalability limitations. Specifically, the likelihood of collisions increases as the number of devices on a shared Ethernet segment increases as well. An alternate approach is called CSMA-CA, where the CA, this refers to collision avoidance. And this technology is common in wireless networks and was made famous by the token ring in the early local area networks. With wired Ethernet, devices on a shared Ethernet segment, they belong to the same collision domain. And one example of a shared Ethernet segment is the 10-base-5 or the 10-base-2 network with multiple devices attaching to the same cable. On that cable, only one device can send at any one time. Therefore, all devices attached to the thicknet or the thinnet cable, they are in the same collision domain. And similarly, devices connected to an Ethernet hub, they are in the same collision domain as well. A hub, this is a layer 1 device and does not make forwarding decisions. Instead, a hub takes bits in on one port and sends them out all the other ports except the one on which the bits were received. And then we have Ethernet switches that can dramatically increase the scalability of Ethernet networks by creating multiple collision domains. In fact, every port on an Ethernet switch is its own collision domain. And Ethernet switches, they have a less obvious but powerful benefit. Now, because a switch port connects to a single device, there is no chance of a collision. With no chance of a collision, collision detection is no longer needed. And with collision detection disabled, network devices can run in full duplex mode rather than half duplex mode. In full duplex mode, a device can simultaneously send and receive data at the same time. When multiple devices are connected to the same shared Ethernet segment, such as a layer 1 hub, CSMA-CD, this must be enabled. And as a result, the network must work in half duplex mode, which means that only a single network device can transmit or receive at any one time. In half duplex mode, a network device cannot simultaneously send and receive, so the device makes inefficient use of the network's bandwidth. And another important mechanism in Ethernet network is called flow control. And flow control, this is a mechanism for temporarily stopping the transmission of data on Ethernet-based networks. The goal of this mechanism is to avoid packet loss in the presence of network congestion. All right, next let's talk about distance and speed limitations. So to understand the bandwidth that's available on networks, you need to understand a few terms. You should already know that a bit refers to one of two values, represented using binary math, which uses only the numbers 0 and 1. On a cable, such as a twisted pair cable, a bit could be represented by the absence or presence of voltage. Fiber optic cable, however, might represent a bit with the absence or presence of light. In the bandwidth of a network, this is measured in terms of how many bits the network can transmit during a 1 second period of time. So for example, if a network has the capacity to send 10 million bits in a 1 second period of time, the bandwidth capacity is said to be 10 megabits per second. In this table right here on your screen, this defines common bandwidth that is supported on distinct types of Ethernet networks. Now, the type of cabling used in an Ethernet network, this influences the bandwidth capacity and the distance limitation of the network. So for example, fiber optic cabling often has a higher bandwidth capacity and a longer distance limitation than twisted pair cabling. When it comes to the size of the frame the media can send, there is a maximum transmission unit value the media can accommodate. And you can even configure support for what are called jumbo frames, which are Ethernet frames with more than 1,500 bytes of payload, and that limit is set by the IEEE 802.3 standard. Now, in previous videos, you learned about single mode fiber and multi-mode fiber. Because of the issues of multi-mode delay distortion, single mode fiber usually has a longer distance limitation than multi-mode fiber. And when you want to uplink from one Ethernet switch to another, you might need different connectors for different installations. Fortunately, some Ethernet switches have one or more empty slots in which you can insert a gigabit interface converter or a GBIC. In GBICs, these are interfaces that have a bandwidth capacity of 1 gigabit per second and are available with multi-mode fiber, single mode fiber, and unshielded twisted pair connectors. And this allows you to have flexibility in the uplink technology you use in an Ethernet switch. And the various interface converters, these are commonly called transceivers. And two common characteristics of fiber optic transceivers are that they are bidirectional and full duplex. This means that they can send data in both directions bidirectional, and they can do this simultaneously or full duplex. And as a side note, a smaller variant of a regular GBIC is called a small form factor pluggable, or an SFP, which is sometimes also called a mini GBIC. And it also comes with variations called SFP plus and quad SFP. Now, on the next two slides, this shows a table of multiple Ethernet standards along with the media types, bandwidth capacity, and distance limitations of each type of Ethernet standard. And here's the second slide showing you some more Ethernet standards and their distance limitations as well. Finally, as a side note, now too often confused terms are 10 base T and 100 base TX. 100 base T itself is not a specific standard. Rather, 100 base T, this is a category of standards that includes 100 base T2, 100 base T4, and 100 base TX. 100 base T2 and 100 base T4, these were early implementations of 100 megabit per second Ethernet, and they are no longer used. Therefore, you can generally use the terms 100 base T and 100 base TX interchangeably. And similarly, the term 1000 base X, this is not a specific standard either. Rather, 1000 base X, this refers to all Ethernet technologies that transmit data at a rate of 1 gigabit per second over fiber optic cabling. In this video, you're going to learn about various Ethernet switch features such as VLANs, switch configuration for an access port, trunks, and switch configuration for a trunk port. So beyond basic frame forwarding, many layer 2 Ethernet switches offer a variety of other features to enhance such things as network performance, redundancy, security, management, flexibility, and scalability. Although these specific features offered by a switch vary, the next few videos will introduce you to some of the most common features of switches. So let's go ahead and talk about virtual LANs. So in a basic switch configuration, all ports on a switch belong to the same broadcast domain. In such an arrangement, a broadcast received on one port gets forwarded out all other ports. Also, from a layer 3 perspective, all devices connected in a broadcast domain have the same network address. Now, in previous videos, you learned about binary math involved in IP addresses, such as logical layer 3 addresses to network devices. A portion of that address is the address of the network to which that device is attached. The remainder of that address is the address of the device itself. And devices that have the same network address, they belong to the same network or subnet. Now, say that you decided to place PCs from different departments within your company into their own subnet. One reason you might want to do this is for security purposes. So for example, by having the accounting department in a separate subnet, which is a separate broadcast domain from the sales department, devices in one subnet will not see the broadcast being sent on the other subnet. And another reason that you might want to do this is to make the overall network segment more efficient. So remember that excessive broadcast frames, they can cause a network to suffer, and there are plenty of operations that rely on broadcast to function properly. Address resolution protocol, this is a great example of such an operation. ARP, this is a broadcast-based solution that permits a system to discover the MAC address that coordinates to a particular IP address. IP version 6, it eliminates this challenge altogether with the introduction and use of neighbor discovery protocol. And as you might guess, neighbor discovery protocol, this is not broadcast-based. This is fortunate as broadcasts are not supported in IP version 6.
Now, the PCs belonging to different departments in your company are scattered across multiple floors in a building as seen in this picture on your screen right here. The accounting and sales department each has a PC on each floor of a building. Because the wiring for each floor runs back to a wiring closet on that floor, to support these two subnets using a switch's default configuration, you would need to install two switches on each floor. For traffic to travel from one subnet to another subnet, that traffic has to be routed, meaning that a device such as a multi-layer switch or a router forwards traffic based on a packet's destination network addresses. So in this example, the accounting department switches are interconnected and then connect to a router, and the sales department switches are connected similarly. And the design described here, it lacks efficiency because you must install at least one switch per subnet. A more efficient design would be to logically separate a switch's ports into different broadcast domains. Then an accounting department PC and a sales department PC could connect to the same switch, even though those PCs belong to different subnets. Fortunately, VLANs, they make such a design possible. Now with VLANs, as shown in this picture right here, a switch can have its ports logically divided into more than one broadcast domain, that is more than one subnet or VLAN. Then devices that need to connect to those VLANs can connect to the same physical switch, but they remain logically separate from one another. Now, VLANs are very handy with another popular configuration requirement in many modern network environments. You can use a special purpose VLAN termed a voice VLAN to segment and provide network access for voice over IP packets. These packets need access to the data for transport, and they also need special priority treatment to ensure that the voice call quality always remains excellent. And using a voice VLAN, this is an ideal segmentation strategy for all of these needs. And one challenge with VLAN configuration in large environments is the need to configure identical VLAN information on all switches. Manually performing this configuration is time consuming and error prone. However, switches from Cisco systems, they support VLAN trunking protocol, which allows a VLAN created on one switch to be propagated to other switches in a group of switches. And this is known as a VTP domain. And the VTP information is carried over a trunk connection. All right, so let's talk about switch configuration for an access port. So configurations used on the switch port may vary based on the manufacturer of the switch. In this example on your screen right here, this shows a sample configuration on an access port without trunking on a Cisco Catalyst switch. And the line with the leading explanation point, this is a comment used to document the next line of the configuration. Now, notice in this configuration the use of port security, which is a small but useful step in securing a network. In this configuration example, the port can learn only two MAC addresses, perhaps the MAC address of a voice over IP phone and the computer that connects to that phone. All right, next let's talk about trunks. So one challenge with carving up a switch into multiple VLANs is that several switch ports, that is one port per VLAN, could be consumed by connecting a switch to a switch or a switch to a router. A more efficient approach is to allow traffic from multiple VLANs to travel over a single connection as shown in this picture. And this type of connection, this is called a trunk. And the most popular trunking standard today is IEEE 802.1q, which is often referred to as .1q. One of the VLANs traveling over an 802.1q trunk, this is called a native VLAN. Frames belonging to the native VLAN are sent unaltered over the trunk, meaning they're untagged or they have no tag. However, to distinguish other VLANs from one another, the remaining VLANs, they are tagged. Now, as a side note, IEEE 802.1q, this is often called tagging or port tagging. And specifically, a non-native VLAN, this has 4 tag bytes, where a byte is a collection of 8 bits that are added to the Ethernet frame, which means that they are a tag frame. And this picture right here on your screen, this shows the format of an IEEE 802.1q header with these 4 bytes. Now, one of these bytes contains a VLAN field, which indicates to which VLAN a frame belongs. And the devices, such as a switch, multi-layer switch, or a router, at each end of a trunk interrogate that field to determine which VLAN an incoming frame is associated with. And as you can see by comparing these pictures on your screen here, VLAN and trunking features, they allow switch ports to be used far more efficiently than merely relying on a default switch configuration. Now, what type of Ethernet Ethernet media do you think you would need for a trunk link? Well, it used to be that you needed a special Ethernet cable called a crossover cable for a trunk link. This is no longer the case in most networks, as switches, they now support auto medium dependent interface crossover, or MIDI-X or MDI-X technology. This technology essentially permits a switch to detect the type of Ethernet cable used, whether it's a straight through or a crossover cable, and adjust accordingly so that communication between the two network devices, such as switches, can be successful. And finally, let's talk about a switch configuration for a trunk port. So this example on your screen right here, this shows a sample configuration on a trunk port on a Cisco Catalyst switch. And remember, the lines that lead with the explanation point, these are comments that are used to document the next lines of the configuration. In this video, you're going to learn about more Ethernet switch features, such as spanning tree protocol, corruption of a switch's MAC address table, broadcast storms, STP operation, link aggregation, and link aggregation control protocol. All right, first let's talk about spanning tree protocol. So administrators of corporate telephone networks, they often boast about their telephone systems, that is their private branch exchange systems or their PBX systems. And these systems have 5 nines of availability. And the 5 nines of availability means that a system is up and functioning 99.999% of the time, which translates to only about 5 minutes of downtime per year. Now, traditionally, corporate data networks, they struggle to compete with corporate voice networks in terms of availability. Today, however, many networks that carried only data now carry voice, video, and data. Therefore, availability is an especially important design consideration. And to improve network availability at layer 2, many networks have redundant links between switches. However, unlike layer 3 packets, layer 2 frames, they lack a time to live field. And as a result, a layer 2 frame can circulate endlessly through a loop layer 2 topology. Fortunately, IEEE 802.1d, the spanning tree protocol, this allows a network to physically have layer 2 loops while strategically blocking data from flowing over one or more switch ports to prevent the looping of traffic. Now, in the absence of spanning tree protocol, if a network has parallel paths, 2 significant symptoms include corruption of a switch's MAC address table and broadcast storms, where frames loop over and over throughout the switch network. Now, an enhancement to the original spanning tree protocol is 802.1w, which is also called rapid spanning tree protocol because it does a quicker job of adjusting to network conditions, such as the addition or removal of layer 2 links in the network. And also shortest path bridging, or IEEE 802.1aq. This is a protocol that is more scalable than spanning tree protocol in larger environments with hundreds of switches that are interconnected. All right, next let's talk about the corruption of a switch's MAC address table. So a switch's MAC address table can dynamically learn what MAC addresses are available off of its ports. However, in the case of spanning tree protocol failure, a switch's MAC address table can be corrupted. Now, in this picture that you're looking at on your screen right here, PC1 is transmitting traffic to PC2. When that frame sent from PC1 is transmitted on segment A, the frame is seen on gigaport 01 ports of switches SW1 and SW2, causing both switches to add an entry to their MAC address tables, associating MAC address AAA.AAA.AAA with port gigaport 01. Because spanning tree protocol is not functioning, both switches then forward the frame out on segment B. As a result, PC2 receives 2 copies of the frame. Also, switch SW1 sees the frame forwarded out of switches SW2's gigabit 02 port. Because that frame has source MAC address AAA.AAA, etc., switch SW1 incorrectly updates its MAC address table, indicating that MAC address AAA.AAA, etc. resides off of gigabit 02's port. Similarly, switch SW2 sees the frame forwarded onto segment B by switch SW1 on its gigabit 02 port. Therefore, switch SW2 also incorrectly updates its MAC address table. All right, next let's talk about broadcast storms. So as previously mentioned, when a switch receives a broadcast frame, that is a frame that is destined for MAC address FFFF.FFF.FFF, etc., the switch floods the frame out all switch ports other than the port on which the frame was received. Because a layer 2 frame does not have a time to live field, a broadcast frame endlessly circulates through the layer 2 topology, consuming resources on both switches and attached devices, such as the user's PC. And this picture right here on your screen illustrates how a broadcast storm can form in a layer 2 topology when spanning tree protocol is not functioning properly. So in step 1, PC will send the broadcast frame onto segment A, and the frame enters the switch on gigabit 01's port. Both switches flood a copy of the broadcast frame out their gig 02 ports, that is, onto segment B, causing PC2 to receive 2 copies of the broadcast frame. In step 3, both switches will receive a copy of the broadcast frame on their gig 02 ports, that is, from segment B, and flood that frame out gig 01 ports or onto segment A, causing PC1 to receive 2 copies of the broadcast frame. And this behavior continues as the broadcast frame copies continue to loop through the network. The performance of PC1 and PC2 is affected because they also continue to receive copies of that broadcast frame. All right, next let's talk about spanning tree protocol operation. So STP, this prevented layer 2 loops, which might result in a broadcast storm or corruption of a switch's MAC address table from occurring in the network. And switches in an STP topology are classified as one of the following. You have what is called a root bridge. And a root bridge, this is a switch elected to act as a reference point for a spanning tree. The switch with the lowest bridge ID is elected as the root bridge, and the bridge ID is made up of a priority value and a MAC address. And then you have what is called the non-root bridge. So all other switches in the STP topology are considered non-root bridges. And this picture illustrates root bridge selection in a network. Now notice that in this case, the bridge priorities are 32768. Therefore, the switch with the lowest MAC address, which is switch 1 or SW1, is elected as the root bridge. And ports that interconnect switches in an STP topology are categorized as the following. The first one you have is called the root port. So every non-root port bridge has a single root port, which is the port on the switch that is closest to the root bridge in terms of cost. Then you have what is called the designated port. So every network segment has a single designated port, which is the port on the segment that is closest to the root bridge in terms of cost. So therefore, all ports on a root bridge are designated ports. And then you have what is called the non-designated port. And non-designated ports, they block traffic to create a loop-free topology. And this picture right here illustrates these port types. So notice that both links are equal in this case with a cost of 19 because both links are fast Ethernet links. Therefore, the root port for switch SW2 is selected because it has the lowest port ID. And this picture shows a similar topology to the last image we looked at. In this picture, however, the top link is running at a speed of 10 megabits per second, whereas the bottom link is running at a speed of 100 megabits per second. Because switch SW2 seeks to get back to the root bridge or switch SW1 with the latest cost, port gig 02 on switch SW2 is selected as the root port. Specifically, port gig 01 has a cost of 100 and gig 02 has a cost of 19. And here is a table that shows the port costs for various link speeds. Now, a new standard for STP port costs is called long STP, and this will be increasingly adopted over the coming years because of link speeds that exceed 10 gigabits per second. And long STP values, they range from 2 million for 10 megabits per second Ethernet to as little as 2 for 10 terabits per second. Now, non-designated ports, they do not forward traffic during normal operation, but do receive bridge protocol data units or BPDUs, and switches exchange STP information in the form of a BPDU, which contain useful information for STP elections, past cost calculations, link suppression, and loop detection. If a link in the topology goes down, the non-designated port detects the link failure and determines whether it needs to transition to the forwarding state.
If a non-designated port needs to transition to the forwarding state, it does not do so immediately. Rather, it transitions through the following states. And the first one is called blocking. So the port remains in the blocking state for 20 seconds by default. During this time, the non-designated port evaluates BPDUs in an attempt to determine its role in the spanning tree. Next, it does listening. So the port moves from the blocking state to the listening state and remains in this state for 15 seconds by default. During this time, the port sources BPDUs, which inform adjacent switches of the port's intent to forward data. Next, we have learning. So the port moves from the listening state to the learning state and remains in this state for 15 seconds by default. During this time, the port begins to add entries to its MAC address table. And then we have forwarding. So the port moves from the learning state to the forwarding state and begins to forward frames. All right, next let's talk about link aggregation. So if all ports on the switch are operating at the same speed, like at 1 gigabit per second, the ports most likely to experience congestion are ports connected to another switch or router. So for example, imagine a wiring closet switch connected via fast Ethernet ports to multiple PCs. That wiring closet switch has an uplink to the main switch for a building. Because this uplink port aggregates multiple 100 megabit per second connections, the uplink port is also at 100 megabits per second. It can quickly become congested if multiple PCs are transmitting that need to be sent over the uplink, as shown in this picture on your screen right here. And to alleviate congested links between switches, you can, on some switch models, logically combine multiple physical connections into a single logical connection over which traffic can be sent. And this feature, which is illustrated in this picture right here, this is called link aggregation. Now, although vendor proprietary solutions for link aggregation have existed for some time, some solutions faced a couple of common issues. First one being each link in a logical bundle was a potential single point of failure, and each end of the logical bundle had to be manually configured. In 2000, the IEEE, they ratified the 802.3 AD standard for link aggregation. This standard supports link aggregation control protocol. Now, unlike some older vendor proprietary solutions, LACP supports automatic configuration and prevents an individual link from becoming a single point of failure. Specifically with LACP, if a link fails, that link's traffic is forwarded over a different link. The Cisco systems implementation of LACP, this is called Ether channel. Groups of interfaces that make up an Ether channel bundle are often referred to as a link aggregation group, or a LAG. An Ether channel group can be configured to act as a layer 2 access port and support only a single VLAN, or it can be configured to act as a layer 2 802.1q trunk and support multiple VLANs of the LAG. In a LAG, it can also be configured as a layer 3 routed interface if the switch supports that feature. In the case of a layer 3 Ether channel, an IP address will be applied to the logical interface that represents the LAG. And another term related to LACP and LAG is port bonding, which also refers to the same concept of grouping multiple ports and using them as a single logical interface. And finally, here is a sample of an LACP configuration on a Cisco switch. And remember, the lines with the leading exclamation point, these are comments used to document the next line of the configuration. In this video, you're going to learn even more Ethernet switch features such as power over Ethernet, port mirroring configuration, user authentication, management access and authentication, first hop redundancy, and other switch features. All right, so let's talk about power over Ethernet. So some switches not only transmit data over a connected UTP cable, but use that cable to provide power to an attached device. So for example, say that you want to mount a wireless access point on the ceiling. Although no electrical outlet is available near the access point's location, you can, as an example, run a Cat6 UTP plenum cable above the drop ceiling and connect it to the access point. Now, some access points, they allow the switch at the other end of the UTP cable to provide power over the same wires that carry data. And examples of other devices that might benefit from receiving power from an Ethernet switch include devices
devices such as security cameras and IP phones. Now, the switch feature that gives power to attached devices, this is called power over Ethernet, and it is defined by the IEEE 802.3AF standard. As you can see in this picture on your screen right here, the power over Ethernet feature of a switch, it checks for 25,000 ohms of resistance in the attached device. To check the resistance, the switch applies as much as 10 volts of direct current across specific pairs of wires, that is pins 1 and 2 combine to form one side of the circuit, and pins 3 and 6 combine to form the other side of the circuit, connecting back to the attached devices, and then it checks to see how much current flows over those wires. So for example, if the switch applies 10 volts direct current across the wires and notice 0.4 milliamps of current, the switch concludes that the attached device has 25,000 ohms of resistance across the wires, and the switch could then apply power across the wires. Next, the switch must determine how much power the attached devices need. So the switch makes this determination by applying 15.5 volts through 20.5 volts DC, making sure that the current never exceeds 100 milliamps to the attached device for a period of time, which is less than 1/10 of a second. The amount of current flowing to the attached device tells the switch the power class of that attached device. The switch then knows how much power should be made available on the port connecting to the device requiring power, and it begins an appropriate amount of voltage in the range of 44 volts to 57 volts to the attached device. And the IEEE 802.3AF standard, this can supply a maximum of 15.4 watts of power. However, the later standard of IEEE 802.3AT offers as much as 32.4 watts of power, enabling PoE to support a wider range of devices such as power-hungry IP video cameras. And the newer standard for PoE, this is often referred to as Power over Ethernet Plus. All right, next let's talk about port mirroring. So for troubleshooting purposes, you might want to analyze packets flowing over a network. To capture packets, that is, store copies of packets on a local hard drive for analysis, you could attach a network sniffer to a hub. Because a hub sends bits received on one port out all other ports, the attached network sniffer sees all traffic entering the hub. Now, several standalone network sniffers are available. However, a low-cost way to perform packet capture and analysis is to use a software program called Wireshark, which you can download for free off the internet. Now, a challenge does arise. However, if you connect the network sniffer, for example, a laptop running the Wireshark software, to a switch port rather than to a hub port, because a switch by design forwards frames out ports containing the frame's destination addresses, a network sniffer attached to one port would not see traffic destined for a device connected to a different port. Fortunately, some switches, they support a port mirroring feature, which makes a copy of traffic seen on one port and sends that duplicated traffic out another port to which a network sniffer could be attached. So as you can see in the picture on your screen right here, this switch is configured to mirror traffic on port 2 to port 3, allowing a network sniffer to capture the packets that need to be analyzed. And depending on the switch, locally captured traffic could be forwarded to a remote destination for centralized analysis of that traffic. And here's an example of a sample configuration from a Cisco Catalyst switch that captures all the frames coming in on port gig 01 and forwards them to port gig 03. All right, next let's talk about user authentication. So for security purposes, some switches require users to authenticate themselves, that is, provide credentials such as a username and password to prove who they are before gaining access to the rest of the network. A standards-based method for enforcing user authentication, this is known as IEEE 802.1x. And with 802.1x enabled, a switch requires a client to authenticate before communicating on the network. After the authentication occurs, a key is generated that is shared between the client and the device to which it attaches. So for example, a wireless LAN controller of a layer 2 switch. Then the key encrypts the traffic coming from and being sent to the client. And this picture right here on your screen, this illustrates the three primary components of an 802.1x network, which are described in the following list. First one you have is called the supplicant.
So the supplicant, this is the device that wants to gain access to a network. Next, you have the authenticator. The authenticator forwards the supplicant's authentication request onto an authentication server. After the authentication server authenticates the supplicant, the authenticator receives a key that is used to communicate securely during a session with the supplicant. Then we have the authentication server. The authentication server, so for example, a remote authentication dial-in user service, also known as a radius server, this checks a supplicant's credentials. If the credentials are acceptable, the authentication server notifies the authenticator that the supplicant is allowed to communicate on the network. The authentication server also gives the authenticator a key that can be used to securely transmit data during the authenticator's session with the supplicant. And an even more sophisticated approach to admission control is the network access control feature offered by some authentication servers. Beyond just checking credentials, network access control can check characteristics of the devices seeking admission to the network, the client's operating system, and version of antivirus software. These are examples of these characteristics. All right, next let's talk about management, access, and authentication. So to configure a managed switch, you can use a secure shell or connect directly to the console port of the switch. An unmanaged switch, this is one that does not support the use of an IP address or a console port to connect to for management purposes. And when possible, using a separate network for management of a managed switch, this is desired. This is referred to as an out-of-band management, when the management traffic is kept on a separate network from the user traffic. And to use remote SSH access, secure shell must be enabled on the switch, and the switch must have an IP address and default gateway configured so it can reply to the secure shell request when the administrator using secure shell is not on the same local network as the switch. And this is an example that shows a sample configuration of an IP and management access on a Cisco Catalyst switch. Now, as a side note, the virtual terminal lines, which you can see right here, they allow for 16 simultaneous connections to the switch by administrators. If more simultaneous connections are required, additional VTY lines could be configured on that switch. All right, next let's talk about first hop redundancy. So many devices such as PCs are configured with default gateways. The default gateway parameter identifies the IP address of a next hop router, and as a result, if that router were to become unavailable, devices that relied on the default gateway's IP address would be unable to send traffic on their local subnet, even if a backup router existed. Fortunately, a variety of technologies are available for providing first hop redundancy, and one such technology is called Hot Standby Router Protocol, which is a Cisco proprietary protocol. In HSRP, this can run on routers or multi-layer switches. In HSRP, it uses virtual IP addresses and virtual MAC addresses. One router, which is known as the active router, services requests destined for the virtual IP and virtual MAC addresses. Another router, which is known as the standby router, can service such requests in the event that the active router becomes unavailable. And this picture right here on your screen, this illustrates a sample of the HSRP topology. So in this picture, notice that router 1 is acting as the active router and router R2 is acting as the standby router. When workstation A sends traffic destined for a remote network, it sends traffic to its default gateway, which is 172.16.1.3, which is the virtual IP address shared by the HSRP routers. When router R1 is the active router, it assumes the virtual IP and virtual MAC addresses and it forwards the traffic off the local network. However, if R2 notices that R1 has become unavailable, R2 transitions to the active router role and assumes the virtual IP and virtual MAC addresses. With default timer settings, the time required to fail over to router R2 is approximately 10 seconds. However, timers can be adjusted so that the failover time is as little as 1 second. And as a side note, Cisco has another proprietary first hop redundancy protocol called Gateway Load Balancing Protocol, whereas GLBP and HSRP, these are Cisco proprietary solutions. You have what is called Virtual Router Redundancy Protocol and Common Address Redundancy Protocol, and these are open standard options for first hop redundancy.
And then finally, let's talk about some other switch features. So switch features, such as those previously described, they vary widely by manufacturer, and some switches offer a variety of security features. So for example, MAC filtering might be supported, which allows traffic to be permitted or denied based on the device's MAC address. Other types of traffic filtering might also be supported based on the criteria, such as IP address information for multi-layer switches. For monitoring and troubleshooting purposes, interface diagnostics might be accessible. This diagnostic information might include various error conditions, such as late collisions or cyclic redundancy check or CRC errors, which might indicate a duplex mismatch. And some switches also support quality of service settings, which make it possible to forward traffic based on the traffic's priority markings. And finally, some switches have the ability to perform marking and remarking of traffic priority values. In this video, you're going to learn about wireless LANs as it relates to wireless routers, wireless access points, antennas, frequencies and channels, CSMA, CA, transmission methods, and wireless LAN standards. So the popularity of wireless local area networks has exploded over the past decade, allowing users to roam within a wireless local area network coverage area, take their laptops and tablets with them, and maintain network connectivity as they move throughout a building or campus environment. And many other devices can also take advantage of wireless networks, such as gaming consoles, smartphones, and printers. Over the next few videos, we're going to discuss wireless local area network technology and wireless LAN design considerations and wireless LAN security, along with various wireless concepts, components, and standards. All right, so let's go ahead and talk about wireless LANs. So this video is going to introduce the basic building blocks of wireless LANs and discuss how wireless LANs connect to a wired local area network. Various design options include antenna design, frequencies, and communication channels. They will be discussed along with a comparison of today's major wireless standards, which are all some variant of the IEEE 802.11 standard. All right, so let's talk about wireless LAN concepts and components. So wireless devices such as laptops, tablets, and smartphones often have built-in wireless cards that allow those devices to communicate on a wireless local area network. But what is the device to which they communicate? It could be another laptop or device with a wireless card. If that's the case, this would be an example of an ad hoc wireless local area network. However, enterprise class wireless LANs and even most wireless LANs in homes, they are configured in such a way that a wireless client connects to some sort of wireless base station, and such as a wireless access point or a wireless router. In many companies, they offer Wi-Fi as a service, and users within a range of an access point can use the access point as a hotspot, indicating that Wi-Fi is available through that access point. Now, as a side note, a much fancier term for an ad hoc network that you should be aware of is called Independent Basic Service Set Wireless LAN, or IBSS wireless LAN. And when it comes to wireless LANs, this communication might be done using a variety of antenna types, frequencies, and communication channels. And the following sections are going to consider some of these elements in more detail. All right, let's talk about wireless routers. So consider the basic wireless LAN topology that is shown in this picture on your screen. Such a wireless LAN might be found in a residence whose internet access is provided by a high-speed cable modem. And in this topology, a wireless router and switch are shown as separate components. However, in many residential networks, a wireless router integrates switch ports and wireless routing functionality into a single device. Also in this pic, the cable modem obtains an IP address via DHCP from the internet service provider. The wireless router behind the modem also uses DHCP to provide IP addresses to the LAN devices attaching to it wirelessly or through a wired connection. The process through which a wireless client, like a laptop or a smartphone, attaches with a wireless router, this is called association. All wireless devices associating with a single access
access point share a collision domain. Therefore, for scalability and performance reasons, wireless LANs might include multiple access points, and the router then uses what is called port address translation to allow packets to leave the LAN and head to the internet. All right, next let's talk about a wireless access point. So, although a wireless access point interconnects a wired local area network with a wireless local area network, it does not interconnect two networks like the service provider's network and the internal network. And this picture right here on your screen shows a typical deployment of an access point. So in this picture, the access point connects to the wired local area network and the wireless devices that connect to the wired LAN via the access point. They are on the same subnet as the access point, and no address translation or port address translation is being performed. So the wireless access point, it is acting as a wireless bridge between the wireless clients connected to the access point and the wired devices connected to the switch in the same layer 2 domain. Now, to manage multiple access points, a company uses a wireless local area network controller, or a WLC, for centralized management and control of the access points. A Cisco Model 5760 WLC, this is an example of a network controller for multiple access points. The protocols used to communicate between an access point and a WLC could be the older lightweight access point protocol or the more current control and provisioning of wireless access points protocol. And with the WLC, VLAN pooling can be used to assign IP addresses to wireless clients from a pool of IP subnets and their associated VLANs. All right, next let's talk about antennas. So the coverage area of a wireless local area network is largely determined by the type of antenna used on a wireless access point or a wireless router. Although some lower end consumer grade wireless access points have fixed antennas, higher end enterprise class wireless access points, they often support various antenna types. And the design goals to keep in mind when selecting an antenna include the following. You need to know the required distance between an access point and a wireless client. You need to know the coverage area pattern. So for example, the coverage area might radiate out in all directions, forming a spherical coverage area around an antenna, or an antenna might provide increased coverage in only one or two directions. You need to know the type of environment you're going to be in, whether it's going to be indoor or outdoor, and you need to avoid interference with other access points. Now, the strength of the electromagnetic waves being radiated from an antenna, this is referred to as gain, and it involves a measurement of both direction and efficiency of a transmission. So, for example, the gain measurement for a wireless access point's antenna transmitting a signal is a measurement of how efficiently the power being applied to the antenna is converted into electromagnetic waves being broadcast in a specific direction. Conversely, the gain measurement for a wireless access point's antenna receiving a signal is a measurement of how efficiently the received electromagnetic waves arriving from a specific direction are converted back into electricity leaving the antenna. And gain is commonly measured using the dBi unit of measure, where dB, that stands for decibels, and the I stands for isotropic. A decibel in this context, this is a ratio of radiated power to a reference value. In the case of dBi, the reference value, this is the signal strength of the power radiated from an isotropic antenna, which represents a theoretical antenna that radiates an equal amount of power in all directions or in a spherical pattern. And an isotropic antenna, this is considered to have a gain of 0 decibels. Now, antennas, they are classified not just by their gain, but also by their coverage area. And there are two broad categories of antennas based on coverage area. The first one you have is called omnidirectional. So an omnidirectional antenna, this radiates power at relatively equal power levels in all directions. And omnidirectional antennas, they are popular in residential wireless local area networks and SOHO locations. And then the next one you have is called a unidirectional. So a unidirectional antenna can focus its power in a specific direction, thus avoiding potential interference with other wireless devices and perhaps reaching greater distances than are possible with omnidirectional antennas. And one application for a unidirectional antenna is interconnecting two nearby buildings. All right, next let's talk about frequencies and channels. So later you're going to learn about a variety of wireless standards, which are all variants of the IEEE 802.11 standard. And as you contrast one standard with another, a characteristic to watch out for is the frequencies at which these standards operate. Although there are some country-specific variations, certain frequency ranges, which are also known as frequency bands, have been reserved internationally for industrial, scientific, and medical purposes. These frequency bands, they are called ISM bands, where the ISM derives from industrial, scientific, and medical. And two of these bands are commonly used for wireless local area networks. Specifically, wireless LANs use the range of frequencies in the 2.4 gigahertz to 5 gigahertz range. In fact, some wireless LANs, they support a mixed environment where 2.4 gigahertz devices can run alongside 5 gigahertz devices. And as a side note, the latest wireless standard, which is 802.11ax or Wi-Fi 6, it takes Wi-Fi operation to the 6 gigahertz frequency. Wi-Fi 6 uses up to 14 additional 80 megahertz channels or 7 additional super wide 160 megahertz channels in the 6 gigahertz band. And this new technology is ideal for applications such as high definition video streaming and virtual reality. Now, within each band are specific frequencies, which are also known as channels, at which wireless devices operate. To avoid interference, nearby wireless access points should use frequencies that do not overlap with one another. And you can use wireless survey tools to analyze what is currently in use so you can set up a new wireless system that does not compete for the frequencies that are already in use. And those same tools can also help you identify wireless channel utilization in existing and new wireless networks. So regarding channel selection, merely selecting different channels, this is not sufficient because transmissions on one channel can spill over into nearby channels. So site survey tools, they can collect data to show the relative strength of signals in the areas being serviced by the access points. And the output, it can be color coded and overlaid on top of a floor plan. And this is often referred to as a heat map of the wireless signals. Now consider, for example, the 2.4 gigahertz band. Here, channel frequencies, they are separated by 5 megahertz, with the exception of channel 14, which has 12 megahertz of separation from channel 13. However, a single channel's transmission can spread over a frequency range of 22 megahertz. And as a result, channels must have 5 channels of separation. And as you can see in this picture right here, in the United States, you could select the non-overlapping channels of channels 1, 6, and 11. Now, as a side note, even though some countries, they use channel 14 as a non-overlapping channel, channel 14 is not supported in the United States. And as a reference, this table right here on your screen, this shows the specific frequencies for each of the channels in the 2.4 gigahertz frequency band. And the 5 gigahertz frequency band, this has more channels than the 2.4 gigahertz band. And this table on your screen, it lists the recommended non-overlapping channels for the 5 gigahertz band in the United States. And note that additional channels, they are supported in some other countries. All right, next let's talk about CSMA-CA. So you learned about carrier sense multiple access with collision detection, or CSMA-CD technology in previous videos. Wireless LANs, they use a similar technology called carrier sense multiple access with collision avoidance. And just as CSMA-CD is needed for half duplex Ethernet connections, CSMA-CA, this is needed for wireless LAN connections because of their half duplex operation. Similar to the way an Ethernet device listens to an Ethernet segment to determine whether a frame exists on the segment, a wireless LAN device listens for a transmission on a wireless channel to determine whether it is safe to transmit. In addition, the collision avoidance part of the CSMA-CA algorithm causes wireless devices to wait for a random back-off timer before transmitting. All right, next let's talk about transmission methods. So earlier you learned about the frequencies used for various wireless channels. However, you need to be aware that each of those frequencies is considered to be the center frequency of a channel. So in actual operation, a channel uses more than one frequency, which is a transmission method called spread spectrum. And these frequencies are, however, very close to one another, which results in what is called narrow band transmission. And here are the three variables variations of spread spectrum technology to be aware of as you study wireless local area networks. The first one is called direct sequence spread spectrum. So direct sequence spread spectrum, this modulates data over an entire range of frequencies by using a series of symbols that are called chips. A chip, this is shorter in duration than a bit, meaning that the chips are transmitted at a higher rate than is the actual data. And these chips encode not only the data being transmitted, but also what appears to be random data. Although both parties involved in the direct sequence spread spectrum communication know which chip represents actual data and which chips do not. If a third party intercepted that transmission, it would be difficult for that party to eavesdrop on the data because they would not easily know which chips represented valid bits. In direct sequence spread spectrum, this is more subject to environmental factors than the next two frequencies of FHSS and OFDM that we're going to talk about in a second because of its use of an entire frequency spectrum. So next we have frequency hopping spread spectrum, or FHSS. So FHSS, this allows the participants in the communication to hop between predetermined frequencies. Security is enhanced because the participants can predict the next frequency to be used, but a third party cannot easily predict the next frequency. And FHSS can also provision extra bandwidth by simultaneously using more than one frequency. And then we have orthogonal frequency division multiplexing, or OFDM. So whereas DSSS, this uses a high modulation rate for the symbols it sends, OFDM uses a relatively slow modulation rate for symbols. And this slower modulation rate combined with the simultaneous transmission of data over 52 data streams, this helps OFDM support high data rates while resisting interference between the various data streams. Now, as a side note, Wi-Fi 6, this features the latest enhancements in technology and uses the latest spread spectrum technology. And this is called orthogonal frequency division multiple access, or OFDMA. And OFDMA, this provides sophisticated scheduling techniques to provide better performance in highly congested Wi-Fi environments. All right, next let's talk about the wireless LAN standards. So most modern wireless LAN standards, once again, they are variations of the original IEEE 802.11 standard, which was developed back in 1997. And this original standard supported a DSSS implementation and an FHSS implementation, both of which operated in the 2.4 gigahertz band. However, with supported speeds of 1 megabit per second or 2 megabit per second, the original 802.11 standard lacks sufficient bandwidth to meet the needs of today's wireless local area networks. And the most popular variants of the 802.11 standard in use today are 802.11a, b, g, n, ac, and ax. So let's talk about 802.11a. So the 802.11a wireless LAN standard, this supports speeds as high as 54 megabits per second. Other supported data rates, which can be used if conditions are not suitable for the 54 megabits per second rate, they include 6, 9, 12, 18, 24, 36, and 48 megabits per second. And the 802.11 standard, it uses the 5 gigahertz band and uses the OFDM transmission method. And interestingly, the 802.11a, it never gained widespread adoption because it was not backwards compatible with the 802.11b, whereas the 802.11g was backwards compatible. However, it is worth noting that the 802.11a is a possible alternative to the 802.11b and g, as the 2.4 gigahertz band is often far more crowded than the 5 gigahertz band. And then next we have the 802.11b. So the 802.11b wireless LAN standard, it supports speeds as high as 11 megabits per second. However, 5.5 megabits per second is another supported data rate. And the 802.11b standard uses the 2.4 gigahertz band and it uses the DSSS transmission method. All right, next we have the 802.11g. So the 802.11g wireless LAN standard supports speeds as high as 54 megabits per second. And like the 802.11a, the 802.11g also supports data rates of 6, 9, 12, 18, 24, 36, and 48 megabits per second. However, like the 802.11b, the the 802.11g operates in the 2.4 gigahertz band, which allows it to offer backwards compatibility to the 802.11b devices. And 802.11g can use either the OFDM or the DSSS transmission method. And next we have the 802.11n, which is also known as Wi-Fi 4. So the 802.11n wireless LAN standard supports a wide variety of speeds depending on its implementation. Although the speed of an 802.11n network could exceed 300 megabits per second through the use of channel bonding, many 802.11n devices on the market have speed ratings in the 120 to 150 megabit per second range. And 802.11n wireless LANs, they can operate in the 2.4 gigahertz band, the 5 gigahertz band, or both of them simultaneously. And 802.11n, it uses the OFDM transmission method. And one way the 802.11n achieves superior throughput is through the use of a technology called multiple input, multiple output, or MIMO. So MIMO uses multiple antennas for transmission and reception. These antennas do not interfere with one another thanks to MIMO's use of what is called spatial multiplexing, which encodes data based on the antenna from which the data will be transmitted. Both reliability and throughput are increased by MIMO's simultaneous use of multiple antennas. And yet another technology implemented by the 802.11n, this is called channel bonding. So with channel bonding, two wireless bands are logically bonded together, forming a band with twice the bandwidth of an individual band. Now, some literature that you might come across might refer to channel bonding as 40 megahertz mode, which is the bonding of two adjacent 20 megahertz bands into a 40 megahertz band. And also the 802.11n high throughput standard, this defines modes for ensuring that older A, B, and G devices and newer 802.11n devices, they avoid collisions with one another. All right, moving on, we have the 802.11ac, which is also known as Wi-Fi 5. So 802.11ac, this is a 5 gigahertz standard that uses more simultaneous streams than the 802.11n and features multiple user MIMO. And it has a single 80 megahertz stream that supports 433 megabits per second. And then finally, we have the 802.11ax, which is known as Wi-Fi 6. So 802.11ax, this is up to 30% faster than Wi-Fi 5 or 802.11ac, but even more exciting are its lower latency, more simultaneously deliverable data, and improved power efficiency. And Wi-Fi 6, this is the first iteration of the 802.11 to include OFDMA, which is an improvement on OFDM. And OFDMA, this can transmit data to multiple devices at the same time. It does so by splitting traffic into smaller packets to eliminate queuing. And also Wi-Fi 6, this adds multiple user MIMO capabilities to upstream connections. And the net effect of this is to allow more devices on one network at the same time. All right, now let's talk about the 802.11x standard summary. So basically what you're looking at right here is a table that provides a reference to help you contrast the characteristics of the various 802.11 standards. Now, other forms of wireless technologies are in a group called cellular because the technology is used on cell phones amongst other mobile devices. And some cellular phone technologies such as long-term evolution or LTE, they support a 100 megabit per second data rate for mobile devices and a 1 gigabit per second data rate for stationary devices. And they can be used to connect a mobile device such as a smartphone to the internet. Other technologies for cellular phones include the older 2G, which was known as Edge, which offers slow data rates. Then we got 2G that was improved upon with 3G. And in addition to the newer 4G, 5G, LTE, and Evolve High-Speed Packet Access or HSPA+. And then we have what is called tethering. This allows a smartphone's data connection to be used by another device, such as a laptop. Also, mobile hotspots, they are growing in popularity because these devices can connect to a cell phone's company's data network and make that data network available available to nearby devices. And this is typically with a maximum of 5 devices via wireless networking technologies. And then we have what is called Code Division Multiple Access, or CDMA, and Global System for Mobile Communications, or GSM. And these are two major radio systems that are used in cell phones. And GSM, this uses what is called Time Division Multiple Access in its operation. In this video, you're going to learn about deploying wireless LANs as it relates to the type of wireless LANs, sources of interference, and wireless access point placement. So a variety of installation options and design considerations are involved in designing and deploying wireless LANs. And this video is going to go into the available options and provide you with some of the best practice recommendations. So let's talk about the types of wireless LANs that are out there. So wireless LANs, they can be categorized based on their use of wireless access points. And the three main categories are independent basic service set, or IBSS, or ad hoc. Do you have basic service set, or BSS? And then you have extended service set, or ESS. And an IBSS wireless LAN, this operates in an ad hoc fashion, whereas BSS and ESS wireless LANs, they operate in infrastructure mode. And the following information is going to describe these three types of wireless LANs in detail. All right, first one you have is the IBSS, or the independent basic service set. So as you can see in this picture right here, a wireless LAN can be created without the use of an access point. And such a configuration, which is once again called an IBSS, this is said to work in an ad hoc fashion. And an ad hoc wireless LAN is useful for temporary connections between wireless devices. So for example, you might temporarily interconnect two laptop computers to transfer a few files. All right, next we have the basic service set, or the BSS. In this picture right here, this depicts a wireless LAN using a single access point. And a wireless LAN that just has one access point, once again, this is called a BSS wireless LAN. And BSS wireless LANs are said to run in infrastructure mode because wireless clients can connect to an access point, which is typically connected to a wired network infrastructure. And BSS networks, they are often used in residential and SOHO locations where the signal strength provided by a single access point is sufficient to service all of the wireless LAN wireless clients. And next we have what is called the extended service set, or the ESS. And this picture right here illustrates a wireless LAN using two access points. And like a BSS wireless LAN, ESS wireless LANs, they operate in infrastructure mode as well. And when you have more than one access point, it is important to prevent one access point from interfering with another. Specifically, the previously discussed non-overlapping channels, which are channels 1, 6, and 11 for the 2.4 gigahertz band, they should be selected for adjacent wireless coverage areas. And then we have what is called a mesh topology. So a mesh wireless network, this is a collection of wireless devices that may not use centralized control, but instead features centralized management. And the combined wireless coverage range defines the range of the network. And this could also be referred to as a mesh cloud. And additional wireless technologies besides Wi-Fi could be used to build a mesh wireless topology. And this type of network could be used for hosts to communicate with other devices in the mesh, or the network could provide a gateway to the internet or to other networks. All right, moving on, let's talk about sources of interference. So a major issue with wireless LANs is radio frequency interference, or RFI, and this is caused by other devices using frequencies similar to those of the wireless LAN devices. Also, physical obstacles can impede or reflect wireless LAN transmissions. And the following, these are some of the most common sources of interference. The first one is other wireless LAN devices. So you've already learned about non-overlapping channels for both the 2.4 gigahertz and 5 gigahertz bands. If two or more wireless LAN devices are in close proximity and use overlapping channels, those devices could interfere with one another. Next, we have cordless phones. So several models of cordless phones operate in the 2.4 gigahertz band, and they can interfere with wireless LAN devices. However, if you need cordless phones to coexist in an environment with wireless LAN devices using the 2.4 gigahertz band, band, you want to consider the use of what is called a digital enhanced cordless telecommunications, or a DECT, or a DEC cordless phone. Although the exact frequencies used by DEC cordless phones, they vary based on the country. DEC cordless phones do not use the 2.4 gigahertz band. So for example, in the United States, DEC cordless phones use frequencies in the range of 1.92 gigahertz to 1.93 gigahertz. Next type of interference is the microwave oven. So older microwave ovens, which might not have sufficient shielding, they can emit relatively high powered signals in the 2.4 gigahertz band, which could result in significant interference with wireless local area network devices that are operating in the 2.4 gigahertz band. Next, we have wireless security system devices. So most wireless security cameras, they operate in the 2.4 gigahertz frequency range, and that can cause potential issues with wireless LAN devices as well. Then you have physical objects. So in electromagnetic theory, radio waves cannot propagate through a perfect conductor. So although metal filing cabinets and large appliances are not perfect conductors, they are sufficient to cause degradation of a wireless LAN signal. So for example, a wireless LAN signal, it might hit a large air conditioning unit, causing the radio waves to be reflected and scattered in multiple directions. Not only does this limit the range of the wireless LAN signal, but radio waves carrying data might travel over different paths. In this multi-path issue, this can cause data corruption. Also, concrete walls, metal studs, and even window film, they can reduce the quality of the wireless network signal. And then we have signal strength. So the range of a wireless LAN device is a function of the device's signal strength. In lower cost consumer grade access points, they do not typically allow administrative adjustment of signal strength. However, enterprise class access points, they often allow signal strength to be adjusted to ensure sufficient coverage of a specific area while avoiding interference with other access points using the same channel. Now, as you can see from the list that I just went over, most RFI occurs in the 2.4 gigahertz band rather than the 5 gigahertz band. Therefore, depending on the wireless clients that you need to support, you might want to consider using the 5 gigahertz band, which is an option with the newer wireless standards. With the increased use of wireless, both coverage and capacity-based planning should be done to provide acceptable goodput. In goodput, this refers to the number of useful information bits that the network can deliver, not including overhead for the protocols being used. And another factor is called the density, or the ratio of users to the access points. And if this is too high, this could harm performance on the network. In areas expecting high density, they include classrooms, hotels, and hospitals, and also device or bandwidth saturation. This could also impact network performance as well. All right, let's talk about wireless access point placement. So a wireless LAN using more than one access point, which is an ESS wireless LAN, this requires careful planning to prevent the access points from interfering with one another while still servicing a desired coverage area. Specifically, an overlap of coverage between access points should exist to allow uninterrupted roaming from one wireless LAN cell to another. In a wireless LAN cell, this is the coverage area that is provided by the access point. However, those overlapping coverage areas should not use overlapping frequencies. In this picture on your screen right here, this shows how non-overlapping channels in the 2.4 gigahertz band can have overlapping coverage areas to provide seamless roaming between access point coverage areas. And a common wireless LAN design recommendation is to have 10 to 15% overlap of coverage between adjoining cells. And if a wireless LAN has more than 3 access points, the access points are deployed in a honeycomb fashion to allow an overlap of access point coverage areas while avoiding an overlap of identical channels. And this picture right here shows an approach to channel selection for adjoining cells in the 2.4 gigahertz band. Notice that the cells using the same non-overlapping channels, which are channels 1, 6, and 11, they are separated by another cell. And so, for example, notice that none of the cells using channel 11 overlap another cell that's using channel 11. Now, as a side note, although a honeycomb channel assignment scheme can be used for the 5 gigahertz band, identical channels should be separated by at least 2 cells rather than a single cell for the 2.4 gigahertz band.
In this video, you're going to learn about securing wireless LANs as it relates to security issues, approaches to wireless LAN security, security standards, and additional wireless options. So wireless LANs, they introduce some unique concerns to a network. So for example, improperly installing wireless access points is roughly equivalent to putting an Ethernet port in a building's parking lot where someone can drive up and access your network. Fortunately, various features are available to harden the security of your wireless LAN. So let's go ahead and talk about some of these security issues. So in the days when dial-up modems were popular, malicious users could run a program on a computer to call all phone numbers in a certain number range. Phone numbers that answered with a modem tone, they became targets for later attacks. This type of reconnaissance was known as war dialing. And a modern day variant of war dialing, this is called war driving, where potentially malicious users, they drive around looking for unsecured wireless LANs. These users might be identifying unsecured wireless LANs for nefarious purposes or simply looking for free internet access. And devices such as cell phones, laptops, tablets, and gaming and media devices, they could act as wireless clients as well and be used in a wireless attack because they have potential Wi-Fi access to the network. And other wireless LAN security threats, they include the following. The first one is called war chalking. So once an open wireless LAN, which is a wireless LAN whose SSID and authentication credentials are known, once that wireless LAN is found in a public place, a user might write a symbol on a wall or some other nearby structure to let others know the characteristics of the discovered network. All right, next we have WEP and WPA security cracking. So like we talked about before, various security standards are available for encrypting and authenticating a wireless local area network client with an access point. And two of the less secure standards are wired equivalent privacy or WEP and Wi-Fi protected access or WPA. Now, although WPA is considered more secure than WEP, utilities are available on the internet for cracking each of these approaches to wireless security. By collecting enough packets transmitted by a secure access point, these cracking utilities can use mathematical algorithms to determine the pre-shared key configured on a wireless access point with which an associating wireless client must also be configured. All right, next we have what is called a rogue access point. So a malicious user may set up an access point called a rogue access point to which legitimate users can't connect. The malicious user might then use a packet sniffer, which displays information about unencrypted traffic, including the traffic's data and header information, to eavesdrop on communications flowing through the rogue access point. And to cause unsuspecting users to connect to the rogue access point, the malicious user could configure the access point with the same service set identifier or SSID used by the legitimate access point. And when a rogue access point is configured with the SSID of a legit access point, the rogue access point is commonly referred to as an evil twin. Now, as a side note, an SSID, this is a string of characters identifying a wireless local area network. And access points participating in the same wireless LAN, that is an ESS, they can be configured with identical SSIDs. An SSID shared among multiple access points, this is called an extended service set identifier or ESSID. All right, so let's talk about approaches to wireless LAN security. So a wireless local area network that does not require authentication or provide encryption for wireless devices, such as a publicly available wireless LAN, such as the ones that you might find in many airports. This is said to be using what is called open authentication. And to protect such a wireless LAN's traffic from eavesdroppers, a variety of security standards and practices have been developed, which include the following. The first one is called MAC address filtering. So an access point, it can be configured with a list of MAC addresses that are permitted to associate with the access point. If a malicious user attempts to connect via a laptop whose MAC address is not on the list of trusted MAC addresses, that user is denied access. Now, one drawback to MAC address filtering is the administrative overhead required to keep an approved list of MAC addresses up to date. Another issue with MAC address filtering is that a knowledgeable user could falsify the MAC address of a wireless network card, making a device appear to be approved. All right, the next way to protect protect the wireless local area network, you can disable the SSID broadcast. So an SSID can be broadcast by an access point to let users know the name of the wireless local area network. For security purposes, an access point might be configured not to broadcast its SSID. However, knowledgeable users could still determine the SSID of an access point by examining captured packets. And then we have what is called pre-shared keys. So to encrypt transmission between a wireless client and an access point, in addition to authentication of a wireless client with an access point, both the wireless client and the access point could be pre-configured with a matching string of characters or a PSK or pre-shared keys. The PSK could be used as part of a mathematical algorithm to encrypt traffic, such that if an eavesdropper intercepted the encrypted traffic, they would not be able to decrypt the traffic without knowing the PSK. Although using a PSK can be effective in providing security for a small network such as a SOHO network, it lacks scalability. So for example, in a large corporate environment, the compromise of a PSK would necessitate the reconfiguration of all devices configured with that PSK. Wireless LAN security based on PSK technology. This is called personal mode. And as a side note, the latest WPA security approach, this is called WPA3, running in personal mode, which replaces the PSK approach with a more secured method of authentication called simultaneous authentication of equals, or SAE. All right, and then we have IEEE 802.1x. So rather than having all devices in a wireless LAN configured with the same PSK, a more scalable approach is to require all wireless users to authenticate using their own credentials, such as a username and password. Allowing users to have their own credentials prevents the compromising of one password from impacting the configuration of all wireless devices. IEEE 802.1x, this is a technology that allows wireless clients to authenticate with an authentication server, typically a radius server or a remote authentication dial-in user service. In this picture right here on your screen, this shows a wireless implementation of the IEEE 802.1x. Now, as a side note, wireless LAN security based on IEEE 802.1x and a centralized authentication server as a radius, this is called enterprise mode. Also, IEEE 802.1x, it works in conjunction with what is called Extensible Authentication Protocol, or EAP, to perform its job of authentication. And a variety of EAP types, they exist, including lightweight extensible authentication protocol. You got EAP, flexible authentication via secure tunneling, or EAP fast. You have EAP transport layer security. You have EAP tunnel transport layer security, protected EAP generic token card, and protected EAP Microsoft Challenge Handshake Authentication Protocol version 2. Now, although these EAP types differ in their procedures, the overriding goal for all of the EAP types is to securely authenticate a supplicant and provide the supplicant and the authenticator a session key that can be used during a single session in the calculation of security algorithms, such as encryption algorithms. All right, next let's talk about security standards. So when you're configuring a wireless client for security, the most common security standards from which you can select are the following. You have what is called wired equivalent privacy, or WEP, Wi-Fi protected access, or WPA, and Wi-Fi protected access version 2, or WPA2. Now, as a side note, while it's not widely implemented currently, remember that WPA3 technology is now available and makes further improvements in the wireless LAN security. So let's go ahead and talk about the first one, which is WEP, or wired equivalent privacy. So the original 802.11 standard, it addressed security. However, the security is a WEP key. And with WEP, an access point is configured with a static WEP key. Wireless clients that need to associate with an access point are configured with an identical key, making this a PSK approach to security. The 802.11 standard specifies a 40-bit WEP key, which is considered to be relatively weak security measures. Now, because a WEP key is a static string of characters, it could be compromised with a brute force attack, in which an attacker attempts all possible character combinations until a match for the WEP key is found. And another concern, however, is that the WEP, it uses what is called RC4 as its encryption algorithm. Now, as a side note, RC4, this stands for Ron's code, or Rives cipher, because it was developed by a person named Ron Rives of RSA Security, and it's also sometimes pronounced ARC4.
Now, RC4, it uses a 24-bit initialization vector, and this is a string of characters added to the transmitted data such that the same plain text data frame will never appear as the same web encrypted data frame. However, the initialization vector is transmitted in plain text. So because a malicious user can see the initialization vector in plain text, if they use packet capture software and capture enough packets having the same web key, they can use a mathematical algorithm to determine the static web key, which can be performed with web cracking software that is available on the internet. In some web implementations, they support the use of a longer web key, such as 128 bits instead of 40 bits, making a web key more difficult to crack. However, both the wireless clients and the access point, they must support the longer web key. All right, next we have Wi-Fi protected access. So the Wi-Fi Alliance, which is a nonprofit organization formed to certify interoperability of wireless devices, developed its own security standard, which is WPA, to address the weaknesses of web. And here are some of the security enhancements offered by WPA. So WPA operating in enterprise mode can require a user to be authenticated before keys are exchanged. In enterprise mode, the keys used between a wireless client and an access point are temporary session keys. And WPA uses what is called TKIP, or Temporal Key Integrity Protocol, for enhanced encryption. Although TKIP does rely on an initialization vector, the IV is expanded from WEP's 24-bit IV to a 48-bit IV. Also, broadcast key rotation can be used, which causes a key to change so quickly that an eavesdropper would not have time to exploit a derived key. And TKIP uses RC4 for its encryption algorithm. So when you're out there taking your CompTIA Network Plus exam, you might see it referenced as TKIP-RC4. And then also TKIP, it leverages what is called message integrity check, which is sometimes referred to as message integrity code, to confirm that data has not been modified in transit. And then we have what is called WPA2. So the IEEE 802.11i standard, which was approved in 2004, this requires stronger algorithms for encryption and integrity checking than those used with previous versions of wireless LAN security protocols such as WEP and WPA. The requirements set forth in the IEEE 802.11i standard are implemented in the Wi-Fi Alliance's WPA version 2, or WPA2 security standard. And WPA2 uses what is called counter mode with cipher blockchaining message authentication code protocol, or CCMP, for integrity checking, and advanced encryption standard, or AES, for encryption. Now, on the Network Plus exam, you might find this referenced simply as CCMP-AES. Now, WPA2, that uses a centralized server for authenticating users, this is called WPA2 Enterprise Mode. And an implementation of WPA2 that uses a configured password, or PSK, instead of a centralized server, this is referred to as WPA2 Personal Mode. All right, finally, let's talk about some additional wireless options. So other wireless technologies such as Bluetooth, infrared, and near-field communication, which are often integrated into smartphones, can also provide connectivity for a personal area network or other short-range networking applications. And many of these technologies, they help to facilitate what is called the Internet of Things. And another interesting wireless technology is called geofencing, which often uses the GPS or the RFID, or radio frequency identification, to define geographic boundaries. Geofencing allows you to define triggers so that when a device enters or exits the boundaries defined by the administrator, an alert is issued. And geofence virtual barriers, they can be active or passive. So active geofences, they require an end user to opt in to location service and require a mobile app to be open. Passive geofences are always on. They rely on Wi-Fi and or cellular data instead of GPS or RFID, and they can work in the background. And a practical application of geofencing might be a hospital with patient information on tablets that the hospital distributes to staff. If these tablets travel beyond the geofence, an administrative alert can trigger. In this video, you're going to learn about monitoring tools as it relates to performance metrics and sensors, and simple network management protocol. All right, so let's talk about some of these monitoring tools. So for several decades, simple network management protocol or SNMP based software packages, they dominated in the enterprise monitoring space. Fortunately, SNMP evolved over several versions to include security enhancements. Even with these advancements, as you'll learn later, there are other methods and technologies to consider when it comes to monitoring a network. And this video is going to discuss some key performance metrics and sensors that you need to monitor. So let's go ahead and talk about the performance metrics and sensors. So as networks have become more and more important to the organizations that host them, metrics have increasingly become available to carefully monitor and assess the health of network components. In fact, you need to be careful not to overwhelm yourself by trying to monitor too many metrics for your devices. So the following are some key metrics that can help you monitor a device and the device's chassis. And the first metric is temperature. So network equipment vendors, they make it very clear what temperature range is supported for inside the device chassis. Of course, you will not want the temperature to exceed or go too far below this recommended range. You might run into temperature problems. So for example, if your network equipment was not installed following best practices and there is not adequate distance between a device and other objects, these other objects might be blocking airflow to the network device. So maybe the warm air that is supposed to be pushed out of the chassis is getting caught and trapped inside the chassis. And sensors, they can provide metrics regarding the temperature inside network devices to help you pinpoint such issues. And later you're going to learn about this tool called environmental monitors that are specialized for monitoring things like temperature, humidity, and much more. All right, the next metric is the CPU usage. So the CPU, this is the brains of a computer, often navigating the tricky waters of the control plane processing requirements for you. And it is very important to monitor CPU utilization consistently over the life of a network device. Doing so can help you identify network attacks and the busy times for network devices where performance is actually suffering. In addition, monitoring the CPU can help you see when components are beginning to fail and causing high CPU utilization. All right, the next metric is memory. So to improve the performance of network devices, data is taken from non-volatile storage and placed in much faster volatile memory. Of course, you need to make sure you have enough memory available for this at all times, and monitoring the various memory metrics, this can help you track down lots of current and potential performance issues. Now, as you can imagine, it is important to carefully monitor these metrics for a network device and its chassis. In addition, you should also carefully monitor the network itself. So the following are some of the basic metrics for monitoring a network. And the first one is called the bandwidth. So the plumbing of your network is the connections between the devices. Remember that these connections might be physical media that you can see, and they might also be wireless media that you cannot see. So carefully measuring the bandwidth available and bandwidth consumed by specific applications or traffic, this is imperative. You want to watch out for bottlenecks in the network design, which often occur when a network designer fails to consider the aggregate bandwidth required. So for example, say that you have 100 gigabit per second ports, and you need to plan for busy times when those 100 really fast ports all have lots of data they want to send. You might require multiple 40 gigabit per second connections upstream to handle the aggregate bandwidth needs. All right, the next metric is latency. So latency, which is also known as delay. So when a network device sends packets, there will be serialization delay, propagation delay, processing delay, and probably even more types of delays. You need to take baseline measurements so you can understand the latency in your network. You should also pay attention to the requirements for certain technologies. So for example, perhaps your organization wants to engage with the latest Cisco collaboration solutions, including voice and video over IP. Cisco will give you documentation on just the latency that the solutions can handle. Cisco might say something like, for this solution to perform well, you must not exceed 120 milliseconds of delay consistently over time. It is important to gather data on such metrics before you even consider rolling out a solution. And the next metric is called jitter. So jitter, this is a large variation in latency. Jitter is especially problematic for voice over IP traffic. And if the latency in the network network is not predictable and fairly steady, it can be very difficult for voice over IP quality to remain steady and satisfactory. Now, as a side note, so for all the major metric categories, you should ensure that you perform baselining and properly store the results for future analytics. In a baseline, this provides a look at the metrics and their values during normal operation. If your network tends to run at 45% capacity, then you will want to watch for this level of usage and then start capturing your metric information to create a baseline. And this is incredibly important and brilliant. So think about it. If you do not know what the metric measures when everything is fast and brilliant and performing just as you need it to, how are you going to be able to identify when things are starting to go badly? Always keep baselines of metric data for your enterprise is the message here. All right, next let's talk about SNMP. So the first request for comments was called Simple Network Management Protocol, which came out in 1988. Since then, SNMP has become the de facto standard for network management protocols. The original intent of SNMP was to manage network nodes such as network servers, routers, and switches. SNMP version 1 and SNMP version 2C specify three major components of an SNMP solution, which are detailed in the following information. So you have what is called the SNMP manager. So in SNMP manager, it runs a network management application. And this SNMP manager is sometimes referred to as a network management system or an NMS. And then you have what is called the SNMP agent. An SNMP agent, this is a piece of software that runs on a managed device, such as a server, router, or a switch. And then you have what is called the management information base, or the MIB, or the MIB. So information about a managed device's resources and activity. This is defined by a series of objects. The structure of these management objects is defined by a managed device's MIB. And interfaces in their details, such as errors, utilization, discards, packet drops, resets, speed and duplex, system memory, utilization of bandwidth, storage, CPU, and memory, all of that can be monitored and reported via the SNMP. Now, as illustrated in this picture on your screen right here, an SNMP manager or an NMS, this can send information to, receive request information from, or receive unsolicited information from a managed device such as a managed router. And the managed device, this runs an SNMP agent and contains the MIB. Now, clearly, the MIB, this is a critical component in the functionality of the SNMP. It is a hierarchical collection of MIB variables that store the data that SNMP relies on. But how are these MIB variables identified? Well, this is done using a unique object identifier, or OID, for each variable. And the OIDs, they're organized in a hierarchical tree-like structure. And SNMP is very efficient at scanning this tree and extracting the exact OIDs and values of these variables that are needed to monitor or even reconfigure a network device. And we have multiple SNMP messages that can be sent between an SNMP manager and a managed device. And there are three broad categories of SNMP message types. And the first one is called a GET message. So an SNMP GET message, this retrieves information from a managed device. You have set. So when SNMP set message, this sets a variable in a managed device or triggers an action on a managed device. And then you have the trap, an SNMP trap message. This is an unsolicited message sent from a managed device to an SNMP manager, which can notify the SNMP manager about a significant event that occurred on the managed device. And SNMP management software, it can make requests for each of the MIB objects from an SNMP agent. And this can be referred to as an SNMP walk, because the management software is logically walking the entire MIB, which is also called a tree, to gather information from the agent. SNMP offers security against malicious users attempting to collect information from a managed device, and they can change the configuration of a managed device, or they can intercept information being sent to an NMS. However, the security integrated with SNMP version 1 and version 2C is considered weak. Specifically, SNMP version 1 and version 2C, they use what are called community strings to gather read-only access or read-write access to a managed device. And you can think of a community string as a password. Also, be aware that multiple SNMP compliant devices on the market today have the read-only community string set to public by default and have the read-write community string set to private by default. And as a result, if such devices are left at their default SNMP settings, they could be compromised. Now, fortunately, the security weaknesses of SNMP version 1 and version 2C are addressed in SNMP version 3. To better understand these security enhancements, consider the concept of a security model and a security level. So you have the security model. So this defines an approach for user and group authentication. For example, SNMP version 1, version 2C, and version 3. You have the security level. This defines the type of security algorithm performed on SNMP packets, and the following are the 3 security levels that are discussed here. The first one you have is called no auth, no priv. So that stands for no authorization and no privacy. This security level uses community strings of authorization and does not use encryption to provide privacy. The next one you have is called auth no priv, which stands for authorization yet no privacy. So these security levels provide authorization using hash message authentication code, or HMAC, with the MD5 or secure hash algorithm, or SHA. However, no encryption is used. Then you got the auth priv, which stands for authorization and privacy. So these security levels, they offer HMAC, MD5, or SHA authentication and provides privacy through encryption. Specifically, the encryption uses what is called the cipher block chaining data encryption standard, or DES56 algorithm. Now, as a side note, the security protocols originally featured in SNMP version 3 are still considered strong enough for today's networks. Since then, additions to SNMP version 3 have made it even more secure, and these additions enable high security environments to call on the latest and strongest security mechanisms for key functions, such as encryption, and feature protocols such as AES, or Advanced Encryption Standard. Now, as summarized in this table on your screen right here, SNMP version 3 supports all 3 security levels, and SNMP version 1 and version 2C support only the no auth, no privilege, or no authorization, no privilege security level. Now, through the use of security algorithms, SNMP version 3 dramatically increases the security of network management traffic. Specifically, SNMP version 3 offers 3 primary security enhancements over SNMP version 1 and version 2C. And those enhancements are integrity. So using hashing algorithms, SNMP version 3 ensures that an SNMP message was not modified in transit. You have authentication. So hashing, this allows SNMP version 3 to validate the source of an SNMP message. We have encryption. So using the CBC DES, or DES56 encryption algorithm, SNMP version 3 provides privacy for SNMP messages, making them unreadable by an attacker who might capture an SNMP packet. And in addition to its security enhancements, SNMP version 3 differs architecturally from SNMP version 1 and version 2C. SNMP version 3 defines SNMP entities, which are groupings of individual SNMP components. And as shown in this picture right here on your screen, SNMP applications and an SNMP manager, they combine into an NMS SNMP entity, whereas an SNMP agent and a MIB combine into a managed node SNMP entity. In this video, you're going to learn about additional monitoring tools such as syslog, logs, application logs, security logs, system logs, environmental monitors, interface statistics and statuses, and NetFlow. All right, so let's talk about additional monitoring tools. So network administrators routinely monitor network resources and review reports to be proactive in their administration. So for example, a potential network issue might be averted by spotting a trend, such as increasing router CPU utilization or increasing bandwidth demand on a wide area network link. Monitoring resources and reports come from various sources, such as a syslog server, an SNMP server, event viewer logs on Microsoft Windows Server, and packet captures from a network sniffer. Remember that monitoring is also critical in the area of network security. So for example, security information and event management are SIEM software products and services. They combine security information management and security event management. And this video is going to introduce a number of resources for monitoring network information. Now, an organization should consistently conduct log reviews. reviews, and a log review should include the following at a minimum. You need to have traffic logs. So you can use a variety of traffic logging mechanisms, many of which are built into devices. So for example, many devices today support what is called NetFlow, which is a powerful traffic monitoring tool that can export traffic flow information to a central collector on a network. Now keep in mind that traffic logging vehicles differ based on the network environment. So for example, while you might rely on NetFlow in an on-premises network, you might be using VPC flow logs in your AWS infrastructure as a service environment. And then you have what is called audit logs. So you might audit many actions in your network environment and record them in an audit log. So for example, a network device might have a setting to log each time an administrator logs into the system and uses admin powers. These logs can be very valuable in tracking and monitoring the admin activities in your network. In AWS Cloud, this offers a tool called CloudTrail that can log every activity that takes place in your public cloud environment. All right, so let's talk about syslog. So a variety of network components such as routers, switches, and servers, they can send their log information to a common syslog server. By having information from multiple devices in a common log and examining timestamps, network administrators can better correlate events occurring on one network device with events occurring on a different network device. And syslog messages and SNMP traps, they can be used to trigger notification messages that may be sent via email and SMS. And the syslog logging solution consists of two primary components. The first one you have is called a syslog server. So a syslog server, it receives and stores log messages sent from syslog clients. And then you have the syslog clients. So as you can see in this picture on your screen right here, various types of network devices can act as syslog clients and send logging information to a syslog server. Messages sent from a syslog client to a syslog server, they can vary in their severity levels. In this table listed on your screen right here, this lists the 8 severity levels of syslog messages. The higher the syslog level, the more detailed the logs. So keep in mind that more detailed logs require additional storage space on a syslog server. And this picture right here shows the format of a syslog message. And the syslog entries, they contain timestamps, which can help you understand how one log message relates to another. And the log entries also include severity level information in addition to the text of the syslog messages. All right, next let's talk about logs. So in addition to logs that are generated by routers, switches, and other infrastructure gear, the operating system powering network clients and servers generally have the capability to produce log output. Rather than containing general log information, such as log information about all of the system's track components, Microsoft Windows incorporates the Event Viewer application, which allows you to view various log types, including application, security, and system logs. And these logs can be archived for later review and can be used to spot network trends and provide data for creating baselines. Now, as a side note, logs are beneficial in your network management endeavors only if they are reviewed. So be sure to document standard operating procedures for periodic and careful review of the many logs that are incorporated into your network. All right, next let's talk about application logs. So Microsoft Windows application logs, they contain information about software applications running on the underlying operating system. And in this picture on your screen right here, you can notice the 3 levels of severity associated with the events in the log. And they are information, warning, and error. The events provide a collection of information about the event, such as the source or the application that caused the event, the severity level of the event, and a date timestamp of that event. And this picture right here shows an example of a Microsoft Windows security log highlighting both successful and failed login attempts. And a Microsoft Windows system log, which you can see on your screen right here, this lists events generated by the underlying operating system. All right, next let's talk about environmental monitors. So components making up a computer network, such as routers, switches, and servers, are designed to operate within certain environmental limits. If the temperature rises too high in a server farm, for example, possibly because of an air conditioning outage, components could begin to fail. To prevent such an occurrence, you can use environmental monitors to send an alert if the temperature in the room rises above or drops below administratively configured thresholds, with the appropriate personnel being alerted about a suspicious temperature variation before it becomes an issue. Action can hopefully be taken to, for example, repairing an air conditioning unit or providing extra ventilation, thus preventing a system failure. In addition to monitoring a room's temperature, you can use environmental monitors to check a room's humidity. Also, environmental monitors, including power and temperature monitors, they can alert appropriate personnel in a variety of ways. So for example, as you learned earlier, some environmental monitors can send alerts to an SNMP server. This type of alert is known as an SNMP trap. Another common modification option allows an environmental monitor to send an email or SMS text message to alert appropriate personnel about the suspect environmental condition. And then you have fault-tolerant power options such as uninterruptible power supplies, fault-tolerance power circuits into the building, generators, and appropriate converters or inverters for the critical network devices. These can assist in preventing downtime in the event of a single power failure. And monitoring systems, they allow you to react and provide redundancy. And devices should be placed in racks in such a way that air can properly flow through the systems in the racks. Racks may be 2 or 4 post racks organized into rows. You have freestanding racks. They can also be used to hold network systems and devices. A rack mounted server, this has rails on the side that allow it to be inserted into a rack. And environmental monitors, they can trigger alerts about potential damage if the humidity or temperature goes outside the values specified for network devices and servers. And environmental monitors and sensors, they can also be used to detect water and send alerts when water is present in a network closet or data center. Whether you had water on the floor due to flooding or water coming from the ceiling due to excessive rain or structural damage to the building, you will want to be alerted to this unwelcome element as quickly as possible. All right, next let's talk about interface statistics and status. So network device interfaces are a key component of a network environment. Fortunately, there are many mechanisms you can use to monitor these important components. You can monitor the various statistics these interfaces have to offer, and you can also obtain at-a-glance status information when you are troubleshooting problems in the network. And the following, these are just some of the statistics and statuses that you need to monitor. So you have what is called the link state. So this tells you if whether or not an interface is up or down or in some other status such as suspended. You got speed and duplex. This shows the speed and duplex settings of the interface. You have the send and receive traffic. So network devices, they can report on the amount of traffic sent and received. You have the CRC, or the cyclic redundancy checks. And CRC, this is a mathematical algorithm that is executed by each sender of packets. The network devices can compare the CRC values received and gather evidence that there was no corruption of the data in transit. And CRC errors, they are an important metric to watch out for. And then you have the protocol packet byte counts. So network interfaces, they can often report on the types of protocols for which they are sending traffic, as well as the number of packets per protocol type. And clearly, this information is very valuable when you are monitoring a network for baseline operation. Now, the following are the specific network interface errors and alerts that you should watch out for at a bare minimum. The first one is the CRC errors. So watch for these errors to ensure that your media is functioning properly and that you do not have attackers attempting to corrupt the data in transit. You have what is called giants. And giants, these are alerts that are reported when packets are larger than 1,500 bytes. In such packet sizes, they might be perfectly normal in your enterprise or data center environment. You have what is called a runt. So like giants, runts are alerts based on packet size. A runt is an Ethernet frame that is less than the IEEE 802.3's minimum length of 64 octets. And runts could be caused by collisions, malfunctioning network interface cards, buffer underruns, duplex mismatches, or other software issues. And then you have encapsulation errors. So perhaps an interface is configured for a PPP operation and you are connected to a device that is not enabled for PPP. This mismatch would prevent the interface from functioning, and the interface would be reported as a line protocol that is down. And then finally, let's talk about NetFlow. So Cisco introduced NetFlow to the world around 1996. And as previously discussed, NetFlow gives network administrators the ability to collect IP network traffic statistics as traffic exits or enters interfaces. By analyzing the data provided by NetFlow, you can learn all kinds of valuable information about how your network is actually being used. And NetFlow can also be a key tool for tracking down network bottlenecks, which tend to be somewhat inevitable. And by using the data collected by NetFlow, you can often quickly determine root causes. So a typical implementation of NetFlow includes the following. You have what is called the flow exporter, and this component aggregates packets into flows and exports flow records towards one or more flow collectors. So you have the flow collector. This component is responsible for reception, storage, and pre-processing of flow data received from a flow exporter. Then you have the analysis application, and you use this application to analyze received flow data in various contexts. So perhaps you were most interested in performance issues during key times of the day, or perhaps you were more concerned about security issues that NetFlow might be able to help pinpoint. In this video, you're going to learn about plans, policies, and common documentation. So let's talk about plans and policies. So many important plans and policies have become fairly commonplace in networks today. While no one likes it when plans and policies are overly complex due to red tape, you should consider many of them for your own organization. And this video is going to list some of the most critical plans and policies for your review. So let's talk about the first one, which is change management. So have you ever made a simple little change to a system and been horrified to see the entire solution self-destruct? It can happen, and because of this, you should ensure that there is a well thought out change management and change control policy in place. You should also have a plan that includes the appropriate change management documentation. And oftentimes, it is necessary to make updates to existing documentation as part of the overall change management process. And change management can help ensure that your network keeps running in good health. It can also ensure that your documentation reflects the true and current state of the objects it is describing. And this is very important for many aspects of your operations, including security purposes and troubleshooting operations. In change management documentation, this often includes the following: a documented reason for a change, the actual change requests, the approval process, the required maintenance window, and the change notification process. Next, we have incident response plan. So because security issues are inevitable in a network, it is critical to prepare a comprehensive incident response plan. And such a policy might outline various phases of incident response, including the following. The first one is prepare, and this often involves being able to identify the start of an incident, preparing a recovery plan, determining how to get everything back to normal, and creating established security policies. Then you have identify. The focus here is on the precise identification of the actual security incident. That you have contain. Here, the main concern is often twofold. First, protecting and keeping available critical computing resources, and second, determining the operational status of the infected computer, system, or network. Ultimately, the goal is to limit the spread of the security incident. Next, you have eradicate. So this phase deals specifically with the removal of the attack or infection. Then we have recover. This phase often includes service restoration as well as recertification of network devices and systems. And then we have review. So all phases should be analyzed in this review phase to gauge their effectiveness and modify the incident response policy as needed for the future. All right, next we have the disaster recovery and business continuity policies. So a business should have a disaster recovery plan and business continuity plan in place so that in the event of any type of downtime due to an attack or natural disaster, the organization can be back up and running to maintain its business. Disaster recovery, this focuses on getting critical applications back online. In business continuity, this focuses on the tasks carried out by an organization to ensure that critical business functions continue to operate during and after a disaster. These plans should include training, identification, training and roles of the first responders, as well as practice drills to confirm that the plans are functional. An organization without these practices in place could fall victim to a permanent denial of service attack, which could ultimately destroy the business if an attacker has damaged the hardware by reflashing firmware with corrupt or defective images to such a point that it is no longer usable. All right, next we have the system life cycle. So your IT networking personnel should consider adhering to a well-planned system life cycle for the equipment and software that is in use. In the system life cycle, this should provide valuable guidance on best practices throughout the organization concerning the network components. So here are some examples of phases in a system life cycle. You have the conceptual design, the preliminary system design, detailed design and development, production and construction, utilization and support, phase out, and disposal. All right, next we're going to talk about common documentation. So documentation, this is useful for proper network management tasks, and it is also critical in troubleshooting, security, optimization, and other key areas of networking today. So consider these important aspects of network documentation. The first one is physical network design. So many of the diagrams that are listed in the bullets that follow can be considered physical network diagrams. And this umbrella term is used to describe many more specifically titled diagrams of specific parts of a network. Then you have what is called the floor plan. So this type of physical network diagram shows the layout of the office space and often the distribution of employee workstations. Next, we have diagram symbols. So your IT department should use standard templates to consistently represent network objects and diagrams, and where needed, legends should clearly delineate one network device from another. You have your standard operating procedures and your work instructions. So whenever possible, it is important to document the procedures your IT staff are to follow given certain network conditions. So for example, steps for dealing with an internet outage could aid staff members in taking quick action and minimizing disruptions. All right, next we have logical network diagrams versus physical diagrams. So the logical and physical flows of data through the organization, this might result in very different diagrams. You have the rack diagrams. So these days, thanks to very small form factors of many network devices, we have more devices than ever before coexisting in a single rack in a data center. Therefore, rack diagrams are needed to assist in the management of all of the various devices in the racks. Then we have the change management documentation. So it is critical that an organization have change controls in place, as well as careful documentation when changes actually take place. And such documentation, this helps ensure the accuracy of network information and can prove critical in security response and troubleshooting operations. And then we have wiring diagrams and port locations. So this documentation allows you to track cable runs from switches and map them to actual wall jacks where users connect to the networks. And these connections might also represent trunks to additional network devices, such as wireless access points. All right, next we have the intermediate distribution frame and the main distribution frame documentation. So these distribution and core facilities, they house critical network data and devices, and proper documentation can aid in all forms of maintenance and security. Then we have labeling. So proper labeling and diagrams, as well as on physical equipment. This can ensure that such documentation is as useful as possible. Then you have network configuration and performance baselines. So you should document the base configuration for network devices, as well as capture data utilization and bandwidth consumption during normal business operations. And this might also include taking SLA or service level agreement measurements during such times. Without this baseline information, it can be nearly impossible to identify subtle performance problems. Next, we have inventory management system. So such a system should track spares, including hot spares, for inevitable hardware malfunctions and keep an inventory of software, including their licenses. You have a site survey report. So site survey reports, these are critical during wireless site surveys, and these site surveys and their reports attempt to describe the Wi-Fi capabilities and potential risk points in an installation. And then you have an audit and assessment report. This report helps you identify and address critical issues that might be occurring in your network infrastructure, and such a report often identifies performance and security issues that need to be addressed in order to help ensure that the network continues to function as desired. Next, we have the baseline configuration. So when you need to return network equipment to the exact configuration that existed at a specific point in time, baseline configuration can come to the rescue. And various stages of the network device life cycle can be captured in these baselines. You have the service level agreement. So it is important to have access to SLAs, which often outline the expected and purchase quality of connections or equipment that is accessed. And then finally, we have what is called a memorandum of understanding. So an MOU, this is an agreement between two parties that outlines the roles and responsibilities that each will play. In MOUs, they often come up in IT business agreements. In this video, you are going to learn about various hardening and security policies, such as password policies, security policies, data loss prevention, remote access policies, bring your own device policies, acceptable use policies, safety procedures, preferred user agreements, onboarding and offboarding procedures, licensing restrictions, international export controls, and non-disclosure agreements. All right, so cybersecurity becomes a bigger challenge for organizations every single day. And we're going to examine many important policies an organization can implement to vastly improve its security posture. Now, keep in mind that not only is it important to create these policies for most organizations, but employees also need to be properly trained in order to closely follow them. So let's go ahead and talk about the first policy, which is a password policy. So because more and more sensitive data is finding its way into storage on our networks, more security measures are required than ever before. Therefore, an organization needs to possess a well-crafted security policy that includes a comprehensive password policy. And as you will learn, you should also provide detailed training on this part of the security policy. Now, keep in mind that in addition to simple username and password combinations, many other powerful technologies used in modern networks are available for user authentication, including the following, such as one-time passwords, client certificates, smart cards, biometrics, and multi-factor authentication. Now, despite these additional security options, simple username and password combinations are still used by themselves in most networks. And it is obvious by glancing at recent news headlines that user credentials, they represent a major area of attack. So your password policy should include the following: education for end users, strong password requirements such as having minimum password lengths, restrictions on the use of proper names, password expiration, no previously used passwords allowed, no words spelled out completely within the password, and the use of characters from the following groups, such as having upper and lowercase letters, numbers, and special characters. Now, your password policy might also detail the use of password management software, which stores passwords for different resources and can help generate complex passwords across these resources. Now, of course, the software itself must be protected with a strong password that the user should memorize. And next, let's talk about security policies. So one of the main reasons security breaches occur within an organization is the lack of a security policy, or if a security policy is in place, the failure to effectively communicate or enforce the security policy to all who are concerned. A security policy, this is a continually changing document that dictates a set of guidelines for network use. And these guidelines complement organizational objectives by specifying rules for how a network is to be used. And the main purpose of a security policy is to protect the assets of an organization. An organization's assets include more than just tangible items. Assets also include intellectual property, processes and procedures, sensitive customer data, and specific server functions such as email or web functions. Now, aside from protecting an organization's assets, a security policy serves other purposes such as the following: making employees aware of their obligations in regard to security practices, identifying specific security solutions required to meet the goals of a security policy, and acting as a baseline for ongoing security monitoring. Now, one of the most well-known components of a security policy is called an acceptable use use policy. In an acceptable use policy, this identifies what users of a network are and are not allowed to do on a network. For example, retrieving sports scores during working hours via an organization's internet connection. This might be deemed inappropriate by the acceptable use policy. Now, because an organization's security policy applies to various categories of employees, such as management, technical staff, and end users, a single document might not be sufficient. So, for example, managerial personnel might not be concerned with the technical intricacies of a security policy, whereas technical personnel might not be very concerned with why a policy is in place. Also, end users might be more likely to comply with the policy if they understand the reasoning behind the rules. Therefore, a security policy, this might be a collection of congruent yet separate documents. In this picture on your screen right here, this essentially offers a high-level overview of these complementary documents. All right, next let's talk about data loss prevention. So a comprehensive data loss prevention policy, this focuses on accidental or malicious data losses. In DLP policies, they consider internal and external users, as well as define practices to guard against the loss or damage of sensitive data. And the best DLP policies, they also cover wide network integration and are not limited to certain areas of networking, such as email. In most DLP policies, they focus on the use of content level scanning and deep content inspection to identify sensitive data and protect it. In DLP policies, they target activities at 3 levels. The first one is called the client level. This is essentially data that is in operation or is being processed. Then you have the network level. This is data that is in transit or is in motion. And then you have the storage level, which is essentially data that is at rest. So you should take the following actions when designing a data loss prevention policy for your organization. You want to consider any risk assessments your organization has performed. You want to incorporate key members of management from the various departments of your organization. You want to identify the organization's most sensitive data. You want to outline a phased implementation of a DLP and incorporate guidelines for tracking success of the initiative. You want to attempt to minimize any negative impacts on the business caused by the policy implementation. You want to periodically review the data loss prevention policy, and you want to include the appropriate event monitoring specifics as they apply to the policy. All right, next let's talk about remote access policies. So remote access to corporate network resources, this presents unique challenges for organizations today. Of primary concern is the fact that the remote network might lack appropriate security controls or may even be currently compromised. And the following are some important considerations for a remote access policy. So the first one is the scope of the policy should be clear and may include applicable targets such as employees, contractors, vendors, and agents with organization-owned or personally owned computers or workstations used to connect to the corporate network. A remote access policy typically applies to remote connections to the organization itself, including reading or sending email and viewing intranet web resources. And such a policy also tends to cover every remote access option, including dial-up, VPN, and web portal access. Next, it is important to clearly detail the requirements of the policy, which might include encryption and security standards, as well as the acceptable areas of network access. Next, an organization might want to include a section on compliance, which could include exceptions to the policy, how to measure compliance, and the consequences of non-compliance. And then you might want to include a section that indicates what other security policies for the network closely relate to this policy. Next, let's talk about a BYOD, or a bring your own device policy. So closely related to a remote access policy is a bring your own device policy. And at the very least, this important policy should incorporate the following. It should have an explicit and detailed list of what devices are permitted, an explicit security policy for each device or device category, an appropriate corporate support policy for each device or device category, a clear delineation of what applications and data are owned by the corporation versus owned by the user and or employee, an explicit list of applications permitted in the BYOD environment, an integration of the BYOD policy with the acceptable use policy, and a detailed presentation of the exit or offboarding policies for employees as they relate to the BYOD policy. All right, next let's talk about the acceptable use policy. So an acceptable use policy, which is sometimes referred to as a fair use policy, this seeks to provide restrictions and overall guidelines on how the network should be used. And such a policy can have tremendous legal implications for an organization in the event of problems with employee actions on the network. An organization might be able to protect itself from such legal situations if its employees have signed a detailed acceptable use policy during the onboarding process. And in AUP, it should have the following characteristics. It needs to be clear, it needs to be concise, it should be detailed regarding acceptable and unacceptable use of the network, it should be congruent with the associated overall security policies of the organization, and it should be concrete regarding the consequences of an acceptable use policy violation. And like many other policies that were listed before, the AUP should be reviewed and updated as required. All right, next let's talk about safety procedures. So an organization should consider implementing safety policies and procedures for the networking equipment. And here are some areas that are commonly addressed in such policies. So following the installation and maintenance guides for the equipment as closely as possible, keeping all work areas as clean and organized as possible, wearing appropriate safety equipment, getting assistance when lifting heavy network objects, using caution when interacting with electricity, and avoiding other risks of some type of electric shock. Next, let's talk about the privileged user agreement. So because network administrators often require godlike power and access over the network and the data that flows through it, it is important to consider implementing a privileged user agreement in the IT department. In a PUA agreement, this might stipulate the following. So privileged access should be granted only to authorized individuals who read and sign the agreement. Privileged access may be used only to perform assigned job duties. If methods other than using privileged access will accomplish an action, those other methods must be used unless the burden of time or other resources required clearly justifies using privileged access. Privileged access may be used to perform standard system-related duties only on machines and networks for which the individual is assigned responsibility. And privileged access may be used to grant, change, or deny resources, access, or privilege to another individual only for authorized account management activities or under exceptional circumstances. All right, next let's talk about onboarding and offboarding procedures. So another excellent best practice is to have detailed onboarding and offboarding procedures in place for the hiring and termination of employees. And these procedures should address the IT staff and the network. So examples of typical onboarding functions, they might include the following: issuing out an ID number and a PIN assignment, username and password assignment, ID card and access assignments, email setup, email client setup, workstation setup, workstation network access verification, IT security and best practice training, phone and BYOD setup, time management and other HR software training, and signing an AUP and an NDA. Now, of course, offboarding is the opposite of onboarding. And this critical phase involves tasks such as the following: disabling user identities, deleting user identities, gathering and examining former employees' computer equipment, whether it's mobile or non-mobile, that belongs to the organization, wiping this computer equipment clean, and disposing of or repurposing this computer equipment. All right, next let's talk about licensing restrictions. So you may need to provide training in the proper licensing and use of corporate hardware or software. As networks have become more complex, such as incorporating public cloud technologies, so have licensing agreements. And it is important that your users remain in compliance with all existing licensing agreements and restrictions. And then we have international export controls. So another important best practice is to educate IT staff and end users on the international export rules your organization must observe. So for example, specific U.S. government agencies, they regulate the transfer of information, commodities, technology, and software considered to be strategically important to the U.S. in the interest of national security, economic, and/or foreign policy concerns. Your management must understand that non-compliance with export controls can result in severe monetary and criminal penalties against both an individual in your organization and the organization itself. And then finally, let's talk about a non-disclosure agreement. So it is a best practice for an organization to have individuals sign non-disclosure agreements. In NDA, this is a legal contract with the following common traits. It is between at least two parties. It outlines confidential material, knowledge, or information that the parties want to share with one another or want to restrict others from accessing. It creates a confidential relationship between the parties to protect any type of confidential and proprietary information or trade secret, and it protects non-public business information. Now understand, it has become quite common for all employees to sign NDAs during the onboarding process. In this video, you're going to learn about various aspects of high availability and disaster recovery. All right, so let's talk about high availability. So if a network switch or router stops operating correctly, meaning that a network fault occurs, communication through the network could be disrupted, resulting in the network becoming unavailable to its users. Therefore, network availability, which is also known as uptime, this is a major design consideration. And this consideration might, for example, lead you to add fault-tolerant devices and fault-tolerant links between those devices. And this video is going to discuss the measurement of high availability along with a number of high availability design configurations. So let's go ahead and talk about high availability measurements. So the availability of a network is measured by its uptime during a year. So for example, if a network has 5 nines of availability, it is up 99.999% of the time, which translates to a maximum of 5 minutes of downtime per year. If a network has 6 nines of availability, that means it's up 99.9999% of the time, and it is down less than 30 seconds per year. Now, as a designer, one of your goals is to select components, topologies, and features that maximize network availability within certain parameters, such as a budget, but be careful not to confuse availability with reliability. A reliable network, for example, does not drop many packets, whereas an available network is up and operational. All right, next let's talk about the mean time to repair, or the MTTR. And this is the average time required to fix a failed component and return it to its production status. This is also sometimes called the mean time to recovery. Then we have the mean time between failures, or the MTBF. And this is the average amount of time that passes between hardware component failures, excluding time spent repairing components or waiting for repairs. Now, yet another important measure, this is called the mean time to failure, or the MTTF. And this is the length of time a device or product is expected to last in operation. It represents how long a product can reasonably be expected to perform based on specific testing. And another goal in your design might be to meet the requirements set forth in a service level agreement, or an SLA. And an SLA, this is an official commitment that exists between a service provider and a client. Aspects of the IT services provided, such as quality, availability, specific responsibilities, these are agreed upon between the service provider and the service user. And strict SLAs, they are becoming increasingly common in networking today as more and more cloud services find their way into the IT landscape. The cloud provider, this is a specialized service provider, and a cloud consumer, well, that is the client. So 2 other measures that an organization should consider are the recovery time objective, or the RTO, and the recovery point objective, or the RPO. And these 2 measurements might sound the same, but they are very different measures. So the RTO, this is the time in the future when you expect to restore availability after some failure or even a disaster has rendered your IT services unavailable. The RTO value is a very important measure of how long you expect the network to be down. Then we have the RPO, and as important as the RTO is the RPO, and this is the point in time to which you can recover the network. So for example, say that your network system failed at 4 p.m. last Monday, your RPO might be for that very point in time. Sometimes on unfortunately, RPO will not be the exact point of failure. This is often the case with database systems. So for example, a failure might occur at 4 p.m. on a Monday, but you might only be able to recover to 11 a.m. that Monday. This gap in your data might be a result of your disaster recovery plans. Perhaps your backup design can only restore your systems to that 11 a.m. point. An organization, they must ensure it can accept a particular amount of potential data and service loss. Now, as a side note, the RPO, this is the amount of data that will be lost or will have to be re-entered because of network downtime. The RTO, this is the amount of time that can pass before the disruption begins to seriously impede normal business operations. All right, next let's talk about fault-tolerant network design. So 2 important concepts to know when designing a fault-tolerant network are as follows. The first one is called a single point of failure. So if the failure of a single network device or link, such as a switch, router, or wide area network connection, would result in a network becoming unavailable, that single device or link is a potential single point of failure. To eliminate single points of failure from your design, you might want to include redundant links and redundant hardware. So for example, some high-end Ethernet switches support 2 power supplies, and if one power supply fails, the switch continues to operate by using the backup power supply. Link redundancy, as you can see in this picture on your screen right here, this can be achieved by using more than one physical link. If a single link between a switch and a router fails, the network would not go down because the link redundancy that is currently in place. All right, next we have no single points of failure. So a network without a single point of failure contains redundant network infrastructure components such as routers and switches. In addition, these redundant devices are interconnected with redundant links. Although a network host could have 2 network interface cards, each connecting to a different switch, such a design is rarely implemented because of the increased cost. Instead, as you can see in this picture right here, a network with no single points of failure in the backbone allows any single switch or router in the backbone to fail or any single link in the backbone to fail while maintaining end-to-end network connectivity. And approaches to fault-tolerant network design, they can be used to increase the network's availability even further. Now, as a side note, creating multiple paths that data can take in a network is often simply termed multipathing. Routing protocols can make multiple paths very valuable to use since they can engage in what is called equal cost multipathing. In fact, Enhanced Interior Gateway Routing Protocol, or EIGRP, even provides the unique capability of load sharing between paths of unequal cost. All right, next let's talk about hardware redundancy. So having redundant route processors in a switch or router chassis improves the reliability of the chassis. If a multi-layer switch has 2 route processors, for example, one of the route processors could be active and the other route processor could be standing by to take over in the event that the active processor becomes unavailable. And in system, it can have redundant NICs. And there are 2 modes of NIC redundancy, or network interface card redundancy. You have what is called active-active. So both NICs are active at the same time, and each has its own MAC address. This makes troubleshooting more complex while giving you slightly better performance than the active-passive approach. You have the active-passive approach, so only one NIC is active at a time. And this approach allows the client to appear to have a single MAC address and IP address, even in the event of a NIC failure. And NIC redundancy is most often used in strategic network hosts rather than in end-user client computers because of the expensive and administrative overhead incurred with redundant NIC configurations. And as a side note, different vendors use different terms to refer to combining NICs for hardware redundancy. The 2 most commonly used terms are NIC interface card teaming, or NIC teaming, and NIC bonding. But CompTIA, it prefers the term NIC teaming. And another powerful method of hardware redundancy comes in the form of computer clustering. A computer cluster consists of a set of tightly connected computers that work together. In many respects, clients view them as a single system. And the servers in the cluster, they're usually connected to each other through fast local area networks, with each node running in its own instance of an operating system. In most circumstances, all of the nodes use the same hardware and the same operating system, although in some setups, different operating systems, or even different hardware can be used on each computer. And computer clusters, they emerged as a result of the convergence of a number of computing trends, including the availability of low-cost microprocessors, high-speed networks, and software for high-performance distributed computing. They have a wide range of applicability and deployment, ranging from small business clusters with a handful of nodes to some of the fastest supercomputers in the world. And the clustering approach has also made its way to networking devices themselves. So for example, today it is not uncommon for large enterprises and data centers to feature clustered solutions for switches, routers, and firewalls. All right, next let's talk about layer 3 redundancy. So in systems not running a routing protocol, they point to a default gateway. The default gateway is traditionally the IP address of a router on the local subnet. However, if the default gateway router fails, the end systems are unable to leave their subnet. And there are 4 first-hop redundancy protocol technologies which offer layer 3 redundancy. The first one is called the Hot Standby Router Protocol. So HSRP, this is a Cisco proprietary approach to first-hop redundancy. In this picture right here on your screen, this shows a sample of HSRP topology. So in this picture, workstation A is configured with the default gateway. That is the next hop gateway of 172.16.1.3. To prevent the default gateway from becoming a single point of failure, HSRP enables routers R1 and R2 to each act as the default gateway, supporting the virtual IP address of the HSRP group, which is 172.16.1.3, although only one of the routers will act as the default gateway at any one time. Under normal conditions, router R1, which is the active router, forwards packets sent to the virtual IP address 172.16.1.3. However, if router R1 is unavailable, router R2, which is the standby router, can take over and start forwarding traffic sent to 172.16.1.3. Now notice that neither router R1 nor R2 has a physical interface with IP address 172.16.1.3. Instead, a logical router or the virtual router, which is serviced by either router R1 or R2, it maintains the 172.16.1.3 IP address. And the next protocol is called Common Address Redundancy Protocol. And this is an open standard variant of HSRP. Then we have Virtual Router Redundancy Protocol. And this is an open standard that operates in a similar method to Cisco's proprietary HSRP. As with HSRP, with VRRP, or Virtual Router Redundancy Protocol, many routers can operate in a group and ensure that there is always a router available for the host to use a default gateway. Also, as with HSRP, a virtual IP address is assigned to the host for their default gateway setting. The routers in the VRRP group can also respond if needed to that virtual IP address. Then we have what is called Gateway Load Balancing Protocol. So this is another first-hop redundancy protocol that is proprietary to Cisco systems. Now, with each of these technologies, the MAC address and the IP address of a default gateway can be serviced by more than one router or multi-layer switch. Therefore, if a default gateway becomes unavailable, the other router or the multi-layer switch can take over and still service the same MAC and IP addresses. And another type of layer 3 redundancy is achieved by having multiple links between devices and selecting a routing protocol that balances the load over the links. Link Aggregation Control Protocol enables you to assign multiple physical links to a logical interface, which appears as a single link to a route processor. In this picture on your screen right here, this illustrates a network topology that is using Link Aggregation Control Protocol. And another important redundancy technique is to ensure that your default gateways can connect to multiple internet service providers using diverse paths when redundant internet connectivity is required. Now, note that such a solution protects against internal device failures as well as ISP failures that are beyond your control. Your network design can even incorporate periodic reachability tests to ensure that your ISPs are truly available and able to direct you to remote resources successfully. All right, next let's talk about design considerations for high availability networks. So when designing networks for high availability, it is important to consider the following questions, like where will module and chassis redundancy be used? So module redundancy, this provides redundancy within within a chassis by allowing one module to take over in the event that a primary module fails. And chassis redundancy means having more than one chassis, thus providing a path from the source to the destination, even in the event of a chassis or link failure. Now, you need to know what type of software redundancy features are appropriate, what protocol characteristics affect design requirements, what redundancy features should be used to provide power to an infrastructure device. So, for example, using an uninterruptible power supply, a generator, or dual power supplies, and what redundancy features should be used to maintain environmental conditions, such as a dual air conditioning unit. Another question you should ask is, will dual circuits be provided in the event of a lost connection with one of the circuits? What backup strategy exists for infrastructure and user data? And the main backup strategies, they are as follows. You have what is called a full backup. This is a backup of all of the data set. Although this is the safest and most comprehensive way to ensure data availability, it can also be the most time consuming and costly. You have what is called an incremental backup, and this backs up only data that has changed since the previous incremental backup. And an incremental backup is incomplete for full recovery without a valid full backup in all incremental backups since the last full backup. Then the next type of backup is a differential backup, and this is similar to an incremental backup in that it starts with a full backup, then subsequent backups contain only data that has changed. The difference is that whereas an incremental backup only includes the data that has changed since the previous backup, a differential backup contains all the data that has changed since the last full backup. You have what is called a snapshot. A snapshot, this is a read-only copy of a data set that is frozen in a point in time. This type of backup is often used with virtual machines and file system objects. And then the final question you want to ask yourself when it comes to design considerations is, what backup strategy exists for your network devices, whether they're software, images, and configurations? And are you backing up the information and configuration information from these devices? All right, next let's talk about high availability best practices. So these are the 5 best practices for designing high availability networks. You need to examine the technical goals. You need to identify the budget for funding these high availability features. You need to categorize business applications into profiles, each of which require a certain level of availability. You need to establish performance standards for high availability solutions, and you need to define how to manage and measure the high availability solution. Now, although existing networks can be retrofitted to make them highly available, network designers can often reduce expenses by integrating high availability best practices and technologies into the initial design of a network. Next, we have what is called content caching. So a content engine, this is a network appliance that can receive a copy of content stored elsewhere, such as a video presentation located on a server at a corporate headquarters, and serve that content to local clients, which reduces the bandwidth burden on an IP wide area network. Then we have what is called load balancing. So content switching, this allows a request coming into a server farm to be distributed across multiple servers containing identical content. This approach to load balancing, it lightens the load on individual servers in a server farm and allows servers to be taken out of the farm for maintenance without disrupting access to the server farm's data. All right. And then finally, we're going to talk about hardware redundancy. So it is possible to design site redundancy into your network configuration. Doing so requires redundant data and equipment located in geographically distant areas. Now, how fast can your IT infrastructure be back up and running in the event that issues arise in your primary site? Well, the following options for that are available here. We have what is called a cold site. So recovery is possible, but it is difficult and time consuming with a cold site. And a cold site, this is the weakest of the recovery site options, but it is also the least costly. However, keep in mind that although a cold site might be the least costly when you're planning for disaster, after a disaster occurs, the equipment purchased for a cold site might be expensive or difficult to obtain. You have what is called a warm site. So recovery is possibly fairly quickly, but the site might not have the resources and responsiveness as the original site. And the warm site, this is basically a scaled down version of a hot site. The recovery site is often only configured with phone, power, and network network jacks, and it may have computers and other resources, but they are not configured and ready to go. And then we have what is called a hot site, and this is where downtime is minimal with a service level that is nearly identical to that of the organization's main site. And this type of site is the most expensive, and it functions like the original site and is equipped with all necessary hardware, software, network, and internet connectivity fully installed, configured, and ready to go. And then as a side note, thanks to the advancements in public cloud computing, cloud sites are also possible. And you can configure sites as cold, warm, or hot sites, typically with ease. And more hot site configurations are capable thanks to cloud sites. And this is due to the lower costs and technological requirements that are made possible by the cloud. In this video, you're going to learn about the core security concepts pertaining to confidentiality, integrity, and availability. All right, so let's talk about confidentiality, integrity, and availability, also known as the CIA triad. So for most of today's corporate networks, the demands of e-commerce and customer contact require connectivity between internal corporate networks and the outside world. Today's corporate networks tend to be large and interconnected with other networks, and they typically run both standards-based and proprietary protocols. In addition, the devices and applications connecting to and using corporate networks are continually increasing in complexity, and it will be unusual for a corporate network not to need network security. So, like I stated earlier, CIA, this refers to the three primary goals of network security, which are confidentiality, integrity, and availability. And the following information is going to explain these goals in more detail. So let's talk about confidentiality. So, data confidentiality. This involves keeping data private by physically or logically restricting access to sensitive data or encrypting traffic traversing a network. A network that provides confidentiality would, for example, do the following. We would use network security mechanisms such as firewalls and access control lists to prevent unauthorized access to network resources. You would require appropriate credentials such as username and passwords to access specific network resources. You would encrypt traffic such that any traffic captured off the network by an attacker cannot be deciphered by the attacker. And confidentiality can be provided by using encryption. Encryption allows a packet to be encoded in such a way that it can be decoded by an intended party. However, a malicious user who intercepted an encrypted packet in transit would not be able to decrypt the packet. The way most modern encryption algorithms prevent decryption by a third party is through the use of a key. Because the encryption or decryption algorithm uses a key in this mathematical calculation, a third party who does not possess the key cannot interpret intercepted data that is encrypted. And encryption, this has two basic forms. You have what is called symmetric encryption and asymmetric encryption. All right, so let's talk about symmetric encryption. So symmetric encryption, this is faster than asymmetric encryption. And the word symmetric in symmetric encryption, this implies that the same key is used on both the sender and receiver to encrypt or decrypt a packet. And examples of symmetric encryption algorithms include the following. First one is called DES, and that stands for Data Encryption Standard. And this is an older encryption algorithm developed in the mid-70s that uses a 56-bit key. And it is considered weak by today's standards and has been deprecated. Next, we have triple DES, and this was developed in the 1990s. And this uses three 56-bit DES keys for a total of 168 bits. And this was originally considered a strong encryption algorithm. However, the security of triple DES varies based on the way it is implemented. Specifically, triple DES has three keying options. All three keys may be different, which is keying option 1. Then you have two of the three keys may be the same, which is keying option number 2, or all three keys may be the same, which is keying option number 3, and that is to maintain backwards compatibility with DES. Because of the high computational overhead of triple DES, many companies have moved directly to the much faster AES instead of using triple DES. And next we have AES, or the Advanced Encryption Standard, and this was released in 2001, and this is the preferred symmetric encryption algorithm. AES is available in 128-bit key, 192, and 256-bit key versions. This technology is being used more and more for many different applications, including wireless, mobile, VPNs, and web security implementations, and it is popular because of its overall strength and its ability to provide various levels of security based on the key length. And for lower security environments, you can use the 128-bit 64-bit key AES, but the 256-bit key implementation, this is considerably almost unbreakable. And this picture on your screen right here, this provides an example of symmetric encryption where both parties have a shared key to be used during a session, which is called a session key. And as a side note, another widely deployed encryption algorithm is called Pretty Good Privacy, or PGP, which is often used to encrypt email traffic. And PGP, it uses both symmetric and asymmetric algorithms. And the free variant of PGP, this is called New Privacy Guard, or GPG. All right, next let's talk about asymmetric encryption. So asymmetric encryption, this is slow compared to symmetric encryption, but provides better security. And as its name suggests, asymmetric encryption uses asymmetric or different keys for the sender and receiver of a packet. Because of its speed, asymmetric encryption is not typically used to encrypt large quantities of real-time data. Rather, asymmetric encryption might be used to encrypt a small chunk of data that's being used. So for example, to authenticate the other party in a conversation, or to exchange a shared key to be used during a session, after which the parties in the conversation could start using symmetric encryption. One of the most popular asymmetric encryption algorithms in use today is called RSA, and its name comes from the last initials of its three inventors, who are Ronald L. Rivas, Adi Shamir, and Leonard M. Adelman. And RSA is commonly used as part of what is called a public key infrastructure system, or PKI, and specifically PKI uses what are called digital certificates and a certificate authority for authentication and encryption services. So here's an example of how asymmetric encryption works. So when client A wants to communicate securely with server 1, the following steps will occur. So client A receives server's 1 digital certificate, then server 1 sends its digital certificate, and client A knows the received certificate is really from server 1 because the certificate has been authenticated or signed by a trusted third party, which is called a certificate authority. Step 3, client A extracts server's 1 public key from server's 1 digital certificate. The data encrypted using server 1's public key can only be decrypted with server 1's private key, which only server 1 has. Step 4, client A generates a random string of data called a session key. Step 5, the session key is encrypted using server 1's public key and is sent to server 1. And then step 6, server 1 decrypts the session key by using its private key. Now, at this point, both client A and server 1 know the session key, which can be used to symmetrically encrypt traffic during the session. And as a side note, symmetric key algorithms, they are faster and often used for bulk encryption of data. And asymmetric key algorithms, they are slower and are often used for initial security transactions, such as authentication. All right, next let's talk about integrity. So ensuring data integrity, this involves making sure data has not been modified in transit. Also, a data integrity solution might perform origin authentication to verify that traffic is originating from the source that should send the traffic. And examples of integrity violations include the following: modifying the appearance of a corporate website, intercepting and altering an e-commerce website, and modifying financial records that are stored electronically. And hashing, this is one approach to providing integrity to data transmissions crossing a network. Specifically, hashing takes a string of data such as a password and runs it through an algorithm. The result of the algorithm is called a hash or a hash digest. If the sender of that data runs a hashing algorithm on the data and sends the hash along with the data, when the recipient receives the data, he can also run the data through the same hashing algorithm. If the recipient calculates the same hash data, he might conclude that the data has not been modified in transit. That is, he has confirmed the integrity of the data. And note that a hashing algorithm produces a hash digest of the same length, regardless of the size of the data that's being hashed. And two hashing algorithms that are commonly used, the first one is called Message Digest 5 or MD5, and this creates a 129-bit hash digest. And then you have Secure Hash Algorithm 1 or SHA-1, and this creates a 160-bit hash digest. And hashing by itself, however, this does not guarantee data integrity because an attacker could intercept a string of data, manipulate it, and recalculate the hash value based on the manipulated data. The victim would then determine that the hash is valid based on that data. And to overcome this limitation of pure hashing, hash message authentication code, or HMAC, this uses an additional security key in the calculation of a hash value. Therefore, an attacker would not be able to create a valid hash value because he would not know the secret key. In other variants of hashing algorithms, such as SHA-256, this involves longer digests. So in cryptography, a bigger digest, this implies better security. All right. And finally, let's talk about availability. So the availability of data, this is a measure of the data's accessibility. So for example, if a server was only down 5 minutes per year, the server would have an availability of 99.999%, or the 5 nines of availability. And here are a couple of examples of how an attacker could attempt to compromise the availability of a network. They could send improperly formatted data to a network device, which would result in an unhandled exception error, or they can flood a network system with an excessive amount of traffic or requests, which would consume a system's processing resources and prevent the system from responding to many legitimate requests. And this type of attack, this is commonly referred to as a DOS attack or a denial of service attack. In this video, you're going to learn about threats, vulnerabilities, and exploits, least privilege, role-based access, zero trust, and defense in depth. All right, so let's talk about threats. So you should work with your team carefully to identify the realistic security threats that your enterprise could face. This might mean dealing with hypotheticals, but it is nonetheless a very important exercise. While the focus is often on external threats to an organization, you cannot forget that internal threats do exist. In fact, a network often faces more internal threats than they do from external ones. And then next we have vulnerabilities. So one of the reasons there are so many potential threats against organizations today is the fact that vulnerabilities are constantly discovered in networks and network components. New code that is installed on a network device, such as a router, this might cause a vulnerability. So for example, this code could introduce a new feature that creates a backdoor into the device for unauthorized persons. And because vulnerabilities are a major issue for IT staff, a number of tools have been developed to deal with them. You have what is called the Common Vulnerabilities and Exposure, or the CVE system, and this is free to use and can be incredibly helpful. This online resource provides excellent search tools and can leverage a large database of publicly known information security vulnerabilities and exposures. And CVE, which was officially launched in September of 1999, this is sponsored by US CERT within the US Department of Homeland Security. Now, there are two catalogs of known vulnerabilities that you should be familiar with, and they are CVE and CVSS. CVE, once again, this is a list of publicly known vulnerabilities containing an ID number, a description, and a reference for each vulnerability. And then we have the CVSS, or the Common Vulnerability Scoring System. And this provides a score from 0 to 10 that indicates the severity of a vulnerability. Also of great value is this thing called the Open Web Application Security Project, or OWASP. And this is a foundation that works to improve software security. And each year, OWASP, they publish the OWASP Top 10 for web application security exploits. And then as a side note, we have what are called zero-day attacks. And these are cybersecurity attacks that use techniques or vulnerabilities that have not already been discovered by cybersecurity specialists or anti-malware companies. While it might sound hopeless, remember that today's sophisticated security appliances can typically prevent or mitigate damage from zero-day attacks by using machine learning to stop activities in the network that are outside the normal baseline activities. And next, let's talk about exploits. So as mentioned earlier, when we discuss threats, we are typically talking about hypotheticals, events that might possibly occur in the network. When we discuss exploits, however, we are talking about facts. So an exploit consists of a hopefully detailed description of what exactly occurred with a security breach. And an exploit, this often describes the most likely attacker, the technology used, and any vulnerabilities or misconfigurations that made the attack possible. Right, next, let's talk about least privilege. So an important security best practice that you should implement everywhere possible in your network is called least privilege. You and every other person who interacts with the network should always be using a user account that has the least number of privileges required to do a job. It is important to carefully audit the required permissions to complete tasks and then create accounts or groups that have just those permissions. Then, if a computer criminal manages to begin operating on the network using your account, the criminal will only be able to accomplish minimal tasks. Implementing least privilege, this might sound easy, but human nature often opposes this common sense measure. So for example, an administrator might prefer to use an administrator or a root account for all administrative tasks because switching between accounts, this can be tedious. It can also be very easy to violate this best practice without even knowing it. And this often happens in public cloud environments. An administrator, they may start a free tier Amazon Web Services account using his email address. He may not have studied much about AWS and might not realize that there is a service called Identity and Access Management, which is designed for the creation of accounts and permissions in AWS. The administrator may continue to use that administrative account email address for day-to-day cooperation in AWS, even though AWS makes it clear that using such a high-level account is not safe. The only time you should use that high-level admin account is when you are performing some specific change that requires it, such as changing the credit card on the account or the billing configurations. Then we have what is called role-based access. So most network device designers, they strive to implement role-based access control for administrators who must manage devices. In addition, more and more network access models for users, they are emphasizing role-based access control for network access. And the idea with role-based access control is to create permissions around roles that you can then assign to users. So for example, you might use RBAC for guest access, and to do so, you would create a guest role and assign that role to visitors to your organization where you want to give them limited privileges. Or perhaps you just want such visitors to be able to access your public internet connection for limited internet access. You might also use RBAC to create network administrator accounts for users who need to have the ability to access the network and also reconfigure it. And as a side note, a scalable method for assigning roles or permissions to user accounts is to include those user accounts and roles, which are also called groups, that have the appropriate permissions already assigned. And the users, they will inherit the permissions thanks to their group membership. And on some network devices, RBAC is more limited, and you can only assign permissions to the user accounts themselves. All right, next we have what is called zero trust. So zero trust, this is a relatively new security model that many corporations are starting to use. As the name indicates, this model seeks to reduce or eliminate security breaches for an organization by trusting absolutely nothing by default. In fact, the credo of this approach is called never trust, always verify. And zero trust, this was created by a guy named John Kindervag of Forrester Research. He realized that traditional security models, they operate on the silly assumption that everything inside of an organization's network should be trusted. With models based on this assumption, once a network attacker has gained access, that user account is then trusted. The zero trust model, it views this trust as a vulnerability. And zero trust, this is implemented using many different technologies in a network, including the following: segmenting the network, preventing lateral movement, providing layer 7 threat prevention, and simplifying granular user access control. All right, next let's talk about defense in depth. So Cisco Systems is one of the networking giants that helped to popularize the great idea of defense in depth for network security. And defense in depth, this involves striving to secure each layer of a solution. So for example, you might use strong security on containers or virtual machines that provide software as a service for your organization. You can then use strong security controls in place on the network switch that connects to those hosts. This process continues, building layer after layer of security into the network and the systems that connect to it. As with the zero trust security approach, there is no single technique that makes defense in depth what it is. So this section right here is just going to describe some of these security approaches you might employ when you're using a defense in depth approach. And the first technique is called network segmentation enforcement. So Logical segmentation of networks. This helps to enforce strong security designs. So for example, VLANs can be used to constrain broadcasts and permit the definition of VLAN access control lists and router access control lists for controlling communication between the VLANs. The network segmentation enforcement, this can also help to minimize the effects of security attacks by limiting them to the local subnet. And at layer 3, you can segment by using virtual routing and forwarding tables for network devices. And these tables, which are like virtual routers running within the main router, can be separate and distinct from the main routing table. And the main routing table, this is also known as a global routing table. All right, the next strategy is called a screen subnet. And this was previously called a DMZ or a demilitarized zone. This often contains servers that should be accessible from the public internet. With a screen subnet, you could allow users on the internet to initiate an email or web session coming into your organization's email or web server. However, you could block other protocols for those users. And we have what is called separation of duties. So a popular security best practice is to implement a separation of duties policy in the network. This policy ensures that user accounts in the network do not have too much power. You can also ensure that your IT staff are mapped to these various duties and even rotated through them. This helps to ensure that internal attacks against your network do not occur. It is important to include separation of duties when planning for security policy compliance. Without this separation, all areas of control and compliance could end up in the hands of a single individual. All right, the next strategy is called network access control. So network access control, this involves using a set of protocols to ensure that users are immediately identified when they try to access the network. A network access control system might integrate automatic remediation processes to fix the issues with host systems so that they are brought in compliance with corporate security policies. And a common approach to building a network access control system is to incorporate the 802.1x protocol into the network. And then finally, we have what is called the honeypot. So a honeypot, this acts as a distractor. Specifically, a system designated as a honeypot appears to be an attractive attack target. One school of thought on the use of honeypots is to place one or more honeypot systems in a network to entice attackers into thinking a system is real. The attacker then uses their resources to attack the honeypot, and in doing so, they leave the real servers alone. Honeypot, this can also be used to see what attackers are attempting to do on the system. A honeypot could, for example, be a Unix or Linux-based system configured with a weak password. After an attacker logs in, surveillance software could log what the attacker does on the system, and this knowledge could then be used to protect the real servers in the network. As a side note, for larger networks, a network administrator, they might deploy multiple honeypots, which are called a honey net. In this video, you're going to learn about various aspects related to authentication methods, risk management, and security information and event management. All right, so let's go ahead and talk about some authentication methods. So because authentication is such an important part of network security, it is a little surprised that today there are many different approaches that you can use. And this video is going to describe several authentication methods. And the first one we're going to talk about is multi-factor authentication. So authentication that requires multiple factors. This is called multi-factor authentication. Some of those factors might include the following, such as something you know, like a passcode, a PIN or a one-time passcode, something you are, such as your biometrics, something you have or possess, something like a smart card or a smartphone, and something you must perform, such as connecting to a specific network. And today, smartphones, they are often used in multi-factor authentication. A smartphone, this is something that you possess, and the network can take advantage of this by sending a one-time password to your smartphone to make sure you are who you claim to be. All right, next we have what is called TACACS Plus. So this stands for Terminal Access Controller Access Control System Plus, and this is a Cisco proprietary TCP-based protocol. TACACS Plus, this has 3 separate and distinct sessions or functions for authentication, authorization, and accounting, which are known known as AAA, and it is similar to Radius, or Remote Authentication Dial-In User Service, but uses TCP instead of UDP as its transport model. And it also uses port 49 as the default port. And TACACS Plus, basically it takes a client-server model approach. The next authentication method is called single sign-on, or SSO, and this allows a user to authenticate only once to gain access to multiple systems or applications without requiring the user to independently authenticate with each system or application. And we have Radius, and once again, this stands for Remote Authentication Dial-In User Service, and this is a UDP-based protocol used to communicate with a AAA server. And unlike TACACS Plus, Radius does not encrypt an entire authentication packet. It only encrypts the password. However, Radius does offer more robust accounting features than TACACS Plus. Also, Radius, this is a standards-based protocol, where TACACS Plus is a Cisco proprietary protocol. In Radius, it uses UDP port 1812 for authentication and authorization, and then it uses UDP port 1813 for accounting. Next authentication method is LDAP, and that stands for Lightweight Directory Access Protocol. And this permits a set of standards for the storage and access of user account information. And many proprietary user stores support LDAP for ease of access, including Microsoft's Active Directory. And by default, LDAP traffic is unsecured over port 389. LDAP over TLS SSL, or LDAP-S. This is the secure form of LDAP with secured communications using port 636. And then we have local authentication, and this refers to a network device authenticating the user with a database of user account information stored on the device itself. And this is often an important fallback authentication method used when another external method fails. All right, the next authentication method we have is called Kerberos. So this is a client-server authentication protocol that supports mutual authentication between a client and a server. With Kerberos, a trusted third party, or a key distribution center, or KDC, it hands out tickets that are used instead of a username and password combination. And here is a look at the process of how this works. So step one, the client contacts a CA, or a certificate authority. The CA creates a timestamp session with a limited duration, and by default, the duration is set to 8 hours by using the client's key and a randomly generated key that includes the identification of the target service. The CA sends this information back to the client in the form of a ticket granting ticket, or a TGT. Then the client submits the TGT to a ticket granting server, or a TGS, and then the TGS generates a timestamp key encrypted with the service keys and returns both keys to the client. Then the client uses its key to decrypt its ticket, contacts the server, and offers the encrypted ticket to the TGS. The TGS then uses its key to decrypt the ticket and verify that the timestamps match and the ticket remains valid. Then the service contacts the KDC and receives a timestamp session key ticket that it returns to the client. And finally, the client decrypts the key ticket by using its key. When the client and the server agree that they are on the proper accounts and that the keys are within the valid lifetimes, then communication is initiated. All right, the next authentication method is IEEE 802.1x. So IEEE 802.1x, this is a network access control that involves permitting or denying a wireless or wired LAN client access to a network. If IEEE 802.1x is used to permit access to a LAN via a switch port, then the 802.1x is being used for port security. And the device seeking admission to the network, this is called the supplicant. The device to which the supplicant connects either wirelessly or through a wired connection, this is called the authenticator. And the device that checks the supplicant's credentials and permits or denies the supplicant to access the network, this is called the authentication server. And usually a Radius server is used as the authentication server. All right. And the next authentication method is called EAP, or Extensible Authentication Protocol. And this specifies how authentication is performed by 802.1x. And a variety of EAP types exist. You got what is called PEEP, or Protected EAP. You got Extensible Authentication Protocol, Flexible Authentication via Secure Tunneling, or EAP Fast. You have EAP TLS, or EAP Transport Layer Security. And then you got EAP TTLS, and that stands for EAP Tunnel Transport Layer Security. Now, in a typical 802.1x setup, EAP is used to carry the credential information provided by the supplicant to the authenticator. And EAP is then encapsulated into Radius for transmission to the authentication server. All right, so let's go ahead and talk about risk management and SIEM. So, two final areas of cybersecurity that this video will examine are risk management and security information and event management, or SIEM. And every organization should consider risk management, and many would argue that every organization should also consider SIEM. And both of these areas can help an organization save money, time, and ultimately become more secure. So let's talk about risk management. So it is important for an organization to take a formal approach to risk management in order to secure the organization, and also help ensure that the organization is spending its time and resources on the best possible security solutions for the situation. Risk management, this involves carefully identifying, evaluating, and prioritizing risks. It typically also involves the coordinated application of resources to minimize, monitor, and control the probability or impact of cybersecurity related events. All right, so let's go ahead and talk about security risk assessments. So cybersecurity concerns continue to increase in number and importance. Fortunately, there are many assessments that you can conduct to help improve the overall security of your network infrastructure. This information is going to detail some of the ones that you should be familiar with. First one is called a threat assessment. So oftentimes, as part of risk management, you need to engage in threat assessment. This process involves evaluating the credibility and seriousness of potential threats and analyzing the probability that particular threats will become a reality. You have what is called a vulnerability assessment. So another common part of risk management is the vulnerability assessment. And when you perform a vulnerability assessment, you identify, quantify, and prioritize the vulnerabilities in the system. And as a side note, vulnerability assessments, they can be performed for a wide variety of systems within an IT department and in a network as a whole. Then you have what is called penetration testing. And this can be an important part of the risk management process for an organization. Penetration testing, this involves trying to find vulnerabilities and problems with the security settings of a network or a network component. And penetration testing, this can help you find problems with systems and mitigate the risk of a cyber attack. And then another common part of risk management is called posture assessment. And this involves examining the state of a network and the network nodes from a security perspective. You can use the results of posture assessments to implement new security rules through a AAA system. With posture assessment, you can design requirements related to patch levels, software updates, or things like firewall rules. And if an incoming system does not meet those requirements, you can deny it access to the network. All right, next let's talk about a business risk assessment. Thorough risk management processes, they might include a business risk assessment. And with this type of assessment, the focus may be on the business processes and the vendors the organizations have partnered with. And process and vendor assessments are just two of the many types of business risk assessments an organization might perform. So the first one we're going to talk about is the process assessment. A thorough process assessment, this can help determine the security consciousness of the various business processes that an organization engages in. And process assessments, they often concentrate on many other areas beyond security. So for example, an organization may find many inefficiencies in the business processes that it uses on a daily basis. And one of the many reasons that business process assessments are necessary is that companies can become complacent and fail to update their process documentation, even though many small changes have been implemented over time. And next, we
we have what is called the vendor assessment. So this is a type of risk assessment in which a team analyzes the many vendors an organization uses in its business processes. And this type of assessment considers how much organizational data vendors have access to and the security practices of the vendors. And there are a number of issues that you need to consider in assessing the vendors that your business relies upon. And finally, we're going to take a look at security information and event management, also known as SIEM. So monitoring, this is a critical part of network security. So for example, SIEM software products and services, they combine security information management and security event management. In SIEM systems, they provide real-time analysis of security alerts generated by applications and network hardware. And these systems can log security data and generate reports for compliance purposes. In a SIEM system, this can take many forms. It can be implemented as software, as an appliance, or as a managed service. And here are just some of the focuses of various SIEM products. The first one is log management. So this aspect of the SIEM, this helps administrators back up and archive the many log files in the network, along with many other management tasks that are appropriate for this data. You have what is called the security information management, and this focuses on long-term storage as well as analysis and reporting of log data. Then you have the security event manager. This involves real-time monitoring, correlation of events, notifications, and console views. Then we have the MSS, or the Managed Security Service, and the MSSP, or the Managed Security Service Provider. So the most common managed services, they are related to connectivity and bandwidth, network monitoring, security, virtualization, and disaster recovery. And then we have what is called security as a service. So these security services, they often include authentication, antivirus, anti-malware, and spyware, intrusion detection, penetration testing, and security event management, amongst a whole bunch of other stuff. In this video, you're going to learn about various technology-based attacks such as denial of service, distributed denial of service, an on-path attack, DNS poisoning, VLAN hopping, ARP spoofing, rogue DHCPs, rogue access points, evil twins, ransomware, password attacks, MAC spoofing, IP spoofing, deauthentication, and malware. All right, so let's go ahead and talk about some technology-based attacks. So when you think about cybersecurity attacks, you are likely to think about attacks that make use of technology, considering that you are learning about the field of technology. But these are not the only attacks that affect networks. Social engineering attacks are also a major problem today, and often the first step in more sophisticated attacks that take place. So before we launch into a look at these human and environmental attacks, let us take a detailed look at a variety of common technology-based attacks. And the first one we're going to talk about is called a DOS attack, or a denial of service attack. So an attacker, they can launch a DOS attack on a system by sending the target system a flood of data or requests that consume the target system's resources. In addition, some operating systems and applications crash when they receive specific strings of improperly formatted data, and the attacker can leverage such operating system application vulnerabilities to render a system or an application inoperable. And the attacker, they often use IP spoofing to conceal their identity when they launch a DOS attack. And DOS attacks, they are often categorized as the following. And the first one you have is called reflective. So a third-party system, this is used to help carry out this type of attack. Often this third party is not compromised, which makes a reflective attack very difficult to track down. You have what is called an amplified DOS attack. So a DNS server, this is often used in an amplification attack, but other services could be used in such an exploit as well. And with these attacks, legitimate servers are tricked into flooding responses at a target system, and the forge request tends to be small, but results in large responses hitting the target. And it can be difficult to mitigate amplified attacks because the server involved, which is called a reflector server, this is a legitimate device.
All right, next we have a DDoS attack, or a distributed denial of service attack. And distributed denial of service attacks, they can increase the amount of traffic flooded to a targeted system. A DDoS attack, this is a coordinated attack. Specifically, an attacker compromises multiple systems, then instructs those compromised systems, which are called zombies or bots, to simultaneously launch a DDoS attack against a target system. And the attacker uses what is called command and control software to instruct the zombies to do their job. And the zombies, they are remotely controlled. And as a side note, a botnet, this is an entire network segment that is filled with bots. And a significant traffic spike as compared to the baseline, this could provide an early indication that an attack is taking place. An intrusion prevention system, or IPS, this is designed to recognize and alert when attacks or malicious traffic is present on the network. And as another side note, you want to remember that a DOS attack, this originates from a single system, whereas a DDoS attack, this originates from multiple systems simultaneously. All right, next type of attack we have is called an on-path attack. So an attacker who can get in the direct path between a client and a server can then eavesdrop on the conversation between the client and the server. And once again, this type of attack is called an on-path attack. If cryptography is being used and the attacker fools the client and server both into building VPNs to the attacker instead of to each other, the attacker can see all the data in plain text. On a local Ethernet network, methods such as address resolution protocol spoofing, ARP cache poisoning, DHCP spoofing, and DNS spoofing and poisoning, this may be used to redirect a client's traffic through the attacker instead of directly to the server. Now, as a side note, the newer terminology on-path attack, this is a much more accurate description than the older term of man-in-the-middle attack, because the man-in-the-middle attack, it does not properly convey that the attacker can carry out an attack from any point on the path and not just in the middle. All right, next attack we have is called DNS poisoning, or domain name system poisoning. So another potential for attacks against cybersecurity involves the DNS services and systems, and many advancements have therefore been made in the DNS security mechanism. One simple approach to DNS attacks is the injection of false entries into the DNS system, which is known as DNS poisoning. This might be done in order to deny service to systems or to redirect them to websites that might be designed to disseminate malware or collect credentials. All right, next we have what is called VLAN hopping. So 802.1q trunk lists, they support a feature called Q&Q tunneling. And this approach, which involves encapsulating 802.1q traffic inside of other 802.1 traffic, can be very beneficial for service providers that might take trunk traffic from customers and need to tunnel that traffic through their own service providers. Unfortunately, the use of a native VLAN can be exploited with this Q&Q tunneling technology. Specifically, an attacker can use the combination of Q&Q tunneling and the native VLAN feature to send traffic into a VLAN that the attacker would not normally be able to send traffic into. And this type of attack, once again, is called VLAN hopping. Now, common security changes to prevent VLAN hopping attacks include ensuring that the native VLAN is set to a completely unused VLAN, or for switches that support it, tagging the native VLAN. In both measures, they eliminate VLAN hopping attacks altogether. All right, next we have ARP spoofing. So as you might expect, ARP spoofing, this involves falsifying identity. So with ARP spoofing, the layer 2 MAC address is misrepresented. An attacker might use MAC spoofing to bypass simple MAC-based security mechanisms, such as port security. And then we have a rogue DHCP server. So rogue DHCP servers might be accidental or malicious in a network. And when they are malicious, the attacker is seeking to disrupt or redirect end-user traffic by providing false DHCP leased IP address information. And today, DHCP snooping provides excellent protection against such attacks, and this technology seeks to ensure that DHCP server traffic is legitimate in the network at all times. All right, next we have what is called a rogue access point. So rogue access points, these are unauthorized access points that prevent legitimate network access through intentional misconfiguration. And this approach is very similar to the rogue DHCP server approach. We have what is called an evil twin. An evil twin, this is a special type of rogue access point attack. An evil twin attack is designed to capture authentication information from an unsuspecting network user. And this attack is so named because a rogue access point is configured in this scenario to appear just like the legitimate access point that the client should be connecting with. And then we have what is called ransomware. So ransomware has been an extremely popular type of cybersecurity attack for the past several years. And with this style of exploit, the attacker locks access to a system or files, often using encryption, or at least they pretend to have locked the access to the system or files. And the attacker asks the computer user to pay a ransom to get the system or files unlocked. And attackers, they commonly ask for the ransom in Bitcoin or some other cryptocurrency to make the attack less traceable. Next, we have what is called a password attack. So for as long as computer systems have existed, password attacks have also existed. So with this type of attack, the attacker seeks to gain access to systems or files by using the actual password required for that access. There are many different forms of password attacks, including the following. You have what is called a brute force password attack. So in this type of attack, the attacker tries all possible combinations until a match is found. So for example, a brute force attack might start with the letter A and go through the letter Z, and then the attacker might attempt letters AA through ZZ, continuing to try combinations until the password is determined. Now, using complicated passwords with a mixture of upper and lowercase letters as well as special characters and numbers, this can help prevent brute force attacks. And we have what is called a dictionary password attack. So in this type of attack, the attacker tries multiple password guesses. However, a dictionary attack is based on a dictionary of commonly used words rather than trying all possible combinations as with a brute force attack. And picking a password that is not a common word, this helps to prevent dictionary attacks. All right, next we have what is called MAC spoofing. So this is a simple attack in which a cyber criminal pretends to possess a different MAC address than is actually on the criminal system. MAC spoofing, this is often the first step in a much larger and more sophisticated attack. Because MAC spoofing is relatively easy to accomplish, port security is not often viewed as a sophisticated and comprehensive defense in a network. More sophisticated security solutions, such as dynamic ARP inspection or DAI, are more robust and more effective mechanisms to mitigate issues like MAC spoofing in the network. All right, next we have what is called IP spoofing. So it did not take long in the history of TCP/IP and the internet for attackers to realize that they could fool many IP security mechanisms by simply pretending to possess a different IP address. And think about how many security mechanisms, such as access control lists, focus on the IP address that a source of traffic is using. Faking this address is often all that is required to breach an IP address-based security solution. And it's relatively easy to modify a source IP address, but there are many mechanisms you can use in modern networks to guard against IP address spoofing. One Cisco solution is called IP Source Guard, which is a tool that relies on DHCP snooping and coordinates DHCP assigned IP addresses to systems in a network based on the MAC addresses of those systems. All right, next we have what is called deauthentication. So in a deauthentication attack, the attacker sends a deauthentication frame to the victim to disconnect that client from the wireless LAN. While continuously disconnecting a client from the Wi-Fi would do a great job frustrating the end user and the local help desk, it would not in and of itself cause much damage. Typically, the attacker carries out further attacks against the client. So for example, an attacker who has installed an evil twin on the network might first carry out a deauthentication attack, and then when the client is reconnecting to the network, they attempt to ensure that the end user connects to the evil twin. All right, and then finally we have malware. So malware, this has become a catch-all term for the various types of viruses, worms, spyware, trojans, and other problematic and malicious software code on the network. Malware, it can vary from a mere inconvenience to a catastrophic type of security incident. So for example, after a single machine in an organization is compromised and is running malicious software, the attacker might use that single machine to proceed further into the internal network and use the compromised host as a pivot point. Malware in your organization may have been implemented by an outside attacker or by an inside disgruntled employee. And antivirus and anti-malware software, they should be run on all systems, and users should be given very limited rights related to installation of any software on the computers that they use.
In this video, you're going to learn about various human, environmental, and other miscellaneous attacks. All right, so let's talk about human and environmental attacks. So, attacks that leverage human nature and human behavior, these are called social engineering attacks. And these types of attacks are very common and are often the first step or steps in much larger attacks. And the following are some specific types of social engineering attacks that you need to be familiar with. The first one is called phishing. So, this variation of a social engineering attack, this involves sending an email to a user that appears to be legitimate in an attempt to have the user input authentication information that is then captured. So for example, the email may ask the reader to click a website link to claim a package from FedEx. The attacker constructs a website at a false address that looks just like the actual FedEx website. Then we have what is called tailgating. So with tailgating, the attacker physically follows a valid employee through a secured area of the organization. So for example, the attacker might notice that a security badge swipe opens a door and that the door, once open, does not lock again for 30 seconds. The attacker will wait for a valid entry and then sneak into the area after that entry and before 30 seconds has elapsed. Then we have what is called piggybacking. So this is similar to tailgating, and in fact, the two terms are often used interchangeably. However, piggybacking is often distinguished from tailgating in that the valid employee knows and is cooperating with the cyber criminal. In addition, the term piggybacking is used to refer to a purely electronic transaction. In this form of piggybacking, data flows through some key point in the network, and while that channel is open, the criminal sneaks their data through. And then we have what is called shoulder surfing. So in this classic form of social engineering attacks, the cyber criminal simply watches over the shoulder of an authorized employee to learn passwords and other inputs to gain access at a later time. In addition, a shoulder surfer might look for sensitive information such as employees' social security numbers on the screen of an HR person. So let's talk about some miscellaneous attacks that you need to be familiar with in today's network environment. And the first one we're going to talk about is called a packet capture. So an attacker can use a packet capture or packet sniffing utility such as Wireshark to capture packets after placing a PC's network interface card in promiscuous mode. In some protocols such as Telnet and HTTP, they are sent in plain text, which means packets sent with those protocols can be read by an attacker, perhaps allowing the attacker to see confidential information. All right, next we have what is called confidentiality attacks or ping sweeps and port scans. So a confidentiality attack might begin with a scan of network resources to identify attack targets on the network. A ping sweep could be used to ping a series of IP addresses, and ping replies might indicate to an attacker that network resources were reachable at those IP addresses. After a collection of IP addresses are identified, the attacker might scan a range of UDP or TCP ports to see what services are available on the host at the specified IP addresses. Also, port scans, they often help attackers identify the operating system running on a target system, and these attacks are commonly referred to as reconnaissance attacks. All right, next we have what is called dumpster diving. So many organizations, they throw away hard copies containing confidential information without properly shredding them. And attackers, they may rummage through an organization's trash in hopes of discovering information that could be used to compromise network resources. And we have electromagnetic interference. So data is often transmitted over wires such as unshielded twisted pair wires. Attackers can sometimes copy information traveling over a wire by intercepting the EMI emanations being emitted by the transmission medium. And then we have what is called wire tapping. So an attacker who gains physical access to a wiring closet might physically tap into telephone cabling to eavesdrop on telephone conversations, or might insert a shared media hub inline with a network cable to connect to the hub and receive copies of packets flowing through the network cable. All right, next we have what is called information sent over overt channels. So an attacker might send or receive confidential information over a network by using an overt channel. An example of using an overt channel is tunneling one protocol inside of another. For example, sending instant messaging traffic via HTTP. Steganography, this is another example of sending information over an overt channel. So for example, an attacker might send the digital image made up of millions of pixels with secret
secret information encoded in specific pixels, where only the sender and the receiver know which pixels represent the encoded information. All right, next we have information sent over covert channels. So an attacker might send or receive confidential information over a network by using a covert channel, which can communicate information as a series of codes or events. So for example, an attacker could represent binary data by sending a series of pings to a destination. A single ping within a certain period of time, this could represent a binary 0, and 2 pings within the same time period could represent a binary 1. All right, next we have what is called an FTP bounce. So FTP, this supports a variety of commands for setting up a session and managing file transfers. An attacker may use one of these commands, like the port command, to access a system that would otherwise deny the attacker. Specifically, an attacker connects to an FTP server by using the standard port 21. However, FTP uses a secondary connection to send data. The client issues a port command to specify the destination port and destination IP address for the data transmission. Normally, the client would send its own IP address and an ethereal port number. The FTP server would then use the source port 20 and the destination port specified by the client when sending data to the client. However, an attacker might issue a port command specifying the IP address of a device to access, along with an open port number on that device. As a result, the targeted device might allow an incoming connection from the FTP server IP address, but reject the connection in from the attacker's IP address. Fortunately, most modern FTP servers do not accept the port command coming from a device that specifies a different IP address than the client's IP address. All right, next we have what is called session hijacking. So an attacker could hijack a TCP session, for example, by completing the third step in the three-way TCP handshake process between an authorized client and a protected server. An attacker who successfully hijacks the session of an authorized device might be able to maliciously manipulate data on the protected server. All right, next we have what is called a salami attack. So a salami attack, this is a collection of small attacks that result in a larger attack when combined. So for example, an attacker who has a collection of stolen credit card numbers could withdraw small amounts of money using each credit card. The combination of the multiple small withdrawals would add up to a significant sum for the attacker. All right, next we have what is called data diddling. So data diddling, this involves changing data before it is stored in a computing system. Malicious code in an input application or a virus could perform data diddling. So for example, a virus, a Trojan horse, or a worm could be written to intercept keyboard input while the appropriate characters are displayed on screen so that the user doesn't see an issue. Manipulated characters could be entered into a database application or sent over a network. Then we have what is called a trusted relationship exploitation. So different devices in the network might share a trust relationship. So for example, a certain host might be trusted to communicate through a firewall using specific ports, while other hosts are denied passage through the firewall using those same ports. If an attacker were able to compromise a host that had a trust relationship with the firewall, the attacker could use the compromised host to pass normally denied data through a firewall. All right, next we have what is called a logic bomb. So in this type of attack, malicious code is hidden in a system and can be triggered by the author or by another attacker. So for example, a programmer might hide malicious code that starts deleting files if the programmer's employment is terminated. We have what is called a TCP send flood. So in this variant of a DOS attack, the attacker initiates multiple TCP sessions by sending send segments, but then never completing the three-way TCP handshake. The attacker can send multiple send segments to a target system with false source IP addresses in the header of the send segments. Because many servers limit the number of TCP sessions they can have open simultaneously, a send flood can render a target system incapable of opening a TCP session with a legitimate user. All right, next we have what is called a buffer overflow. So a computer program may be given a buffer, which is a dedicated area of memory to which it can write. If the program attempts to write more information than the buffer can accommodate, a buffer overflow may occur. If permitted to do so, the program can fill up its buffer and then have its output spill over into the memory area being used for a different program. This potentially can cause the other program to crash. And some programs are known to have this vulnerability. That is, as being able to overrun their memory buffers, which can be exploited by attackers. Then we have what is called an ICMP attack. So many networks permit the use of internet control message protocol traffic, such as ping traffic, because pings can be useful for network troubleshooting. However, attackers can use ICMP for DOS attacks. And one ICMP DOS attack variant is called the ping of death, and it uses ICMP packets that are too big. Another variant sends ICMP traffic as a series of fragments in an attempt to overflow the fragment reassembly buffers on the target device. And then we have what is called a Smurf attack, and this can use ICMP traffic directed to a subnet to flood a target system with ping replies. Then we have what is called electrical disturbance. So at a physical level, an attacker may launch an availability attack by interrupting or interfering with the electrical service available to a system. So for example, an attacker who gains physical access to a data center's electrical system might be able to cause a variant of electrical disturbances such as power spikes, electrical surges, blackouts, and brownouts. And as a side note, the attack types that were listed in this video, these are just some of the many attack types being used today. New attacks and even new categories of attacks are being created all of the time. Also, keep in mind that many attacks are actually perpetuated by employees of an organization. And these type of attacks, they are called insider attacks. In this video, you're going to learn about best practices for network hardening techniques in addition to wireless security and IoT considerations. So for a long time, many network vendors emphasize using a defense in depth strategy. And while they would still stand behind this approach, today plenty of other security initiatives are being promoted, such as zero trust. And if you think about the defense in depth concept for a moment, you'll realize the importance of network device hardening in this strategy. After all, it is wise to tightly secure the network devices themselves in an attempt to build a very secure network. In addition, network device hardening, this is an excellent idea because many devices, they ship from the manufacturer with default configurations that can be quite dangerous. So for example, you might receive a network router that has a web server process enabled inside it. This web server software might permit HTTP and not HTTPS connections. There may be no access control list or firewall of any kind protecting this web server. Perhaps this security vulnerability is meant to permit web-based management of the device. Your security policy probably does not permit such a vulnerability. Hardening this device by disabling or even eliminating the web server, that would be an excellent idea. In fact, because you should always try to adhere to your security policy in this scenario, the web server must be installed or at least disabled. So we're going to go ahead and talk about some best practices. So while hardening of the network through the hardening of its network devices can be a daunting task, the great news is that there are many standard practices in this regard. So just remember that whenever you see a list like this, you should be prepared to encounter plenty of best practices that will not be applicable for your particular network or your particular network device. And the following, this is just a list of network hardening techniques that you should at least consider. And the first one is called changing the default credentials. So at a very minimum, you should always do this step first. The first thing an attacker is likely to do as an initial step in a larger scale attack is try using the default username and password credentials to access the network devices. And plenty of websites, they provide a list of default username and password credentials for common systems from popular vendors. And if you take none of the other steps that are described in this video, at least take this one as it is very crucial. All right, next you want to avoid using common passwords and usernames on devices. So avoid using usernames like admin and passwords like password123. You'll also need to follow your own enforced password complexity and length policies. And today, it is recommended that passwords be at least 8 to 12 characters long and include a certain combination of special characters, numbers, and upper and lowercase letters. You also want to upgrade the firmware. So by installing updated firmware, you gain new functionality on the device, and oftentimes the device, it gets a much needed security patch and some other enhancements. Next, you want to patch and update your devices. So just as your firmware needs consistent attention to patches and updates, so does your operating system and applications. Many network devices from popular vendors today, they are so sophisticated with their operating systems that they can run plug-in types of applications or even full-blown applications. And patches and apps, they might bring advanced features to a device. Next, you want to disable unneeded network services. So modern network devices, they tend to have many network services that are enabled by default. And to reduce the attack area, you should trim off any unnecessary services by disabling them. Reducing the attack surface by not running services, this means that there is less that the attacker can target. Attackers, they commonly target Bluetooth and remote desktop services as methods of carrying out access for their subsequent attacks. Next, you want to use secure protocols. So use secure protocols over unsecure protocols whenever possible. So for example, use secure shell rather than the insecure telnet for remote management using terminals. Also, you want to secure the SNMP. So be sure to use the security features of the relatively new SNMP version 3, which provides encryption. All right, next you want to generate new keys and credentials. So rotate important credentials that are used to guard your corporate systems and data. And also remember that responsible encryption key management, this is crucial to securing cryptographic keys. Go ahead and disable unneeded switch ports. So you might have a few or you might have a ton of ports on switches that are not connected to anything. These ports need to be shut down. One primary reason to disable unneeded switch ports is that if someone gains physical access to a network switch and connects to a switch port, you want to ensure that the person cannot access the network through that port. And you can use port blocking as well as physical security practices to prevent such access. Next, you want to ensure spanning tree protections. So if you are stuck with spanning tree protocol in your network, you need to be sure to use any protections offered by a network device. And these protections might include a root guard, a bridge protocol data unit guard or a BPDU guard, and a flood guard. Also, you want to enable DHCP snooping. This involves preventing rogue DHCP servers and DHCP pool exhaustion attacks, restricting ports from accepting certain DHCP messages. All right, next you want to use VLAN segmentation. So doing so inherently protects systems from accidental or malicious attacks from systems and other broadcast domains. In VLAN segmentation, this also forces inter-VLAN communications to pass through a router, allowing you to easily enforce security policy and security checks on the traffic. You also want to use port security. So locking down switch ports to MAC addresses is a good first step in hardening a network, and doing so guards against MAC flood attacks nicely, but note that the network is still vulnerable to MAC spoofing attacks. Next, you want to use router advertisement guard. So this helps protect against attacks in IP version 6 environments where routers can advertise the network prefix information to end systems, and these end systems can configure their own unique host IDs. Therefore, you can address end systems without requiring DHCP implementation. While these types of features are excellent, you need security controls such as router advertisement guard to make sure these features cannot be exploited. All right, next you want to use dynamic ARP inspection. So this layer 2 security mechanism, it guards against MAC address spoofing, and it can pair nicely with port security. You also want to use control plane policing, so COPP. This is an excellent security feature that can control the rate of packets to and from the control plane of a network device. And think about life without control plane policing. Attackers, they could easily cause denial of services on a network device by simply flooding fake border gateway protocol updates to the device. All right, next you want to use private VLANs. So you will often implement networks for special types of deployments. So for example, say that you are creating a network to be shared by a row of stores in a shopping mall. Well, each store needs to be segmented from every other store, and private VLANs are excellent for such a design. Each store will have its own private VLAN, and all of these private VLANs can reach the internet, but they cannot enter the other private VLANs. And all of the VLANs in this case, they can be in the same IP subnet. This type of topology, it will confuse an attacker who is unaware of the private VLAN feature. The attacker will see that all the systems are clearly in the same IP subnet, internet, but they would not be able to communicate with each other. Next, you want to change the default VLAN. So most network devices that offer switch ports place all of these ports in a default VLAN. So for example, Cisco switches all have ports in VLAN 1 by default. Attackers, they know this and they seek out these ports in the default configuration to try to exploit them. And next, you want to use access control lists. So you want to use ACLs wherever possible to help strengthen security. So for example, a network device might actually be using the built-in web server for network management. If this device offers an ACL feature to protect the internal web server from unauthorized access, you should take advantage of that feature. All right, next you want to use role-based access. So consider using role-based access control by creating groups or roles on network devices. And you can map these groups to different permission levels. This would allow you to permit junior engineers read-only access to devices to help you with monitoring. At the same time, you can have groups with much higher levels of privileges to help with configuration and optimization. Then you want to go ahead and use firewall rules. So many network devices, they have full-blown firewall services that are built in, and it is important to consider how a firewall operates with traffic that does not match any permit statement in the firewall configuration. So does the device have an implicit deny rule for all of this traffic, or do you need to configure an explicit deny for this traffic? Now, as traffic passes through the firewall rules, it is permitted or denied based on those rules. And when it reaches the end of the explicitly stated rules, will it be dropped due to an implicit deny, or do you need to configure an explicit deny rule at the end? And the most common configuration is to have an implicit deny in place for all of the unmatched traffic in the firewall rules. Side note, for a firewall that consists of all deny entries, you might need to add an explicit permit all entry at the end of the rules to override an implicit deny all. All right, next, let's go ahead and talk about wireless security and IoT considerations. So there are a number of security best practices to consider for wireless networks and the ever-growing Internet of Things, and here are just a few of them. So you want to go ahead and use MAC filtering. So MAC filtering, which is similar to port security, is important in a wireless environment. With MAC filtering, you can lock down access to the Wi-Fi network by allowing only specific MAC addresses. You also want to consider antenna placement. So it often helps to place and direct Wi-Fi antennas so that there is not a lot of overflow to the reach of the signal. So for example, you might want to use a directional antenna to beam a signal as directly as possible to another system. This helps keep the signal strong, and it also prevents many potential devices from receiving the signal. And you should also try to minimize the placement of Wi-Fi antennas in unsecured network locations. Now, as a side note, a professional site survey for Wi-Fi environments. This can help you determine what access point placement approaches to use to address coverage areas and security concerns. All right, next you want to adjust the power levels. So a nice feature of wireless LAN controllers is that they can automatically adjust the power levels of access points and their antennas so that signals are not sent into areas where they are not wanted or not needed. Next, you want to use wireless client isolation. So wireless client isolation, this is a security feature that prevents wireless clients from communicating with one another. And this feature is useful for guest and BYOD wireless networks. You might also want to use guest network isolation. So if you do not care if your guest Wi-Fi nodes can reach each other, you might want to consider implementing isolation for the entire guest Wi-Fi network. And this is a very common practice. The guest Wi-Fi basically permits the nodes inside of it to access the public internet, but it does not permit any of the network devices in the enterprise hosting the guest Wi-Fi. You also want to rotate and secure the use of strong PSKs or pre-shared keys. So if you are relying on PSKs in your Wi-Fi security environment, you want to be sure to rotate and protect these credentials, just as you do with more traditional passwords for user accounts in your enterprise.
certificates. All right, next you want to use Extensible Authentication Protocol, or EAP. So EAP, this has become the de facto standard for carrying security credentials in a Wi-Fi network. And in the case of the popular 802.1x, the EAP client, which is also known as the supplicant, this sends the security credentials to the wireless LAN controller wrapped in an EAP packet, and the WLC wraps this packet in a radius packet and sends the information to an authentication server on the network. This system then checks the security credentials and then instructs the WLC whether it should permit the device or the user on the network. All right, next you want to use geofencing where needed. So this technology often uses GPS or RFID to define geographical boundaries. In geofencing, this allows you to define triggers so that when a device enters or exits the boundaries defined by the administrator, an alert will be issued. In geofence virtual barriers, they can be active or passive. In active geofence, this requires an end user to opt into location services and requires a mobile app to be open. Passive geofences are always on. They rely on Wi-Fi and or cellular data instead of GPS or RFID, and they can work in the background. So for example, say that a hospital keeps patient information on tablets that the hospital distributes to the staff. If these tablets travel beyond the geofence, an administrative alert can be triggered. All right, next you want to consider using captive portals. So captive portals, they can obtain information about guests that are attempting to access guest networks or other network resources. And with this approach, you send the user to a web page to enter credential information and or accept agreements on usage. And most public networks, including Wi-Fi hotspots, they use a captive portal, which requires users to agree to some conditions before they can use the network or the internet. And then finally, you want to control IoT access. So you need to be concerned about breaches of security in your IoT infrastructures, which often rely on Wi-Fi, or at least portions of it do. Therefore, many of the other best practices that were listed in this video, they are appropriate for IoT infrastructures, and it is a good idea to consistently update your IoT devices for new security enhancements that inevitably will come. And you should also segment the IoT traffic as much as possible in the enterprise environment. In this video, you're going to learn about VPNs, IPsec with Internet Key Exchange version 1, authentication header and encapsulating security payloads, setting up and tearing down an IPsec site-to-site VPN, Internet Key Exchange version 2, and other VPN technologies. All right, so let's talk about VPNs. So prior to the pandemic, some employees worked in remote offices and others telecommuted. Remote employees, they can communicate to their main corporate network by using a variety of WAN technologies, such as leased lines or high-speed fiber connections. However, these WAN technologies typically cost more than widely available broadband technologies, such as cable, which might also offer faster speeds or at least comparable speeds. Virtual private networks, they support secure communication between sites over an untrusted network such as the internet. And the two primary categories of VPNs are site-to-site and client-to-site VPNs. So a site-to-site VPN, they interconnect two sites as an alternative to a leased line at a reduced cost. In this picture on your screen right here, this shows an example of a site-to-site VPN. And next we have what is called a client-to-site VPN, which is also known as a remote access VPN. And this interconnects a remote user with a site as an alternative to dial-up or ISDN connectivity, also at a reduced cost. And once again, this picture on your screen right here, this shows you what a client-to-site VPN looks like. Now, although a VPN tunnel might physically pass through multiple service provider routers, the tunnel appears to be a single router hop from the perspective of the routers at each end of the tunnel. In a client-to-site VPN, this allows a user with software on a client computer to connect to a centralized VPN termination device. In a site-to-site VPN, it interconnects two sites without requiring the computers at those sites to have any specialized VPN software installed. Client-to-site VPNs, they could be implemented using a VPN-compatible device such as a router, a firewall, or a special purpose device called a VPN concentrator that is custom built for handling remote access client-to-site VPN connections. And it is also possible with the correct software for two computers to connect to each other directly
specifically using host-to-host IPsec VPN connections. And one very popular option in client-to-site VPNs is called a clientless VPN, although this is a bit of a misnomer. With a clientless VPN, there is a client software piece, but it is not a separate piece of software. Rather, the client's web browser acts as the VPN client software. In this type of VPN connection, it leverages the SSL TLS capabilities of the modern internet and web browsers to provide a secure connection. And another important consideration when it comes to VPN configuration is whether you will be using a split tunnel or a full tunnel configuration. So with a full tunnel configuration, you have all the end user traffic go through the VPN tunnel. With a split tunnel configuration, you don't have all of the end user traffic go through the VPN tunnel. So for example, you might choose to have just the traffic that needs to access the corporate network sent through the VPN tunnel, while allowing traffic destined for the internet or perhaps Office 365 traffic to bypass the tunnel. Split tunneling is often an advantageous configuration because the bandwidth required by the VPN connection and the overhead that's associated with it can be minimized. Next, let's talk about IPsec with Internet Key Exchange version 1. So broadband technologies such as cable, in addition to other VPN transport mechanisms, often traverse an untrusted network such as the internet. Therefore, a primary concern with using a broadband technology as a VPN transport is security. And VPN technologies such as IPsec, generic routing encapsulation, layer 2 tunneling protocol, and layer 2 forwarding, they offer a variety of features, but IPsec VPNs, they offer strong security features. Specifically, IPsec offers CIA protection for traffic. And if you can recall the components of the CIA triad, they are as follows. You have confidentiality. So data confidentiality is provided by encrypting data. A third party who intercepts the encrypted data will not be able to interpret it. You have integrity. So data integrity, this ensures that data is not modified in transit. So for example, routers at each end of a tunnel can calculate a checksum value or a hash value for the data. And if both routers calculate the same value, the data has most likely not been modified in transit. And you have authentication. So data authentication, this allows parties involved in the conversation to verify that the other party is the party that they claim to be. Also, IPsec or IP security, this also scales to a wide range of networks. IPsec operates at layer 3 of the OSI model, which is the network layer. And as a result, IPsec is transparent to applications, which means that applications do not require any sort of integrated IPsec support. All right, next let's talk about Internet Key Exchange modes and their phases. So IPsec, it uses a collection of protocols to provide its features. And one of the primary protocols that IPsec uses is the Internet Key Exchange. Specifically, IPsec can provide encryption between authenticated peers using encryption keys that are periodically changed. In Internet Key Exchange, however, this allows an administrator to manually configure the keys. Now, the Internet Key Exchange can use 3 modes of operation to set up a secure communication path between IPsec peers. The first one you have is called main mode, and this involves 3 exchanges of information between the IPsec peers. So you have exchange 1. This is where the responder selects a proposal it received from the initiator. You have exchange 2. So Diffie-Hellman, this is an algorithm, is used to securely establish a shared secret key over the unsecured medium. And then you have exchange 3, an Internet Security Association and Key Management Protocol session is established. And this secure session is then used to negotiate an IPsec session. And then one peer, which is called the initiator, it sends 1 or more proposals to the other peer, which is called the responder. The proposals include supported encryption and authentication protocols and key lifetimes. In addition, the proposals indicate whether perfect forward secrecy should be used. When perfect forward secrecy, this ensures that a session key remains secure, even if one of the private keys used to derive the session key becomes compromised. All right, and the next mode is called aggressive mode. So aggressive mode more quickly achieves the same results as main mode using only 3 packets. The initiator sends the first packet, which contains all the information necessary to establish a security association, which is an agreement between the 2 IPsec peers about the cryptographic parameters parameters to be used in the ISA KMP session. The responder sends the second packet, which contains the security parameters selected by the responder, which are the proposal, the king material, and its ID. The responder uses this second packet to authenticate the session, and the third and final packet, which is sent by the initiator, finalizes the authentication of the ISA KMP session. And then we have what is called quick mode. So quick mode, this negotiates the parameters of the SA for the IPsec session, and this negotiation occurs within the protection of an ISA KMP session. So the Internet Key Exchange version 1 modes, they reflect the two primary phases of establishing an IPsec tunnel. So for example, during Internet Key Exchange phase 1, a secure ISA KMP session is established using either main mode or aggressive mode. During Internet Key Exchange phase 1, the IPsec endpoints establish what are called transform sets, which are collections of encryption and authentication protocols, hash methods, and other parameters needed to establish a secure ISA KMP session, which is sometimes called an ISA KMP tunnel or an IKE phase 1 tunnel. And this collection of parameters is called a security association or an SA. And with IKE phase 1, the SA is bidirectional, which means that the same key exchange is used for data flowing across the tunnel in either direction. So IKE phase 2, this occurs within the protection of an IKE phase 1 tunnel using the previously described quick mode of parameter negotiation. A session formed during the IKE phase 2, this is sometimes called an IKE phase 2 tunnel or simply an IPsec or IP security tunnel. However, unlike in IKE phase 1, IKE phase 2 performs a unidirectional SA negotiation, which means that each data flow uses a separate key exchange. Now, although an IPsec tunnel can be established using just an IKE phase 1 and IKE phase 2, an optional IKE phase 1.5 can be used. An Internet Key Exchange phase 1.5, this uses the extended authentication protocol to perform user authentication of IPsec tunnels. And like IKE phase 2, IKE phase 1.5 is performed within the protection of an Internet Key Exchange phase 1 tunnel. The user authentication provided by this phase adds a layer of authentication for VPN clients. Also, parameters such as IP, WINs, and DNS server information can be provided to a VPN client during this optional phase. A newer version called IKE version 2, this combines many of the same functions of IKE version 1 and uses an initial IKE version 2 tunnel instead of the IKE version 1 phase 1 and child security associations or SAs and tunnels for the IPsec tunnels instead of calling them IKE or Internet Key Exchange phase 2 tunnels. The stuff sounds very confusing. Trust me, I know. All right, next let's talk about authentication header and encapsulating security payloads. So in addition to Internet Key Exchange, which establishes the IP security tunnel, IPsec relies on either the authentication header protocol, which is IP protocol number 51, or the encapsulating security protocol, which is IP protocol number 50. In both authentication headers and ESPs, they offer origin authentication and integrity services, which ensures that the IPsec peers are who they claim to be and that the data was not modified in transit. However, the main distinction between AH and ESP is encryption support. ESP encrypts the original packet, whereas AH does not offer encryption. And as a result, ESP is much more popular on today's network. Now, both authentication headers and ESP can operate in one of two modes. You got transport mode or tunnel mode. And this picture on your screen right here, this illustrates the structure of an ESP transport mode packet versus an ESP tunnel mode packet. Now, as a side note, you might be concerned that transport mode allows the IP address of the IPsec peers to remain visible during transit because the original packet's IP header is used to route a packet. However, IPsec is often used in conjunction with the generic routing encapsulation tunneling protocol. And with transport mode, the original IP packet is encapsulated inside a GRE tunnel packet, which adds a new GRE tunnel header. And the GRE packet is then then sent over an IPsec tunnel. And even if the IPsec tunnel were running in transport mode, the original packet's IP header would still not be visible. Instead, the GRE's packet header would be visible. Now, the following, this is a detailed description of these two modes. So let's talk about transport mode. So transport mode, this uses a packet's original IP header as opposed to adding an additional tunnel header. And this approach works well in networks where increasing a packet size might cause an issue. Also, transport mode is often used for client-to-site VPNs, where a PC running VPN client software connects back to a VPN termination device at a headquarters location. And then we have what is called tunnel mode. So unlike transport mode, tunnel mode encapsulates an entire packet. As a result, the encapsulated packet has a new header or an IPsec header. And this new header has a source and destination IP address information that reflects the two VPN termination devices at different sites. Therefore, tunnel mode is often used in an IPsec site-to-site VPN. Now, one reason a GRE tunnel might be used with an IPsec tunnel is a limitation on the part of the IPsec. Specifically, an IPsec tunnel can only transmit unicast IP packets. The challenge is that large enterprise networks might have a significant amount of broadcast or multicast traffic, such as routing protocol traffic, and GRE can take any traffic type and encapsulate the traffic in a GRE tunnel packet, which is a unicast IP packet that can be then sent over an IPsec tunnel. So take, for example, a multicast packet used by a routing protocol. Although IPsec cannot directly transport the multicast packet, if the packet is first encapsulated by GRE, the GRE packet can then be sent over an IPsec tunnel, thereby securing the transmission of the multicast packet. All right, next let's go over the 5 steps in setting up and tearing down an IPsec site-to-site VPN using Internet Key Exchange version 1. Step 1, PC 1 sends traffic destined for PC 2. Router 1 classifies the traffic as quote-unquote interesting traffic, and this classification initiates the creation of an IPsec tunnel. Step 2, Router 1 and Router 2, they negotiate an SA used to form an Internet Key Exchange Phase 1 tunnel, which is also known as an ISA KMP tunnel. Step 3, within the protection of the Internet Key Exchange Phase 1 tunnel, the Internet Key Exchange Phase 2 tunnel is negotiated and set up. An Internet Key Exchange Phase 2 tunnel, this is also known as an IPsec tunnel. Step 4, after the IPsec tunnel is established, interesting traffic, such as traffic classified by an access control list, flows through the protected IPsec tunnel. And note that the traffic not deemed interesting can still be sent between PC 1 and PC 2. However, the non-interesting traffic is transmitted outside the protection of the IPsec tunnel. And then step 5, after no interesting traffic is seen for a specified amount of time, the IPsec tunnel is torn down and the IPsec SA is then deleted. Now, this example describes an IPsec site-to-site VPN, but the procedure is similar for a client-to-site VPN. An IPsec is typically deployed using Internet Key Exchange version 1 with its 2 phases, which are Phase 1 and Phase 2. All right, next let's talk about Internet Key Exchange version 2. So the latest version of Internet Key Exchange is Internet Key Exchange version 2. This offers many great improvements over version 1. Version 2 uses fewer packets in setting up the SAs between VPN peers and does not use the terms Phase 1 and Phase 2. Instead, the initial tunnel is called the Internet Key Exchange version 2 SA, and the IPsec SA, this is referred to as a child tunnel instead of being called an Internet Key Exchange Phase 2 tunnel. And additional features that are integrated into version 2 include the following. You have EAP, you have NAT traversal, which is the ability to detect network address translation in the path between the peers, and the ability to validate the tunnel. Now, Internet Key Exchange version 1, this requires additional configuration and vendor add-ons to implement similar types of features. All right, and finally, let's talk about other VPN technologies. So although IPsec VPNs are popular for securely interconnecting sites or connecting a remote client to a site, you need to be aware of other VPN protocols, examples of which I'm going to provide to you right now. And the first one is called SSL. So Secure Socket Layer. This provides cryptography and reliability for the upper layers, or layers 5 through 7 of the OSI model. And SSL, which was introduced in 1985, has largely been replaced by TLS or Transport Layer Security. However, recent versions of SSL, such as SSL 3.3, have been enhanced to be more comparable with TLS. In both SSL and TLS, they provide secure web browsing via HTTPS. Next, you have what is called L2TP. That stands for Layer 2 Tunneling Protocol. This is a VPN protocol that lacks security features such as encryption. However, L2TP can still be used for a secure VPN connection if it is combined with another protocol that does provide encryption. Then you have what is called L2F, and that stands for Layer 2 Forwarding. And this is a VPN protocol designed by Cisco with the goal of providing a tunneling protocol for PPP or point-to-point protocol. Like L2TP, Layer 2 Forwarding, this lacks native security features. Next, we have what is called PPTP, and that stands for Point-to-Point Tunneling Protocol. And this is an older VPN protocol which supported the dial-up networking feature in older versions of Microsoft Windows. And like L2TP and L2F, Point-to-Point Tunneling Protocol, this lacks native security features. However, Microsoft versions of Point-to-Point Tunneling Protocol bundled with various versions of Microsoft Windows are enhanced to offer security features. Then we have TLS or Transport Layer Security. This has largely replaced SSL or Secure Sockets Layer as the VPN protocol of choice for providing cryptography and reliability to upper layers of the OSI model. So for example, when you securely connect to a website using HTTPS, you are probably using TLS. And next we have what is called SSTP, and that stands for Secure Socket Tunneling Protocol. And this is a VPN tunnel that transports peer-to-peer protocol traffic through an SSL TLS channel. In SSL TLS, this provides transport level security. SSTP's use of SSL TLS over TCP port 443, this allows SSTP to pass through virtually all firewalls and proxy servers. And then finally, we have what is called OpenVPN. This is a software VPN system that creates secure point-to-point or site-to-site connections in routed or bridge configurations and remote access facilities, and it implements both client and server applications. In this video, you're going to learn about other remote access technologies, authentication, authorization considerations, and in-band versus out-of-band management. All right, so let's talk about other remote access technologies. So when it comes to remote access solutions, it is not surprising that varying amounts of security are possible today and can be implemented in a wide variety of ways. Your organization might require the strongest possible protections over one remote access connection, while another might require the mildest possible security treatment. Fortunately, remote access technologies abound today, and these varying degrees of security can be accommodated with no problem. Now, although access control lists can be used to permit or deny specific connections flowing through a router or a switch, you also need to control connections to network devices such as routers, switches, and servers. And here are some of the various types of remote access technologies. First one is called RRAS, and that is the Microsoft Routing and Remote Access Server. And this is a Microsoft Windows Server feature that allows Microsoft Windows clients to remotely access a Microsoft Windows network. And this product is often used in Windows-centric corporate networks, and this is partly due to the fact that RRAS is included in Windows Server 2016 or higher. And to make this solution even more accessible to Windows systems, Windows 10 features a built-in VPN client that works well in conjunction with RRAS. And we're comparing RRAS to other technologies. Just remember that we are talking about a very Windows-centric environment. And to be fair, however, the RRAS server could easily provide VPN services for a wide variety of operating systems using VPN software sets to common standards. All right, next we have the Remote Desktop Protocol. So this is a Microsoft protocol that allows a user to view and control the desktop of a remote computer. The RDP uses port 3389, and this solution, which has been around for a long time, permits simple desktop sharing over an internet or other network connection. And this product has widespread use because, once again, it is technology that is built into the Windows system. And thankfully, RDP access to your local Windows 10 device is not enabled by default. Today, RDP usage has leveled off because a wide variety of best-selling software applications do the same thing, or desktop sharing, but also offer many advanced features. And these applications include products such as LogMeIn, TeamViewer, and Splashtop. And once again, RDP is a Windows-centric solution. However, you can run the Windows Remote Desktop Client in a variety of operating systems, so you can access your Windows desktop from Mac or a Linux machine. All right, next we have the remote desktop connection. So when you have a user accessing a system remotely using RDP or a similar remote desktop technology, this is called the remote desktop connection. All right, next we have the remote desktop gateway. So the remote desktop gateway feature, this is a service available on Windows Server systems. It is a very clever use of the RDP protocol in which the server becomes a gateway to permit access to the server for management purposes for administrators who need to connect. These administrators can use Secure Shell for secure remote access. And this is a common practice that administrators perform with non-Windows systems. So now they can feel right at home when managing Windows servers. And then we have what is called VNC, or virtual network computing. And this can be thought of as a platform independent version of Microsoft's RDP. And just like RDP, it seeks to provide an easy to use graphical user interface driven remote desktop experience. In VNC, this is used with Mac and Linux operating systems that do not have desktop sharing software built in, as in with the case of Windows and RDP. And this certainly makes sense in the case of Linux, because many Linux administrators prefer the command line Linux environment and do not use a GUI-based front end. All right, next we have what is called a virtual desktop. So virtual desktop technology is growing at a fast pace, thanks in large part to the adoption of cloud technologies and increased bandwidth between data centers and end users. Using this approach, a user accesses a desktop that is housed on a server in the data center, and the user might not even realize that the operating system is not hosted on the local PC or laptop. Now, note that the virtual desktop concept discussed here, this is different from other types of virtual desktops in IT. So for example, in both Windows and Mac operating systems, you can create virtual desktops. However, these are just running quote unquote spaces on the local system that have different windows and programs running within them, which makes it easier to multitask. And notice how very different this technology is from the virtual desktops that we are referencing here. All right, next we have what is called point-to-point protocol. And this is a common layer 2 protocol that offers features such as multi-link interface, loop link detection, error detection, and authentication. Then we have what is called point-to-point protocol over Ethernet. And this is a protocol commonly used between a DSL modem in a home or a business and a service provider. Specifically, point-to-point protocol over Ethernet, this encapsulates PPP frames within Ethernet frames. And this allows each Ethernet connection to leverage features of point-to-point protocol, such as authentication. All right, next we have what is called the independent computing architecture. And this is a Citrix proprietary protocol that allows an application running one platform, such as Microsoft Windows, to be seen and controlled from a remote client, independent of the client, such as Unix or Linux. Then we have what is called Secure Shell. And this is a protocol used to securely connect to a remote host, typically via a terminal emulator. And Secure Shell has enjoyed such widespread success that it is even used as the basis of several other security protocols and techniques. So for example, SCP, this calls on SSH for some of its functionality. In SSH, it uses port 22. And as mentioned earlier, Linux administrators often prefer to use the command line for all operation and work in the operating system. And SSH is a perfect secure remote access tool for such users. Administrators can use the CLI, or the command line interface, to connect securely with SSH, and then they can operate in what is called a bash CLI environment to manage or work within the system. All right, next we have what is called Kerberos, and this is a client-server authentication protocol that supports mutual authentication between a client and a server. And Kerberos uses the concept of a trusted third party, which is also called a key distribution center, that hands out tickets that are used instead of username and password combinations. Next we have authentication, authorization, authorization and accounting, or AAA. This allows a network to have a single repository of user credentials. A network administrator can, for example, supply the same credentials to log into various network devices, such as routers and switches. And Radius and TACACS Plus, these are protocols used to communicate with a AAA server. Then we have what is called Radius, and that stands for Remote Authentication Dial-In User Service. And this is a UDP-based protocol used to communicate with a AAA server. Unlike TACACS Plus, Radius does not encrypt an entire authentication packet. Rather, it encrypts only the password. However, Radius does offer more robust accounting features than TACACS Plus. And also Radius, this is a standards-based protocol, whereas TACACS Plus, this is a Cisco proprietary protocol. All right, next we have what is called TACACS Plus, and that stands for Terminal Access Controller Access Control System Plus. And this is a Cisco proprietary TCP-based AAA protocol. In TACACS Plus, it has 3 separate and distinct sessions or functions for authentication, authorization, and accounting. Next, we have what is called Network Access Control. And this can be used to permit or deny access to a network based on characteristics of the device seeking admission rather than just checking user credentials. So for example, a client's operating system and version of antivirus software could be checked against a set of requirements before allowing the client to access a network. In this process of checking a client's characteristics, this is called a posture assessment. All right, next we have the IEEE 802.1x. And this is a type of network access control that can permit or deny a wireless or wired LAN client access to a network. So if 802.1x is used to permit access to a LAN via a switch port, then 802.1x, this is being used for port security. In the 802.1x, the device seeking admission to the network, this is called the supplicant. The device to which the supplication connects, either wirelessly or through a wired connection, this is called the authenticator. And the device that checks the supplicant's credentials and permits or denies the supplicant to access the network, this is called the authentication server. And usually an authentication server is a Radius server. All right, next we have what is called CHAP, and that stands for Challenge Handshake Authentication Protocol. This performs a one-way authentication for a remote access connection. However, authentication is performed through a 3-way handshake, which is the challenge, response, and acceptance messages between a server and a client. And the 3-way handshake allows a client to be authenticated without sending credential information across the network. And then we have what is called Password Authentication Protocol, or PAP, and this is an unencrypted plain text method of password exchange that should be avoided at all costs. And then next we have what is called MS-CHAP, or Microsoft Challenge Handshake Authentication Protocol. And this is a Microsoft enhanced version of CHAP that offers a collection of additional features not present with regular CHAP, including 2-way authentication. All right, next we have what is called EAP, and that stands for Extensible Authentication Protocol. And this specifies how authentication is performed by 802.1x. And then you have a variety of EAP types. You got what is called EAP Fast. You have what is called EAP MD5 and EAP TLS. Then we have what is called two-factor authentication, or 2FA. And this requires 2 types of authentication from a user seeking admission to a network. So for example, a user might have to know something such as a password and have something such as a specific fingerprint, which can be checked with the biometric authentication device. And we have what is called MFA, or multi-factor authentication. And this requires 2 or more types of successful authentication factors before being granted access to a network. And then we have what is called SSO, or single sign-on. And this allows a user to authenticate only once to gain access to multiple systems rather than needing to independently authenticate with each system. All right, next we have what is called local authentication, and this refers to a network device authenticating the user with a database of user account information stored on the device itself. This is often an important fallback method of authentication used when another external method fails. Then we have what is called LDAP, and that stands for Lightweight Directory Access Protocol, and this permits a set of standards for the storage and access of user account information. And many proprietary user stores, including Microsoft's Active Directory, they support LDAP for ease of access. LDAP, this uses port 389. And then we have what is called Captive Portal. And this is a web page that appears before a user is able to access a network resource. And this web page accepts the credentials of the user for authentication and presents them to the authentication server. And next, let's talk about authentication and authorization considerations. So there is a strong emphasis in IT on authentication and authorization for remote access as this area continues to explode in popularity and usage. So for example, multi-factor authentication is currently surging in popularity due to its availability to help secure networks and their data. And the following are some of the options for components of multi-factor authentication. So you have something you know, which could be a passcode or a PIN, something you have that could be a smart card or a badge, something you are that could be a fingerprint or a retinal scan, something you do such as a swipe pattern or solving some type of puzzle. Then somewhere you are, this could be geolocation or IP address. And technology has also progressed in the specific area of authorization. New technologies such as data loss prevention, they enable mechanisms for the protection of data throughout its lifetime and in use in all locations related to the enterprise. And this type of technology is especially heavy in mobile environments. In fact, the DLP functions are often a key aspect of MDM solutions or mobile device management solutions. And DLP systems, they are designed to detect and prevent unauthorized use and transmission of confidential information based on one of the three states of data. And those three states are in use, in motion, and at rest. In a well-designed DLP strategy, this allows control over sensitive data, reduces the cost of data breaches, and achieves greater insight into organizational data use. All right. And finally, we're going to talk about in-band versus out-of-band management. So one of the reasons for the explosion in remote access technologies and their adoption is the growing number of solutions emphasizing out-of-band management. Out-of-band management, this means that the network management traffic, it never mingles with the user data traffic. And your network device can have separate network interfaces for this purpose. And this separate network interface, this connects to a separate wide area network connection. And this separate connection is used only for the network management traffic. Now consider the advantages of out of band versus in-band management. With in-band management, security issues are possible because the network management traffic shares the same path. There is also a contention for bandwidth in this scenario. While out-of-band management may sound like the de facto answer and solution you should implement, you need to keep in mind that not all designs are optimal for all different topologies, technologies, and solutions. There are plenty of in-band management solutions that run securely and optimally. In fact, well-designed network management solutions tend to involve low bandwidth consumption as a part of their excellent design. In this video, you're going to learn about physical security as it relates to detection methods, prevention methods, and asset disposal. All right, so let's talk about detection methods. So when you think about detecting an attack against your network, you likely envision monitoring packets traveling into and out of your network devices. When you think about physical security, you can think in similar terms, and you will certainly need to monitor the flow of humans into and out of the area where the network devices exist. Today, there are many affordable options in the physical security detection realm of network security, and here are just some of the ones that you should be aware of. The first one is called motion detection. So using either mechanical or electronic methods, you can install motion detection devices that alert you when objects change position in the physical network location. Then we have cameras. So cameras allow you to view network areas by using video surveillance. In video footage, this is often recorded and stored locally or in the cloud. In modern camera systems, they have been combined with more advanced intelligence to detect weapons and other threats. Next, we have what is called asset tracking tags. So you can use various wireless technologies to track the physical locations of network objects and personnel by using tag technologies attached to the entities. So for example, radio frequency identification or RFID, this uses electromagnetic fields and allows one-way communication of information from a chip to an RFID reader. All right, next we have what is called tamper detection. So you can take steps to to ensure that network equipment is not tampered with. So for example, you might place key network cable runs in clearly viewable conduits and make appliances readily viewable through glass enclosures. And you can also use IP camera systems to send alerts when certain areas containing hardware are infiltrated, and tamper panels to detect when the cover of an all-in-one system or computer case is open or tampered with. All right, next let's talk about prevention methods. So there are many options you can use to assist in the area of physical attack prevention. And many security professionals today, they will beg you to accept the fact that the most important prevention method that you can take is complete and thorough employee training. One of the reasons for this common opinion is that many attacks cannot be carried out without user intervention. So for example, social engineering, this requires a user to give sensitive information such as username and password credentials to an attacker in order for the attacker to access the user's account. And as a result, a number of potential cybersecurity related attacks can be thwarted through effective user training. So for instance, users could be trained on using policies such as the following. So you can tell your employees to never give out their passwords to anyone, even if that person claims to be from the IT department. Do not open email attachments from unknown sources. Select strong passwords consisting of at least 8 to 12 characters and containing a mix of alphabetic upper and lowercase letters, numbers, and special characters. Tell them not to visit unauthorized websites, report suspicious activity, do not run or install any applications not provided directly by the company, and make sure they're changing their passwords at least on a monthly basis. Now, that list is only an example, and you should develop a collection of best practices for your users based on your network's specific circumstances. And users should also know whom to contact in the event of a suspected data breach or compromise of the computers and the systems the users are responsible for. And users, they should also know never to run penetration testing tools or other network discovery tools that may unintentionally lead to denial of service attacks or other harm to the network and its devices. And technical controls such as web and content filtering, port filtering, IP filtering, and access control lists that deny specific traffic, they can be used to assist in the enforcement of the policies agreed to by the users. And as part of user training and for the safety of human life, emergency procedures should also be communicated and verified with each user, including the following: the building layout, fire escape plan, safety and emergency exits, doors that automatically fail close or fail open based on their purpose to contain or to allow access, emergency alert systems, fire suppression systems, HVAC operations, and emergency shut-off procedures. Also, in a data center, procedures for safety related to electrostatic discharge or ESD, grounding, rack installation, lifting, tool safety, and the correct placement of devices, this should also be planned, communicated, and verified as well. If there are dangerous substances in or near the work area, a material safety data sheet should be created to identify procedures for handling and working with those substances. And while employee training is undeniably important, keep in mind that it transcends just physical security concerns. And here are some of the additional prevention methods that you can engage in for physical security. So the first one is a badge reader. So identification badges, they assist with physical security regarding employees. And badge readers, they are specialized hardware devices that read identification badges, and the data they collect is valuable for physical security. Whereas identification might be limited to a name and a photo, more sophisticated approaches can include electronic swipes and asset tags. All right, next we have what is called biometrics. So although at one time biometrics was reserved for the most sophisticated of environments, now using a thumbprint reader, facial recognition, or a retina scan, this is a reality with such common devices as your cell phones. And as a side note, it is common to refer to badge readers and biometrics as belonging to a category of devices that are called access control hardware. And the next one we have is called a smart card. So a smart card, this looks like a credit card but possesses circuitry that allows it to authenticate a user against network systems. And this aids security and is known as multi-factor authentication because the user must possess something such as the smart card, and they have to know something such as a PIN or a password. And this multi-factor authentication approach has worked well for ATMs in the banking system for decades. And next we have what is called a key fob. So a key fob, this is an electronic attachment to a key ring that might provide access to a network system or might simply lock or unlock a secure door. All right, next we have locks. So sometimes the simplest of security mechanisms are the most effective. And this is often the case with locks on network areas and equipment. Your enterprise might feature racks for network equipment that have locking cages over them, and they are often simply referred to as locking racks. And you can also use locking cabinets for physical security. Then we have what are called smart lockers. So it is always wonderful when one technology can assist another, and this is certainly the case with smart lockers. These lockers might look like typical lockers from the outside, but they include network connectivity, intelligence, and might even be configured for internet access. In smart lockers, they can accurately log user access and provide a level of security never seen before with basic lockers. Then we have what is called an access control vestibule or a man trap. So as you've learned in prior lessons, there are at least two forms of social engineering attacks. You got tailgating and piggybacking that require an attacker to follow an authorized user through a secured entrance or exit. An access control vestibule, which is a small entry area with two interlocking doors, this provides assurance that these forms of social engineering cannot take place. All right, next we're going to talk about asset disposal. So early in the development of networking, there were many infamous tales of sensitive data being retrieved from networking assets that were disposed of. Perhaps the engineering team thought that no one would be interested in fishing through the large dumpster behind the headquarters to find the hard drives nestled inside the decade-old PCs that were being disposed of. These same engineers might have felt very secure in this disposal method if they had taken the additional step of formatting the hard drives before disposal. Unfortunately, data can be removed from a disk that has been formatted, and of course, attackers, they would be happy to dig through the dumpster, which is known as dumpster diving, to retrieve these drives. In fact, attackers, they would even be thrilled to have such an easy way to obtain an organization's data. So today, there are many excellent techniques for proper and safe asset disposal, and the following are some examples. First one is called a factory reset. So one step in ensuring that a device does not contain information that can be used against an organization is a factory reset. And such a reset can often ensure that a networking device contains no data or settings that are specific to the organization. Next, we have what is called a wipe configuration. So in many organizations, it is a standard procedure to wipe the configuration from a networking device when disposal is needed. In fact, in many bring your own device or BYOD environments, mobile devices are programmed so that it is possible to automatically wipe their configurations if they are reported stolen. And then we have sanitizing devices for disposal. So in high security environments, there is often a process in place for completely sanitizing a device of all existing data before disposal of the device. And this might involve degaussing, which involves passing powerful magnets over the surface of storage to ensure that the data can never be recovered. In other environments, even degaussing, this might not even be considered strong enough, and physical destruction or shredding of the component that might be required to erase the data permanently. And then finally, some legislation, including HIPAA, which applies to medical records, this requires that paper records be properly disposed of due to privacy concerns and regulations. In fact, many government agencies that require a signed certificate of disposal after a data disposal. In this video, you're going to learn about the network troubleshooting methodology. As you perform your day-to-day tasks of administering a network, a significant percentage of your time will be dedicated to resolving network issues. Now, whether the issues you are troubleshooting were reported by an end user or were issues that you discovered, you need an effective plan to respond to them. Specifically, you need a systematic approach to clearly articulate an issue, gather information about the issue, hypothesize the underlying cause of the issue, validate your hypothesis, create an action plan, implement that action plan, observe the results, and document your resolution. Without a plan, your efforts might be inefficient as you try one thing after another, possibly causing other issues in the process. So although your troubleshooting efforts can most definitely benefit from a structured approach, realize that troubleshooting is part art and part science. Specifically, your intuition and instincts, they play a huge role in isolating an issue. Of course, those skills are developed over time and come with experience and exposure to more and more scenarios. So to help you start developing or continue honing your troubleshooting skills, this video presents a troubleshooting methodology that can act as a guide for addressing almost any network issue. So let's talk about the troubleshooting basics. So troubleshooting network issues is implicit in the responsibilities of a network administrator. Such issues could arise as a result of human error, such as a misconfiguration, equipment failure, software bugs, or traffic problems. For example, high utilization or a network being under attack by malicious traffic. Many network issues can be successfully resolved using a variety of approaches. And this section begins by introducing you to troubleshooting fundamentals and then presents a structured troubleshooting methodology that you should know for the Network Plus exam. So let's talk about the troubleshooting fundamentals. So the process of troubleshooting at its essence, this is the process of responding to a problem report, oftentimes called a trouble ticket, diagnosing the underlying cause of the problem, and resolving the problem. Although you normally think of the troubleshooting process beginning when a user reports an issue, through effective network monitoring, you might detect a situation that could become a troubleshooting issue and resolve that situation before it impacts users. Now, after an issue is reported, the first step towards resolution is clearly defining the issue. Now, after an issue is reported, the first step towards resolution is clearly defining the issue. After you have a clearly defined troubleshooting target, you can begin gathering information related to that issue. And based on the information collected, you might be able to better define the issue. Then you can hypothesize the likely cause of the issue, and evaluation of these likely causes leads to the identification of the suspected underlying root cause of the issue. Now, after a suspected underlying cause is identified, you can define approaches to resolve an issue and select what you consider to be the best approach. Sometimes the best approach to resolving an issue cannot be implemented immediately. So, for example, a piece of equipment might need to be replaced. However, implementing such an approach during working hours might disrupt a business's workflow. In such situations, a troubleshooter might use a temporary fix until a permanent fix can be put in place. And a simplified model of the troubleshooting steps are as follows. You have the problem report, the problem diagnosis, and the problem resolution. Now, of these three steps, the majority of a troubleshooter's efforts are spent in the problem diagnosis step. And here are the key components of this diagnosis step. First, you want to gather information. Because a typical problem report lacks sufficient information to give a troubleshooter insight into a problem's underlying cause, the troubleshooter should collect additional information, perhaps using network maintenance tools or interviewing the impacted users. Do you want to duplicate the problem if possible? So testing to see if you can duplicate the problem is often a key step in problem diagnosis. Next, you want to question the users. Although it can be difficult to gather information from your end users, doing so is often critical in correctly pinpointing the exact problem. And oftentimes, finding out user actions prior to the problem is critical. All right, next you want to identify symptoms. So figure out what are the symptoms that the problem created. Then you want to determine if anything has changed. Perhaps your end users will provide valuable clues if they accurately indicate what changes they might have made to the systems. And then you want to approach multiple problems individually. Unfortunately, you might discover that there are multiple issues, so be sure to approach each one individually. All right, next let's talk about the structured troubleshooting methodology. So troubleshooting skills varies from administrator to administrator. Therefore, although most troubleshooting approaches include the collection and analysis of information, elimination of potential causes, hypothesis of likely causes, and testing of the suspected cause, different troubleshooters might spend different amounts of time performing these tasks. If a troubleshooter does not follow a structured approach, the temptation is to move between the previously listed troubleshooting tasks in a fairly random way, often based on instinct. troubleshooting. Although such an approach might well lead to problem resolution, it can become confusing to remember what you have tried and what you have not tried. Also, if another administrator comes to assist you, communicating to that other administrator the steps that you have already gone through could be challenging. Therefore, following a structured troubleshooting approach not only helps prevent you from trying the same thing more than once and inadvertently skipping a task, but also aids in communicating to someone else the possibilities you have already eliminated. Now, you might encounter a variety of structured troubleshooting methodologies in networking literature. However, for the Network Plus exam, this 7-step methodology is the one that you need to memorize. So step 1, you need to identify the problem. So effective troubleshooting, this begins with a clear problem definition. And this definition might include specific symptoms. So here's an example. User A's computer is unable to communicate with server 1 as verified by a ping test. However, user A can communicate with all of the other servers. Also, no other user seems to have an issue connecting to server 1. Now, this problem definition might come from questioning the impacted users and doing your own testing, such as seeing if you can ping from user A's computer to server 1. If possible, determine whether anything has changed in the network or in the computer configuration. Also, find out whether this is a new installation that has failed to work in the past. Step 2, you need to establish a theory of probable cause. This is the point in the troubleshooting process where your experience and intuition can be extremely helpful, because it is when you brainstorm a list of possible causes. As you brainstorm, be sure to question the obvious. Also, think in terms of top to bottom troubleshooting, which is moving from top to bottom within the OSI model, or the bottom to top troubleshooting. Alternatively, you could use what is called a divide and conquer troubleshooting approach. So when examining all of your collected data, you essentially want to question everything. All right, next is step 3. So you want to test the theory to determine the cause. So before taking action on what you consider to be the most likely cause of a problem, do a sanity check on your theory. Would your hypothesized cause lead to the observed symptoms? If you notice a flaw in your logic, you need to formulate an alternate hypothesis. The information of an alternate hypothesis might involve escalating the problem to someone more familiar with the device in question. Next is step 4. So you want to establish a plan of action to resolve the problem and identify potential effects. So once you have confirmed that your theory makes sense technically, you need to develop an action plan. If time permits, you should document your action plan. The documentation of your action plan can be used as a backup plan if your hypothesis is incorrect. Step 5, you want to implement the solution or escalate as necessary. So based on your documented plan of action, you should schedule an appropriate time to implement the action plan. The selection of an appropriate time is a balance between the severity of a problem and the impact your action plan will have on other users. Sometimes when attempting to implement an action plan, you realize that you do not have sufficient administrative privileges to perform a task in your action plan. In such cases, you should escalate the issue to someone who has appropriate admin rights. Step 6, you want to verify full system functionality and, if applicable, implement preventative measures. So after implementing an action plan, you need to verify that the symptoms listed in your original plan definition are gone. You also need to attempt to determine whether your action plan has caused any other issues on the network. A mistake many troubleshooters make at this point is believing that the issue has been resolved because the specific symptoms they were looking for are now gone. However, the user who originally reported the issue might still be having a problem. Therefore, troubleshooters should live by the mantra which states a problem isn't fixed until the user believes it's fixed, meaning you should get confirmation from the person reporting an issue that from their perspective, the reported issue has indeed been resolved. And then step 7, you want to document your findings, actions, outcomes, and the lessons learned. So you have what is called a post-mortem report. And this is a document that describes the reported issue, its underlying causes, and what was done to resolve the issue. And this report might be useful when troubleshooting similar issues in the future. Now, keep in mind when working your way through the previous steps that you might encounter an issue that you do not have sufficient information to solve. When that happens, you might need to further research the issue yourself. However, if time is of the essence, you might need to immediately escalate the issue to someone else within your organization, to an equipment vendor, or to an outside consultant.
In this video, you're going to learn about common cabling problems as it relates to specifications and limitations, cable considerations and applications, common issues, and common tools. So a lot can go wrong when it comes to the physical media or the cables that make up a network. But the great news is that there are more tools and techniques than ever before to proactively head off physical layer issues. And this video is going to ensure that you understand the common problems to watch out for, as well as the tools that the best in the industry commonly use to solve these many potential issues. So let's go ahead and talk about the specifications and limitations. So there are some very basic requirements when it comes to thinking about the physical layer media of your infrastructure. You need to focus on at least 3 aspects of the specifications and limitations for the media. And the first one is throughput. So this is a measure of the total amount of data that media can send over a given time period. Next is speed. This is a measure of the data send rate. So for example, Cat6 media supports a maximum speed of 10 gigabits per second. And then the third aspect is distance. So for both wired and wireless media, as you get farther away from the sender over the media, you start to suffer the effects of what is called attenuation. And that is a weakening of the signal over distance. So you need to pay attention to the maximum distances that are supported by various physical layer media options. So for example, Cat6 has become the minimum standard for new network cable installations. And while the speed of Cat6, which is 10 gigabits per second, is exciting, remember that Cat6 only supports distances up to 55 meters. All right, next let's talk about cable considerations and applications. So the following are some considerations you should keep in mind when considering physical cable. So the first one is shielded twisted pair versus unshielded twisted pair. So physical cable often needs to be twisted or shielded or both in order to not suffer from EMI or electromagnetic interference. So for example, in shielded twisted pair cables, a metallic shielding covers the twisted pair inside the cable. This shielding helps protect against EMI, but it does so at a cost. And these types of cables can be much more expensive than unshielded cables due to the shielding. And with unshielded twisted pair, the twists in the cables are tighter to reduce EMI. And this eliminates the need for expensive shielding. All right, next let's talk about plenum and riser rated. So if a twisted pair cable is to be installed under raised flooring or in an open air return, fire codes must be considered. So for example, imagine that a fire breaks out in a building. If the outer insulation of a twisted pair cable catches fire or starts to melt, it could release toxic fumes. If those toxic fumes were released in a location such as an open air return, those fumes would be spread throughout a building, posing a huge health risk. So to mitigate the concern of pumping poisonous gas throughout a building's HVAC system, plenum rated cabling can be used. The outer insulation of a plenum twisted pair cable is fire retardant. In addition, some plenum cables use a fluorinated ethanol polymer or FEP or a low smoke polyvinyl chloride or PVC to minimize dangerous fumes. Now, as a side note, you always want to check your local fire codes before installing any network cabling. And then we have what is called a riser. So a riser, this is a vertical area that passes from one floor to another floor inside a building. Riser rated cables are cables that run through risers. They should be fireproof to prevent flames from traveling up the cable. However, the fire rating requirements for riser areas, they are less strict than the requirements for plenum areas. Also, you should consider the following physical cable applications. So the first one is called a rollover cable or a console cable. So the flattened cable that comes with a network device from the factory, this is called a rollover cable. Because you typically use these cables to make console connections to devices, these cables are often referred to as simply console cables. All right, next we have what is called a crossover cable. So the concern about whether you need a crossover cable versus a straight through Ethernet cable is quickly fading from our concerns due to what is called auto MDIX technology, which permits a port to adjust to the type of cable that it is connected to. So before this technology came along, administrators had to be careful to use crossover cables to connect like devices. So for example, connecting 2 switches together to form a trunk, that required using a crossover cable. All right, next we have what is called power over Ethernet. So power over Ethernet, this is a technology that makes it simple to connect devices such as cameras and access points to the network and have these devices get power from the single network connection. This prevents you from having to find an
an outlet for plugging in a number of smart devices. And for PoE to work, you need to use at least a Cat5e or better media. All right, next, let's talk about some common issues. So to be an effective troubleshooter, it helps to understand the types of things that commonly go wrong in networks so you can become more proficient in recognizing and solving these issues. Here are just some of the things you need to be on the lookout for with cabling in a network. So the first one is called attenuation. So as mentioned earlier, distance is the enemy of cabling. The longer the signal travels through the media, the more it weakens. And it is very important to know the maximum distances for the various media in your enterprise network. Attenuation, this is measured in decibels, which we'll talk about shortly. The next one is called interference. While they are not as sensitive to interference as wireless media, cables can suffer from EMI and other types of interference. And just as with wireless networks, you need to do proper testing for interference issues before deploying physical media. In addition, to reduce interference, you should follow the recommendations of the cable manufacturer. Then we have what is called decibel loss. So if a physical cable has lots of different splits or splices in it, there might be a great deal of decibel loss. This loss is also more prone to happen as the signal needs to go farther and farther in the media. All right, next we have bad cables, incorrect pinouts, or bent pins. So faulty cables with electrical characteristics preventing successful transmission or faulty connectors which do not properly make connections. They can prevent successful data transmission at layer 1. A bad cable could simply be an incorrect category of cable being used for a specific purpose. So for example, using a Cat5 cable instead of a Cat6 or higher cable to connect two 1000 base TX devices, this would result in data corruption. Bent pins in a connector or incorrect pinouts, they could also cause data to be corrupted as well. Then we have bad ports. So a physical port on a network device might be bad, and you can often easily confirm whether a port is bad by looking at the network connection LED and status indicators. Then we have opens and shorts. So an open, this is a broken strand of copper that prevents the flowing through a current. A short occurs when two copper connectors touch each other, resulting in current flowing through the short rather than through the attached electrical circuit because the short has a lower resistance. All right, next we have LED status indicators. So many network devices are very specialized and require special types of indicators. Oftentimes, indicators are implemented in the form of special LED status indicators. And thanks to such indicators, with a simple glance, a network administrator can ascertain whether there is a problem with the network device. So for example, a solid green LED for a network card normally indicates that the card is connected for receiving a signal. If there are no lights present, or if the lights are orange or red, the network may not be connected properly or may not be receiving a signal from the network. Next, we have incorrect transceivers. So a transceiver, this is a device that is able to both send and receive analog or digital signals. You must be sure to select transceivers carefully. The transceiver you select for a network device must match the cable type used and the wavelengths that are used on the network. Then we have speed and duplex issues. So speed and duplex mismatches can be tricky to troubleshoot in a network, especially considering that connectivity is often maintained, although at unacceptable levels. All right, the next common issue we have is transmit and receive or reversed. So some Ethernet switches, they support media dependent interface crossover, or MDIX, which allows a switch port to properly configure its lead as either transmit or a receive lead. And you can interconnect such switches by using a straight through cable as opposed to a crossover cable. However, if a network device does not support MDIX, it needs a crossover cable in order for its transmit leads to connect to the receive leads on a connected device and vice versa. Therefore, you must take care when selecting cable types for interconnecting network components. And then we have dirty optical cables. So an often overlooked aspect of fiber optic media care and maintenance is keeping the fiber optic connector ends faces clean. A dirty fiber connection can either slow down or completely inhibit network traffic. And one method to clean optical cables is to use a combination of wet and dry cleaning approaches. So for example, you might use a small amount of solvent on a wiping material and immediately dry the surface. All right, so let's talk about some common tools. While a number of of issues related to physical layer cables can cause problems for you. The great news is that there are many tools that you can use to attack these problems and even prevent them from occurring. So here are just some of the tools. The first one is called a cable crimper. So a crimper, this could be used to attach a connector such as an RJ45 connector to the end of a UTP cable. To accompany a crimper, you might want to purchase a spool of cables such as category 6 or higher UTP cable and a box of RJ45 connectors. You will then be equipped to make your own Ethernet patch cables, which might be less expensive than buying pre-terminated UTP cables. And making your own is also convenient. You need a patch cable of non-standard length, or when you need a non-standard pinout on the RJ45 connector, such as when you need a T1 crossover cable. And many crimpers, they have a built-in wire stripper and a wire snip that function as well. All right, next we have what is called a punch down tool. So when terminating wires on a punch down block, such as a 110 block, you insert an insulated wire between two contact blades. These blades cut through the insulation and make electrical contact with the inner wire. As a result, you do not have to strip off the insulation. However, if you attempt to insert the wire between the two contact blades using a screwdriver, for example, the blades might be damaged to the point where they will not make a good connection. Therefore, you should also use a punch down tool, which is designed to properly insert an insulated wire between the two contact blades without damaging the blades. All right, next we have what is called a tone generator. So if you are working on a punch down block and attempting to identify which pairs of wires connect back to an end user's location, which is usually someone's office, you can use a toner probe. A toner probe, this allows you to place a tone generator at one end of a connection, such as somebody's office, and use a probe on a punch down block to audibly detect which pair of wires the tone generator is connected. Toner probe, therefore, comes in two pieces. You have the tone generator, and then you have the probe. Another common name for a toner probe is called a fox and hound, where the tone generator is the fox, and the probe, which searches for the tone, this is called the hound. And some network devices have built-in troubleshooting tools, such as a voice-enabled Cisco router, where they can produce test tones. All right, next tool we have is called a loopback plug. So when troubleshooting a network device, you might want to confirm that a network interface is functional, such as ensuring that it can transmit and receive traffic. And one way to perform such a test is to attach a loopback plug to a network interface or run a diagnostic software designed to use the loopback plug. A loopback plug takes the transmit pins on the Ethernet connector and connects them to the receive pins such that everything is transmitted is received back on the interface. Similarly, a fiber optic loopback plug, this interconnects a fiber connector's transmit fiber with a connector's receive fiber, and the diagnostic software can then transmit traffic out of the network interface and confirm its successful reception on the same interface. All right, the next tool we have is called an optical time domain reflectometer and a time domain reflectometer. So suppose that you have been troubleshooting a network cable, either copper or fiber optic, and you determine that there is a break-in or physical damage to the cable. Identifying exactly where a break or damage exists in a long length of cable, this can be problematic. Fortunately, you can use a time domain reflector for copper cabling or an optical time domain reflector for fiber optic cabling to locate a cable fault. And both light and electricity, they travel at speeds approaching 186,000 miles per second, although the speeds are a bit slower and vary depending on the media. A TDR, this can send an electrical signal down a copper cable, or an OTDR can send light down a fiber optic cable. And when the electrical signal or light encounters a cable fault, a portion of the electrical signal or light reflects back to the source. And based on the speed of electricity or light in the medium, the amount of time required for the reflected electricity signal or light to be returned to the source, a TDR or an OTDR can mathematically determine where the cable fault lies. All right, next we have what is called a multimeter. So when working with copper cabling as opposed to fiber optic cabling, you can use a multimeter to check a variety of electrical characteristics in a cable, including resistance, current, and voltage. So for example, you could use the ohm meter function of a multimeter or the resistance feature to check the continuity of an Ethernet cable. Another common use of a multimeter is for measuring voltage. So for example, you could check the leads of an Ethernet cable to see whether DC voltage is being applied to a device requiring power over Ethernet. All All right, the next tool we have is called a cable tester. So a cable tester can test the conductors in an Ethernet cable. By connecting the two parts of a cable tester to the ends of a cable under test, you can check the wires in the cable for continuity, which is checking to make sure there are no opens or breaks in a conductor. In addition, you can verify an RJ45 connector's pinouts by ensuring that the wires are connected to the appropriate pins on an RJ45 connector. All right, next tool we have is called a wire map tester. So wire map testing, this enables you to determine whether a wire has continuity and whether each conductor of a 4-pair cable is correctly connected to the corresponding pin at the far end. And wire map testing tests for opens, shorts, reverse pairs, cross pairs, and split pairs. Next, we have what is called a traffic access point or a TAP. So a traffic access point or a test access point, this is a hardware device inserted at a specific point in a network where data can be accessed for testing or troubleshooting purposes. And network taps are mainly used to monitor the network traffic between 2 points in the network infrastructure. Right, next tool we have is called fusion splicing. So fusion splicing, this is a way to join 2 fibers by using heat. Prepared fiber ends are placed in the splicer and automatically align and then fuse together. Fusion splicing ensures greater reliability with less light being scattered or reflected back by the splice. If you follow the instructions for a fusion splicer, you should end up with an optical cable that is as strong as the original cable. Next, we have what is called a spectrum analyzer. So a spectrum analyzer, this measures the magnitude of an input signal versus frequency with the full frequency range of the instrument. And the primary use is to measure the power of the spectrum of known and unknown signals. Next, we have snips and cutters. So as a network administrator, you often need to precisely cut or snip cables and cabling accessories. And it is important that you have a pair of well-maintained snips or cutters in your supply bag at all times. Next, we have a cable stripper. So cable strippers, they allow you to remove the plastic shielding from cables, and they are often built into cable crimpers. And then finally, we have what is called a fiber light meter. So a fiber light meter, this is a device used to measure the power in an optical signal, and it is a device for testing average power in fiber optic systems. In this video, you're going to learn about network software tools, command line tools, and basic network platform commands. All right, so let's talk about software tools. So a number of software tools are designed to help with managing networks. And this video is going to provide an excellent starting point, introducing you to some of the commonly used tools, which many of these are freely available. So let's talk about the Wi-Fi analyzer. So a Wi-Fi analyzer, this is software that runs on a general purpose computer or on a specialized device that can perform wireless analysis of Wi-Fi signals. And this type of tool will be used as part of a wireless site survey after Wi-Fi has been implemented to create a heat map of the wireless airspace. All right, next we have what is called a protocol analyzer or a packet capture. So if you understand the characteristics of the protocols running on your network, such as the fields on the protocol's header, a protocol analyzer, which is also known as a network sniffer or simply a packet capture tool, this could be a tremendous troubleshooting asset. A protocol analyzer could be a standalone device or software running on a laptop or other mobile computer. And you can use a protocol analyzer to capture traffic flowing through a network switch using the port mirroring feature of the switch. By examining the captured packets, you can discern the details of communication flows, which are called sessions, as they are being set up, maintained, and tore down. In the examination of these captured packets, which are referred to as traffic analysis, this provides an administrator with valuable insight about the nature of traffic flowing through a network. Protocol analyzers, they come with a wide range of features and at a variety of price points. Wireshark, this is a free software program that can make your laptop act like a protocol analyzer. And protocol analyzers, they can assist in identifying details such as who are the top talkers, top destinations, top protocols in use, and quantity of traffic on the network. All right, next we have what is called a bandwidth speed tester. So many bandwidth speed testers are available to assist you in verifying throughput from a local computer to an internet site. And one example is speedtest.net. So using sites such as this can assist you in determining whether an overall connection to the internet is slow or whether just a specific site or server is too slow to respond. All right, next we have what is called a port scanner. And this is a useful software tool that probes a network device to determine which ports are open on the device. A port scanner can send port scans to a single device, or it can perform a port sweep where it checks for open ports on a number of network devices at one time. And many port scanners today are considered IP scanners. And IP scanners are superb at running port sweeps against entire subnets of IP address network hosts or systems. In addition to being helpful to network administrators, port scanners can be used to carry out harm. And computer criminals, they might use port scanners in launching attacks on open ports. All right, next we have what is called iPerf, and this is a software tool for networking that obtains active measurements of the maximum bandwidth available on IP networks. And this software tool supports tuning of various parameters related to timing, buffers, and protocols. And the protocols that you can tune, they include TCP, UDP, Stream Control Transmission Protocol, and IP version 4 and IP version 6. All right, next we have what is called a NetFlow analyzer. So NetFlow, which is a software component included in many network devices today, this collects statistics about the traffic flows through a device. However, the data that NetFlow collects is not useful unless you can analyze it and see it in a way that makes sense. And you can use NetFlow analyzers, which are also called collectors, to examine NetFlow collections and get valuable and insightful representations of the data. All right, next we have what is called a TFTP server. So for network maintenance, it is helpful to have a TFTP server or a trivial file transfer protocol server or two on your network. These low overhead producing servers allow you to store backups of software images that power network devices, as well as backup and baseline configurations. And many network devices today, they can install their software or configurations from a TFTP server directly over the network. Next, we have what is called a terminal emulator. So a software tool you are likely to find yourself using all the time would be a terminal emulator. This program allows you to access a command line interface to monitor and configure devices, which is often a very efficient way to carry out these networking tasks. All right, next software tool we have is called an IP scanner. So many tools can provide IP address information for systems in the network, but IP scanners can do this precise function better than any alternative. IP scanners can acquire information more accurately and faster than the alternatives. And many IP scanners can also provide additional information from nodes such as operating systems, software application, and physical resource usage information. All right, next let's talk about some command line tools. So you will often find yourself firing open a terminal emulator to access a command line interface when you are maintaining or troubleshooting a network. In this section right here, this is going to ensure you are very familiar with many of the command line tools that are in use today. So the first command line tool that you're going to be familiar with is called ping, and this sends IP packets to check network connectivity. Then you have ipconfig, and this displays TCP/IP network information on a computer. In Mac and Linux, the command will be referred to as ifconfig. So it's ipconfig in Windows-based machines and ifconfig in Mac and Linux-based machines. And then we have what is called IP tables, and this is a Linux command to put rules in place for packet filtering for the Linux kernel firewall. Next command you need to be familiar with is called NSLOOKUP, and this gathers the network DNS information, or the domain name, system, or server information. Next we have what is called traceroute. And this is similar to ping, but returns path information to an IP address destination. In Mac or Linux, the command is called traceroute. In Windows-based systems, it's called traceroute as well, but it's spelled out TRACERT. And then the full word is spelled out when you're using a Mac and Linux system. All right, next command is the Address Resolution Protocol, or ARP, and this displays and modifies entries in the Address Resolution Protocol cache. In the ARP cache, this contains one or more tables that are used to store IP addresses and their resolved Ethernet or token ring physical addresses. All right, next command we have is called netstat, and this displays a list of active TCP connections on a local network. All right, next command we have is called hostname. So on a Windows system, this command simply displays the computer host name. On a Linux system, this command is used to change the computer name or domain name of a system. All right, next command we have is called route. So this allows you to make manual entries into network routing tables. It distinguishes between routes to hosts and routes to networks by interpreting the network address of the destination variable, which can be specified either by symbolic name or numeric address. All right, the next command we have is called telnet. So this is a method of remote access for remote devices, and it does not provide any security mechanisms. And this is why we prefer to use Secure Shell or SSH, because it does provide security mechanisms like encryption. Then we have what is called a TCP dump. So this is a data network packet analyzer program that runs under a command line interface. It displays TCP IP information and other packets being transmitted and received over networks to which a computer is attached. And then we have what is called Nmap. And this discovers hosts, services, and operating system detection on networks by sending packets and analyzing their responses. And finally, we're going to talk about basic network platform commands. So although the Network Plus exam is a vendor neutral certification, you need to be aware of several Cisco network device commands that are incredibly popular and are used on equipment from a number of different vendors. And the first one is called the show interface command. So the show interface command, this allows you to examine the statistics and the status of the interfaces on a network system. Then we have the show configuration or the show config. So the show config command and some variations of it, this is used to examine the configurations of a network device. So for example, on a Cisco router, configuration of the device, which is stored in the RAM of the device, to view the saved configuration that is loaded when the system is rebooted, you can use the command show startup configuration. And then we have the show route command. So the show route command or some variation of it, this is used to view the routing table configuration of the network device. And on a Cisco router, you can use the show IP route command to view the IP version 4 routing table. In this video, you're going to learn about common wireless connectivity issues, such as specifications and limitations, considerations, and common issues. All right, so let's talk about some specifications and limitations. So as you've learned in previous lessons, there are big differences in the 802.11 standards when it comes to the specifications and limitations of each standard. And this video is going to review just some of the key values and concepts that you need to be concerned about when troubleshooting wireless local area network deployments. So the first one we're going to talk about is speed. So typically, when the speed of the wireless technology is described, it is actually the theoretical maximum speed that is actually being described. So for example, the speed of 802.11n is typically said to be 300 megabits per second. But is that true? In short, the answer is no. A more accurate way to describe how a wireless LAN is actually performing is to look at the throughput. And speaking of throughput, this term is typically used to indicate the amount of data you are able to send on the network media. In this case, of course, the media is the radio frequencies that power wireless. Although the stated speed of 802.11n is 300 megabits per second, when you actually test the throughput, you might discover that the network is averaging 255 megabits per second. This actual throughput measurement provides a much more accurate picture of the capabilities of the network segment. And then we have distance. So attenuation, this is a fact of life with network media. As the signal gets further and further away from the source, the signal weakens and the speed and throughput will suffer. And notice that in a wired infrastructure, the effective distance can be much easier to predict. When you're troubleshooting wireless environments, it's important to keep in mind that all distances are not created equal. So for example, there might be only half the distance between your access point and your client as between your access point and another client in your network. If there is a large source of wireless LAN interference in the shorter path, this might be the much more problematic client system. Now, as a side note, There are actually many places in the wireless infrastructure where attenuation can be an issue. A careful analysis of the Wi-Fi design might find attenuation signal loss resulting from the antenna cable that is in use. And this might add to the existing and known problems of RF attenuation and signal loss. All right, next we have what is called the Receive Signal Strength Indication, or the RSSI signal strength. So when you are performing site surveys or just performing typical wireless troubleshooting, it is important to use metric information that you can trust and interpret accurately. The RSSI, this might be presented in different formats depending on the software you are working with, but comparing your internal testing results can make this measurement extremely valuable. And no matter how exactly you see the value, the RSSI, this is a measure of the power level being received by the local client you are testing with. In most software packages, the greater the RSSI value, the stronger the signal, and the better the chances for higher throughput. Then we have what is called the effective isotropic radiated power, or the EIRP, in the power settings. So another very valuable metric used with wireless today is EIRP. This measures the maximum amount of power that could be radiated from an antenna. Of course, this value must incorporate the antenna gain and the transmitter power of the RF system. And you most often see EIRP being presented as decibels over isotropic, or dBi. All right, so let's talk about some considerations. So troubleshooting wireless networks, this might seem overwhelming compared with troubleshooting wired infrastructures. And as described in the following information, there are certainly many unique considerations when troubleshooting Wi-Fi networks. However, through study and practice, you will soon be as efficient at troubleshooting Wi-Fi as you are at troubleshooting a network printer. So let's talk about the first consideration, which are antennas. So as discussed in previous videos, antenna choices are often critical for the proper functioning of a wireless LAN. And you need to ensure that the most critical design goals are met, such as double checking distances from the client and the access points, testing the coverage area of the antenna type and the form factor selected, testing both the indoor and outdoor coverages, and testing for interference with other access points. Now, recall from previous videos that there are multiple types of wireless antennas, and they fall into two broad categories based on coverage area. First category is called omnidirectional. That means the signal is spread in nearly a 360-degree radius around the antenna. You have unidirectional, and the signal is projected in a single, relatively precise direction. Now, as a side note, the direction in which an antenna emits signal, this is called polarization. The next considerations are frequencies and channels. So keep in mind these key facts regarding frequencies and channels when troubleshooting wireless networks. First one is wireless LANs. They use frequencies in the 2.4 to 2.5 gigahertz range, or in the 5.725 through 5.875 gigahertz range. Within each band are specific frequencies or channels at which wireless devices will operate, and to avoid interference, nearby wireless access points should use frequencies that do not overlap with one another. In the 2.4 gigahertz band, channel frequencies, they are separated by 5 megahertz, with the exception of channel 14, which has a 12 megahertz of separation from channel 13. And a single channel's transmission, it can spread over a frequency range of 22 megahertz. As a result, 5 consecutive channels, they tend to overlap one another. In the US, the non-overlapping channels are channels 1, 6, and 11. And also more and more 802.11ax or Wi-Fi 6 devices are becoming available. And this technology extends Wi-Fi into the 6 gigahertz band. All right, so let's talk about some other considerations. So an exhaustive list of wireless LAN considerations is beyond the scope of this course, but there are a few you might encounter in a network and that might be asked about on the Network Plus exam. The first one is called the access point association time. So in larger enterprise environments, wireless LAN controllers, they often provide the control plane intelligence that access points lack. And key metrics to consider in this environment are how long it takes for a typical client client to properly associate with an access point and is the length of time it takes an access point to associate with a wireless LAN controller. And these are both points of latency as well as potential failures. The next one is a site survey. So there is no substitute for a thorough, well-planned, well-documented site survey when it comes to planning and deploying wireless successfully. When implementing a production wireless LAN, planning is a much better option than simply trying and failing. A proper site survey, this can set you up for great success. It will help you determine where to place antennas and what types of antennas you need, and it will help you learn about potential sources of interference and other enemies of the wireless LAN. Fortunately, there are many options to choose from when it comes to site survey blueprints and software packages. Now, in a site survey, you use Wi-Fi and other Wi-Fi analyzers to understand and map out the wireless infrastructure. One output is called a wireless heat map, and this provides a visual method for understanding coverage and signal strength. All right, next let's talk about some common issues. So network engineers are consistently thinking about what can go wrong. Fortunately, this type of doomsday thinking can be very valuable in networking. And the following are some of the common issues you need to be aware of when it comes to wireless networking. So the first one is called interference. So wireless communication can be interrupted due to radio frequency interference, or RFI. And common RFI sources that impact wireless networks include 2.4 gigahertz cordless phones, microwaves, baby monitors, and gaming consoles. The next issue is called signal strength. So the RSSI value, this measures the power of a wireless signal. And RSSI values, they vary based on distance from a wireless antenna and physical objects interfering with line-of-sight communications with a wireless antenna. So for example, drywall, metal filing cabinets, elevator shafts, etc. And some wireless networks, they automatically drop their wireless transmission rate when an RSSI value drops below a certain value. The next issue is the misconfiguration of wireless parameters. So for communication to occur, a variety of wireless parameters must match between a wireless client and a wireless access point. So for example, the client needs to be using a wireless standard supported by the wireless access point, such as 802.11, ABG, NAC-AX, or whichever one you're using. And wireless channels, they also must match. However, a wireless client usually automatically sets its channel based on the wireless access point's channel. Also, encryption standards, they have to match. So for example, a wireless client using WPA would not successfully communicate with a wireless access point that is using WPA2. In addition, the SSID, or the service set identifier of a wireless access point, that must be selected by the wireless client. In many cases, a wireless access point broadcasts its SSID, and a wireless client can select that SSID from a list of visible SSIDs. In other cases, a wireless access point will not broadcast its SSID. In a wireless client, it must have a matching SSID that is manually configured. All right, the next issue we have is called latency. So wireless networks, they may experience more delay than their wired counterparts. And one reason for this increased delay is the use of carrier sense multiple access with collision avoidance, or CSMACA, that are used in wireless LANs. And CSMACA, this introduces a random delay before data is transmitted in an attempt to avoid collisions. Another reason for the increased delay is the fact that all wireless devices associated with a single wireless access point are in the same collision domain, introducing the possibility of collisions or retransmissions, which could increase delays. All right, the next issue is called multiple paths of propagation. So an electromagnetic waveform cannot pass through a perfect conductor. Admittedly, perfect conductors do not exist in most office environments. However, very good conductors, such as metal filing cabinets, they are commonplace in offices. And as a result, if the waveform of a wireless transmission encounters one of these conductive objects, most of the signal bounces off the object, creating multiple paths or modes of propagation. And these multiple modes of propagation, they can cause data such as bits to arrive at uneven intervals, possibly corrupting data. And this problem is similar to multi-mode distortion, which occurs in multi-mode fiber optic cabling. All right, next issue we have is called incorrect access point placement. So wireless access points, they should be strategically located in a building to provide sufficient coverage to all desired coverage areas. However, the coverage areas of wireless access points using overlap overlapping channels, they should not overlap. To maintain coverage between coverage areas, you should have overlapping coverage areas among wireless access points that are using non-overlapping channels, such as channels 1, 6, and 11 for wireless networks that are using the 2.4 gigahertz frequency band. And a common design recommendation is that overlapping coverage areas that are using non-overlapping channels, they should have an overlap of approximately 10 to 15%. Now keep in mind that the 5 gigahertz band and the 6 gigahertz band of Wi-Fi 6E, it offers more non-overlapping channels. And the next issue we have is captive portal issues. So many wireless network environments, they make use of a captive portal. And a captive portal, this is a web page that often presents an acceptable use policy that the user must accept in order to access the internet via a wireless connection. And the web page also typically collects profile information from end users. It might even market products to the wireless user as well. And the captive portal, this is a key element of the wireless association process, and so it must perform as expected. And most wireless networks, they fail closed, which means if the captive portal or any other step of the process is not functioning, the wireless network remains inaccessible to new clients. The next issue we have is called client disassociation issues. So clients appreciate a wireless network much more if they are able to remain connected. While you might be able to immediately rule out many categories of issues that could cause disassociation, there are plenty that require additional inspection and analysis. And remember that there is an entire category of attacks that target client disassociation, and these attacks are often initial steps in much larger attacks. And an attacker, it may disassociate a client and then associate it to a rogue device. All right. And finally, we're going to talk about wireless network troubleshooting. So as a practice troubleshooting scenario for wireless networks, consider the image on your screen right here. And based on this topology, can you spot the design issue that is taking place with this wireless network? Well, if you can't, here's the answer. So the wireless network presented in this picture, it includes 2 wireless access points. Although these wireless access points have a matching wireless standard, a matching encryption type, and a matching SSID, the channels being used are channels 1 and 5, and they interfere with one another. So recall from previous lessons that channels in the 2.4 gigahertz band, they need at least 5 channels of separation for overlapping coverage areas. But the channels that are used in this picture have only 4 channels of separation. And the fix for this channel overlap issue is to assign access point 2 to channel 6, thus providing 5 channels of separation between access point 1 and access point 2. Now, a wireless analyzer, it may be needed to identify problems such as signal loss, overlapping or mismatched channels, unacceptable signal to noise ratios, rogue access points, and power levels. Breaking down a problem into smaller pieces, this allows you to identify the fault domain or the area that is causing the problem. So for example, if a user cannot access the wireless network, the pieces involved may be the user connecting to an incorrect SSID or problems with the access point, the switch, the wireless LAN controller, the radius server, the Active Directory server, or the user account and password. And by testing the individual components where possible, you can then isolate the problem and then hopefully correct it. In this video, you're going to learn about general network issues pertaining to considerations for general network troubleshooting and various common issues that you are bound to come across. All right, so let's talk about some considerations for general network troubleshooting. So the list of potential issues, it grows all the time as new services and data types are provided by networks. Fortunately, there are common considerations that can help you greatly as you approach this vast and challenging topic. And here are some common considerations and best practices that you should keep in mind. So the first one we're going to talk about is called device configuration. So you should be consistently reviewing the configurations of network devices to ensure that your network is not suffering from what is called configuration drift, which is configurations that gradually change from their original documented defaults for a network. Many software packages and tools, such as Ansible, they can assist you in making sure all your network devices remain in a constant, stable, and known configuration state.
All right, next we have routing tables. So it is important to carefully monitor and analyze the routing tables of layer 3 devices. Forwarding decisions are critical to the operation of a network, and you want to ensure that packets are flowing exactly as you want and expect them to. All right, next issue we have is interface statuses. So one embarrassing network issue that you do not want to experience is the administratively down interface scenario. So in this scenario, you try to desperately reach a key network device only to discover that you failed to enable the interface that you are trying to contact. Remember that there are simple commands you can use and even GUI-based web pages that give you status information on your critical network interfaces. And knowing which are healthy and which are not can be critical in network troubleshooting. And as a side note, often the status of an interface in a network is contingent on the network layer settings. The physical and data link layer settings might be fine. That is, the Cisco displays the status as up. But if the IP settings are incorrect, the physical and data link layer health of the interfaces are not of great benefit to you. In the following settings, they typically have to be perfect. That is the default gateway IP address, the subnet mask, the IP address, and the DNS address. Now, think about the symptoms you might see for each of these potential misconfigurations. So for example, if your default gateway IP address is incorrect, you might be able to communicate with your local subnet peers just fine, but you will not be able to successfully reach any remote destinations, which ultimately would not be a good thing. Next, we have the VLAN assignment. So ensuring that the right interfaces are in the correct VLANs is very important. Now, remember that VLANs are IP subnets. So it makes perfect sense that if you have two machines in the same network, these machines must be in the same VLAN to properly communicate with one another. And next we have network performance baselines. Now, as you have probably noticed throughout this course, it is critical that you know the details about how your network performs under quote unquote normal conditions and what its speeds and throughput really are. Now, how can you know that you are having a problem if you don't even know what your network should be performing like when there are no problems? Fortunately, as this course has discussed, there are many tools and techniques for capturing accurate and detailed network performance baselines and using the data you collect to keep tabs on the network. Next, let's talk about some common issues. So the following list of common general network issues may be a bit intimidating, and it is not even an exhaustive list. As a network administrator, and as a candidate for the Network Plus certification, you need to understand the following common issues. So the first one is the duplicate IP address. So hosts on the subnet should have unique IP addresses. If two hosts are configured with the same IP address, unpredictable traffic patterns can occur for those hosts. And one reason out of many that this might happen is because a DHCP server is inadvertently leasing out an address that has been statically assigned on the network. And these statically assigned addresses should be excluded from the DHCP scope. Next issue you might experience are duplicate MAC addresses. So although it's rarer than a duplicate IP address on a network, a MAC address can be duplicated. A MAC address on a network is typically taken from the address that is burned in to the hardware by the device vendor. To ensure uniqueness between vendors, each network device vendor is assigned a MAC prefix and the vendor can control the remaining bits. So therefore, when a MAC address is duplicated on a network, it is most often a human error that occurs when MAC addresses are software defined to override the hardware addresses that are burned in. All right, next issue is expired IP addresses. So perhaps a leased DHCP address has expired for a workstation. This might be the case, for example, if the lease duration has been set to a small value, perhaps because of an IP address shortage in a particular area of the network. Then we have DHCP scope exhaustion. So if your end user network device population has grown, you might have issues with DHCP scope exhaustion that are innocent in nature. In DHCP scope exhaustion, this refers to the scope being completely out of IP addresses that it can lease to clients. If your population is outgrowing your design, a redesign is expected, and you should not be surprised by this. DHCP scope exhaustion attacks can be very disruptive because you will not know it's coming. Suddenly, clients in your network cannot communicate properly as they have lost their IP address configuration. Next, you got what is called a rogue DHCP server. So this security concern could certainly cause troubleshooting headaches on the network due to the incorrect IP configurations that could result. When rogue DHCP servers appear on the
network, it is often because users have brought in their own devices, either maliciously or accidentally. Next, we have what is called an untrusted SSL certificate. So if you're using certificates for authentication, you might have an issue with an SSL certificate preventing such authentication. Perhaps a certificate is invalid due to time, or perhaps it has been manually revoked for some reason. Next issue you might experience is incorrect time. So because many network configurations rely on the correct time, you might have problems in the network due to a workstation server or network appliance having the wrong time set. Remember that you should strongly consider using network time protocol or a competing technology to help ensure that your network devices are all set to the correct time. Another issue you might experience is blocked TCP and UDP ports, services, or addresses. So a trouble ticket may be about blocked TCP or UDP ports, and this type of blockage is often the result of misconfigured security devices in the network path. There may be other security mechanisms that are blocking specific IP addresses or services, and these are all worthy of inspection when you are experiencing unexpected connectivity issues in a network. Another issue is incorrect firewall settings. So host-based firewall settings and network-based firewall settings may cause problems. Firewalls are great, but you need to make sure they are not blocking traffic that you need to pass through the network. Then we have incorrect access control list settings. So ACLs can have effects on network traffic, and if their settings are incorrect, you could end up with a bunch of trouble tickets. We have unresponsive services, and these are services that have failed in a network, and they can be a common source of problems. Next issue you might encounter are collisions. So you should not see any collisions taking place if you have built a network using modern techniques and standards. Remember that micro-segmentation of a network means keeping single devices in collision domains so that you do not experience collisions on the network. Often, if you are seeing collisions on the network, it is an indicator that you have a misconfiguration or a hardware device that is malfunctioning. Next, you might experience broadcast storms. So this might sound crazy, but it is possible to go to a layer 2 switch and turn off the spanning tree protocol. However, this is never recommended. Even in cases when you don't need STP because you have used technologies like port channels, you need to make sure STP is still enabled and running in the background. If STP isn't running, a broadcast storm may occur as a result of a layer 2 loop. You might experience broadcast storms for other reasons as well, such as a NIC that's malfunctioning and flooding the network with erroneous broadcast frames. All right, next you might experience multicast flooding. So you need to be concerned about broadcast, unknown unicast, and multicast traffic, which is also known as bum traffic on your network. And this is the traffic that layer 2 switches must flood. You want to minimize the amount of traffic flooding your network must perform, and you therefore often need to closely analyze the amount of bum traffic flooding. In addition, you can use protection mechanisms such as network storm control to guard against excessive amounts of bum traffic hampering network operations. Another issue is called asymmetrical routing. So sometimes packets take very different paths to you than they took towards the destination. This situation called asymmetrical routing is not always a bad thing. Sometimes you even engineer it to happen for specific reasons. Often, however, asymmetrical routing is not wanted and can likely lead to issues. Then we have what are called switching loops. So if STP is not running correctly or it's not running at all, it will not be long before you have broadcast storms and switching loops. These are the enemies that STP is engineered to protect you from. Then we have what are called routing loops. So the dynamic routing protocols in use today, they do an excellent job of protecting themselves against loops. In fact, a loop could never get terribly bad because of the time to live mechanism at layer 3, which prevents a packet from circulating on the network endlessly in a loop. And layer 3 can still happen though, especially when redistribution between routing protocols is configured incorrectly and they are still awful. So be very careful when performing redistribution. Another issue you might experience is missing routes. So when a user indicates that a remote destination must be down, be sure to run through your methodical troubleshooting steps. In many cases, you may discover that the issue is simply a missing route in the local routing table. And remember that networks change. You need to ensure that your dynamic routing protocols or even static routes are being updated properly. Then you might experience a hardware failure. So network devices or parts, they can sometimes fail and components can burn out. Such failures are rare, but
but you need to consider them in your troubleshooting flow. Then we have what is called a low optical link budget. So a fiber optic link budget, which is also known as a loss budget. This indicates the total acceptable amount of optical power loss, which is expressed in decibels, that a fiber optic link can withstand. In such power loss, this results from cables, connectors, splices, and couplers that are installed in the system. Next issue you might encounter are BYOD challenges. So perhaps the investigation of a trouble ticket reveals that an end user is trying to interact with your network by using a tablet he or she brought in from home. Whether or not your BYOD policy allows this type of use, and how you control this potential nightmare, such as through a mobile device management policy, this is an area of networking that deserves your attention. Then we have license feature issues. So sometimes a network does not function properly because the organization lacks the appropriate licensing. And licensing of network devices can get quite complicated. So you might need a license for a network device itself, and then you might also need additional licenses for certain features or levels of scalability. And then finally, we have network performance issues. So sometimes you know exactly why a network is not performing well. So for example, you might have to fail over to another service provider and a very slow backup wide area network link when the main service provider is down for maintenance. It is always an excellent idea to inform end users about these kinds of issues up front to prevent the disruption that will be caused by a flood of trouble tickets. All right, so that was my video where we talked about general network issues pertaining to considerations for general network troubleshooting and various common issues.